Data has evolved in the last decade like never before, and currently data generation has increased by leaps and bounds. And all this data is collectively termed as big data. Businesses require big data engineers who can handle this data, and big data engineers do this with the help of frameworks like Hadoop and Spark. On that note, hi everyone, welcome to this video on Big Data Engineer full course. In this video, we will help you understand how you can become a big data engineer, and we will also cover the fundamentals of big data, Hadoop and Spark. We'll begin this full course by understanding how to become a big data engineer. We will then understand the top skills required for big data jobs. Here, we will also take a close look at other top job roles in the big data domain. We will then understand big data analytics and understand how big data is used across several domains by learning a few crucial big data applications. We will then gain a deeper understanding of big data, its evolution, and its challenges, following which we will learn about Hadoop and how it solves big data problems. We will also take an individual look at components of Hadoop like HDFS, Mapreduce, and Yarn. We will also be learning about Sqoop, Hive, Pig, and HBase. The next topic we will be covering is Spark. Here we will understand the architecture of Spark and look at Spark streaming. Finally, we will conclude this full course by looking into a set of top Hadoop interview questions and answers. So, let's start off with our full course. But before we begin, make sure to subscribe to our YouTube channel and hit the bell icon to never miss an update from Simplilearn.
We all use smartphones, but have you ever wondered how much data it generates in the form of texts, phone calls, emails, photos, videos, searches, and music? Approximately 40 exabytes of data gets generated every month by a single smartphone user. Now, imagine this number multiplied by 5 billion smartphone users. That's a lot for our mind to even process, isn't it? In fact, this amount of data is quite a lot for traditional computing systems to handle. And this massive amount of data is what we term as big data. Let's have a look at the data generated per minute on the internet. 2.1 million snaps are shared on Snapchat. 3.8 million search queries are made on Google. 1 million people log on to Facebook. 4.5 million videos are watched on YouTube. 188 million emails are sent. That's a lot of data. So, how do you classify any data as big data? This is possible with the concept of 5 V's: volume, velocity, variety, veracity, and value. Let us understand this with an example from the healthcare industry. Hospitals and clinics across the world generate massive volumes of data. 2,314 exabytes of data are collected annually in the form of patient records and test results. All this data is generated at a very high speed, which attributes to the velocity of big data. Variety refers to the various data types, such as structured, semi-structured, and unstructured data. Examples include Excel records, log files, and X-ray images. Accuracy and trustworthiness of the generated data is termed as veracity. Analyzing all this data will benefit the medical sector by enabling faster disease detection, better treatment, and reduced cost. This is known as the value of big data. But how do we store and process this big data? To do this job, we have various frameworks such as Cassandra, Hadoop, and Spark. Let us take Hadoop as an example and see how Hadoop stores and processes big data. Hadoop uses a distributed file system known as Hadoop Distributed File System to store big data. If you have a huge file, your file will be broken down into smaller chunks and stored in various machines. Not only that, when you break the file, you also make copies of it, which goes into different nodes. This way, you store your big data in a distributed way and make sure that even if one machine fails, your data is safe on another. Mapreduce technique is used to process big data. A lengthy task A is broken into smaller tasks, B, C, and D. Now, instead of one machine, 3 machines take up each task and complete it in a parallel fashion and assemble the results at the end. Thanks to this, the processing becomes easy and fast. This is known as parallel processing. Now that we have stored and processed our big data, we can analyze this data for numerous applications. In games like Halo 3 and Call of Duty, designers analyze user data to understand at which stage most of the users pause, restart, or quit playing. This insight can help them rework on the storyline of the game and improve the user experience, which in turn reduces the customer churn rate. Similarly, big data also helped with disaster management during Hurricane Sandy in 2012. It was used to gain a better understanding of the storm's effect on the east coast of the U.S., and necessary measures were taken. It could predict the hurricane's landfall 5 days in advance, which wasn't possible earlier. These are some of the clear indications of how valuable big data can be once it is accurately processed and analyzed.
Today, I'm going to tell you how you can become a big data engineer. Now, it should come as no surprise for you guys to know that organizations generate as well as use a whole lot of data. This vast volume of data is called big data. Companies use big data to draw meaningful insights and take business decisions. And big data engineers are the people who can make sense out of this enormous amount of data. Now, let's find out who is a big data engineer. A big data engineer is a professional who develops, maintains, tests, and evaluates the company's big data infrastructure. In other words, develop big data solutions based on a company's requirements. They maintain these solutions. They test out these solutions as to the company's requirements. They integrate this solution with the various tools and systems of the organization. And finally, they evaluate how well the solution is working to fulfill the company's requirements. Next up, let's have a look at the responsibilities of a big data engineer. Now, they need to be able to design, implement, verify, and maintain software systems. Now, for the process of ingesting data as well as processing it, they need to be able to build highly scalable as well as robust systems. They need to be able to extract data from one database, transform it, as well as load it into another data store with the process of ETL or the extract, transform, load process. And they need to research as well as propose new ways to acquire data, improve the overall data quality and the efficiency of the system. Now, to ensure that all the business requirements are met, they need to build a suitable data architecture. They need to be able to integrate several programming languages and tools together so that they can generate a structured solution. They need to build models that reduce the overall complexity and increase the efficiency of the whole system by mining data from various sources. And finally, they need to work well with other teams, ones that include data architects, data analysts, and data scientists. Next up, let's have a look at the skills required to become a big data engineer. The first step is to have programming knowledge. One of the most important skills required to become a big data engineer is that of experience with programming languages, especially hands-on experience. Now, the big data solutions that organizations would want you to create will not be possible without experience in programming languages. I can even tell you an easy way through which you can get experience with programming languages. Practice, practice, and more practice. Some of the most commonly used programming languages used for big data engineering are Python, Java, and C++. The second skill that you require is to have in-depth knowledge about DBMS and SQL. You need to know how data is maintained as well as managed in a database. You need to know how SQL can be used to transform as well as perform actions on a database, and by extension, know how to write SQL queries for any relational database management systems. Some of the commonly used database management systems for big data engineering: MySQL, Oracle Database, and the Microsoft SQL Server. The third skill that you require is to have experience working with ETL and warehousing tools. Now, you need to know how to construct as well as use a data warehouse so that you can perform the ETL operation or the extract, transform, and load operations. Now, as a big data engineer, you'll be constantly tasked with extracting unstructured data from a number of different sources, transforming it into meaningful information, and loading it into other data storages, databases, or data warehouses. Now, what this is basically aggregating unstructured data from multiple sources, analyzing it so that you can take better business decisions. Some of the tools used for this purpose are Talent, IBM DataStage, Pentaho, and Informatica. Next up, we have the fourth skill that you require, which is knowledge about operating systems. Now, since most big data tools have unique demands, such as root access to operating system functionality, as well as hardware, having a strong understanding of operating systems like Linux and Unix is absolutely mandatory. Some of the operating systems used by big data engineers are Unix, Linux, and Solaris. Now, the fifth skill that you require to have experience with Hadoop-based analytics. Since Hadoop is one of the most commonly used tools when it comes to big data engineering, it's understood that you need to have experience with Apache Hadoop-based technologies. Technologies like HDFS, Hadoop Mapreduce, Apache HBase, Hive, and Pig. The sixth skill that you require is to have worked with real-time processing frameworks like Apache Spark. Now, as a big data engineer, you'll have to deal with vast volumes of data. So for this data, you need an analytics engine like Spark, which can be used for large-scale real-time data processing. Now, Spark can process live streaming data from a number of different sources like Facebook, Instagram, Twitter, and so on. It can also perform interactive analysis and data integration. And now we're at our final skill requirement, which is to have experience with data mining and modeling. So as a data engineer, you'll have to examine massive pre-existing data so that you can discover patterns as well as new information. With this, you'll create predictive models for your business so that you can make better informed decisions. Some of the tools used for this are R, RapidMiner, Weka, and Nime. Now let's talk about a big data engineer's salary as well as other roles they can look forward to. Now the average salary of a big data engineer in the United States is approximately $90,000 per year. Now this ranges from $66,000 all the way to $130,000 per annum. In India, the average salary is around 7 lakh rupees and ranges from 4 lakhs to 13 lakhs per annum. After you've become a big data engineer, some of the job roles that you can look forward to are that of a senior big data engineer, a business intelligence architect, and a data architect. Now let's talk about certifications that a big data engineer can opt for. First off, we have the Cloudera CCP data engineer. A Cloudera certified professional data engineer possesses the skills to develop reliable and scalable data pipelines that result in optimized datasets for a variety of workloads. It is one of the industry's most demanding performance-based certification. CCP evaluates and recognizes a candidate's mastery of the technical skills most sought after by employers. The time limit for this exam is 240 minutes and it costs $400. Next, we have the IBM Certified Data Architect Big Data Certification. An IBM Certified Big Data Architect understands the complexity of data and can design systems and models to handle different data variety, including structured, semi-structured, unstructured, volume, velocity, veracity, and so on. A big data architect is also able to effectively address information governance and security challenges associated with the system. This exam is 75 minutes long. And finally, we have the Google Cloud Certified Data Engineer. A Google Certified Data Engineer enables data-driven decision-making by collecting, transforming, and publishing data. They should also be able to leverage, deploy, and continuously train pre-existing machine learning models. The length of the certification exam is 2 hours and its registration fee is $200. Now let's have a look at how Simplilearn can help you become a big data engineer. Simplilearn provides the Big Data Architect Master's Program. This includes a number of different courses like Big Data Hadoop and Spark Developer, Apache Spark and Scala, Mongodb Developer and Administrator, Big Data and Hadoop Administrator, and so much more. This course goes through 50 plus in-demand skills and tools, 12 plus real-life projects, and the possibility of an annual average salary of 19 to 26 lakh rupees per annum. It will also help you get noticed by the top hiring companies. This course will also go through some major tools like Kafka, Apache Spark, Flume, HBase, MongoDB, Hive, Pig, Mapreduce, Java, Scala, and much more. Now why don't you head over to Simplilearn.com and get started on your journey to get certified and get ahead.
Back in the early 2000s, there was relatively less data generated, but with the rise of various social media platforms and multinational companies across the globe, the generation of data has increased by leaps and bounds. According to the IDC, the total volume of data is expected to reach 175 zettabytes in 2025. That's a lot of data. So we can define big data as massive amount of data which cannot be stored, processed, and analyzed using the traditional ways. Let's now have a look at the challenges with respect to big data. The first challenge with big data is its storage. Storing big data is not easy as the data generation is endless. In addition to this, storing unstructured data in our traditional databases is a great challenge. Unstructured data refers to data such as photographs and videos. The second challenge was processing big data. Data is only useful to us if it is processed and analyzed. Processing big data consumes a lot of time due to its size and structure. To overcome these challenges of big data, we have various frameworks such as Hadoop, Cassandra, and Spark. Let us have a quick look at Hadoop and Spark. So what is Hadoop? It is a framework that stores big data in a distributed way and processes it parallelly. How do you think Hadoop does this? Well, Hadoop uses a distributed file system known as Hadoop Distributed File System to store big data. If you have a huge file, your file will be broken down into smaller chunks and stored in various machines. This is why it is termed as distributed storage. Mapreduce is the processing unit of Hadoop. Here, we have multiple machines working parallelly to process big data. Thanks to this technique, the processing becomes easy and fast. Let's now move on to Spark. Spark is a framework that is responsible for processing data both in batches and in real time. Spark is used to analyze data across various clusters of computers. Now that you have understood big data, Hadoop, and Spark, let's look into a few of the different job roles in this domain. Career opportunities in this field are limitless as organizations are using big data to enhance their products, business decisions, and marketing effectiveness. So here we will understand in depth as to how to become a big data engineer. In addition to this, we will also look into the various skills required to become a Hadoop developer, Spark developer, and a big data architect. Starting off with the big data engineer role. Do you know who a big data engineer is? Well, big data engineers are professionals who develop, maintain, test, and evaluate a company's big data infrastructure. They have several responsibilities. Firstly, they are responsible for designing and implementing software systems. They verify and maintain these systems for the ingestion and processing of data. They build robust systems. Extract, transform, load, operations known as the ETL process is carried out by big data engineers. They also research various new methods to obtain data and improve its quality. Big data engineers are also responsible for building data architectures that meet the business requirements. They provide a solution by integrating various tools and programming languages. In addition to the above responsibilities, their primary responsibility is to mine data from plenty of different sources to build efficient business models. Lastly, they also work closely with data architects, data scientists, and data analysts. Those are quite a lot of responsibilities. Let us now have a look at the skills required to achieve these responsibilities. As you can see on your screens, we have listed the top 7 skills needed to be possessed by a big data engineer. Starting off, the essential skill is programming. A big data engineer needs to have hands-on experience in any one of the programming languages such as Java, C++, or Python. As a big data engineer, you should also have in-depth knowledge of DBMS and SQL. This is because you have to understand how data is managed and maintained in a database. Hence, you need to know how to write SQL queries for any RDBMS systems. Some of the commonly used database management systems for big data engineering are MySQL, Oracle Database, and the Microsoft SQL Server. As mentioned earlier, carrying out an ETL operation is a big data engineer's responsibility. Now you need to know how to construct as well as use a data warehouse so that you can perform these ETL operations. As a big data engineer, you will be continuously tasked with extracting data from various sources, transforming them into meaningful information, and loading it into other data storages. Some of the tools used for this purpose are Talent, IBM DataStage, Pentaho, and Informatica. Next up, we have the 4th skill that you require, which is knowledge about operating systems. Big data tools run on operating systems, hence a sound understanding of Unix, Linux, Windows, and Solaris is mandatory. The 5th skill that you require is to have experience with Hadoop-based analytics. Since Hadoop is one of the most commonly used big data engineering tools, it's understood that you need to have experience with Apache Hadoop-based technologies like HDFS, Mapreduce, Apache Pig, Hive, and Apache HBase. The 6th skill that you require is to have worked with real-time processing frameworks like Apache Spark. As a big data engineer, you would deal with large volumes of data. So for this, you need an analytics engine like Spark, which can be used for both batch and real-time processing. Spark can process live streaming data from several different sources like Facebook, Instagram, Twitter, and so on. And now we are at our final skill requirement. which is to have experience with data mining and data modeling. As a big data engineer, you would have to examine massive pre-existing data so that you can discover patterns and new information. This will help you create predictive models that will help you make various business decisions. Some of the tools used for this are R, RapidMiner, Weka, and NIME. Now let's talk about a big data engineer's salary. In the US, a big data engineer's average annual salary is around $102,000 per annum. In India, a big data engineer makes about 7 lakh rupees per annum. That was all about our first role, big data engineer. Moving on to our second role, we have Hadoop Developer. As the name suggests, a Hadoop developer looks into the coding and programming of the various Hadoop applications. This job role is more or less similar to that of a software developer. Moving on to the skills required to become a Hadoop developer, at first, it is a knowledge of the Hadoop ecosystem. A Hadoop developer should have in-depth knowledge about the Hadoop ecosystem and its components, which include HBase, Pig, Sqoop, Flume, Oozie, etc. You should also have data modeling experience with OLAP and OLTP. Knowledge of SQL is required. Like a big data engineer, a Hadoop developer must also know popular tools like Pentaho, Informatica, and Talent. Finally, you should also be well-versed in writing Pig Latin scripts and Mapreduce jobs. The average annual salary of a Hadoop developer in the US is nearly $76,000 per annum. In India, a Hadoop developer makes approximately 4,57,000 rupees per annum. Moving to our third job role, we have Spark Developer. We saw what Spark is. Now let's understand what a Spark developer does. Spark developers create Spark jobs using Python or Scala for data aggregation and transformation. They also write analytics code and design data processing pipelines. A Spark developer needs to have the following skills. They need to know Spark and its components such as Spark Core, Spark Streaming, Spark Machine Learning Library, etc. They should also know the scripting languages like Python or Perl. Just like the previous job roles, a Spark developer should also have basic knowledge of SQL queries and a database structure. In addition to the above, a Spark developer is also expected to have a fairly good understanding of Linux and its commands. Moving to the average annual salary of a Spark developer, it is nearly $81,000 per annum in the US. In India, a Spark developer earns nearly 5,87,000 rupees per annum. Let's now move on to our final job role, that is Big Data Architect. So let's understand who a Big Data Architect is. Well, a Big Data Architect is a professional who is responsible for designing and planning big data systems. They also manage large-scale development and deployment of Hadoop applications. Moving on to the skills required to become a big data architect, first up, the individual must have advanced data mining and data analysis skills. Big data architects should also be able to implement and use a NoSQL database and cloud computing techniques. They must also have an idea of various big data technologies like Hadoop, Mapreduce, HBase, Hive, and so on. Finally, big data architects must hold experience with Agile and Scrum frameworks. Let's now have a look at the average annual salary of a big data architect in the United States and India. In the US, a big data architect earns a whopping $118,000 per annum. Meanwhile, in India, a big data architect makes nearly 19 lakh rupees per annum. These are huge numbers, right? So now that we have understood the job roles of a big data engineer, Hadoop developer, Spark developer, and a big data architect, let us have a look at the companies hiring these professionals. As y'all can see on your screens, we have IBM, Amazon, American Express, Netflix, Microsoft, and Bosch to name a few.
Let us now understand why big data analytics is required with an example. So all of you listen to music online, isn't it? Here we will take an example of Spotify, which is a Swedish audio streaming platform, and see how big data analytics is used here. Spotify has nearly 96+ million users, and all these users generate a tremendous amount of data. Data like the songs which are played repeatedly, the numerous likes, shares, and the
user's search history. All these data can be termed as big data here with respect to Spotify. Have you ever wondered what Spotify does with all this big data? Well, Spotify analyzes this big data for suggesting songs to its users. I'm sure all of you might have come across the recommendation list which is made available to each one of you by Spotify. Each one of you will have a totally different recommendation list. This is based on your likes, your past history, like the songs you like listening to, and your playlists. This works on something known as the recommendation system. Recommendation systems are nothing but data filtering tools. They collect all the data and then filter them using various algorithms. This system has the ability to accurately predict what a user would like to listen to next with the help of big data analytics. This prediction helps the users stay on the page for a longer time, and by doing so, Spotify engages all its users. The users don't have the need to go on searching for different songs. This is because Spotify readily provides them with a variety of songs according to their taste. Well, this is how big data analytics is used by Spotify. Now that we have understood why big data analytics is required, let us move on to our next topic, that is, what is big data analytics? But before that, there is another term we need to understand, that is big data. We all hear the term big data many a times, but do you know what exactly big data means? Well, we will understand the term big data clearly right now. Big data is a term for data sets that cannot be handled by traditional computers or tools due to their value, volume, velocity, and veracity. It is defined as massive amount of data which cannot be stored, processed, and analyzed using various traditional methods. Do you know how much data is being generated every day, every second? Even as I talk right now, there are millions of data sources which generate data at a very rapid rate. These data sources are present across the world. As you know, social media sites generate a lot of data. Let's take an example of Facebook. Facebook generates over 500 plus terabytes of data every day. This data is mainly generated in terms of your photographs, videos, messages, etc. Big data also contains data of different formats like structured data, semi-structured data, and unstructured data. Data like your Excel sheets all fall under structured data. This data has a definite format. Your emails fall under semi-structured, and your pictures and videos all fall under unstructured data. All this data together make up for big data. It is very tough to store, process, and analyze big data using RDBMS. If you have looked into our previous videos, you would know that Hadoop is the solution to this. Hadoop is a framework that stores and processes big data. It stores big data using the distributed storage system, and it processes big data using the parallel processing method. Hence, storing and processing big data is no more a problem using Hadoop. Big data in its raw form is of no use to us. We must try to derive meaningful information from it in order to benefit from this big data. Do you know Amazon uses big data to monitor its items that are in its fulfillment centers across the globe? How do you think Amazon does this? Well, it is done by analyzing big data, which is known as big data analytics. What is big data analytics? In simple terms, big data analytics is defined as the process which is used to extract meaningful information from big data. This information could be your hidden patterns, unknown correlations, market trends, and so on. By using big data analytics, there are many advantages. It can be used for better decision making, to prevent fraudulent activities, and many others. We will look into 4 of them step by step. I will first start off with big data analytics, which is used for risk management. BDO, which is a Philippine banking company, uses big data analytics for risk management. Risk management is an important aspect for any organization, especially in the field of banking. Risk management analysis comprises a series of measures which are employed to prevent any sort of unauthorized activities. Identifying fraudulent activities was a main concern for BDO. It was difficult for the bank to identify the fraudster from a long list of suspects. BDO adopted Big Data Analytics, which helped the bank to narrow down the entire list of suspects. Thus, the organization was able to identify the fraudster in a very short time. This is how Big Data Analytics is used in the field of banking for risk management. Let us now see how Big Data Analytics is used for product development and innovations with an example. All of you are aware of Rolls-Royce cars, right? Do you also know that they manufacture jet engines which are used across the world? What is more interesting is that they use Big Data Analytics for developing and innovating this engine. A new product is always developed by trial and error method. Big Data Analytics is used here to analyze if an engine design is good or bad. It is also used to analyze if there can be more scope for improvement based on the previous models and on the future demands. This way, Big Data Analytics is used in designing a product which is of higher quality. Using Big Data Analytics, the company can save a lot of time. If the team is struggling to arrive at the right conclusion, Big Data can be used to zero in on the right data which have to be studied, and thus the time spent on the product development is less. Big Data Analytics helps in quicker and better decision making in organizations. The process of selecting a course of action from various other alternatives is known as decision making. Lot of organizations take important decisions based on the data that they have. Data-driven business decisions can make or break a company. Hence, it is important to analyze all the possibilities thoroughly and quickly before making important decisions. Let us now try to understand this with an use case. Starbucks uses Big Data Analytics for making important decisions. They decide the location of their new outlet using Big Data Analytics. Choosing the right location is an important factor for any organization. The wrong location will not be able to attract the required amount of customers. Positioning of a new outlet a few miles here or there can always make a huge difference for an outlet, especially a one like Starbucks. Various factors are involved in choosing the right location for a new outlet. For example, parking adequacy has to be taken into consideration. It would be inconvenient for people to go to a store which has no parking facility. Similarly, the other factors that have to be considered are the visibility of the location, the accessibility, the economic factors, the population of that particular location, and also we would have to look into the competition in the vicinity. All these factors have to be thoroughly analyzed before making a decision as to where the new outlet must be started. Without analyzing these factors, it would be impossible for us to make a wise decision. Using Big Data Analytics, we can consider all these factors and analyze them quickly and thoroughly. Thus, Starbucks makes use of Big Data Analytics to understand if their new location would be fruitful or not. Finally, we will look into how Big Data Analytics is used to improve customer experience using an example. Delta, an American airline, uses Big Data Analytics to improve its customer experiences. With the increase in global air travel, it is necessary that an airline does everything they can in order to provide good service and experience to its customers. Delta Airlines improves its customer experience by making use of Big Data Analytics. This is done by monitoring tweets, which will give them an idea as to how their customer's journey was. If the airline comes across a negative tweet and if it is found to be the airline's fault, the airline goes ahead and upgrades that particular customer's ticket. When this happens, the customer is able to trust the airlines, and without a doubt, the customer will choose Delta for their next journey. By doing so, the customer is happy and the airlines will be able to build a good brand recognition. Thus, we see here that by using analysis, Delta Airlines was able to improve its customer experience. Moving on to our next topic, that is life cycle of Big Data Analytics. Here we will look into the various stages as to how data is analyzed from scratch. The first stage is the business case evaluation stage. Here, the motive behind the analysis is identified. We need to understand why we are analyzing so that we know how to do to it and what are the different parameters that have to be looked into. Once this is done, it is clear for us and it becomes much easier for us to proceed with the rest. After which we will look into the various data sources from where we can gather all the data which will be required for analysis. Once we get the required data, we will have to see if the data that we received is fit for analysis or not. Not all the data that we receive will have meaningful information. Some of it will surely just be corrupt data. To remove this corrupt data, we will pass this entire data through a filtering stage. In this stage, all the corrupt data will be removed. Now we have the data minus the corrupt data. Do you think our data is now fit for analysis? Well, it is not. We still have to figure out which data will be compatible with the tool that we will be using for analysis. If we find data which is incompatible, we first extract it and then transform it to a compatible form depending on the tool that we use. In the next stage, all the data with the same fields will be integrated. This is known as the data aggregation stage. The next stage, which is the analysis stage, is a very important stage in the life cycle of big data analytics. Right here in this step, the entire process of evaluating your data using various analytical and statistical tools to discover meaningful information is done. Like we've discussed before, the entire process of deriving meaningful information from data, which is known as analysis, is done here in this stage. The result of the data analysis stage is then graphically communicated using tools like Tableau, Power BI, ClickView. This analysis result will then be made available to different business stakeholders for various decision making. This was the entire life cycle of big data analytics. We just saw how data is analyzed from scratch. Now we will move on to a very important topic, that is the different types of big data analytics. Well, we have 4 different types of big data analytics. As you see here, these are the types, and below this are the questions that each type tries to answer. We have descriptive analytics, which asks the question, what has happened? Then we have diagnostic analytics, which asks, why did it happen? Predictive analytics, asking what will happen? And prescriptive analytics, which questions by asking what is the solution. We will look into all these 4 one by one with an use case for each. We will first start off with descriptive analytics. As mentioned earlier, descriptive analytics asks the question, what has happened? It can be defined as the type that summarizes past data into a form that can be understood by humans. In this type, we will look into the past data and arrive at various conclusions. For example, an organization can review its performance using descriptive analytics. That is, it analyzes its past data such as revenue over the years and arrives at a conclusion with the profit. By looking at this graph, we can understand if the company is running at a profit or not. Thus, descriptive analytics helps us understand this easily. We can simply say that descriptive analytics is used for creating various reports for companies and also for tabulating various social media metrics like Facebook likes, tweets, etc. Now that we have seen what is descriptive analytics, let us look into an use case of descriptive analytics. The Dow Chemical Company analyzed all its past data using descriptive analytics, and by doing so, they were able to identify the underutilized space in their facility. Descriptive analytics helped them in this space consolidation. On the whole, the company was able to save nearly $4 million annually. So we now see here that descriptive analytics not only helps us derive meaningful information from the past data, but it can also help companies in cost reduction if it is used wisely. Let us now move on to our next type, that is diagnostic analytics. Diagnostic analytics asks the question why a particular problem has occurred. As you can see, it will always ask the question, why did it happen? It will look into the root cause of a problem and try to understand understand why it has occurred. Diagnostic analytics makes use of various techniques such as data mining, data discovery, and drill down. Companies benefit from this type of analytics because it helps them look into the root cause of a problem. By doing so, the next time the same problem will not arise, as the company already knows why it has happened and they will arrive at a particular solution for it. Inetsoft's BI query tool is an example of diagnostic analytics. We can use query tool for diagnostic analytics. Now that you know why diagnostic analytics is required and what diagnostic analytics is, I will run you through an example which shows where diagnostic analytics can be used. All of us shop on e-commerce sites, right? Have you ever added items to your cart but ended up not buying it? Yes, all of us might have done that at some point. An organization tries to understand why its customers don't end up buying their products although it has been added to their carts. And this understanding is done with the help of diagnostic analytics. An e-commerce site wonders why they have made few online sales although they have had a very good marketing strategy. There could have been various factors as to why this has happened. Factors like the shipping fee which was too high, or the page that didn't load correctly, not enough payment options available, and so on. All these factors are analyzed using diagnostic analytics and the company comes to a conclusion as to why this has happened. Thus, we see here that the root cause is identified so that in future the same problem doesn't occur again. Let us now move on to the third type, that is predictive analytics. As the name suggests, predictive analytics makes predictions of the future. It analyzes the current and historical facts to make predictions about future. It always asks the question, what will happen next? Predictive analytics is used with the help of artificial intelligence, machine learning, data mining to analyze the data. It can be used for predicting customer trends, market trends, customer behavior, etc. It solely works on probability. It always tries to understand what can happen next with the help of all the past and current information. A company like PayPal, which has 260 plus million accounts, always has the need to ensure that their online fraudulent and unauthorized activities are brought down to nil. Fear of constant fraudulent activities have always been a major concern for PayPal. When a fraudulent activity occurs, people lose trust in the company, and this brings in a very bad name for the brand. It is inevitable that fraudulent activities will happen in a company like PayPal, which is one of the largest online payment processors in the world. But PayPal uses analytics wisely here to prevent such fraudulent activities and to minimize them. It uses predictive analytics to do so. The organization is able to analyze past data, which includes a customer's historical payment data, a customer's behavior trend, and then it builds an algorithm which works on predicting what is likely to happen next with respect to their transaction. With the use of big data and algorithms, the system can gauge which of the transactions are valid and which could be potentially a fraudulent activity. By doing so, PayPal is always ready with precautions that they have to take to protect all their clients against fraudulent transactions. We will now move on to our last type, that is prescriptive analytics. Prescriptive analytics, as the name suggests, always prescribes a solution to a particular problem. The problem can be something which is happening currently. Hence, it can be termed as the type that always asks the question, what is the solution? Prescriptive analytics is related to both predictive and descriptive analytics. As we saw earlier, descriptive analytics always asks the question, what has happened? And predictive analytics helps you understand what can happen next. With the help of artificial intelligence and machine learning, prescriptive analytics helps you arrive at the best solution for a particular problem. Various business rules, algorithms, and computational modeling procedures are used in prescriptive analytics. Let us now have a look at how and where prescriptive analytics is used with an example. Here we will understand how prescriptive analytics is used by an airline for its profit. Do you know that when you book a flight ticket, the price of it depends on various factors, both internal and external factors. Apart from taxes, seat selection, there are other factors like oil prices, customer demand, which are all taken into consideration before the flight's fare is displayed. Prices change due to availability and demand. Holiday seasons are a time when the rates are much higher than the normal days. Seasons like Christmas and school vacations, also weekends, the rates will be much higher than weekdays. Another factor which determines a flight's fare is your destination. Depending on the place where you are traveling to, the flight fare will be adjusted accordingly. This is because there are quite a few places where the air traffic is less, and in such places the flight's fare will also be less. So Prescriptive Analytics analyzes all these factors that are discussed, and it builds an algorithm which will automatically adjust a flight's fare. By doing so, the airline is able to maximize its profit. These were the 4 types of analytics. Now let us understand how we achieve these with the use of big data tools. Our next topic will be the various tools used in big data analytics. These are a few of the tools that I will be talking about today. We have Hadoop, Mongodb, Talend, Kafka, Cassandra, Spark, and Storm. We will look into each one of them one by one. We will first start off with Hadoop. When you speak of big data, the first framework that comes into everyone's mind is Hadoop, isn't it? As I mentioned earlier, Apache Hadoop is used to store and process big data in a distributed and parallel fashion. It allows us to process data very fast. Hadoop uses Mapreduce, Pig, and Hive for analyzing this big data. Hadoop is easily one of the most famous big data tools. Now let us move on to the next one, that is MongoDB. MongoDB is a cross-platform, document-oriented database. It has the ability to deal with large amount of unstructured data. Processing of data which is unstructured and processing of data sets that change very frequently is done using MongoDB. Talend provides software and services for data integration, data management, and cloud storage. It specializes in big data integration. Talend Open Studio is a free open source tool for processing data easily on a big data environment. Cassandra is used widely for an effective management of large amounts of data. It is similar to Hadoop in its feature of fault tolerance, where data is automatically replicated to multiple nodes. Cassandra is preferred for real-time processing. Spark is another tool that is used for data processing. This data processing engine is developed to process data way faster than Hadoop Mapreduce. This is done in a way because Spark does all the processing in the main memory of the data nodes, and thus it prevents unnecessary input-output overheads with the disk. Whereas Mapreduce is disk-based, and hence Spark proves to be faster than Hadoop Mapreduce. Storm is a free big data computational system which is done in real time. It is one of the easiest tools for big data analysis. It can be used with any programming language. This feature makes Storm very simple to use. Finally, we will look into another big data tool which is known as Kafka. Kafka is a distributed streaming platform which was developed by LinkedIn and later given to Apache Software Foundation. It is used to provide real-time analytics result, and it is also used for fault-tolerant storage. These were few of the big data analytics tools. Now let us move on to our last topic for today, that is big data application domains. Here we will look into the various sectors where big data analytics is actively used. The first sector is e-commerce. Nearly 45% of the world is online, and they create a lot of data every second. Big data can be used smartly in the field of e-commerce by predicting customer trend, forecasting demands, adjusting the price, and so on. Online retailers have the opportunity to create better shopping experience and generate higher sales if big data analytics is used correctly. Having big data doesn't automatically lead to a better marketing strategy. Meaningful insights need to be derived from it in order to make right decisions. By analyzing big data, we can have personalized marketing campaigns, which can result in better and higher sales. In the field of education, depending on the market requirements, new courses are developed. The market requirement needs to be analyzed correctly with respect to the scope of a course, and accordingly a scope needs to be developed. There is no point in developing a course which has no scope in the future. Hence, to analyze the market requirement and to develop new courses, we use Big Data Analytics here. There are a number of uses of Big Data Analytics in the field of healthcare, and one of it is to predict a patient's health issue. That is, with the help of their previous medical history, Big Data Analytics can determine how likely they are to have a particular health issue in the future. The example of Spotify that we saw previously showed how Big Data Analytics is used to provide a personalized recommendation list to all its users. Similarly, in the field of media and entertainment, Big Data Analytics is used to understand the demands of shows, songs, movies, and so on to deliver personalized recommendation lists as we saw with Spotify. Big Data Analytics is used in the field of banking. As we saw previously with a few use cases, Big Data Analytics was used for risk management. In addition to risk management, it is also used to analyze a customer's income and spend patterns and to help the bank predict if a particular customer is going to choose any of the bank offers such as loans, credit cards, schemes, and so on. This way, the bank is able to identify the right customer who is interested in its offers. It is noticed that telecom companies have begun to embrace big data to gain profit. Big Data Analytics helps in analyzing network traffic and call data records. It can also improve its service quality and improve its customer experience. Let us now look into how Big Data Analytics is used by governments across the world. In the field of law enforcement, Big Data Analytics can be applied to analyze all the available data to understand crime patterns. Intelligence services can use predictive analytics to forecast the crime which could be committed. In Durham, the police department was able to reduce the crime rate using Big Data Analytics. With the help of data, police could identify whom to target, where to go, when to patrol, and how to investigate crimes. Big Data Analytics helped them to discover patterns of crime emerging in the area. Before we move on to the applications, let's have a quick look at the Big Data market revenue forecast worldwide from 2011 to 2027. So here's a graph in which the y-axis represents the revenue in billion US dollars and the x-axis represents the years. As it is seen clearly from the graph, big data has grown until 2019 and statistics predict that this growth will continue even in the future. This growth is made possible as numerous companies use big data in various domains to boost their revenue. We will look into a few of such applications. The first big data application we will look into is weather forecast. Imagine there is a sudden storm and you're not even prepared. That would be a terrifying situation, isn't it? Dealing with any calamities such as hurricanes, storms, floods would be very inconvenient if we are caught off guard. The solution is to have a tool that predicts the weather of the coming days well in advance. This tool needs to be accurate, and to make such a tool, big data is used. So how does big data help here? Well, it allows us to gather all the information required to predict the weather. Information such as the climate change details, wind direction, precipitation, previous weather reports, and so on. After all this data is collected, it becomes easier for us to spot a trend and identify what's going to happen next by analyzing all of this big data. A weather prediction engine works on this analysis. It predicts the weather of every region across the world for any given time. By using such a tool, we can be well prepared to face any climate change or any natural calamity. Let's take an example of a landslide and try to understand how big data is used to tackle such a situation. Predicting a landslide is very difficult with just the basic warning signs. Lack of this prediction can cause a huge damage to life and property. This challenge was studied by the University of Melbourne, and they developed a tool which is capable of predicting a landslide. This tool predicts the boundary where a landslide is likely to occur 2 weeks before. This magical tool works on both big data and applied mathematics. An accurate prediction like this, which is made 2 weeks before, can save lives and help in relocating people in that particular region. It also gives us an insight into the magnitude of the upcoming destruction. This is how big data is used in weather forecast and in predicting any natural calamities across the world. Let us now move on to our next application, that is big data application in the field of media and entertainment. The media and the entertainment industry is a massive one. Leveraging big data here can produce sky-high results and boost the revenue for any company. Let us see the different ways in which big data is used in this industry. Have you ever noticed that you come across relevant advertisements in your social media sites and in your mailboxes? Well, this is done by analyzing all your data such as your previous browsing history and your purchase data. Publishers then display what you like in the form of ads, which will in turn catch your interest in looking into it. Next up is customer sentiment analysis. Customers are very important for a company. The happier the customer, the greater the company's revenue. Big data helps in gathering all the emotions of a customer through their posts, messages, conversations, etc. These emotions are then analyzed to arrive at a conclusion regarding the customer's satisfaction. If the customer is unhappy, the company strives to do better the next time and provides their customers a better experience. While purchasing an item from an e-commerce site or while watching videos on an entertainment site, you might have noticed a segment which says most recommended list for you. This list is a personalized list which is made available to you by analyzing all the data such as your previous watch history, your subscriptions, your likes, and so on. Recommendation engine is a tool that filters and analyzes all this data and provides you with a list that you would most likely be interested in. By doing so, the site is able to retain and engage its customer for a longer time. Next is customer churn analysis. In simple words, customer churn happens when a customer stops their subscription with a service. Predicting and preventing this is of paramount importance to any organization. By analyzing the behavioral patterns of previously churned customers, an organization can identify which of their current customers are likely to churn. By analyzing all of this data, the organization can then implement effective programs for customer retention. Let us now look into an use case of Starbucks. Big data is effectively used by the Starbucks app. 17 million users use this app, and you can imagine how much data they generate. Data in the form of their coffee buying habits, the store they visit, and to the time they purchase. All of this data is fed into the app. So when a customer enters a new Starbucks location, the system analyzes all their data and they are provided with their preferred order. This app also suggests new products to the customer. In addition to this, they also provide personalized offer and discounts on special occasions. Moving on to our next sector, which is healthcare. It is one of the most important sectors. Big data is widely used here to save lives. With all the available big data, medical researches are done very effectively. They are performed accurately by analyzing all the previous medical histories, and new treatments and medicines are discovered. Cure can be found out even for few of the incurable diseases. There are cases when one medication need not be effective for every patient. Hence, personal care is very important. Personal care is provided to each patient depending on their past medical history. An individual's medical history along with their body parameters are analyzed, and personal attention is given to each of them. As we all know, medical treatments are not very pocket friendly. Every time a medical treatment is taken, the amount increases. This can be reduced if readmissions are brought down. Analyzing all the data precisely will deliver a long-term efficient result, which will in turn prevent a patient's readmission frequently. With globalization came an increase in the ease for infectious diseases to spread widely. Based on geography and demographics, big data helps in predicting where an outbreak of epidemic viruses are most likely to occur. An American healthcare company, United Healthcare, uses big data to detect any online medical fraud activities such as payment of unauthorized benefits, intentional misrepresentation of data, and so on. The healthcare company runs disease management programs. The success rates of these programs are predicted using big data depending on how patients respond to it. The next sector we will look into is logistics. Logistics looks into the process of transportation and storage of goods. The movement of a product from its supplier to a consumer is very important. Big data is used to make this process faster and efficient. The most important factor in logistics is the time taken for the products to reach their destination. To achieve minimum time, sensors within the vehicle analyze the fastest route. This analysis is based on various data such as the weather, traffic, the list of orders, and so on. By doing so, the fastest route is obtained and the delivery time is reduced. Capacity planning is another factor which needs to be taken into consideration. Details regarding the workforce and the number of vehicles are analyzed thoroughly, and each vehicle is allocated a different route. This is done as there is no need for many trucks to travel in the same direction, which will be pointless. Depending on the analysis of the available workforce and resources, this decision is taken. Big data analytics also finds its use in managing warehouses efficiently. This analysis, along with tracking sensors, provide information regarding the underutilized space, which results in efficient resource allocation and eventually reduces the cost. Customer satisfaction is important in logistics just like it is in any other sector. Customer reactions are analyzed from the available data, which will eventually create an instant feedback loop. A happy customer will always help the company gain more customers. Let us now look into a use case of UPS. As you know, UPS is one of the biggest shipping company in the world. They have a huge customer database and they work on data every minute. UPS uses big data to gather different kinds of data regarding the weather, the traffic jams, the geography, the locations, and so on. After collecting all this data, they analyze it to discover the best and the fastest route to the destination. In addition to this, they also use big data to change the routes in real time. This is how efficiently UPS leverages big data. Next up, we have a very interesting sector, that is the travel and tourism sector. The global tourism market is expected to grow in the near future. Big data is used in various ways in this sector. Let us look into a few of them. Hotels can increase their revenue by adjusting the room tariffs depending on the peak seasons, such as holiday seasons, festive seasons, and so on. The tourism industry uses all of this data to anticipate the demand and maximize their revenue. Big data is also used by resorts and hotels to analyze various details regarding their competitors. This analysis result helps them to incorporate all the good facilities their competitors are providing, and by doing so, the hotel is able to flourish further. A customer always comes back if they are offered good packages which are more than just the basic ones. Looking into a customer's past travel history, likes, and preferences, hotels can provide its customers with personalized experiences which will interest them highly. Investing in an area which could be the hub of tourism is very wise. Few countries use big data to examine the tourism activities in their country, and this in turn helps them discover new and fruitful investment opportunities. Let us look into one of the best online homestay networks, Airbnb, and see how big data is used by them. Airbnb undoubtedly provides its customers with the best accommodation across the world. Big data is used by it to analyze the different kinds of available properties. Depending on the customer's preferences, the pricing, the keywords, previous customers, ratings, and experiences, Airbnb filters out the best result. Big data works its magic yet again. Now we will move on to our final sector, which is the government and law enforcement sector. Maintaining law and order is of utmost importance to any government. It is a huge task by itself. Big data plays an active role here, and in addition to this, it also helps governments bring in new policies and schemes for the welfare of its citizens. The police department is able to predict criminal activities way before it happens by analyzing big data information such as the previous crime records in a particular region, the safety aspect in that region, and so on. By analyzing these factors, they are able to predict any activity which breaks the law and order of the region. Governments are able to tackle unemployment to a great extent by using big data. By analyzing the number of students graduating every year to the number of relevant job openings, the government can have an idea of the unemployment rate in the country and then take necessary measures to tackle it. Our next factor is poverty. In large countries, it is difficult to analyze which area requires attention and development. Big data analytics makes it easier for governments to discover such areas. Poverty gradually decreases once these areas begin to develop. Governments have to always be on the lookout for better development. A public survey voices the opinion of a country's citizens. Analyzing all the data collected from such surveys can help governments build better policies and services which will benefit its citizens. Let us now move on to our use case. Did you know that the New York Police Department uses big data analytics to protect its citizens? The department prevents and identifies crimes by analyzing a huge amount of data, which includes fingerprints, certain emails, and records from previous police investigations, and so on. After analyzing all of this data, meaningful insights are drawn from it, which will help the police in taking the required preventive measures against crimes.
Now, when we talk about evolution of big data, we have known that data has evolved in last 5 years like never before. Now, in fact, before going to big data or before understanding these solutions and the need and why there is a rush towards big data technology and solution, I would like to ask a question. Take a couple of minutes and think, why are organizations interested in big data? Why is there sudden rush in industry where everyone would want to ramp up their current infrastructure or would want to be working on technologies which allow them to use this big data? Think about it. What is happening and why are organizations interested in this? And if you think on this, you will start thinking about what organizations have been doing in past, what organizations have not done, and why are organizations interested in big data. Now, before we learn on big data, we can always look into internet and check for use cases where organizations have failed to use legacy systems or relational databases to work on their data requirements. Now, over past 5 years or in recent decade, what has happened is organizations have started understanding the value of data, and they have decided not to ignore any data as being uneconomical. Now, we can talk about different platforms through which data is generated. Take an example of social media like Twitter, Facebook, Instagram, WhatsApp, YouTube. You have e-commerce and various portals, say eBay, Amazon, Flipkart, Alibaba.com. And then you have various tech giants such as Google, Oracle, SAP, Amazon, Microsoft, and so on. So lots of data is getting generated every day in every business sector. The point here is that organizations have slowly started realizing that they would be interested in working on all the data. Now, the question which I asked was, why are organizations interested in big data? And some of you might have already answered or thought about that organizations are interested in doing precise analysis, or they want to work on different formats of data, such as structured, unstructured, semi-structured data. Organizations are interested in gaining insights or finding the hidden treasure in the so-called big data. And this is the main reason where organizations are interested in big data. Now, there are various use cases. We can compare that organizations from past 50 or more than 50 years have been handling huge amount of data. They have been working on huge volume of data. But the question here is, have they worked on all the data or have they worked on some portion of it? What have they used to store this data? And if they have used something to store this data, what is happening? What is changing now? When we talk about the businesses, we cannot avoid talking about the dynamism involved. Now, any organization would want to have a solution which allows them to store data and store huge amount of data, capture it, process it, analyze it, and also look into the data to give more value to the data. Organizations have then been looking for solutions. Now let's look at some facts that can convince you, or that would convince you, that data is exploding and needs your attention, right? 55 billion messages and 4.5 billion photos are sent each day on WhatsApp. 300 hours of video are uploaded every minute on YouTube. Did you guys know that YouTube is the second largest search engine after Google? Every minute, users send 31.25 million messages and watch 2.77 million videos on Facebook. Walmart handles more than 1 million customer transactions every hour. Google, 40,000 search queries are performed on Google per second. That is 3.46 million searches a day. In fact, you could also say that a lot of times people, when they are loading up the Google page, is basically just to check their internet connection. However, that is also generating data. IDC reports that by 2025, real-time data will be more than a quarter of all the data. And by 2025, the volume of digital data will increase to 163 zettabytes. That is, we are not even talking about gigabytes or terabytes anymore. We are talking about petabytes, exabytes, and zettabytes. And zettabytes means 10 to the power 21 bytes. So this is how data has evolved. Now you can talk about different companies which would want to use their data to take business decisions. They would want to collect the data, store it, and analyze it. And that's how they would be interested in drawing insights for the business. Now, this is just a simple example about Facebook and what it does to work on the data. Now, before we go to Facebook, you could always check in Google by just typing in companies using big data. And if we say companies using big data, we should be able to find a list of different companies which are using big data for different use cases. There are various sources from where you can find. We could also search for solution, that is Hadoop, which we'll discuss later, but you could always say companies using Hadoop, and that should take you to the wiki page, which will basically help you know what are the different companies which are using this so-called solution called Hadoop. Okay, now coming back to what we were discussing about, so organizations are interested in big data, as we discussed, in gaining insights. They would want to use the data to find hidden information which probably they ignored earlier. Now take an example of RDBMS. What is biggest drawback in using an RDBMS? Now you might think that RDBMS is known for stability and consistency, and organizations would be interested in storing their data in Oracle or DB2 or MySQL or Microsoft SQL Server, and they have been doing that for many years now. So what has changed now? Now, when we talk about RDBMS, the first question which I would ask is, do we have access to 100% of data being online in RDBMS? The answer is no. We would only have 10 or 20 or 30% of data online, and rest of the data would be archived, which means that if an organization is interested in working on all the data, they would have to move the data from the archived storage to the processing layer, and that would involve bandwidth consumption. Now, this is one of the biggest drawbacks of RDBMS. You do not have access to 100% of data online. In many of the cases, organizations started realizing that the data which they were ignoring as being uneconomical had hidden value which they had never exploited. I had read a presentation somewhere which said, torture the data and it will confess to anything. Now that's the value of data which organizations have realized in recent past. Take an example of Facebook. Now this shows what Facebook does with its big data. And we'll come to what is big data, but let's understand a use case. Now Facebook collects huge volumes of user data, whether that is SMS, whether that is likes, whether that is advertisements, whether that is features which people are liking, or photographs, or even user profiles. Now by collecting this data and providing a portal which people can use to connect, Facebook is also accumulating huge volume of data. And that's way beyond petabytes. They would also be interested in analyzing this data. And one of the reasons would be they would want to personalize the experience. Take an example of personalized news feed. Depending on a user behavior, depending on what a user likes, what a user would want to know about, they can recommend a personalized news feed to every particular user. That's just one example of what Facebook does with its data. Take an example of photo tag suggestions. Now, when you log into Facebook account, you could also get suggestions on different friends whom you would like to connect to, or you would want to tag so that they could be known by others. Some more examples which show how Facebook uses its data are as follows. So the flashback, collection of photos and posts that receive the most comments and likes. Okay, there was something called as I voted that was used for 2016 elections with reminders and directions to tell users their time and place of polling. Also, something called as safety checks. In incidents such as earthquake, hurricane, or mass shooting, Facebook gives you safety checks. Now, these are some examples where Facebook is using big data. And that brings us to the question, what is big data? This was just an example where we discussed about one company which is making use of that data which has been accumulated. And it's not only for companies which are social media oriented like Facebook, where data is important. Take an example of IBM, take an example of JP Morgan Chase, take an example of GE, or any other organization which is collecting huge amount of data. They would all want to gather insights, they would want to analyze the data, they would want to be more precise in building their services or solutions which can take care of their customers. So what is big data? Big data is basically a term. It is used to describe the data that is too large and complex to store in traditional databases. And as I gave an example, it's not just about storing the data. It is also about what you can do with the data. It also means that if there is a lot of dynamism involved, can you change the underlying storage and handle any kind of data that comes in? Now, before we get into that, let's just understand what is big data. So big data is basically a term which has been given to categorize the data if it has different characteristics. Organizations would want to have the big data stored, processed, and then analyzed to get whatever useful information they can get from this data. Now, there are 5 V's of big data: volume, velocity, variety, value, veracity. Although these are 5 V's, but then there are other V's which also categorize the data as big data, such as volatility, validity, viscosity, virality of data. Okay, so these are 5 V's of big data, and if the data has one or all of these characteristics, then it can be considered as big data, including the other V's which I just mentioned. So volume basically means incredible amount of data, huge volumes of data generated every second. Now that could be used for batch processing, that could be used for real-time stream processing. Okay, you might have data being generated from different kind of devices like your cell phones, your social media websites, online transactions, wearable devices, servers, and these days with IoT, we are also talking about data getting generated via Internet of Things. That is, you could have different devices which could be communicating to each other. You could be getting data from radars or lidars or even camera sensors. So there is a huge volume of data which is getting generated. And if we are talking about data which has huge volume, which is getting generated constantly or has been accumulated over a period of time, we would say that is big data. Velocity. Now this is one more important aspect of big data. Speed with which the data is getting generated. Think about stock markets. Think about social media websites. Think about online surveys or marketing campaigns or airline industry. So if the data is getting generated with a lot of speed, where it becomes difficult to capture, collect, process, cure, mine, or analyze the data, then we are certainly talking about big data. The next aspect of big data is variety. Now this is where we talk about structured data, semi-structured data, or unstructured data. And here I would like to ask a question. What is the difference? When do you call the data as structured, semi-structured, or unstructured? Now let's look at an example before we theoretically discuss about this. I always would like to use some examples. Let's look at a log file and let's see what is it. So if I look at this log file and if I would say what kind of data is this, which is the highlighted one. The answer would be it is structured data. It has specific delimiters such as space. It has data which is separated by space. And if I had 100 or 1,000 or million rows which had similar kind of data, I could certainly store that in a table. I could have a predefined schema to store this data. So I would call the one which is highlighted as structured. But if I look at this portion where I would look at a combination of this kind of data where some data has a pattern and some data doesn't. Now this is an example of semi-structured data. So if I would have a predefined structure to store this data, probably the pattern of data would break the structure. And if I look at all the data, then I would certainly call it unstructured data because there is no clear schema which can define this data. Now this is what I mean by variety of data. That is structured data which basically has a schema or has a format which could be easily understood. You have semi-structured, which could be like in XML or JSON or even your Excel sheets, where you could have some data which is structured and the other is unstructured. And when we talk about unstructured, we are talking about absence of schema. It does not have a format, it does not have a schema, and it is hard to analyze, which brings its own challenges. The next aspect is value. Now, value refers to the ability to turn your data useful for business. You would have a lot of data which is being collected, as we mentioned in previous slides, right? There would be a lot of data wrangling or data pre-processing or cleaning up of data happening. And then finally, you would want to draw value from that data. But from all the data collected, what percentage of data gives us value? And if all my data can give me value, then why wouldn't I use it? This is an aspect of big data, right? Veracity. Now this means the quality of data. Billions of dollars are lost every year by organizations because the data which was collected was not of good quality, or probably they collected a lot of data and then it was erroneous. Take an example of autonomous driving projects which are happening in Europe or US, where there are car fleets which are on the road collecting data via radar sensors and camera sensors. And when this data has to be processed to train algorithms, it is realized that sometimes the data which was collected was missing in some values, might be was not appropriate, or had a lot of errors. And all this process of collecting the data becomes a repetitive task because the quality of data was not good. This is just one example. We can take example from healthcare industry or stock markets or financial institutions and so on. So extracting loads of data is not useful if the data is messy or poor in quality. And that basically means that veracity is a very important V of big data. Now, apart from veracity, volume, variety, velocity, and value, we have the other V's such as viscosity, how dense the data is. Validity, is the data still valid? Volatility, is my data volatile? Or virality, is the data viral? Now, all of these different V's categorize the data as big data. Now, here we would like to talk on a big data case study, and we have taken an example of Google, which obviously is one of the companies which is churning and working on huge amount of data. Now it's actually said that if you compare one grain of sand with one byte of data, then Google is processing or Google is handling whole world's sand every week. That is the kind of data which Google is processing. Now in early 2000 and since then, when the number of internet users started growing, Google also faced a lot of problems in storing, increasing user data, and using the traditional servers to manage that. Now that was a challenge which Google started facing. Could they use traditional data server to store the data? Well, yes, they could, right? Storage devices have been getting cheaper day by day. But then, how much time does it take to retrieve that data? What is the seek time? What is the time taken to read and process that data? Thousands of search queries were raised per second, no doubt. Now we could say millions and billions of queries are raised per second. Every query read 100 MBs of data and consumed tens of billions of CPU cycles based on these queries. So the requirement was that they wanted to have a large distributed, highly fault-tolerant file system. Large to store, to capture, process huge amount of data. Distributed because they could not rely just on one server. Even if that had multiple disks stacked up, that was not an efficient choice. What would happen if this particular machine failed? What would happen if the whole server was down? So they needed a distributed storage and a distributed computing environment. They needed something which can be highly fault tolerant, right? So this was the requirement which Google had, and the solution which came out as a result was GFS, Google File System. Now let's look at how GFS works. So normally in any particular Linux system or Linux server, you would have a file system. You would have set of processes, you would have set of files and directories which could store the data. GFS was different. So to facilitate GFS, which could store huge amount of data, there was an architecture which had one master and multiple chunk servers, or you can say slave servers or slave machines. Master machine was to contain metadata, was to contain data about data. When we say metadata, we are talking about information about data. And then you have the chunk servers or the slave machines which could be storing data in a distributed fashion. Now any client or an API or an application which would want to read the data would first contact the master server. It would contact the machine where the master process was running, and client would place a request of reading the data or showing an interest of reading the data. Internally, what it is doing is it is requesting for metadata. Your API or an application would want to know from where it can read the data. Master server, which has metadata, whether that is in RAM or disk, we can discuss that later. But then master server would have the metadata, and it would know which are the chunk servers or the slave machines where the data was stored in a distributed fashion. Master would respond back with the metadata information to the client, and then client could use that information to read or write to these slave machines where actually the data was stored. Now this is what the process or set of processes work together to make GFS. So when you say a chunk server, we would basically have the files getting divided into fixed size chunks. Now how would they get divided? So there would be some kind of chunk size or a block size which would determine that. If the file is bigger than the pre-decided chunk size, then it would be split into smaller chunks and be distributed across the chunk servers or the slave machines. If the file was smaller, then it would still use one chunk or a block to get stored on the underlying slave machines. So these chunk servers or slave machines are the ones which actually store the data on local disks as your Linux files. Client, which is interacting with master for metadata and then interacting with chunk servers for read-write operations, would be the one which would be externally connecting to the cluster. So this is how it would look. So you have a master which would obviously be receiving some kind of heartbeats from the chunk servers to know their status and receive information in the form of packets which would let the master know which machines were available for storage, which machines already had data, and master would build up the metadata within itself. The files would be broken down into chunks. For example, we can look at file 1. It is broken down into chunk 1 and chunk 2, and file 2 has one chunk which is one portion of it, and then you have file 2 residing on some other chunk server, which also lets us know that there is some kind of auto replication for this file system, right? And the data which is getting stored in the chunk could have a data of 64 MB. Now that chunk size could be changed based on the data size, but Google File System had the basic size of the chunk as 64 MB. Each chunk would be replicated on multiple servers. The default replication was 3, and that could again be increased or decreased as per requirement. This would also mean that if a particular slave machine or a chunk server would die or would get killed or would crash, there would never be any data loss, because a replica of data residing on the failed machine would still be available on some other slave server, chunk server, or slave machine. Now this helped Google to store and process huge volumes of data in a distributed manner and thus have a fault tolerant, distributed, scalable storage, which could allow them to store a huge amount of data. Now, that was just one example which actually led to the solution which today we call as Hadoop. Now, when we talk about big data, here I would like to ask you some questions that if we were talking about the RDBMS case, take an example of something like NASA, which was working on a project called SETI, Search of Extraterrestrial Intelligence. Now, this was a project where they were looking for a solution to take care of their problem. The problem was that they would roughly send some waves in space, capture those waves back, and then analyze this data to find if there was any extraterrestrial object in space. Now, they had two options for it. They could either have a huge server built which could take care of storing the data and processing it, or they could go for volunteer computing. Now, volunteer computing basically means that you could have a lot of people volunteering and being part of this project, and what they would in turn do is they would be donating their RAM and storage from their machines when they are not using it. How would that happen? Basically download some kind of patch on their machine which would run as a screensaver, and if the user is not using his machine, some portion of data could be transferred to these machines for intermittent storage and processing using RAM. Now, this sounds very interesting and this sounds very easy. However, it would have its own challenges, right? Think about security, think about integrity, but those problems are not bigger as much as is the requirement of bandwidth. And this is the same thing which happens in RDBMS. If you would have to move data from archived solution to the processing layer, that would consume huge amount of bandwidth. Big data brings its own challenges. Huge amount of data is getting generated every day. Now, the biggest challenge is storing this huge volume of data. And especially when this data is getting generated with a lot of variety, where it can have different kind of formats, where it could be viral, it could be having a lot of value, and nobody has looked into the veracity of data. But the primary problem would be handling this huge volume of data. Variety of the data would bring in challenges of storing it in legacy systems if processing of the data was required. Now, here again I would suggest you need to think what is the difference between reading a data and processing a data. So reading might just mean bringing in the data from disk and doing some IO operations, and processing would mean reading the data, probably doing some transformations on it, extracting some useful information from it, and then storing it in the same format or probably in a different format. So processing this massive volume of data is the second challenge. Organizations don't just store their big data. They would eventually want to use it, to process it, to gather some insights. Now, processing and extracting insights from big data would take huge amount of time unless and until there was an efficient solution to handle and process this big data. Securing the data, that's again a concern for organizations, right? Encryption of big data is difficult to perform. If you would think about different compression mechanisms, then that would also mean decompressing of data, which would also mean that you could take a hit on the CPU cycles or on disk usage. Providing user authentication for every team member, now that could also be dangerous. So that led to Hadoop as a solution. So big data brings its own challenges. Big data brings its own benefits. And here we have a solution which is Hadoop. Now, what is Hadoop? It's an open source framework for storing data and running applications on clusters of commodity hardware. Hadoop is an open source framework. And before we discuss on two main components of Hadoop, it would be good to look into the link which I was suggesting earlier, that is companies using Hadoop. And any person who would be interested in learning big data should start somewhere here, where you could list down different companies, what kind of setup they have, why are they having Hadoop, what kind of processing they are doing, and how are they using these so-called Hadoop clusters to process and in fact store, capture, and process huge amount of data. Another link which I would suggest is looking at different distributions of Hadoop. Any person who is interested in learning in big data should know about different distributions of Hadoop. Now in Linux, we have different distributions like Ubuntu, CentOS, Red Hat, SUSE, Debian. In the same way, you have different distributions of Hadoop, which we can look on the wiki page. And this is the link which talks about products that include Apache Hadoop or derivative works and commercial support, which basically means that Apache Hadoop, the sole products that can be called a release of Apache Hadoop come from apache.org. That's an open source community. And then you have various vendor specific distributions like Amazon Web Services, you have Cloudera, you have Hortonworks, you have IBM's Big Insight, you have Mapr. All these are different distributions of Hadoop. So basically all of these vendor specific distributions are depending or using on core Apache Hadoop. In brief, we can say that these are the vendors which take up the Apache Hadoop, package it within a cluster management solution so that users who intend to use Apache Hadoop would not have difficulties of setting up a cluster, setting up a framework. They could just use a vendor specific distribution with its cluster installation solutions, cluster management solution, and easily plan, deploy, install, and manage a cluster.
Let's rewind to the days before the world turned digital. Back then, minuscule amounts of data were generated at a relatively sluggish pace. All the data was mostly documents, and in the form of rows and columns. Storing or processing this data wasn't much trouble, as a single storage unit and processor combination would do the job. But as years passed by, the internet took the world by storm, giving rise to tons of data, generated in a multitude of forms and formats every microsecond. Semi-structured and unstructured data was available now in the form of emails, images, audio, and video, to name a few. All this data became collectively known as big data. Although fascinating, it became nearly impossible to handle this big data, and a storage unit processor combination was obviously not enough. So, what was the solution? Multiple storage units and processors were undoubtedly the need of the hour. This concept was incorporated in the framework of Hadoop that could store and process vast amounts of any data efficiently using a cluster of commodity hardware. Hadoop consisted of three components that were specifically designed to work on big data. In order to capitalize on data, the first step is storing it. The first component of Hadoop is its storage unit, the Hadoop Distributed File System, or HDFS. Storing massive data on one computer is unfeasible. Hence, data is distributed amongst many computers and stored in blocks. So, if you have 600 megabytes of data to be stored, HDFS splits the data into multiple blocks of data that are then stored on several data nodes in the cluster. 128 megabytes is the default size of each block. Hence, 600 megabytes will be split into 4 blocks, A, B, C, and D of 128 megabytes each, and the remaining 88 megabytes in the last block, E. So, now you might be wondering, what if one data node crashes? Do we lose that specific piece of data? Well, no. That's the beauty of HDFS. HDFS makes copies of the data and stores it across multiple systems. For example, when block A is created, it is replicated with a replication factor of 3 and stored on different data nodes. This is termed the replication method. By doing so, data is not lost at any cost, even if one data node crashes, making HDFS fault-tolerant. After storing the data successfully, it needs to be processed. This is where the second component of Hadoop, Mapreduce, comes into play. In the traditional data processing method, entire data would be processed on a single machine having a single processor. This consumed time and was inefficient, especially when processing large volumes of a variety of data. To overcome this, Mapreduce splits data into parts and processes each of them separately on different data nodes. The individual results are then aggregated to give the final output. Let's try to count the number of occurrences of words taking this example. First, the input is split into 5 separate parts based on full stops. The next step is the mapper phase, where the occurrence of each word is counted and allocated a number. After that, depending on the words, similar words are shuffled, sorted, and grouped. Following which, in the reducer phase, all the grouped words are given a count. Finally, the output is displayed by aggregating the results. All this is done by writing a simple program. Similarly, Mapreduce processes each part of big data individually and then sums the result at the end. This improves load balancing and saves a considerable amount of time. Now that we have our Mapreduce job ready, it is time for us to run it on the Hadoop cluster. This is done with the help of a set of resources, such as RAM, network bandwidth, and CPU. Multiple jobs are run on Hadoop simultaneously, and each of them needs some resources to complete the task successfully. To efficiently manage these resources, we have the third component of Hadoop, which is Yarn. Yet another resource negotiator, or Yarn, consists of a resource manager, node manager, application master, and containers. The resource manager assigns resources. Node managers handle the nodes and monitor the resource usage in the node. The containers hold a collection of physical resources. Suppose we want to process the Mapreduce job we had created. First, the application master requests the container from the node manager. Once the node manager gets the resources, it sends them to the resource manager. This way, Yarn processes job requests and manages cluster resources in Hadoop. In addition to these components, Hadoop also has various big data tools and frameworks dedicated to managing, processing, and analyzing data. The Hadoop ecosystem comprises several other components like Hive, Pig, Apache Spark, Flume, and Sqoop, to name a few. The Hadoop ecosystem works together on big data management.
Before we dive into the technical side of Hadoop, we're going to take a little detour to try to give you a visual understanding and relate it to maybe a more life setup. And we're going to go to the farm in this case. So we have in a farm far away. I almost wish they'd put far, far away. It does remind me a little bit of a Star Wars theme. So we're going to look at fruit at a farm. We have Jack who harvests grapes and then sells it in the nearby town. After harvesting, he stores his produce in a storage shed, or a storage room in this case. What we found out though is there was a high demand for other fruits, so he started harvesting apples and oranges as well. Hopefully he has a couple fields with these different fruit trees growing, and he set up there, and you can see that he's working hard to harvest all these different fruits, but he has a problem here because there's only one of him, so he can't really do more work. So what he needs to do then is hire 2 more people to work with him. With this, harvesting is done simultaneously. So instead of him trying to harvest all this different fruit, he now has 2 more people in there who are putting their fruit away and harvesting it for him. Now the storage room becomes a bottleneck to store and access all the fruits in a single storage area. So they can't fit all the fruit in one place. So Jack decides to distribute the storage area and give each one of them a separate storage. And you can look at this computer terms. We have our people that are the processors. We have our fruit that's the data, and you can see it's storing it in the different storage rooms. So you can see me popping up there getting my hello, I want fruit basket of 3 grapes, 2 apples, and 3 oranges. I'm getting ready for a breakfast with family, a very large family. My family's not that large. To complete the order on time, all of them work parallelly with their own storage space. So here we have a process of retrieving or querying the data, and you can see from the one storage space he pulls out 3 grapes, she pulls out 2 apples, and then another storage room he pulls out 3 oranges. And we complete a nice fruit basket, and this solution helps them to complete the order on time without any hassle. All of them are happy. They're prepared for an increase in demand in the future. So they now have this growth system where you can just keep hiring on new people. They can continue to grow and develop a very large farm. So how does this story relate to big data? And I hinted at that a little bit. Earlier, the limited data, only one processor, one storage unit was needed. I remember back in the 90s, they would just upgrade the computer. Instead of having a small computer, you would then spend money for a huge mainframe with all the flashing lights on it. Then the Cray computers were really massive. Nowadays, a lot of the computers that sits on our desktop are powerful as the mainframes they had back then. So it's pretty amazing how time has changed. But you used to be able to do everything on one computer, and you had structured data and a database you stored your structured data in. So most of the time you were querying databases, SQL queries. Just think of it as a giant spreadsheet with rows and columns where everything has a very specific size and fits neatly in that rows and columns. And back in the 90s, this was a nice setup. You just upgraded your computer, You would get yourself a nice big Sun computer or mainframe if you had a lot of data and a lot of stuff going on, and it was very easy to do. Soon, though, the data generation increased, leading to high volume of data along with different data formats. And so you can imagine, in today's world, this year we will generate more data than all the previous years summed together. We will generate more data just this year than all the previous years summed together. And that's the way it's been going for some time. And you can see we have a variety of data. We have our structured data, which is what you'd think about a database with rows and columns and easy to look at, nice spreadsheet. We have our semi-structured data. They have emails as an example here. That would be one example, your XML, your HTML, web pages. And we have unstructured data. If you ever look through your folder on photos, I have photos that were taken on my phone with high quality. I've got photos from a long time ago. I got web photos, low quality. So just in my pictures alone, none of them are the same. You know, there certainly are groups of them that are, but overall there are a lot of variety in size and setup. So a single processor was not enough to process such high volume of different kinds of data, as it was very time consuming. You can imagine that if you are Twitter with millions of Twitter feeds, you're not going to be able to do a query across one server. There's just no way that's going to happen unless people don't mind waiting a year to get the history of their tweets or look something up. Hence, we start doing multiple processors. So they're used to process high volume of data, and this saved time. So we're moving forward. We got multiple processors. The single storage unit became the bottleneck, due to which network overhead was generated. So now you have your network coming in, and each one of these servers has to wait before it can grab the data from the single stored unit. Maybe you have a SQL server there with a nice setup or a file system going. The solution was to use distributed storage for each processor. This enabled easy access to storage and access to data. So this makes a lot of sense. You have multiple workers, multiple storage units, just like we had our storage room and the different fruit coming in, your variety. You can see that nice parallel to working on a farm. Now we're dealing with a lot of data. It's all about the data now. This method worked, and there were no network overhead generated. You're not getting a bottleneck somewhere where people are just waiting for data being pulled or being processed. This is known as parallel processing with distributed storage. So parallel processing, distributed storage. And you can see here the parallel processing is your different computers running their processes, and distributed storage.
Here is a quick demo on setting up Cloudera Quick Start VM in case you are interested in working on a standalone cluster. You can download the Cloudera Quick Start VM. So you can just type in download Cloudera Quick Start VM and you can search for package. Now this can be used to set up a Quick Start VM, which would be a single node Cloudera based cluster. So you can click on this link, and then basically based on the platform which you would be choosing to install, such as using a VM box or which version of Cloudera you would install. So here I can select a platform, so I can choose virtual box, and then you can click on get it now. So give your details, and basically then it should allow you to download the Quick Start VM, which would look something like this. And once you have the zip file which is downloaded, you can unzip it, which can then be used to set up a single node Cloudera cluster. So once you have downloaded the zip file, that would look something like this. So you would have a Quick Start VirtualBox and then a VirtualBox disk. Now this can be used to set up a cluster. Ignore these files which are related to Amazon machines, and you don't need to have that. So you would just have this, and this can be used to set up a Cloudera cluster. So for this to be set up, you can click on File, Import Appliance, and here you can choose your Quick Start VM by looking into Downloads, Quick Start VM, select this and click on Open. Now you can click on Next, and that shows you the specifications of CPU, RAM, which we can then change later, and click on Import. This will start importing virtual disk image .vmdk file into your VM box. Once this is done, we will have to change the specifications of our machines to use 2 CPU cores minimum and give a little more RAM, because Cloudera Quick Start VM is very CPU intensive and it needs good amount of RAM. So to survive, I will give 2 CPU cores and 5 GB RAM, and that should be enough for us to bring up a Quick Start VM which gives us a Cloudera distribution of Hadoop in a single node cluster setup, which can be used for working, learning about different distributions in Cloudera cluster, working with HDFS and other Hadoop ecosystem components. Let's just wait for this importing to finish, and then we will go ahead and set up a quick start VM for our practice. Here, the importing of appliance is done, and we see Cloudera quick start machine is added to my list of machines. I can click on this and click on settings. As mentioned, I would like to give it more RAM and more CPU cores. So click on system, and here let's increase the RAM to at least 5 and click on processor, and let's give it 2 CPU cores, which would at least be better than using 1 CPU core. Network, it goes for NAT, and that's fine. Click on OK, and we would want to start this machine so that it uses 2 CPU cores, 5 GB RAM, and it should bring up my Cloudera Quick Start VM. Now let's go ahead and start this machine, which has our Quick Start VM. It might take initially some time to start up because internally there will be various Cloudera services which will be starting up, and those services need to be up for our Cloudera Quick Start VM to be accessible. So unlike your Apache Hadoop cluster, where we start our cluster and we will be starting all our processes, in case of Cloudera, it is your Cloudera SCM server and agents which take care of starting up of your services and starting up of your different roles for those services. I explained in my previous session that for a Cloudera cluster, it would be these services. Let me just show you that. So in case of Apache cluster, we start our services, that is, we start our cluster by running script, and then basically those scripts will individually start the different processes on different nodes. In case of Cloudera, we would always have a Cloudera SCM server which would be running on one machine, and then including that machine, we would have Cloudera SCM agents which would be running on multiple machines. Similarly, if we had a Hortonworks cluster, we would have Ambari server starting up on the first machine and then Ambari agents running on other machines. So your server component knows what are the services which are set up, what are their configurations, and agents running on every node are responsible to send heartbeats to the server, receive instructions, and then take care of starting and stopping up of individual roles on different machines. In case of our single node cluster setup in Quick Start VM, we would just have one SCM server and one SCM agent which will start on the machine, which will then take care of all the roles which need to be started for your different services. So we will just wait for our machine to come up and basically have Cloudera SCM server and agent running. And once we have that, we need to follow few steps so that we can have the Cloudera admin console accessible, which allows you to browse the cluster, look at different services, look at the roles for different services, and also work with your cluster either using command line or using the web interface, that is Hue. Now that my machine has come up and it already is connected to the internet, which we can see here, we need to do certain things so that we can have our admin console accessible. At this point of time, you can click on terminal and check if you have access to the cluster. So here type in host name, and that shows you your host name, which is quickstart.cloudera. We can also type in HDFS command to see if we have access and if my cluster is working. These commands are same as you would give them in a Apache Hadoop cluster or in any other distribution of Hadoop. Sometimes when your cluster is up and you have access to the terminal, it might take few seconds or few minutes before there is a connection established between Cloudera SCM server and Cloudera SCM agent running in the background, which takes care of your cluster. I have given HDFS DFS list command, which basically should show me what by default exists on my HDFS. Let's just give it a couple of seconds before it shows us the output. We can also check by giving a service Cloudera SCM server status, and here it tells me that if you would want to use Cloudera Express free, run this command. It needs 8 GB of RAM and at least 2 virtual CPU cores. And it also mentions it may take several minutes before Cloudera Manager has started. I can log in as root here and then give the command service Cloudera SCM server status. Remember, the password for root is Cloudera. So it basically says that if you would want to check these settings, it is good to have Express Edition running. So we can close this. My HDFS access is working fine. Let's close the terminal, and here we have launch Cloudera Express. Click on this, and that will give you that you need to give a command which is force. Let's copy this command. Let's open a different terminal and let's give this command like this, which will then go ahead and shut down your Cloudera based services, and then it will restart it, only after which you will be able to access your admin console. So let's just give it a couple of minutes before it does this, and then we will have access to our admin console. Here, if you see, it is starting the Cloudera Manager server again. It is waiting for Cloudera Manager API, then starting the Cloudera Manager agents, and then configuring the deployment as per the new settings which we have given as to use the Express Edition of Cloudera. Once all this is done, it will say the cluster has been restarted and the admin console can be accessed by ID and password as Cloudera. We'll give it a couple of more minutes, and once this is done, we are ready to use our admin console. Now that deployment has been configured, client configurations have also been deployed, and it has restarted the Cloudera management service, it gives you an access to quick start admin console using username and password as Cloudera. Let's try accessing it. So we can open up the browser here and let's change this to 7180. That's the default port, and that shows the admin console which is coming up. Now here we can log in as Cloudera, and then let's click on login. Now, as I said, Cloudera is very CPU intensive and memory intensive, so it would slow down since we have not given enough GB RAM to our Cloudera cluster, and thus it will be advisable to stop or even remove the services which we don't need. Now, as of now, if we look at the services, all of them look in a stop status, and that's good in one way because we can then go ahead and remove the services which we will not use in the beginning, and later we can anytime add services to the cluster. So for example, I can click on key value store here, and then I can scroll down where it says delete to remove this service from the admin console. Now anytime you are removing a particular service, it will only remove the service from the management by Cloudera Manager. All the role groups under this service will be removed from host templates. So we can click on delete. Now if this service was depending on some other service, it would have prompted me with a message that remove the relevant services on which this particular service depends. If the service was already running, then it would have given me a message that the service has to be stopped before it can be deleted from the Cloudera admin console. Now this is my admin console, which allows you to click on services, look at the different roles and processes which are running for this service. We anyways have access to our Cloudera cluster from the terminal using our regular HDFS or yarn or Mapred commands. Now I removed a service. I will also remove Solar, which we will not be using for the beginning, but then it depends on your choice. So we can here scroll down to delete it, and that says that before deleting the Solar service, you must remove the dependencies on this service from the configuration of following services, that is Hue. Now Hue is a web interface which allows you to work with your SDFS, and that is depending on this. So click on configure service dependency, and here we can make sure that our Hue service does not depend on a particular service we are removing, so that then we can have a clean removal of the service. So I'll click on none and I will say save changes. Once this is done, then we can go ahead and try removing the Solar service from our admin console, which will reduce some load on my management console, which will also allow me to work faster on my cluster. Now here we have removed the dependency of Hue on Solar, so we can click on this and then we can delete it. Remember, I'm only doing this so that my cluster becomes a little lighter and I can work on my focus services. At any point of time, if you want to add more services to your cluster, you can anytime do that. You can fix different configuration issues like what we see here with different warning messages. And here we have these services which are already existing. Now, if we don't need any of the service, I can click on the drop down and click on delete. Again, this says that Sqoop 2 also has relevance to Hue. So Hue as a web interface also depends on Sqoop 2. As of now, we'll make it none. At any point of time later, you can add the services by clicking the add service option. Now this is a cluster to which you have admin access, and this is a quick start VM which gives you a single node Cloudera cluster which you can use for learning and practicing. So here we'll click on Sqoop 2 and then we will say delete, as we have configured the dependency now, and we will remove Sqoop 2 also from the list of services which your admin console is managing, right? So once this is done, we have removed 3 services which we did not need. We can even remove Sqoop as a client, and if we need, we can add that later. Now there are various other alerts which your Cloudera admin console shows, and we can always fix them by clicking on the health issues or configuration issues. We can click here and see what is the health issue it is pointing to, if that is a critical one or if that can be ignored. So it says there is an issue with a clock offset, which basically relates to an NTP service, network time protocol, which makes sure that one or multiple machines are in the same time zone and are in sync. So for now, we can click on suppress and we can just say suppress for all hosts, and we can say look into it later and confirm. So now we will not have that health issue reported, that probably the NTP service and the machines might not be in sync. Now that does not have an impact for our use case as of now, but if we have a Kerberos kind of setup which is for security, then basically this offset and time zone becomes important. So we can ignore this message and we are still good to use the cluster. We also have other configuration issues, and you can click on this, which might talk about the heap size or the RAM which is available for machines. It talks about Zookeeper should be in odd numbers. Hue does not have a load balancer. HDFS only has one data node. But all of these issues are not to be worried upon because this is a single node cluster setup. So if you want to avoid all of these warnings, you can always click on suppress and you can avoid and let your cluster be in all green status. But that's nothing to worry. So we can click on cluster and basically we can look at the services. So we have removed some services which we don't intend to use now. I have also suppressed a offset warning which is not very critical for my use case, and basically I'm good to start the cluster. At any point of time, as I said, if you would want to add services, this is the actions button which you can use to add service. So we will just say restart my cluster, which will restart all the services one by one, starting from Zookeeper as the first service to come up. We can always click on this arrow mark and see what is happening in the services, what services are coming up and in which order. If you have any issues, you can always click on the link next to it, which will take you to the logs, and we can click on close to let it happen in the background. So this will basically let my services restart one by one, and my cluster will then become completely accessible either using Hue as a web interface or quick start terminal, which allows you to give your commands. Now while my machines are coming up, you can click on hosts and you can have a look at all the hosts we have. As of now only one, which will also tell you how many roles or processes are running on this machine. So that is 25 roles. It tells you what is the disk usage. It tells you what is the physical memory being used. And using this host tab, we can add new hosts to the cluster. We can check the configuration. We can check all the hosts. In diagnostics, you can look at the logs, which will give you access to all the logs. You can even select the sources from which you would want to have the logs, or you can give the host name. You can click on search. You can build your own charts. You can also do the admin stuff by adding different users or enabling security using the administration tab. So since we have clicked on restart of a cluster, we will slowly start seeing all the services one by one coming up, starting with Zookeeper to begin with. And once we have our cluster up and running, whether that is showing all services in green or in a different status, we still should be able to access the service. Now, as we saw in Apache Hadoop cluster, even here we can click on HDFS and we can access the web UI once our HDFS service is up by clicking on quick links. So the service is not yet up. Once it is up, we should be able to see the web UI link, which will allow you to check things from HDFS web interface. Similarly, Yarn as a service also has a web interface. So as soon as the service comes up, under your quick links, we will have access to the Yarn UI. And similarly, once the service comes up, we will have access to Hue, which will give you the web interface, which allows you to work with your HDFS, which allows you to work with your different other components within the cluster without even using the command line tools or command line options. So we will have to give it some time while the Cloudera SCM agent on every machine will be able to restart the roles which are responsible for your cluster to come up. We can always click here, which tells that there are some running commands in the background which are trying to start my cluster. We can go to the terminal and we can switch as HDFS user. Remember, HDFS user is the admin user and it does not have a password unless you have set one. So you can just log in as HDFS, which might ask you for a password initially, which we do not have. So the best way to do this is by logging in as root, where the password is Cloudera, and then you can log in as HDFS, so that then onwards you can give your HDFS commands to work with your file system. Now, since my services are coming up right now, when I try to give a HDFS DFS command, it might not work, or it might also say that it is trying to connect to the name node which is not up yet. So we will have to give it some time, and only once the name node is up, we will be able to access our HDFS using commands. So this is how you can quickly set up your quick start, and then you can be working using the command line options from the terminal, like what you would do in an Apache Hadoop cluster. You could use the web interfaces which allow you to work with your cluster. Now, this usually takes more time, so you will have to give it some time before your services are up and running. And for any reason, if you have issues, it might require you to restart your cluster several times in the beginning before it gets accustomed to the settings what you have given and it starts up the services. At any point of time, if you have any error message, then you can always go back and look in logs and see what is happening and try starting your cluster. So this is how we set up a quick start VM, and you can be using this to work with your Cloudera cluster.
We'll start with the big data challenges. And the first thing with the big data is you can see here we have a nice chaotic image with all these different inputs, server racks all over the place, graphs being generated, just about everything you can imagine. And so the problems that come up with big data is, one, storing it. How do you store this massive amount of data? And we're not talking about a terabyte or 10 terabytes. We're talking a minimal of 10 terabytes up to petabytes of data. And then the next question is processing. And so the two go hand in hand, because when you're storing the data, that might take up a huge amount of space. Or you might have a small amount of data that takes a lot of processing. And so either one will drive a series of data or processing into the big data arena. So with storing big data was a problem due to its massive volume, just straight up. People would have huge backup tapes, and then you'd have to go through the backup tapes for hours to go find your data, and a simple query could take days. And then processing. Processing big data consumed more time, and so the Hadoop came up with a cheap way to process the data. It used to be like, I've had some processes that if I ran on my computer without trying to use multiple cores and multiple threads, would take years to process. Just a simple data analysis can get that heavy in the data processing. And so processing can be as big of a problem as the size of the data itself. So Hadoop as a solution. This is the solution to big data and big data storage. Storing big data data was a problem due to its massive volume. So we take the Hadoop file system, or the HDFS, and now we're able to store huge data across a large number of machines and access it like it's one file system. And processing big data consumed more time. We talked about some processes you can't even do on your computer because it would take years. Now the Hadoop with the Mapreduce, processing big data was faster. And I'm going to add a little notation right here that's really important to note that Hadoop is the beginning. When we talk about data processing, they've added new processes on top of the Mapreduce that even accelerate it, your Spark setup and some other different functionalities. But really, the basis of all of it, where it all starts with the most basic concept, is your Hadoop Mapreduce. Let us now look into the HDFS in detail. In the traditional approach, all the data was stored in a single central database. With the rise of big data, a single database was not enough for storage. And I remember the old Sun computers or the huge IBM machines with all the flashing lights. Now all the data on one of those can be stored on your phone. It's almost a bit of humor how much this has accelerated over the years. The same thing with our rise of big data. No longer can you just store it on one machine. No longer can you go out and buy a Sun computer and put it on that one Sun computer. No more can you buy a Craig machine or an enterprise IBM server. It's not going to work. You're not going to fit it all into one server. The solution was to use distributed approach to store the massive amount of data. Data was divided and distributed amongst many individual databases. And you can see here where we have 3 different databases going on. So you might actually saw this in one where they divided up the user accounts A through G, so on, by the letter. And so the first query would say, what's the first letter of this, whatever ID it was, and then it would go into that database to find it. So it had a database telling it which database to look for stuff. That was a long time ago, and to be honest, it didn't work really well. Nowadays, so that was a distributed database. You'd have to track which database you put it in. So what is HDFS? Hadoop Distributed File System, HDFS, is a specially designed file system for storing huge data sets in commodity hardware. And commodity is an interesting term because I mentioned enterprise versus commodity. And I'll touch back upon that. It has 2 core components, name node and data node. Name node is the master daemon. There's only one active name node. It manages the data nodes and stores all the metadata. So it stores all the mapping of where the data is on your Hadoop file system. Now the name node is usually an enterprise machine. You spend a lot of extra money on it, so you have a very solid name node machine. And so then we have our data nodes. Our data node, data node, data node, we have 3 here. The data node is the slave. There can be multiple data nodes, and it stores the actual data. And this is where your commodity hardware comes in. The best definition I've heard of commodity hardware is the cheap knockoffs. This is where you can buy 10 of these and you expect one of them not to work because, when they come in, they're going to break right away. So you're looking at hardware that's not as high end. So where you might have your main master node as your enterprise server, then your data nodes are just as cheap as you can get them with all the different features you need on them. As said earlier, name node stores the metadata. Metadata gives information regarding the file location, block size, and so on. So our metadata in the HDFS is maintained by using 2 files. It has the edit log and the FS image. The edit log keeps track of the recent changes made on the Hadoop file system. Only recent changes are tracked here. The FS image keeps track of every change made on the HDFS since the beginning. Now what happens when the edit log file size increases? The name node fails. These are big ones. So what happens, we get our edit log, it just keeps so big until it's too big. Or our main enterprise computer that we spent all that money on so it wouldn't break actually fails because they still fail. The solution, we make copies of the edit log and the FS image files. So that's pretty straightforward. You just copy them over so you have both the most recent edits going on and the long-term image of your file system. And then we also create a secondary name node. It's a node that maintains the copies of the edit log and the FS image. It combines them both to get an updated version of the FS image. Now, the secondary name node only came in the last, 2-3 years where it became as part of the main system. And usually your secondary name node is also an enterprise computer. And you'll put them on separate racks. So if you have 3 racks of computers, you would have maybe the first 2 racks would have the name node and the second rack would have the secondary name node. And the reason you put them on different racks is you can have a whole rack go down. You could have somebody literally trip over the power cable, or the switch that goes between the racks is most common, goes down. Well, if the switch goes down, you can easily switch to the secondary name node And while you're getting your switch replaced and replacing that hardware, because of the way the HDFS works, it still is completely functional. So let's take a look at the name node. We have our edit log, our FS image, and we have our secondary name node. And you take that, it copies the edit log over, and it copies the FS image. And you can see right here you have all the different contents on your main name node now also on your secondary name node. And then your secondary name node will actually take these two, your edit log and your FS image, and it will make a copy so you have a full FS image that contains, it's current, it's up to date. The secondary name node creates a periodic checkpoint of the files, and then it updates the new FS image into the name node. Now it used to be this all occurred on the name node before you had a secondary name node. So now you can use your secondary name node to both back up everything going on the name node, and it does that lifting in the back where you're combining your edit log and bring your FS image so it's current. And then you end up with a new edit log and you have your FS image updated, and you start a fresh edit log. This process of updating happens every hour, and that's how it's scheduled. You can actually change those schedules, but that is the standard, is to update every hour. So we took a look at the master node and the name node and the secondary name node. Let's take a look at the cluster architecture of our Hadoop file system. The HDFS cluster architecture. So we have our name node, and it stores the metadata, and we have our block location. So we have our FS image plus our edit log, and then we have the backup FS image and edit log. And then we have, so you have your rack, we have our switch on top. Remember I was talking about the switch? That's the most common thing to go in the rack, is the switches. And underneath the rack, you have your different data nodes. You have your data node 1, 2, 3, 4, 5. Maybe you have 10, 15 on this rack. You can stack them pretty high nowadays. It used to be you'd only get about 10 servers on there, but now you see racks that contain a lot more. And then you have multiple racks. So we're not talking about just one rack. We also have, rack 2, rack 3, 4, 5, 6, and so on until you have rack N. So if you had 100 data nodes, we would be looking at 10 racks of 10 data nodes each. And that is literally 10 commodity server computers, hardware. And we have a core switch which maintains the network bandwidth and connects the name node to the data nodes. So just like each rack has a switch that connects all your nodes on the rack, you now have core switches that connect all the racks together. And these also connect into our name node setup. So now it can look up your FS image and your edit log and pull that information, your metadata out. So we've looked at the architecture from the name node coming down, and you have your metadata, your block locations. This then sorts it out. You have your core switches which connect everything, all your different racks, and then each individual rack has their own switches which connect all the different nodes and to the core switches. So now let's talk about the actual data blocks, what's actually sitting on those commodity machines. And so the Hadoop file system splits massive files into small chunks. These chunks are known as data blocks. Each file in the Hadoop file system is stored as a data block. And we have a nice picture here where it looks like a Lego. If you ever played with the Legos as a kid, it's a good example. We just stack that data right on top of each other, but each block has to be the same symmetry, has to be the same size so that it can track it easily. And the default size of one data block is usually 128 megabytes. Now you can go in and change that. This standard is pretty solid as far as most data is concerned when we're loading up huge amounts of data. And there's certainly reasons to change it. But 128 megabytes is pretty standard block. So why 128 megabytes? If the block size is smaller, then there will be too many data blocks along with lots of metadata, which will create overhead. So that's why you don't really want to go smaller on these data blocks unless you have a very certain kind of data. Similarly, if the block size is very large, then the processing time for each block increases. Then as I pointed out earlier, each block is the same size, just like your Lego blocks are all the same. But the last block can be the same size or less. So you might only be storing 100 megabytes in the last block. And you can think of this as if you had a terabyte of data that you're storing on here. It's not going to be exactly divided into 128 megabytes. We just store all of it at 128 megabytes except for the last one, which could have anywhere between 1 and 128 megabytes depending on how evenly your data is divided. Now let's look into how files are stored in the Hadoop file system. So we have a file, a text, let's say it's 520 megabytes. We have block A. So we take 128 megabytes out of the 520 and we store it in block A. And then we have block B. Again, we're taking 128 megabytes out of our 520 and storing it there. And so on. Block C, block D, and then block E, we only have 8 megabytes left. So when you add up 128 plus 128 plus 128 plus 128, you only get 512. And so that last 8 megabytes goes into its own block. The final block uses only the remaining space for storage. Data node failure and replication. And this is really where Hadoop shines. This is what makes it, this is why you can use it with commodity computers. This is why you can have multiple racks and have something go down. All the data blocks are stored in various data nodes. You take each block, you store it at 128 megabytes, and then we're going to put it on different nodes. So here's our block A, block B, block C from our last example. And we have node 1, node 2, node 3, node 4, node 5, node 6. And so each one of these represents a different computer. It literally splits the data up into different machines. So what happens if node 5 crashes? Well, that's a big deal. I mean, we might not even have just node 5. You might have a whole rack go down. And if you're a company that's building your whole business off of that, you're going to lose a lot of money. So what does happen when node 5 crashes or the first rack goes down? The data stored in node 5 will be unavailable as there's no copy stored elsewhere in this particular image. So the Hadoop file system overcomes the issue of data node failure by creating copies of the data. This is known as the replication method. And you can see here we have our 6 nodes. Here's our block A, but instead of storing it just on the first machine, we're actually going to store it on the second and fourth nodes. So now it's spread across 3 different computers. And in this, if these are on a rack, one of these is always on a different rack. So you might have 2 copies on the same rack, but you never have all 3 on the same rack. And you never have more than 2 copies on one node. There's no reason to have more than 1 copy per node. And you can see we do the same thing with block B. Block C is then also spread out across the different machines, and same with block D and block E. Node 5 crashes. Will the data blocks B, D, and E be lost? Well, in this example, no, because we have backups of all 3 of those on different machines. The blocks have their copies in the other nodes, due to which the data is not lost, even if the node 5 crashes. And again, because they're also stored on different racks, even if the whole rack goes down, you are still up and live with your Hadoop file system. The default replication factor is 3. In total, we'll have 3 copies of each data block. Now that can be changed for different reasons or purposes, but you got to remember when you're looking at a data center, this is all in one huge room. These switches are connecting all these servers so they can shuffle the data back and forth really quick. And that is very important when you're dealing with big data. And you can see here each block is by default replicated 3 times. That's the standard. There is very rare occasions to do 4, and there's even fewer reasons to do 2 blocks. I've only seen 4 used once, and it was because they had 2 data centers, and so each data center kept 2 different copies. Rack awareness in the Hadoop file system. Rack is a collection of 30 to 40 data nodes. Rack awareness is a concept that helps to decide where the replica of the data block should be stored. So here we have rack 1, we have our data node 1 to 4. Remember I was saying that it used to be you'd only put 10 machines, and then it went to 20, now it's 30 to 40. So you can have a rack with 40 servers on it. Then we have rack 2 and rack 3, and we put block 1 on there. Replicas of block A cannot be in the same rack, and so it'll put the replicas onto a different rack. And notice that these 2 are on the same rack, but you'll never have all 3 stored on the same rack in case the whole rack goes down. And replicas of block A are created in rack 2. And they do by default create the replicas onto the same rack, and that has to do with the data exchange and maximizing your processing time. And then we have of course our block B, and it's replicated onto rack 3, and block C, which will then replicate onto rack 1, and so on for all of your data all the way up to block D or whatever, how much ever data you have on there. HDFS architecture. So let's look over the architecture as a bigger picture. We looked at the name node, and we store some metadata, names, replicas, home, food, data 3. So it has all your different your metadata stored on there. And then we have our data nodes, and you can see our data nodes are each on different racks with our different machines. And we have our name node, and you're going to see we have a heartbeat or pulse here. And a lot of times, one of the things that confuses people sometimes in classes, they talk about nodes versus machines. So you could have a data node that's a Hadoop data node, and you could also have a Spark node on there. Spark's a different architecture. And these are each daemons that are running on these computers. That's why you refer to them as nodes and not just always as servers and machines. So even though I use them interchangeable, be aware that these nodes, you can even have virtual machines if you're testing something out. It doesn't make sense to have 10 virtual nodes on one machine and deploy it, because you might as well just run your code on the machine. And so we have our heartbeat going on here. And the heartbeat is a signal that data nodes continuously send to the name nodes. This signal shows the status of the data node. So there's a continual pulse going up and saying, hey, I'm here, I'm ready for whatever instructions or data you want to send me. And you can see here where we've divided up into rack 1 and rack 2 and our different data nodes. And it also have the replications. We talked about how to replicate data, and it replicates it in 3 different locations. And then we have a client machine. And the client first requests the name node to read the data. Now, if you're not familiar with the client machine, the client is you, the programmer. And the client is, you've logged in external to this Hadoop file system, and you're sending it instructions. And so the client, whatever instructions or script you're sending, is first request the name node to read the data. The name node allows the client to read the requested data from the data nodes. The data is read from the data nodes and sent to the client. And so you can see here that basically the name node connects the client up and says, here's a data stream, and now you have the query that you sent out returning the data you asked for. And then of course it goes and finishes it and says, oh, metadata operations, and it goes in there and finalizes your request. The other thing the name node does as you're sending your information, because the client sends the information in there, is your block operations. So your block operations are performs creation of data. So you're going to create new files and folders, you're going to delete the folders, and also it covers the replication of the folders, which goes on in the background. And so we can see here that we have a nice full picture. You can see where the client machine comes in, it queues the metadata, the metadata goes into, it stores the metadata, and then it goes into block operations, and maybe you're sending the data to the Hadoop file system, maybe you're querying, maybe you're asking it to delete. If you're sending data in there, it then does the replication on there. It goes back, so you have your data client, which is writing the data into the data node, and of course replicating it. And that's all part of the block operations. And so let's talk a little bit about read mechanisms in the Hadoop file system. The Hadoop file system read mechanism. We have our Hadoop file system client, that's you on your computer, and the client JVM on the client node. And so we have our client JVM, or the Java virtual machine that is going through, and then your client node. And we're zooming in on the read mechanism. So we're looking at this picture here. As you can guess, your client is reading the data, and I also have another client down here writing data. We're going to look a little closer at that. And so we have our name node up here. We have our racks of your data nodes and your racks of computers down here. And so our client, the first thing it does is it opens a connection up with the distributed file system to the HDFS. And it goes, hey, can I get the block locations? And so it goes by using the RPC remote procedure call, it gets those locations. And the name node first checks if the client is authorized to access the requested file. And if yes, it then provides a block location and a token to the client, which is shown to the slave for authentication. So here's the name node. It tells the client, hey, here's the token. The client's going to come in and get this information from you. And it tells the client, oh, hey, here's where the information is. So this is what it's telling your script you sent to query your data, whether you're writing your script in one of the many setups that you have available through the Hadoop file system or a connection through your code. And so you have your client machine at this point then reads. So your FS data input stream comes through, and you can see right here, we did 1 and 2, which is verify who you are and give you all the information you need. Then 3, you're going to read it from the input stream, and then the input stream is going to grab it from the different nodes where it's at, and it'll supply the tokens to those machines saying, hey, this client needs this data, here's a token for that, we're good to go, let me have the data. The client will show the authentication token to the data nodes for the read process to begin. So after reaching the end of the data block, the connection is closed. And we can see here where we've gone through the different steps, get block locations. We have step 1, you open up your connection, you get the block locations by using the RPC, then you actively go through the FS data input stream to grab all those different data, brings it back into the client, and then once it's done, it closes down that connection. And then once the client, or in this case the programmer, manager's gone in and pig script, you can do that, there's an actual coding in Hadoop for pulling data called pig or Hive. Once you get that data back, we close the connection, delete all those randomly huge series of tokens so they can't be used anymore, and then it's done with that query. And we can go ahead and zoom in just a little bit more here, and let's look at this even a little closer. Here's our Hadoop file system client and our client JVM, our Java virtual machine, on the client node. And we have the data to be read, block A, block B. And so we request to read block A and B, and it goes into the name node. 2, then it sends the location, in this case IP addresses of the blocks for the DN1 and DN2 where those blocks are stored. Then the client interacts with the data nodes through the switches. And so you have here the core switch. So your client node comes in, 3, and it goes to the core switch, and that then goes to rack switch 1, rack switch 2, and rack switch 3. Now, if you're looking at this, you'll automatically see a point of failure in the core switch, and certainly you want a high-end switch mechanism for your core switch. You want to use enterprise hardware for that. And then when you get to the racks, that's all commodity. All your rack switches, so if one of those goes down, you don't care as much. You just have to get in there and swap it in and out really quick. You can see here we have block A, which is replicated 3 times, and so is block B, and it'll pull from there. So we come in here, and here the data is read from the DN1 and DN2 as they are the closest to each other. And so you can see here that it's not going to read from 2 different racks, it's going to read from 1 rack, whatever the closest setup is for that query. The reason for this is if you have 10 other queries going on, you want this one to pull all the data through one setup, and it minimizes that traffic. So the response from the data nodes to the client that read the operation was successful. It says, we've read the data, we're successful, which is always good. We like to be successful. I don't know about you, I like to be successful. So if we're looking at the read mechanism, let's go ahead and zoom in and look at the write mechanism for the Hadoop file system. So our HDFS write mechanism. And so when we have the HDFS write mechanism, here's our client machine. This is again the programmer on their in computer, and it's going through the client Java machine or Java virtual machine, the JVM. And this is all occurring on the client node, somebody's office, or maybe it's on the local server for the office. So we have our name node, we have data nodes, and we have the distributed file system. So the client first executes create file on the distributed file system. It says, hey, I'm going to create this file over here. And then it goes through the RPC call, just like our read did. The client first executes create file on the distributed file system. Then the DFS interacts with the name node to create a file. Name node then provides a location to write the data. And so here we have our HDFS client and the FS data output stream. So this time, instead of the data going to the client, it's coming from the client. And so here the client writes the data through the FS data output stream. Keep in mind that this output stream, the client could be a streaming code. It could be, I always refer to the client as just being this computer that your programmer is writing on. It could be you have your SQL server there where your data is, that's current with all your current cells, and it's archiving all that information through Sqoop, one of the tools in the Hadoop file system. It could be streaming data. It could be a connection to the stock servers, and you're pulling stock data down from those servers at a regular time, and that's all controlled. You can actually set that code up to be controlled in many of the different features in the Hadoop file system and some of the different resources you have that sit on top of it. So here the client writes the data through the FS data output stream, and the FS data output stream, as you can see, goes into write packet. So it divides it up into packets, 128 megabytes. And the data is written, and the slave further replicates it. So here's our data coming in, and then if you remember correctly, that's part of the FS data setup, is it tells it where to replicate it out. But the data node itself is like, oh, hey, okay, I've got the data coming in, and it's also given the tokens of where to send the replications to. And then acknowledgement is sent after the required replicas are made. So then that goes back up saying, hey, successful, I've written data, made 3 replications on this, as far as our, going through the pipeline of the data nodes. And then that goes back and it says, after the data is written, the client performs the close method. So the client's done, it says, okay, I'm done, here's the end of the data, we're finished. And after the data is written, the client performs a close method. And we can see here, just a quick reshape, we go in there just like we did with the read, we create the connection. This creates a name node, which lets it know what's going on. Step 2, step 3, that also includes the tokens and everything. And then we go into step 3, where we're now writing through the FS data output stream. And that sorts it out into whatever data node it's going to go to, and which also tells it how to replicate it. So that data node then sends it to other data nodes, so we have a replication. And of course, you finalize it and close everything up, marks it complete to the name node, and it deletes all those magical tokens in the background so that they can't be reused. And we can go ahead and just do this with an example, the same setup. So, and whether you're doing a read or a write, they're very similar. As we come in here from our client and our name node, and you can see right here, we actually depicting these as the actual rack and the switches going on. And so as the data comes in, you have your request, like we saw earlier. It sends the location of the data nodes, and this actually turns your IP addresses, your dynamic node connections. They come back to your client, your HDFS client, and at that point with the tokens, it then goes into the core switch, and the core switch says, hey, here it goes. The client interacts with the data nodes through the switches. And you can see here where you're writing in block A, replication of block A, and a second replication of block A on the second server. So block A gets replicated on the second server and the third server. At this point, you now have 3 replications of block A, and it comes back and says, it acknowledges, it says, hey, we're done, and that goes back into your Hadoop file system to the client, and it says, okay, we're done, and finally the success written to the name node, and it just closes everything down. A quick recap of the Hadoop file system and the advantages. And so the first one is probably all of these are huge. One, you have multiple data copies are available, so it's very fault tolerant. Whole racks can go down, switches can go down, even your main name node can go down if you have a secondary name node. Something we didn't talk too much about is how scalable it is. As it uses distributed storage, you run into there and you go, oh my gosh, I'm out of space, or I need to do some heavier processing. Let me just add another rack of computers. So you can scale it up very quickly, and it's a linear scalability, where it used to be if you bought a server, you would have to pay a lot of money to get that the Craig computer. Remember the big Craig computers coming out? The Craig computer runs $2 million a year just the maintenance to liquid cool it. That's very expensive compared to just adding more racks of computer and extending your data center. So it's very cost effective. Since commodity hardware is used, we're talking cheap knockoff computers. You still need your high-end enterprise for the name node, but the rest of them, literally it is 1/10 of the cost of storing data on more traditional high-end computers. And then the data is secure, so it has a very high-end data security and provides data security for your data. So all theory and no play doesn't make for much fun. So let's go ahead and show you what it looks like as far as some of the dimensions when you're getting into pulling data or putting data into the Hadoop file system. And you can see here I have Oracle Virtual Machine, VirtualBox Manager. I have a couple of different things loaded on there. Cloudera is one of them. So we should probably explain some of these things if you're new to virtual machines. The Oracle VirtualBox allows you to spin up a machine as if it is a separate computer. So in this case, this is running, I believe, CentOS Linux, and it creates like a box on my computer. So the CentOS is running on my machine while I'm running my Windows 10. This happens to be a Windows 10 computer. And then underneath here, I can actually go under, let me just open up the general. Might be hard to see there. And you can see I can actually go down to System, Processor. I happen to be on an 8-core. It has 16 dedicated threads. Registers as 16 CPUs, but 8 cores. And I've only designated this for one CPU. So it's only going to use one of my dedicated threads on my computer. And this, the Oracle Virtual Machine, is open source. And you can see right here we're on the Oracle, www.oracle.com. I usually just do a search for downloading VirtualBox. If you search for VirtualBox, all one word, it will come up with this page, and then you can download it for whatever operating system you're working with. There certainly are a number of different options, and let me go ahead and point those out if you're setting this up as a for demoing for yourself. The first thing to note for doing a VirtualBox and doing a Cloudera or Horton setup on that VirtualBox for doing the Hadoop system to try it out, you need a minimum of 12 gigabytes. It cannot be a Windows 10 Home Edition because you'll have problems with your virtual setup. And sometimes you have to go turn on the virtual settings so it knows it's in there. So if you're on a home setup, there are other sources. There's Cloudera, and we'll talk a little bit about Cloudera here in just a second. But they have the Cloudera Online Live. We can go try the Cloudera setup. I've never used it, but Cloudera is a pretty good company. Cloudera and Hortonworks are two of the common ones out there. And we'll actually be running a Cloudera Hadoop cluster on our demo here. So you have Oracle Virtual Machine. You also have the option of doing it on different VMware. That's another one like Virtual Machine. This is more of a paid service. There is a free setup for just doing it for yourself, which will work fine for this. And then in the Cloudera, like again, they have the new online setup where you can go in there to the online. And for Cloudera, you want to go underneath the Cloudera Quick Start. If you type in a search for Cloudera Quick Start, it'll bring you to this website, and then you can select your platform. In this case, I did VirtualBox. There's VMware we just talked about. Docker. Docker is a very high-end virtual setup. Unless you already know it, you really don't want to mess with it. Then your KVM is if you're on a Linux computer, that sets up multiple systems on that computer. So the two you really want to use are usually the VirtualBox or do an online setup. And you can see here with the download, if you're going into the Horton version, it's called HortonWorks, and they call it Sandbox. So you'll see the term HortonWorks Sandbox. And these are all test demos. You're not going to deploy a single node Hadoop systems. That would just be kind of ridiculous and defeat the whole purpose of having a Horton or having a Hadoop system if it's only installed on one computer in a virtual node. So a lot of different options. If you're not on a professional Windows version or you don't have at least 12 gigabytes RAM to run this, you'll want to try and see if you can find an online version. And of course, Simplilearn has our own lab, so if you sign up for our classes, we set you up. I don't know what it is now, but last time I was in there was a 5-node setup, so you can get around and see what's going on, whether you're studying for the admin side or for the programming side in script writing. And if I go into my Oracle VirtualBox and I go under my Cloudera and I start this up, and each one has their own flavors. Horton uses just a login, so you log everything in through a local host through your Internet Explorer, or I might use Chrome. Cloudera actually opens up a full interface, so you actually are in that setup. And you can see when I started it, let me go back here, once I downloaded this is a big download by the way, I had to import the appliance in VirtualBox. The first time I ran it, it takes a long time to configure the setup, and the second time it comes up pretty quick. And with the Cloudera Quick Start, again this is a pretend single node, it opens up and you'll see that it actually has Firefox here. So here's my web browser. I don't have to go to a local host. I'm actually already in the Quick Start for Cloudera. And if we come down here, you can see getting started. I have some information, analyze your data, manage your cluster, your general information on there. And what I always want to start to do is to go ahead and open up a terminal window. So we'll open up a terminal, widen this a little bit. Let me just maximize this out here so you can see. So we are now in a virtual machine. This virtual machine is CentOS Linux. So I'm on a Linux computer on my Windows computer. And so when I'm on this terminal window, and this is your basic terminal, if I do list, you'll see documents, Eclipse. These are the different things that are installed with the Quick Start guide on the Linux system. So this is a Linux computer. And then Hadoop is running on here. So now I have Hadoop single node. So it has both the name node and the data node and everything squished together in one virtual machine. We can then do, let's do HDFS, telling it that it's a Hadoop file system. DFS minus LS. Now notice the LS is the same. I have LS for list and LS for list. And I click on here, and it'll take it just a second reading the Hadoop file system, and it comes up with nothing. So a quick recap. Let's go back over this. 3 different environments. I have this one out here. Let's just put this in a bright red so you can actually see it. I have this environment out here, which is my slides. I have this environment here, or I did a list, that's looking at the files on the Linux CentOS computer. And then we have this system here, which is looking at the files on the Hadoop file system. So 3 completely separate environments. And then we connect them. And so right now I have whatever files, I have my personal files, and the of course we're also looking at the screen for my Windows 10. And then we're looking at the screen here. Here's our list there that's looking at the files, and this is the screen for CentOS Linux. And then this is looking at the files right here for the Hadoop file system. So 3 completely separate files. This one here, which is the Linux, is running in a VirtualBox. So this is a VirtualBox. I'm using 1 core to run it, or 1 CPU, and everything in there it has its own file system. You can see we have our desktop and documents and whatever in there. And then you can see here we right now have no files in our Hadoop file system. And this Hadoop file system currently is stored on the Linux machine, but it could be stored across 10 Linux machines, 20, 100. This could be stored across in petabytes. I mean, it could be really huge, or it could just be, in this case, just a demo where we're putting it on just 1 computer. And then once we're in here, let me just see real quick if I can go under View, zoom in, View, zoom in. And this is just a standard browser, so I could use any like the Control Plus and stuff like that to zoom in. And this is very common to be in a browser window with the Hadoop file system. So right now I'm in a Linux, and I'm going to do, let's just create a file. We'll go File, My New File. and I'm going to use Vi, and this is a Vi editor, just a basic editor, and we go ahead and type something in here, 1, 2, 3, 4, maybe it's columns, 44, 66, 77. Of course, Hadoop file system, just like your regular computer, can also, so in our Vi editor, you hit your colon. I actually work with a lot of different other editors, and we'll right quit Vi. So let's take a look and see what happened here. I'm in my Linux system. I type in ls for list, and we should see my new file. And sure enough, we do over here. There it is. Let me just highlight that, my new file. And if I then go into the Hadoop system, HDFS, DFS minus ls for list, we still show nothing. It's still empty. So what I can simply do is I can go HDFS, DFS minus put, and then we're going to put my new file. And this is just going to move it from the Linux system, because I'm in this file folder, into the Hadoop file system. And now if we go in and we type in our list for Hadoop file system, you will see in here that I now have just the one file on there, which is my new file. And very similar to Linux, we can do cat, and the cat command simply evokes reading the file. So HDFS, DFS minus cat. And I had to look it up. Remember Cloudera. The format is going to be user, then of course the path location and the file name. And in here when we did the list, here's our list. So you can see it lists our file here, and we realize that this is under user Cloudera. And so I can now go user Cloudera my new file and the minus cat, and we'll be able to read the file in here. And you can see right here, this is the file that was in the Linux system, is now copied into the Cloudera system, and it's 1345, what I entered in there. And if we go back to the Linux and do list, you'll still see it in here, my new file. And we can also do something like this in our HDFS minus MV. I will do my new file, and we're going to change it to my new file. And if we do that underneath our Hadoop file system, the minus MV will rename it. So if I go back here to our Hadoop file system ls, you'll now see instead of my new file, it has my new file coming up. And there it is, my new file. So we've renamed it. We can also go in here and delete this. So I can now come in here. So in our HDFS, DFS, we can also do a remove. And this will remove the file. And so if we come in here, we run this, we'll see that when I come back and do the list, the file is gone. And now we just have another empty folder with our Hadoop file system. And just like any file system, we can take this and we can go ahead and make directory, create a new directory. So MK for make directory. We'll call this my dir. So we're going to make a directory my dir. It'll take it just a second, and of course if we do the list command, you'll see that we now have the directory in there. Give it just a second. There it comes, my dir. And just like we did before, I can go in here and we're going to put the file, and if you remember correctly from our files in the setup, I called it my new file. So this is coming from the Linux system, and we're going to put that into my dir. That's the target in my Hadoop setup. And so if I hit enter on there, I can now do the Hadoop list, and that's not going to show the file, because remember I put it in a subfolder. So if I do the Hadoop list, this will show my directory, and I can do list, and then I can do my dir for my directory. And you'll see underneath of my directory in the Hadoop file system, it now has my new file put in there. And with any good operating system, we need a minus help. So just like you can type in help in your Linux, you can now come in here and type in HDFS help, and it shows you a lot of the commands in there underneath the Hadoop file system. Most of them should be very similar to the Linux on here. And we can also do something like this, Hadoop version, and the Hadoop version shows up that we're in Hadoop 2.60, CDH is that we're Cloudera 5, and compiled by Jenkins, and it has a date and all the different information on our Hadoop file system. So this is some basics in the terminal window. Let me go ahead and close this out, because if you're going to play with this, you should really come in here. Let me just maximize the Cloudera, and it opens up in a browser window. And so once we're in here, again, this is a browser window which you could access, might look like any access for a Hadoop file system. One of the fun things to do when you're first starting is to go under Hue. You'll see it up here at the top. It has Cloudera, Hue, Hadoop, your HBase, your Impala, your Spark. These are standard installs now. And Hue is basically an overview of the file system. And so come up here and you can see where you can do queries as far as if you have a HBase or a Hive, the Hive database. We can go over here to the top where it says File Browser. And if we go under File Browser, now this is the Hadoop file system we're looking at. And once we open up the file browser, you can now see there's my directory, which we created. And if I click on my directory, there's my new file, which is in here. And if I click on my new file, it actually opens it up. And you can see from our Hadoop file system, this is in the Hadoop file system, the file that we created. So we covered the terminal window. You can see here's a terminal window up here. It might be if you were in a web browser, it'll look a little different because it actually opens up as a web browser terminal window. And we've looked a little bit at Hue, which is one of the most basic components of Hadoop, one of the original components for going through and looking at your data and your databases. Of course, now they're up to the Hue 4. It's gone through a number of changes. And you can see there's a lot of different choices in here for other different tools in the Hadoop file system. And I'll go ahead and just close out of this. And one of the cool things with the virtual box, I can either save the machine state, send the shutdown signal, or power off the machine. I'll go ahead and just power off the machine completely.
Now, suppose you have a library that has a collection of huge number of books on each floor, and you want to count the total number of books present on each floor. What would be your approach? You could say, I will do it myself, but then don't you think that will take a lot of time? And that's obviously not an efficient way of counting the number of books in this huge collection on every floor by yourself. Now, there could be a different approach or an alternative to that. You could think of asking 3 of your friends or 3 of your colleagues, and you could then say if each friend could count the books on every floor, then obviously that would make your work faster and easier to count the books on every floor. Now, this is what we mean by parallel processing. So when you say parallel processing in technical terms, you're talking about using multiple machines, and each machine would be contributing its RAM and CPU cores for processing, and your data would be processed on multiple machines at the same time. Now, this type of process involves parallel processing in our case, or in our library example, where you would have person 1 who would be taking care of books on floor 1 and counting them, person 2 on floor 2, then you have someone on floor 3 and someone on floor 4. So every individual would be counting the books on every floor in parallel. So that reduces the time consumed for this activity. And then there should be some mechanism where all these counts from every floor can be aggregated. So what is each person doing here? Each person is mapping the data of a particular floor, or you can say each person is doing a kind of activity or basically a task on every floor, and the task is counting the books on every floor. Now then you could have some aggregation mechanism that could basically reduce or summarize this total count, and in terms of Mapreduce, we would say that's the work of reducer. So when you talk about Hadoop Mapreduce, it processes data on different node machines. Now this is the whole concept of Hadoop framework, right? That you not only have your data stored across machines, but you would also want to process the data locally. So instead of transferring the data from one machine to other machine, or bringing all the data together into some central processing unit and then processing it, you would rather have the data processed on the machines wherever that is stored. So we know in case of Hadoop cluster, we would have our data stored on multiple data nodes on their multiple disks, and that is the data which needs to be processed. But the requirement is that we want to process this data as fast as possible, and that could be achieved by using parallel processing. Now, in case of Mapreduce, we basically have the first phase, which is your mapping phase. So in case of Mapreduce programming model, you basically have 2 phases. One is mapping and one is reducing. Now, who takes care of things in mapping phase? It is a mapper class. And this mapper class has the function which is provided by the developer, which takes care of these individual map tasks which will work on multiple nodes in parallel. Your reducer class belongs to the reducing phase. So a reducing phase basically uses a reducer class which provides a function that will aggregate and reduce the output of different data nodes to generate the final output. Now that's how your Mapreduce works, using mapping and then obviously reducing. Now you could have some other kind of jobs which are map only jobs wherein there is no reducing required. But we are not talking about those. We are talking about our requirement where we would want to process the data using mapping and reducing, especially when data is huge, when data is stored across multiple machines, and you would want to process the data in parallel. So when you talk about Mapreduce, you could say it's a programming model. You could say internally it's a processing engine of Hadoop that allows you to process and compute huge volumes of data. And when we say huge volumes of data, we can talk about terabytes, we can talk about petabytes, exabytes, and that amount of data which needs to be processed on a huge cluster. We could also use Mapreduce programming model and run a Mapreduce algorithm in a local mode. But what does that mean? If you would go for a local mode, it basically means it would do all the mapping and reducing on the same node using the processing capacity, that is RAM and CPU cores, on the same machine, which is not really efficient. In fact, we would want to have our Mapreduce work on multiple nodes, which would obviously have mapping phase followed by a reducing phase, and intermittently there would be data generated. There would be different other phases which help this whole processing. So when you talk about Hadoop Mapreduce, you are mainly talking about two main components or two main phases, that is mapping and reducing. Mapping taking care of map tasks, reducing taking care of reduced tasks. So you would have your data which would be stored on multiple machines. Now when we talk about data, data could be in different formats. We could, or the developer could specify what is the format which needs to be used to understand the data which is coming in. That data then goes through the mapping. Internally there would be some shuffling, sorting, and then reducing, which gives you your final output. So the way we access data from HDFS, or the way our data is getting stored on HDFS, we have our input data which would have one or multiple files and one or multiple directories, and your final output is also stored on HDFS to be accessed, to be looked into, and to see if the processing was done correctly. So this is how it looks. So you have the input data which would then be worked upon by multiple map tasks. Now how many map tasks? That basically depends on the file. That depends on the input format. So normally we know that in a Hadoop cluster you would have a file which is broken down into blocks depending on its size. So the default block size is 128 MB, which can then still be customized based on your average size of data which is getting stored on the cluster. So if I have really huge files which are getting stored on the cluster, I would certainly set a higher block size so that my every file does not have huge number of blocks creating a load on name nodes RAM, because that's tracking the number of elements in your cluster or number of objects in your cluster. So depending on your file size, your file would be split into multiple chunks, and for every chunk we would have a map task running. Now what is this map task doing? That is specified within the mapper class. So within the mapper class you have the mapper function which basically says what each of these map tasks has to do on each of the chunks which has to be processed. This data intermittently is written to HDFS where it is sorted and shuffled, and then you have internal phases such as partitioner which decides how many reduce tasks would be used or what data goes to which reducer. You could also have a combiner phase which is like a mini reducer doing the same reduce operation before it reaches reduce. Then you have your reducing phase which is taken care by a reducer class, and internally the reducer function provided by developer which would have reduce task running on the data which comes as an output from map tasks. Finally, your output is then generated which is stored on HDFS. Now in case of Hadoop, it accepts data in different formats. Your data could be in compressed format, your data could be in Parquet, your data could be in Avro, text, CSV, TSV, binary format, and all of these formats are supported. However, remember, if you're talking about data being compressed, then you have to also look into what kind of splittability the compression mechanism supports. Otherwise, when MapReduce processing happens, it would take the complete file as one chunk to be processed. So HDFS accepts input data in different formats. This data is stored in HDFS, and that is basically our input, which is then passing through the mapping phase. Now, what is mapping phase doing? As I said, it reads record by record. Depending on the input format, it reads the data. So we have multiple map tasks running on multiple chunks. Once this data is being read, this is broken down into individual elements. And when I say individual element, I could say this is my list of key value pairs. So your records based on some kind of delimiter or without delimiter are broken down into individual elements, and thus your map creates key value pairs. Now these key value pairs are not my final output. These key value pairs are basically a list of elements which will then be subjected to further processing. So you would have internally shuffling and sorting of data so that all the relevant key value pairs are brought together, which basically benefits the processing. And then you have your reducing, which aggregates the key value pairs into set of smaller tuples or tuples, as you would say. Finally, your output is getting stored in the designated directory as a list of aggregated key value pairs, which gives you your output. So when we talk about MapReduce, one of the key factors here is the parallel processing which it can offer. So we know that our data is getting stored across multiple data nodes, and you would have huge volume of data which is split and randomly distributed across data nodes, and this is the data which needs to be processed. And the best way would be parallel processing. So you could have your data getting stored on multiple data nodes or multiple slave nodes, and each slave node would have again one or multiple disks. To process this data, basically we have to go for parallel processing approach. We have to use the MapReduce. Now let's look at the MapReduce workflow to understand how it works. So basically you have your input data stored on HDFS. Now this is the data which needs to be processed. It is stored in input files, and the processing which you want can be done on one single file, or it can be done on a directory which has multiple files. You could also later have multiple outputs merged, which we achieve by using something called as chaining of mappers. So here you have your data getting stored on HDFS. Now input format is basically something to define the input specification and how the input files will be split. So there are various input formats. Now we can search for that. So we can go to Google and we can basically search for Hadoop Mapreduce Yahoo tutorial. This is one of the good links. And if I look into this link, I can search for different input formats and output formats. So let's search for input format. So when we talk about input format, you basically have something to define how input files are split. So input files are split up and read based on what input format is specified. So this is a class that provides following functionality. It selects the files or other objects that should be used for input. It defines the input split that break a file into tasks, provides a factory for record reader objects that read the file. So there are different formats if you look in the table here, and you can see that the text input format is the default format, which reads lines of a text file, and each line is considered as a record. Here the key is the byte offset of the line, and the value is the line content itself. You can have key value input format, which parses lines into key value pairs. Everything up to the first tab character is the key, and the remainder is the line. You could also have sequence file input format, which basically works on binary format. So you have input format, and in the same way you can also search for output format, which takes care of how the data is handled after the processing is done. So the key value pairs provided to this output collector are then written to output files. The way they are written is governed by output format. So it functions pretty much like input format as described in earlier. right? So we could set what is the output format to be followed, and again you have text output, sequence file output format, null output format, and so on. So these are different classes which take care of how your data is handled when it is being read for processing, or how is the data being written when the processing is done. So based on the input format, the file is broken down into splits, and this logically represents the data to be processed by individual map tasks, or you could say individual mapper functions. So you could have one or multiple splits which need to be processed depending on the file size, depending on what properties have been set. Now once this is done, you have your input splits which are subjected to mapping phase. Internally you have a record reader which communicates with the input split and converts the data into key value pairs suitable to be read by mapper. And what is mapper doing? It is basically working on these key value pairs, the map task, giving you an intermittent output which would then be forwarded for further processing. Now once that is done and we have these key value pairs which is being worked upon by map, your map tasks as a part of your mapper function are generating your key value pairs, which are your intermediate outputs to be processed further. Now you could have, as I said, a combiner phase or internally a mini reducer phase. Now combiner does not have its own class. So combiner basically uses the same class as the reducer class provided by the developer, and its main work is to do the reducing, or its main work is to do some kind of mini aggregation on the key value pairs which were generated by map. So once the data is coming in from the combiner, then we have internally a partitioner phase which decides how outputs from combiners are sent to the reducers. Or you could also say that even if I did not have a combiner, partitioner would decide based on the keys and values, based on the type of keys, how many reducers would be required, or how many reduce tasks would be required to work on your output which was generated by map task. Now once partitioner has decided that, then your data would be then sorted and shuffled, which is then fed into the reducer. So when you talk about your reducer, it would basically have one or multiple reduce tasks. Now that depends on what partitioner decided or determined for your data to be processed. It can also depend on the configuration properties which have been set to decide how many reduce tasks should be used. Now internally all this data is obviously going through sorting and shuffling so that your reducing or aggregation becomes an easier task. Once we have this done, we basically have the reducer, which is the code for the reducer is provided by the developer, and all the intermediate data has then to be aggregated to give you a final output, which would then be stored on HDFS. And who does this? You have an internal record writer which writes these output key value pairs from reducer to the output files. Now this is how your Mapreduce works, wherein the final output data can be not only stored but then read or accessed from HDFS, or even used as an input for further Mapreduce kind of processing. So this is how it overall looks. So you basically have your data stored on HDFS. Based on input format, you have the splits, then you have record reader which gives your data to the mapping phase, which is then taken care by your mapper function. And mapper function basically means one or multiple map tasks working on your chunks of data. You could have a combiner phase which is optional, which is not mandatory. Then you have a partitioner phase which decides on how many reduce tasks or how many reducers would be used to work on your data. Internally there is sorting and shuffling of data happening, and then basically based on your output format, your record reader will write the output to HDFS directory. Now internally you could also remember that data is being processed locally, so you would have the output of each task which is being worked upon stored locally. However, we do not access the data directly from data nodes, we access it from HDFS, so our output is stored on HDFS. So that is your Mapreduce workflow. When you talk about Mapreduce architecture, now this is how it would look. So you would have basically a edge node or a client program or an API which intends to process some data. So it submits the job to the job tracker, or you can say resource manager in case of Hadoop Yarn framework, right? Now before this step, we can also say that an interaction with name node would have already happened, which would have given information of data nodes which have the relevant data stored. Then your master processor. So in Hadoop version 1, we had job tracker, and then the slaves were called task trackers. In Hadoop version 2, instead of job tracker, you have resource manager, and instead of task trackers, you have node managers. So basically, your resource manager has to assign the job to the task trackers or node managers. So your node managers, as we discussed in Yarn, are basically taking care of processing which happens on every node. So internally there is all of this work happening by resource manager, node managers, and application master, and you can refer to the Yarn based tutorial to understand more about that. So here your processing master is basically breaking down the application into tasks. What it does internally is, once your application is submitted, your application to be run on Yarn processing framework is handled by resource manager. Now forget about the Yarn part as of now. I mean, who does the negotiating of resources, who allocates them, how does the processing happen on the nodes, right? So that's all to do with how Yarn handles the processing request. So you have your data which is stored in HDFS, broken down into one or multiple splits. Depending on the input format which has been specified by the developer, your input splits are to be worked upon by your one or multiple map tasks which will be running within the container on the nodes. Basically, you have the resources which are being utilized. So for each map task, you would have some amount of RAM which will be utilized, and then further the same data which has to go through reducing phase, that is your reduce task, will also be utilizing some RAM and CPU cores. Now internally you have these functions which take care of deciding on number of reducers, doing a mini reduce, and basically reading and processing the data from multiple data nodes. Now this is how your Mapreduce programming model makes parallel processing work, or processes your data which is stored across multiple machines. Finally, you have your output which is getting stored on HDFS. So let's have a quick demo on Mapreduce and see how it works on a Hadoop cluster. Now we have discussed briefly about Mapreduce, which contains mainly two phases, that is your mapping phase and your reducing phase. And mapping phase is taken care by your mapper function, and your reducing phase is taken care by your reducer function. Now in between we also have sorting and shuffling, and then you have other phases which is partitioner and combiner, and we will discuss about all those in detail in later sessions. But let's have a quick demo on how we can run a Mapreduce which is already existing as a package jar file within your Apache Hadoop cluster or even in your Cloudera cluster. Now we can build our own Mapreduce programs. We can package them as jar, transfer them to the cluster, and then run it on a Hadoop cluster on Yarn, or we could be using already provided default programs. So let's see where they are. Now these are my two machines which I have brought up, and basically this would have my Apache Hadoop cluster running. Now we can just do a simple start-all.sh. Now I know that this script is deprecated and it says instead use start DFS and start Yarn, but then it will still take care of starting off my cluster on these two nodes, where I would have one single name node, two data nodes, one secondary name node, one resource manager, and two node managers. Now if you have any doubt in how this cluster came up, you can always look at the previous sessions where we had a walkthrough in setting up a cluster on Apache, and then you could also have your cluster running using less than 3 GB of your total machine RAM, and you could have an Apache cluster running on your machine. Now once this cluster comes up, we will also have a look at the web UI which is available for name node and resource manager. Now based on the settings what we have given, our UIs will show us details of our cluster, but remember the UI is only to browse. Now here my cluster has come up. I can just do a JPS to look at Java related processes, and that will show me what are the processes which are running on C1, which is your data node, resource manager, node manager, and name node. And on my M1 machine, which is my second machine which I've configured here, I can always do a JPS, and that shows me the processes running, which also means that my cluster is up with 2 data nodes with 2 node managers. And here I can have a look at my web UI. So I can just do a refresh, and the same thing with this one, just do a refresh. So I had already opened the web pages. So you can always access the web UI using your name node's host name and 570 port. It tells me what is my cluster ID, what is my block pool ID. It gives you information of what is the space usage, how many live nodes you have, and you can even browse your file system. So I have put in a lot of data here. I can click on browse the file system, and this basically shows me multiple directories, and these directories have one or multiple files which we will use for our Mapreduce example. Now if you see here, these are my directories which have some sample files, although these files are very small, like 8.7 kilobytes. If you look into this directory, if you look into this, I have just pulled in some of my Hadoop logs and I have put it on my HDFS. These are a little bigger files. And then we also have some other data which we can see here, and this is data which I've downloaded from web. Now we can either run a Mapreduce on a single file or in a directory which contains multiple files. Let's look at that. Before looking a demo on Mapreduce, also remember Mapreduce will create a output directory, and we need to have that directory created. Plus we need to have the permissions to run the Mapreduce job. So by default, since I'm running it using admin ID, I should not have any problem. But then if you intend to run Mapreduce with a different user, then obviously you will have to ask the admin, or you will have to give the user permission to read and write from HDFS. So this is the directory which I've created, which will contain my output once the Mapreduce job finishes. And this is my cluster file system. If you look on this UI, this shows me about my yarn, which is available for taking care of any processing. It as of now shows that I have total of 8 GB memory and I have 8 weak cores. Now that can be depending on what configuration we have set or how many nodes are available. We can look at nodes which are available, and that shows me I have 2 node managers running. Each has 8 GB memory and 8 weak cores. Now that's not true actually, but then we have not set the configurations for node managers, and that's why it takes the default properties, that is 8 GB RAM and 8 weak cores. Now this is my yarn UI. We can also look at scheduler, which basically shows me the different queues if they have been configured, where you will have to run the jobs. We'll discuss about all these later in detail. Now let's go back to our terminal and let's see where we can find some sample applications which we can run on the cluster. So once I go to the terminal, I can, well, submit the Mapreduce job from any terminal. Now here I know that my Hadoop related directory is here, and within Hadoop you have various directories. We have discussed that in binaries you have the commands which you can run. In sbin you basically have the startup scripts, and here you also notice there is a share directory in the end. If you look in the share directory, you would find Hadoop, and within Hadoop you have various subdirectories in which we will look for Mapreduce. Now this Mapreduce directory has some sample jar files which we can use to run a Mapreduce on the cluster. Similarly, if you are working on a Cloudera cluster, you would have to go into opt Cloudera parcel cdh/lib, and in that you would have directories for HDFS Mapreduce or HDFS yarn, where you can still find the same jars. It is basically a package which contains your multiple applications. Now how do we run a Mapreduce? We can just type in Hadoop and hit enter, and that shows me that I have an option called jar which can be used to run a jar file. Now at any point of time, if you would want to see what are the different classes which are available in a particular jar, you could always do a jar -xvf. For example, I could say jar xvf, and I could say user local Hadoop, share, Hadoop, Mapreduce, and then list down your jar file. So I'll say Hadoop Mapreduce examples, and if I do this, this should basically unpack it to show me what classes are available within this particular jar. And it has done this. It has created a meta file and it has created a org directory. We can see that by doing a ls, and here if you look in ls org, since I ran the command from a home directory, I can look into org Apache Hadoop examples, which shows me the classes which I have, and those classes contain which mapper or reducer classes. So it might not be just mapper and reducer, but you can always have a look. So for example, I am targeting to use word count program, which does a word count on files and gives me a list of words and how many times they occur in a particular file or in set of files. And this shows me that what are the classes which belong to word count. So we have a int sum reducer. So this is my reducer class. I have tokenizer mapper, that is my mapper class, right? And basically this is what is used. These classes are used if you run a word count. Now there are many other programs which are part of this jar file, and we can expand and see that. So I can say Hadoop jar and give your path. So I'll say Hadoop jar user local Hadoop share Hadoop Mapreduce, Hadoop Mapreduce examples, and if I hit on enter, that will show me what are the inbuilt classes which are already available. Now these are certain things which we can use. Now there are other jar files also. For example, I can look at Hadoop, and here we can look at the jar files which we have in this particular path. So this is one Hadoop Mapreduce examples which you can use. You can always look in other jar files, like you can look for Hadoop Mapreduce client, job client, and then you can look at the tests one. So that is also an interesting one. So you can always look into Hadoop Mapreduce client, job client, and then you have something ending with tests. So if I would have tried this one using my Hadoop jar command, so in my previous example, when we did this, it was showing me all the classes which are available, and that already has a word count. Now there are other good programs which you can try, like TerraGen to generate dummy data, TerraSort to check your sorting performance, and so on, and TerraValidate to validate the results. Similarly, we can also do a Hadoop jar, as I said, on Hadoop Mapreduce. I think that was client, and then we have job client, and then test jar. Now this has a lot of other classes which can be used, or programs which can be used for doing a stress testing or checking your cluster status and so on. One of them, interesting one, is HDFS. But let's not get into all the details in first instance. Let's see how we can run a Mapreduce. Now if I would want to run a Mapreduce, I need to give Hadoop jar and then my jar file, and if I hit on enter, it would say it needs the input and output. It needs which class you want to run. So for example, I would say word count, and again if I hit on enter, it tells me that you need to give me some input and output to process. And obviously this processing will be happening on cluster, that is our yarn processing framework, unless and until you would want to run this job in a local mode. So there is a possibility that you can run the job in a local mode, but let's first try how it runs on the cluster. So how do we do that? Now here I can do a HDFS ls / command to see what I have on my HDFS. Now through my UI, I was already showing you that we have set of files and directories which we can use to process. Now we can take up one single file. So for example, if I pick up new data, and I can look into the files here, what we have, and we can basically run a Mapreduce on a single file or multiple files. So let's take this file, whatever that contains, and I would like to do a word count so that I get a list of words and their occurrence in this file. So let me just copy this. Now I also need my output to be written, and that will be written here. So here, if I want to run a Mapreduce, I can say Hadoop, which we can pull out from history. So Hadoop jar word count. Now I need to give my input, so that will be new data, and then I will give this file which we just copied. Now I'm going to run the word count only on a single file, and I will basically have my output which will be stored in this directory, the directory which I have created already, mr output. So let's do this out output, and this is fair enough. Now you can give many other properties. You can specify how many map jobs you want to run, how many reduce jobs you want to run. Do you want your output to be compressed? Do you want your output to be merged? Or many other properties can be defined when you are specifying word count, and then you can pass in an argument to pass properties from the command line which will affect your output. Now once I go ahead and submit this is basically running a simple inbuilt Mapreduce job on our Hadoop cluster. Now obviously internally it will be looking for name node. Now we have some issue here and it says the output already exists. What does that mean? So it basically means that Hadoop will create an output for you. You just need to give a name, but then you don't need to create it. So let's append the output with number 1, and then let's go ahead and run this. So I've submitted this command. Now this can also be run in background if you would want to run multiple jobs on your cluster at the same time. So it takes total input paths to process is 1. So that is, there is only one split on which your job has to work. Now it will internally try to contact your resource manager, and basically this is done. So here we can have a look and we can see some counters here. Now what I also see is for some property which it is missing, it has run the job, but it has run in a local mode. It has run in a local mode. So although we have submitted, so this might be related to my yarn settings, and we can check that. So if I do a refresh, when I have run my application, it has completed. It would have created an output, but the only thing is it did not interact with your yarn. It did not interact with your resource manager. We can check those properties, and here if we look into the job, it basically tells me that it went for mapping and reducing. It would have created an output. It worked on my file, but then it ran in a local mode. It ran in a local mode. So Mapreduce, remember, is a programming model, right? Now, if you run it on Yarn, you get the facilities of running it on a cluster where Yarn takes care of resource management. If you don't run it on Yarn and run it on a local mode, it will use your machine's RAM and CPU cores for processing. But then we can quickly look at the output, and then we can also try running this on Yarn. So if I look into my HDFS and if I look into my output, MR output, that's the directory which was not used actually. Let's look into the other directory which is ending with 1, and that should show me the output created by this Mapreduce. Although it ran in a local mode, it fetched an input file from your HDFS and it would have created output in HDFS. Now that's my part file which is created, and if you look at part minus R minus these zeros, if you would have more than one reducer running, then you would have multiple such files created. We can look into this. What does this file contain? Which should have my word count, and here I can say cat, which basically shows me what is the output created by my Mapreduce. Let's have a look into this. So the file which we gave for processing has been broken down, and now we have the list of words which occur in the file plus a count of those words. So if there is some word which is more, then it shows me the count. So this is a list of my words and the count for that. So this is how we run a sample Mapreduce job. I will also show you how we can run it on Yarn. Now let's run Mapreduce on Yarn, and initially when we tried running a Mapreduce, it did not hit Yarn, but it ran in a local mode, and that was because there was a property which had to be changed in Mapreduce-site file. So basically if you look into this file, the error was that I had given a property which says mapred.framework.name, and that was not the right property name, and it was ignored, and that's why it ran in a local mode. So I changed the property to mapreduce.framework.name, restarted my cluster, and everything should be fine now, and that mapred-site file has also been copied across the nodes. Now to run a Mapreduce on a Hadoop cluster so that it uses Yarn, and Yarn takes care of resource allocation on one or multiple machines. So I'm just changing the output here, and now I will submit this job, which should first connect to the resource manager. And if it connects to the resource manager, that means our job will be run using yarn on the cluster rather than in a local mode. So now we have to wait for this application to internally connect to resource manager, and once it starts there, we can always go back to the web UI and check if our application has reached yarn. So it shows me that there is one input part to be processed. That's my job ID, that's my application ID, which you can even monitor status from the command line. Now here the job has been submitted, so let's go back here and just do a refresh on my yarn UI, which should show me the new application which is submitted. It tells me that it is in accepted state. Application master has already started, and if you click on this link, it will also give you more details of how many map and reduce tasks would run. So as of now, it says the application master is running. It would be using this node, which is M1. We can always look into the logs. We can see that there is a one task attempt which is being made. And now if I go back to my terminal, I will see that it is waiting to get some resources from the cluster. And once it gets the resources, it will first start with the mapping phase, where the mapper function runs. It does the map tasks, one or multiple depending on the splits. So right now we have one file and one split, so we will have just one map task running. And once the mapping phase completes, then it will get into reducing, which will finally give me my output. So we can be toggling through these sessions. So here I can just do a refresh to see what is happening with my application. Is it proceeding? Is it still waiting for resource manager to allocate some resources? Now, just a couple of minutes back, I tested this application on yarn, and we can see that my first application completed successfully. And here we will have to give some time so that yarn can allocate the resources. Now, if the resources were used by some other application, they will have to be freed up. Now, internally, yarn takes care of all that, which we will learn more detail in yarn, or you might have already followed the yarn based session. Now here we will have to just give it some more time, and let's see if my application proceeds with the resources what yarn can allocate to it. Sometimes you can also see a slowness in what web UI shows up, and that can be related to the amount of memory you have allocated to your nodes. Now for Apache, we can have less amount of memory and we can still run the cluster. And as I said, the memory which shows up here, 16 GB and 16 cores, is not the true one. Those are the default settings, right? But then my yarn should be able to facilitate running of this application. Let's just give it a couple of seconds and then let's look into the output here. Again, I had to make some changes in the settings because our application was not getting enough resources, and then basically I restarted my cluster. Now let's submit the application again to the cluster, which first should contact the resource manager, and then basically the map and reduce process should start. So here I've submitted an application. It is connecting to the resource manager, and then basically it will start internally an app master, that is application master. It is looking for the number of splits, which is 1. It's getting the application ID, and it basically then starts running the job. It also gives you a tracking URL to look at the output. And now we should go back and look at our yarn UI if our application shows up here, and we will have to give it a couple of seconds when it can get the final status change to running, and that's where my application will be getting resources. Now if you closely notice here, I have allocated specific amount of memory, that is 1.5 GB for node manager on every node, and I have basically given 2 cores each, which my machines also have, and my yarn should be utilizing these resources rather than going for default. Now the application has started moving, and we can see the progress bar here, which basically will show what is happening. And if we go back to the terminal, it will show that first it went in deciding map and reduce. It goes for map. Once the mapping phase completes, then the reducing phase will come into existence, and here my job has completed. So now it has basically used, we can always look at how many map and reduce tasks were run. It shows me that there was 1 map and 1 reduce task. Now with the number of map tasks depends on the number of splits, and we had just 1 file which is less than 128 MB, so that was 1 split. to be processed, and reduce task is internally decided by the reducer, or depending on what kind of property has been set in Hadoop config files. Now it also tells me how many input records were read, which basically means these were the number of lines in the file. It tells me output records, which gives me the number of total words in the file. Now there might be duplicates, and that which is processed by internal combiner, further processing or forwarding that information to reducer, and basically reducer works on 335 records, gives us a list of words and their count. Now if I do a refresh here, this would obviously show my application is completed. It says succeeded. You can always click on the application to look for more information. It tells me where it ran. Now we do not have a history server running as of now, otherwise we can always access more information. So this leads to history server where all your applications are stored. But I can click on this attempt tasks, and this will basically show me the history URL, or you can always look into the logs. So this is how you can submit a sample application which is inbuilt, which is available in the jar on your Hadoop cluster, and that will utilize your cluster to run. Now you could always, as I said, when you are running a particular job, remember to change the output directory, and if you would not want it to be processing a single individual file, you could also point it to a directory. That basically means it will have multiple files, and depending on the file sizes, there would be multiple splits, and according to that, multiple map tasks will be selected. So if I click on this, this would submit my second application to the cluster, which should first connect to resource manager. Then resource manager has to start an application master. Now here we are targeting 10 splits. Now you have to sometimes give a couple of seconds in your machines so that the resources which were used are internally already freed up, so that your cluster can pick it up and then your yarn can take care of resources. So right now my application is in undefined status, but then as soon as my yarn provides it the resources, we will have the application running on our yarn cluster. So it has already started. If you see, it is going further. Then it would launch 10 map tasks, and the number of reduced tasks would be decided on either the way your data is or based on the properties which have been set at your cluster level. Let's just do a quick refresh here on my yarn UI to show me the progress. Also take care that when you are submitting your application, you need to have the output directory mentioned. However, do not create it. Hadoop will create that for you. Now, this is how you run a Mapreduce without specifying properties, but then you can specify more properties. You can look into what are the things which can be changed for your mapper and reducer, or basically having a combiner class which can do a mini reducing, and all those things can be done. So we will learn about that in the later sessions. Now we will compare Hadoop version 1, that is with Mapreduce version 1. We will understand and learn about the limitations of Hadoop version 1. What is the need of yarn? What is yarn? What kind of workloads can be running on yarn? What are yarn components? What is yarn architecture? And finally, we will see a demo on yarn. So Hadoop version 1 or Mapreduce version 1, well, that's outdated now and nobody is using Hadoop version 1, but it would be good to understand what was in Hadoop version 1 and what were the limitations of Hadoop version 1, which brought in the thought for the future processing layer, that is yarn. Now, when we talk about Hadoop, we already know that Hadoop is a framework, and Hadoop has two layers. One is your storage layer, that is your HDFS, Hadoop Distributed File System, which allows for distributed storage and processing, which allows fault tolerance by inbuilt replication, and which basically allows you to store huge amount of data across multiple commodity machines. When we talk about processing, we know that Mapreduce is the oldest and the most mature processing programming model, which basically takes care of your data processing on your distributed file system. So in Hadoop version 1, Mapreduce performed both data processing and resource management, and that's how it was problematic. In Mapreduce, we had basically when we talk about the processing layer, we had the master, which was called job tracker, and then you had the slaves, which were the task trackers. So your job tracker was taking care of allocating resources, it was performing scheduling, and even monitoring the jobs. It basically was taking care of assigning map and reduce tasks to the jobs running on task trackers. And task trackers, which were co-located with data nodes, were responsible for processing the jobs. So task trackers were the slaves for the processing layer, which reported their progress to the job tracker. So this is what was happening in Hadoop version 1. Now, when we talk about Hadoop version 1, we would have, say, client machines or an API or an application which basically submits the job to the master, that is job tracker. Now, obviously, we cannot forget that there would already be an involvement from name node, which basically tells which are the machines or which are the data nodes where the data is already stored. Now, once the job submission happens to the job tracker being the master daemon for taking care of your processing request and also resource management, job scheduling, would then be interacting with your multiple task trackers, which would be running on multiple machines. So each machine would have a task tracker running, and that task tracker, which is a processing slave, would be co-located with the data nodes. Now we know that in case of Hadoop, you have the concept of moving the processing to wherever the data is stored rather than moving the data to the processing layer. So we would have task trackers which would be running on multiple machines, and these task trackers would be responsible for handling the tasks. What are these tasks? These are the application which is broken down into smaller tasks which would work on the data which is respectively stored on that particular node. Now these were your slave daemons, right? So your job tracker was not only tracking the resources, so your task trackers were sending heartbeats, they were sending in packets and information to the job tracker, which would then be knowing how many resources. And when we talk about resources, we are talking about the CPU cores, we are talking about the RAM, which would be available on every node. So task trackers would be sending in their resource information to job tracker, and your job tracker would be already aware of what amount of resources are available on a particular node, how loaded a particular node is, what kind of work could be given to the task tracker. So job tracker was taking care of resource management, and it was also breaking the application into tasks and doing the job scheduling part, assign different tasks to these slave daemons, that is your task trackers. So job tracker was eventually overburdened, right? Because it was managing jobs, it was tracking the resources from multiple task trackers, and basically it was taking care of job scheduling. So job tracker would be overburdened, and in a case if job tracker would fail, then it would affect the overall processing. So if the master is killed, if the master daemon dies, then the processing cannot proceed. Now this was one of the limitations of Hadoop version 1. So when you talk about scalability, that is the capability to scale, due to a single job tracker, scalability would be hitting a bottleneck. You cannot have a cluster size of more than 4,000 nodes and cannot run more than 40,000 concurrent tasks. Now that's just a number. We could always look into the individual resources which each machine was having, and then we can come up with an appropriate number. However, with a single job tracker, there was no horizontal scalability for the processing layer because we had single processing master. Now when we talk about availability, job tracker, as I mentioned, would be a single point of failure. Now any failure kills all the queued and running jobs, and jobs would have to be resubmitted. Now why would we want that? In a distributed platform, in a cluster which has hundreds and thousands of machines, we would want a processing layer which can handle huge amount of processing, which could be more scalable, which could be more available, and could handle different kind of workloads. When it comes to resource utilization, now if you would have a predefined number of map and reduce slots for each task tracker, you would have issues which would relate to resource utilization, and that again is putting a burden on the master which is tracking these resources, which has to assign jobs which can run on multiple machines in parallel. So limitations in running non-MapReduce applications. Now that was one more limitation of Hadoop version 1 and MapReduce, that the only kind of processing you could do is MapReduce. And MapReduce programming model, although it is good, it is oldest, it has matured over a period of time, but then it is very rigid. You will have to go for mapping and reducing approach. And that was the only kind of processing which could be done in Hadoop version 1. So when it comes to doing a real-time analysis, or doing ad hoc querying, or doing a graph-based processing or massive parallel processing, there were limitations because that could not be done in Hadoop version 1, which was having MapReduce version 1 as the processing component. Now that brings us to the need for YARN. So YARN, it stands for Yet Another Resource Negotiator. So as I mentioned, before YARN in Hadoop version 1, well, you could have applications which could be written in different programming languages, but then the only kind of processing which was possible was MapReduce. We had the storage layer, we had the processing, but then kind of limited processing which could be done. Now, this was one thing which brought in a thought that why shouldn't we have a processing layer which can handle different kind of workloads? As I mentioned, might be graph processing, might be real-time processing, might be massive parallel processing, or any other kind of processing which would be a requirement of an organization. Now, designed to run MapReduce jobs only and having issues in scalability, resource utilization, job tracking, etc., that led to the need of something what we call as YARN. Now from Hadoop version 2 onwards, we have the two main layers have changed a little bit. You have the storage layer which is intact, that is your HDFS, and then you have the processing layer which is called YARN, Yet Another Resource Negotiator. Now we will understand how YARN works, but then YARN is taking care of your processing layer. It does support MapReduce, so MapReduce processing can still be done, but then now you can have a support to other processing frameworks. YARN can be used to solve the issues which Hadoop version 1 was posing. Something like resource management, something like different kind of workload processing, something like scalability, resource utilization, all that is now taken care by YARN. Now, when we talk about YARN, we can have now a cluster size of more than 10,000 nodes and can run more than 100,000 concurrent tasks. That's just to take care of your scalability. When you talk about compatibility, applications which were developed for Hadoop version 1, which were primarily MapReduce kind of processing, can run on YARN without any disruption or availability issues. When you talk about resource utilization, there is a mechanism which takes care of dynamic allocation of cluster resources. And this basically improves the resource utilization. When we talk about multi-tenancy, so basically now the cluster can handle different kind of workloads. So you can use open source and proprietary data access engines. You can perform real-time analysis. You can be doing graph processing. You can be doing ad hoc querying. And this can be supported for multiple workloads which can run in parallel. So this is what YARN offers. So what is YARN? As I mentioned, YARN stands for Yet Another Resource Negotiator. So it is the cluster resource management layer for your Apache Hadoop ecosystem, which takes care of scheduling jobs and assigning resources. Now, just imagine when you would want to run a particular application, you would basically be telling the cluster that I would want resources to run my applications. That application might be a MapReduce application. That might be a Hive query, which is triggering a MapReduce. That might be a pig script, which is triggering a MapReduce. That could be Hive with Taze as an execution engine. That could be a Spark application. That could be a graph processing application. In any of these cases, you would still, as in sense client or basically an API or the application would be requesting for resources. YARN would take care of that. So YARN would provide the desired resources. Now when we talk about resources, we are mainly talking about the network related resources. We are talking about the CPU cores, or as in terms of YARN we say virtual CPU cores. We would talk about RAM, that is in GB or MB or in terabytes, which would be offered from multiple machines, and YARN would take care of this. So with YARN, you could basically handle different workloads. Now these are some of the workloads which are showing up here. You have the traditional Mapreduce, which is mainly batch oriented. You could have an interactive execution engine, something as Taze. You could have HBase, which is a column oriented or a 4-dimensional database, and that would be not only storing data on HDFS but would also need some kind of processing. You could have streaming functionalities, which would be from Storm or Kafka or Spark. You could have graph processing. You could have in-memory processing such as Spark and its components, and you could have many others. So these are different frameworks which could now run and which can run on top of Yarn. So how does Yarn do that? Now when we talk about Yarn, this is how a overall Yarn architecture looks. So at one end you have the client. Now client could be basically your edge node where you have some applications which are running. It could be an API which would want to interact with your cluster. It could be a user triggered application which wants to run some jobs which are doing some processing. So this client would submit a job request. Now what is Resource Manager doing? Resource Manager is the master of your processing layer. In Hadoop version 1, we basically had job tracker, and then we had task trackers which were running on individual nodes. So your task trackers were sending your heartbeats to the job tracker. Your task trackers were sending it their resource information, and job tracker was the one which was tracking the resources and it was doing the job scheduling. And that's how, as I mentioned earlier, job tracker was overburdened. So job tracker is now replaced by your resource manager, which is the master for your processing layer. Your task trackers are replaced by node managers, which would be then running on every node. And we have a temporary daemon, which you see here in blue, and that's your app master. So this is what we mention when we say yet another resource negotiator. So app master would be existing in a Hadoop version 2. Now when we talk about your resource manager is the master for processing layer. So it would already be receiving heartbeats, and you can say resource information from multiple node managers which would be running on one or multiple machines. And these node managers are not only updating their status, but they are also giving an information of the amount of resources they have. Now when we talk about resources, we should understand that if I'm talking about this node manager, then this has been allocated some amount of RAM for processing and some amount of CPU cores. And that is just a portion of what the complete node has. So if my node has, say, imagine my node has around 100 GB RAM and I have, say, 60 cores, all of that cannot be allocated to node manager. So node manager is just one of the components of Hadoop ecosystem. It is the slave of the processing layer. So we could say, keeping in all the aspects, such as different services which are running, might be Cloudera or Hortonworks related services running, system processes running on a particular node, some portion of this would be assigned to node manager for processing. So we could say, for example, say 60 GB RAM per node and say 40 CPU cores. So this is what is allocated for the node manager on every machine. Similarly, we would have here. Similarly, we would have here. So node manager is constantly giving an update to resource manager about the resources, what it has. Probably there might be some other applications running, and node manager is already occupied, so it gives an update. Now we also have a concept of containers, which is basically we will talk about, which is about these resources being broken down into smaller parts. So resource manager is keeping a track of the resources which every node manager has, and it is also responsible for taking care of the job request. How do these things happen? Now as we see here, resource manager at a higher level, you can always say this is the processing master which does everything. But in reality, it is not the resource manager which is doing it, but it has internally different services or components which are helping it to do what it is supposed to do. Now let's look further. Now, as I mentioned, your resource manager has these services or components which basically helps it to do the things. It is basically an an architecture where multiple components are working together to achieve what Yarn allows. So resource manager has mainly two components, that is your scheduler and applications manager, and these are at high level four main components here. So we talk about resource manager, which is the processing master. You have node managers, which are the processing slaves, which are running on every nodes. You have the concept of container, and you have the concept of application master. How do all these things work? Now let's look at Yarn components. So resource manager basically has two main components, you can say, which assist resource manager in doing what it is capable of. So you have scheduler and applications manager. Now there is, when you talk about resources, there is always a requirement for the applications which need to run on cluster of resources. So your application which has to run, which was submitted by client, needs resources, and these resources are coming in from multiple machines wherever the relevant data is stored and a node manager is running. So we always know that node manager is co-located with data nodes. Now, what does the scheduler do? So we have different kind of schedulers here. We have basically a capacity scheduler, we have a fair scheduler, or we could have a FIFO scheduler. So there are different schedulers which take care of resource allocation. So your scheduler is responsible for allocating resources to various running applications. Now imagine a particular environment where you have different teams or different departments which are working on the same cluster. So we would call the cluster as a multi-tenant cluster. And on the multi-tenant cluster, you would have different applications which would want to run simultaneously accessing the resources of the cluster. How is that managed? So there has to be some component which has a concept of pooling or queuing so that different departments or different users can get dedicated resources or can share resources on the cluster. So scheduler is responsible for allocating resources to various running applications. Now it does not perform monitoring or tracking of the status of applications. That's not the part of scheduler. It does not offer any guarantee about restarting the failed tasks due to hardware or network or any other failures. Scheduler is mainly responsible for allocating resources. Now, as I mentioned, you could have different kind of schedulers. You could have a FIFO scheduler, which was mainly in older version of Hadoop, which stands for first in, first out. You could have a fair scheduler, which basically means multiple applications could be running in the cluster and they would have a fair share of the resources. You could have a capacity scheduler, which would basically have dedicated or fixed amount of resources across the cluster. Now, whichever scheduler is being used, scheduler is mainly responsible for allocating resources. Then it's your applications manager. Now, this is responsible for accepting job submissions. Now, as I said, at higher level, we could always say resource manager is doing everything. It is allocating the resources, it is negotiating the resources, it is also taking care of listening to the clients and taking care of job submissions. But who is doing it in real? It is these components. So you have applications manager, which is responsible for accepting job submissions. It negotiates the first container for executing the application specific application master. It provides the service for restarting the application master. Now, how does this work? How do these things happen in coordination? Now, as I said, your node manager is the slave process which would be running on every machine. Slave is tracking the resources, what it has. It is tracking the processes. It is taking care of running the jobs. And basically, it is tracking each container resource utilization. So let's understand what is this container. So normally when you talk about an application request which comes from a client, so let's say this is my client which is requesting or which is coming up with an application which needs to run on the cluster. Now this application could be anything. It first contacts your master. That's your resource manager, which is the master for your processing layer. Now, as I mentioned, and as we already know, that your name node, which is the master of your cluster, has the metadata in its RAM, which is aware of the data being split into blocks, the blocks being stored on multiple machines, and other information. So obviously there was a interaction with the master which has given this information of the relevant nodes where the data exists. Now for the processing need, your client, basically the application which needs to run on the cluster. So your resource manager, which basically has the scheduler which takes care of allocating resources, and a resource manager has mainly these two components which are helping it to do its work. Now for a particular application which might be needing data from multiple machines. Now we know that we would have multiple machines where we would have node manager running, we would have a data node running, and data nodes are responsible for storing the data on disk. So your resource manager has to negotiate the resources. Now when I say negotiating the resources, it could basically ask each of these node managers for some amount of resources. For example, it would be saying, can I have 1 GB of RAM and 1 CPU core from you? Because there is some data residing on your machine and that needs to be processed as part of my application. Can I again have 1 GB and 1 CPU core from you? And this is again because some relevant data is stored. And this request which resource manager makes of holding the resources, of total resources which the node manager has, your resource manager is negotiating or is asking for resources from the processing slave. So this request of holding resources can be considered as a container. So resource manager, now we know it is not actually the resource manager, but it is the application manager which is negotiating the resources. So it negotiates the resources which are called container. So this request of holding resource can be considered as a container. So basically a container can be of different sizes. We will talk about that. So resource manager negotiates the resources with node manager. Now node manager, which is already giving an update of the resources it has, what amount of resources it holds, how much busy it is, can basically approve or deny this request. So node manager would basically approve in saying, yes, I could hold these resources. I could give you this container of this particular size. Now once the container has been approved or allocated, or you can say granted by your node manager, resource manager now knows that resources to process the application are available and guaranteed by the node manager. So resource manager starts a temporary daemon called app master. So this is a piece of code which would also be running in one of the containers. It would be running in one of the containers, which would then take care of execution of tasks in other containers. So your application master is per application. So if I would have 10 different applications coming in from the client, then we would have 10 app masters, one app master being responsible for per application. Now what does this app master do? It basically is a piece of code which is responsible for execution of the application. So your app master would run in one of the containers and then it would use the other containers which node manager is guaranteed that it will give when the application request comes to it, and using these containers the app master will run the processing tasks within these designated resources. So it is mainly the responsibility of application master to get the execution done and then communicate it to the master. So resource manager is tracking the resources, it is negotiating the resources, and once the resources have been negotiated, it basically gives the control to application master. Application master is then running within one of the containers on one of the nodes and using the other containers to take care of execution. This is how it looks. So basically container, as I said, is a collection of resources like CPU, memory, your disk, which would be used or which already has the data and network. So your node manager is basically looking into the request from application master, and it basically is granting this request or basically is allocating these containers. Now again, we could have different sizing of the containers. Let's take an example here. So as I mentioned, from the total resources which are available for a particular node, some portion of resources are allocated to the node manager. So let's imagine this is my node where node manager as a processing slave is running. So from the total resources which the node has, some portion of RAM and CPU cores is basically allocated to the node manager. So I could say out of total 100 GB RAM, we can say around 60 cores which the particular node has. So this is my RAM which the node has, and these are the CPU cores which the node has, some portion of it, right? So we can say might be 70% or 60% of the total resources. So we could say around 60 GB RAM, and then we could say around 40 vCores have been allocated to node manager. So there are these settings which are given in the yarn-site file. Now, apart from this allocation, that is 60 GB RAM and 40 vCores, we also have some properties which say what will be the container sizes. So for example, we could have a small container setting which could say my every container could have 2 GB RAM and say 1 virtual CPU core. So this is my smallest container. So based on the total resources, you could calculate how many such small containers could be running. So if I say 2 GB RAM, then I could have around 30 containers. But then I'm talking about 1 virtual CPU core. So totally I could have around 30 small containers which could be running in parallel on a particular node. And as of that calculation, you would say 10 CPU cores are not being utilized. You could have a bigger container size which could say I would go for 2 CPU cores and 3 GB RAM. So 3 GB RAM and 2 CPU cores. So that would give me around 20 containers of bigger size. So this is the container sizing which is again defined in the yarn-site file. So what we know is on a particular node which has this kind of allocation, either we could have 30 small containers running or we could have 20 big containers running. And same would apply to multiple nodes. So node manager, based on the request from application master, can allocate these containers. Now remember, it is within this one of these containers you would have an application master running, and other containers could be used for your processing requirement. Application master, which is per application, it is the one which uses these resources. It basically manages or uses these resources for individual application. So remember, if we have 10 applications running on Yarn, then it would be 10 application masters, one responsible for each application. Your application master is the one which also interacts with the scheduler to basically know how much amount of resources could be allocated for one application. And your application master is the one which uses these resources, but it can never negotiate for more resources to node manager. Application master cannot do that. Application master has to always go back to resource manager if it needs more resources. So it is always the resource manager, and internally resource manager's component, that is application manager, which negotiates the resources. At any point of time, due to some node failures or due to any other requirements, if application master needs more resources on one or multiple nodes, it will always be contacting the resource manager, internally the applications manager, for more containers. Now this is how it looks. So your client submits the job request to resource manager. Now we know that resource manager internally has scheduler and applications manager. Node managers which are running on multiple machines are the ones which are tracking their resources, giving this information to resource manager so that resource manager, or I would say its component applications manager, could request resources from multiple node managers. When I say request resources, it is these containers. So your resource manager basically will request for the resources on one or multiple nodes. Node manager is the one which approves these containers. And once the container has been approved, your resource manager triggers a piece of code, that is application master, which obviously needs some resources, so it would run in one of the containers and will use other containers to do the execution. So your client submits an application to resource manager. Resource manager allocates a container, or I would say this is at a high level, right? Resource manager is negotiating the resources, and internally who is negotiating the resources? It is your applications manager. Who is granting this request? It is node manager. And that's how we can say resource manager allocates a container. Application master basically contacts the related node manager because it needs to use the containers. Node manager is the one which launches the container, or basically gives those resources within which an application can run. And application master itself will then accommodate itself in one of the containers and then use other containers for the processing. And it is within these containers the actual execution happens. Now that could be a map task, that could be a reduce task, that could be a Spark executor taking care of Spark tasks, and many other processing. So before we look into the demo on how Yarn works, I would suggest looking into one of the blogs from Cloudera. So you can just look for Yarn untangling, and this is really a good blog which basically talks about the overall functionality which I explained just now. So as we mentioned here, so you basically have the master process, you have the worker process which basically takes care of your processing, your resource manager being the master, and node manager being the slave. This also talks about the resources which each node manager has. It talks about the Yarn configuration file where you give all these properties. It basically shows you node manager which reports the amount of resources it has to resource manager. Now remember, if worker node shows 8 into 8 CPU cores and 128 GB RAM, and if your node manager says 64 V cores and RAM 128 GB, then that's not the total capacity of your node. It is some portion of your node which is allocated to node manager. Now once your node manager reports that, your resource manager is requesting for containers based on the application. What is a container? It is basically a logical name given to a combination of vCore and RAM. It is within this container where you would have basically the process running. So once your application starts and once node manager is guaranteed these containers, your application or your resource manager has basically already started an application master within the container. And what does that application master do? It uses the other containers where the tasks would run. So this is a very good blog which you can refer to, and this also talks about Mapreduce. If you have already followed the Mapreduce tutorials in past, then you would know about the different kind of tasks, that is map and reduce, and these map and reduce tasks could be running within the container in one or multiple. As I said, it could be map task, it could be reduce task, it could be a Spark based task which would be running within the container. Now once the task finishes, basically that resources can be freed up. So the container is released and the resources are given back to Yarn so that it can take care of further processing. If you'll further look in this blog, you can also look into the part 2 of it where you talk mainly about configuration settings. You can always look into this, which talks about why and how much resources are allocated to the node manager. It basically talks about your operating system overhead. It talks about other services. It talks about Cloudera or Hortonworks related services running and other processes which might be running. And based on that, some portion of RAM and CPU cores would be allocated to node manager. So that's how it would be done in the yarn-site file. And this basically shows you what is the total amount of memory and CPU cores which is allocated to node manager. Then within every machine where you have a node manager running, on every machine in the yarn-site file, you would have such properties which would say what is the minimum container size, what is the maximum container size. in terms of RAM. What is the minimum for CPU cores? What is the maximum for CPU cores? And what is the incremental size in where RAM and CPU cores can increment? So these are some of the properties which define how containers are allocated for your application request. So have a look at this, and this could be a good information which talks about different properties. Now you can look further, which talks about scheduling. If you look in this particular blog, which also talks about scheduling, where it talks about scheduling in Yarn, which talks about fair scheduler, or you basically having different queues in which allocations can be done. You also have different ways in which queues can be managed and different schedulers can be used. So you can always look at this series of blog. You can also be checking for Yarn, schedulers, and then search for Hadoop definitive guide, and that could give you some information on how it looks when you look for Hadoop definitive guide. So if you look into this book, which talks about the different resources, as I mentioned, so you could have a FIFO scheduler, that is first in first out, which basically means if a long running application is submitted to the cluster, all other small running applications will have to wait. There is no other way, but that would not be a preferred option if you look in FIFO scheduler. If you look for capacity scheduler, it basically means that you could have different queues created, and those queues would have resources allocated. So then you could have a production queue where production jobs are running in a particular queue which has fixed amount of resources allocated. You could have a development queue where development jobs are running and both of them are running in parallel. You could then also look into fair scheduler, which basically means again multiple applications could be running on the cluster, however they would have a fair share. So when I say fair share, in brief, what it means is if I had given 50% of resources to a queue for production and 50% of resources for a queue of development, and if both of them are running in parallel, then they would have access to 50% of cluster resources. However, if one of the queue is unutilized, then second queue can utilize all cluster resources. So look into the fair scheduling part. It also shows you about how allocations can be given, and you can learn more about schedulers and how queues can be used for managing multiple applications. Now we will spend some time in looking into few ways or few quick ways in interacting with Yarn in the form of a demo. To understand and learn on how Yarn works, we can look into a particular cluster. Now here we have a designated cluster which can be used. You could be using the similar kind of commands on your Apache based cluster or a Cloudera Quick Start VM if you already have, or if you have a Cloudera or a Hortonworks cluster running. There are different ways in which we can interact with Yarn and we can look at the information. One is basically looking into the admin console. So if I would look into Cloudera Manager, which is basically an admin console for a Cloudera's distribution of Hadoop. Similarly, you could have a Hortonworks cluster and access to the admin console. So if you have even read access for your cluster, and if you have the admin console, then you can search for Yarn as a service which is running. You can click on Yarn as a service, and that gives you different tabs. So you have the instances, which tells basically what are the different roles for your Yarn service running. So we have here multiple node managers. Now some of them show in stop status, but that's nothing to worry. So we have 3 and 6 node managers. We have resource manager, which is 1, but then that can also be in a high availability where you can have active and standby. You also have a job history server, which would show you the applications once they have completed. Now you can look at the Yarn configurations, and as I was explaining, you can always look for the properties which are related to the allocation. So you can here search for cores, and that should show you the properties which talk about the allocations. So here, if we see, we can be looking for Yarn app Mapreduce application master resource CPU cores. What is the CPU cores allocated for Mapreduce, map task, reduce task? You can be looking at Yarn node manager resource CPU cores, which basically says every node manager on every node would be allocated with 6 CPU cores. and the container sizing is with minimum allocation of 1 CPU core and the maximum could be 2 CPU cores. Similarly, you could also be searching for memory allocation, and here you could then scroll down to see what kind of memory allocation has been done for the node manager. So if we look further, it should give me information of node manager, which basically says here that the container minimum allocation is 2 GB, the maximum is 3 GB, and we can look at node manager, which has been given 25 GB per node. So it's a combination of this memory and CPU cores, which is the total amount of resources which have been allocated to every node manager. Now we can always look into applications tab that would show us different applications which are submitted on Yarn. For example, right now we see there is a Spark application running, which is basically a user who is using Spark shell, which has triggered a application on Spark, and that is running on Yarn. You can look at different applications, workload information. You can always do a search based on the number of days, how many applications have run, and so on. You can always go to the web UI and you can be searching for the resource manager web UI, and if you have access to that, it will give you overall information of your cluster. So this basically says that here we have 100 GB memory allocated, so that could be say 25 GB per node, and if we have 4 node managers running and we have 24 cores, which is 6 cores per node. If we look further here into nodes, I could get more information. So this tells me that I have 4 node managers running, and node managers basically have 25 GB memory allocated per node and 6 cores, out of which some portion is being utilized. We can always look at the scheduler here, which can give us information what kind of scheduler has been allocated. So we basically see that there is just a root queue, and within root you have default queue and you have basically users queue based on different users. We can always scroll here and that can give us information if it is a fair share. So here we see that my root.default has 50% of resources and the other queue also has 50% of resources, which also gives me an idea that a fair scheduler is being used. We can always confirm that if we are using a fair scheduler or a capacity scheduler which takes care of allocation. So search for scheduler, and that should give you some understanding of what kind of scheduler is being used and what are the allocations given for that particular scheduler. So here we have fair scheduler. It shows me you have under root, you have the root queue which has been given 100% capacity, and then you have within that default which also takes 100%. So this is how you can understand about Yarn by looking into the Yarn web UI. You can be looking into the configurations, you can look at applications, you can always look at different actions. Now since we do not have admin access, the only information we have is to download the client configuration. We can always look at the history server, which can give us information of all the applications which have successfully completed. Now this is from your Yarn UI. What I can also do is I can be going into Hue, which is the web interface, and your web interface also basically allows you to look into the jobs. So you can click on Hue Web UI, and if you have access to that, it should show up, or you should have a way to get to your Hue, which is a graphical user interface, mainly comes with your Cloudera. You can also configure that with Apache. Hortonworks has a different way of giving you the web UI access. You can click and get into Hue, and that is also one way where you can look at Yarn, you can look at the jobs which are running, if there are some issues with it, and these are your web interfaces. So either you look from Yarn web UI, or here in Hue you have something called as job browser, which can also give you information of your different applications which might have run. So here I can just remove this one, which should basically give me a list of all the different kind of jobs or workloads which were run. So either it was a Spark based application, or it was a Mapreduce, or it was coming from Hive. So here I have list of all the applications, and it says this was a Mapreduce, this was a Spark, something was killed, something was successful, and this was basically probably a Hive query which triggered a Mapreduce job. You can click on the application, and that tells you how many tasks were run for it. So there was a map task which ran for it. You can get into the metadata information, which you can also look from the Yarn UI to look into your applications, which can give you a detailed information of if it was a Mapreduce, how many map and reduce tasks were run, what were the different counters. If it was a Spark application, it can let you follow through Spark history server or job history server. So you can always use the web UI to look into the jobs. You can be finding in a lot of useful information here. You can also be looking at how many resources were used and what happened to the job. Was it successful? Did it fail? And what was the job status? Now, apart from web UI, which always you might not have access to. So in a particular cluster, in a production cluster, there might be restrictions, and the organization might not have access given to all the users to graphical user interface like you, or might be you would not have access to the Cloudera manager or admin console because probably organization is managing multiple clusters using this admin console. So the one way which you would have access is your web console, or basically your edge node or client machine from where you can connect to the cluster and then you can be working. So let's log in here, and now here we can give different commands. So this is the command line from where you can have access to different details. You can always check by just typing in Mapred, which gives you different options where you can look at the Mapreduce related jobs. You can look at different queues. If there are queues configured, you can look at the history server, or you can also be doing some admin stuff provided you have access. So for example, if I just say Mapred and queue here, this basically gives me an option. Says what would you want to do? Would you want to list all the queues? Do you want information on a particular queue? So let's try a list, and that should give you different queues which were being used. Now here we know that per user a queue dynamically gets created which is under root.users, and that gives me what is the status of the queue, what is the capacity, has there been any kind of maximum capacity or capping done. So we get to see a huge list of queues which dynamically get configured in this environment, and then you also look at your root.default. I could have also picked up one particular queue and I could have said show me the jobs. So I could do that. Now here we can also give a yarn command. So let me just clear the screen and I will say yarn, and that shows me different options. So apart from your web interface, something like web UI, apart from your yarn's web UI, you could also be looking for information using yarn commands here. So these are some list of commands which we can check. Now you can just type in yarn and version if you would want to see the version, which basically gives you information of what is the Hadoop version being used and what is the vendor specific distribution version. So here we see we are working on Cloudera's distribution 5.14, which is internally using Hadoop 2.6. Now similarly, you can be doing a yarn application list. So if you give this, that could be an exhaustive list of all the applications which are running or applications which have completed. So here we don't see any applications because right now probably there are no applications which are running. It also shows you could be pulling out different status such as submitted, accepted, or running. Now you could also say I would want to see the services that have finished running. So I could say yarn application list and app states as finished. So here we could be using our command. So I could say yarn application list, and then I would want to see the app states, which gives me the applications which have finished. And we would want to list all the applications which finished. Now that might be applications which succeeded, right? And there is a huge list of application which is coming in from the history server, which is basically showing you the huge list of applications which have completed. So this is one way. And then you could also be searching for one particular application. If you would want to search a particular application, if you have the application ID, you could always be doing a grep. That's a simple way. I could say, basically, let's pick up this one. And if I would want to search for this, if I would want more details on this, I could obviously do that by calling in my previous command, and you could do a grep if that's what you want to do. And if you would want to search, is there an application which is in the list of my applications that shows my application? I could pull out more information about my application. So I could look at the log files for a particular application by giving the application ID. So I could say yarn logs. Now that's an option. And anytime you have a doubt, just hit enter. It will always give you options what you need to give with a particular command. So I can say yarn logs application ID. Now we copied an application ID and we could just give it here. We could give other options like app owner, or if you would want to get into the container details, or if you would want to check on a particular node. Now here I'm giving yarn logs and then I'm pointing it to an application ID and it says the log aggregation has not completed. Might be this was an application which was triggered based on a particular interactive shell or based on a particular query. So there is no log existing for this particular application. You can always look at the status of an application. You can kill an application. So here you can be saying yarn application, and then what would you want to do with an application? Hit and enter. It shows you the different options. So we just tried app states. You could always look at the last one which says status. And then for my status, I could be giving my application ID. So that tells me what is the status of this application. It connects to the resource manager. It tells me what's the application ID, what kind of application it was, who ran it, which was the queue, where the job was running, what was the start and end time, what is the progress, the status of it, if it is finished or if it has succeeded. And then it basically gives me also an information of where the application master was running. It gives me the information where you can find this job details in history server if you are interested in looking into. It also gives you a aggregate resource allocation which tells how much GB memory and how many core seconds it used. So this is basically looking out at the application details. Now I could kill an application if the application was already running. I could always do a yarn application minus kill, and then I could be giving my application. Now I could try killing this. However, it would say the application is already finished. If I had an application running and if my application was already given an application ID by resource manager, I could just kill it. I can also say yarn node list, which should give me a list of the node managers. Now this is what we were looking from the yarn web UI, and we were pulling out the information, so we can get this kind of information from your command line. Always remember and always try to be well accustomed with the command line, so you can do various things from the command line. And then obviously you have the web UIs which can help you with a graphical interface, easily able to access things. Now you could be also starting the resource manager, which we would not be doing here because we are already running in a cluster. So you could give a yarn resource manager. You could get the logs of resource manager if you would want by giving yarn daemon. So we can try that. So you can say yarn and then daemon. So it says it does not find the daemon. So you can give something like this, get level, and here I will have to give the node and the IP address where you want to check the logs of resource manager. So you could be giving this, for which we will have to then get into Cloudera manager to look into the nodes and the IP address. You could be giving a command something like this, which basically gives you the level of the log which you have, and I got this resource manager address from the web UI. Now I can be giving in this command to look into the daemon log, and it basically says you would want to look at the resource manager related log, and you have the log4j which is being used for logging. the kind of level which has been set as info, which can again be changed in the way you're logging the information. Now you can try any other commands also from yarn. For example, looking at the yarn rm admin. So you can always do a yarn rm admin, and this basically gives you a lot of other informations like refreshing the queues or refreshing the nodes, or basically looking at the admin ACLs or getting groups. So you could always get group names for a particular user. Now we could search for a particular user such as yarn or HDFS itself. So I could just say here I would want get groups, and then I could be searching for, say, username HDFS. So that tells me HDFS belongs to a Hadoop group. Similarly, you could search for, say, Mapred, or you could search for yarn. So these are service related users which automatically get created, and you can pull out information related to these. You can always do a refresh nodes kind of command, and that is mainly done internally. This can be useful when you're doing commissioning, decommissioning. But then in case of Cloudera or Hortonworks kind of cluster, you would not be manually giving this command, because if you are doing a commissioning, decommissioning from an admin console, and if you are an administrator, then you could just restart the services which are affected, and that will take care of this. But if you were working in an Apache cluster, and if you were doing commissioning, decommissioning, then you would be using in two commands: refresh nodes, and basically that's for refreshing the nodes which should not be used for processing. And similarly, you could have a command refresh nodes which comes with HDFS. So these are different options which you can use with your yarn on the command line. You could also be using curl commands to get more information about your cluster by giving curl -x and then basically pointing out to your resource manager web UI address. Now here I would like to print out the cluster related metrics, and I could just simply do this, which basically gives me a high level information of how many applications were submitted, how many are pending, what is the reserved resources, what is the available amount of memory or CPU cores, and all the information. Similarly, you can be using the same curl commands to get more information like scheduler information. So you would just replace the metrics with scheduler, and you could get the information of the different queues. Now that's a huge list. We can cancel this, and that would give me the list of all the queues which are allocated and what are the resources allocated for each queue. You could also get cluster information on application IDs and status running of applications running in yarn. So you would have to replace the last bit of it, and you would say I would want to look at the applications, and that gives me a huge list of applications. Then you can do a grep, and you can be filtering out specific application related information. Similarly, you can be looking at the nodes. So you can always be looking at node specific information, which gives you how many nodes you have. But this could be mainly used when you have an application which wants to, or a web application which wants to use a curl command and would want to get information about your cluster from an HTTP interface. Now, when it comes to application, we can basically try running a simple or a sample Mapreduce job, which could then be triggered on yarn, and it would use the resources. Now I can look at my application here, and I can be looking into my specific directory, which is this one, which should have a lot of files and directories which we have here. Now I could pick up one of these, and I could be using a simple example to do some processing. Let's take up this file. So there is a file, and I could run a simple word count, or I could be running a Hive query which triggers a Mapreduce job. I could even run a Spark application which would then show that the application is running on the cluster. So for example, if I would say Spark to shell. Now I know that this is an interactive way of working with Spark, but this internally triggers a Spark submit, and this runs an application. So here, when you do a Spark to shell, by default it will contact Yarn. So it gets an application ID. It is running on Yarn with the master being Yarn. And now I have access to the interactive way of working with Spark. Now if I go and look into applications, I should be able to see my application which has been started here, and it shows up here. So this is my application 3827 which has been started on Yarn, and as of now we can also look into the Yarn UI, and that shows me the application which has been started, which basically has one running container which has one CPU core allocated, 2 GB RAM, and it's in progress, although we are not doing anything there. So we can always look at our applications from the Yarn UI, or as I mentioned, from your applications tab within Yarn services, which gives us the information, and you can even click on this application to follow and see more information, but you should be given access to that. Now this is just a simple application which I triggered using Spark Shell. Similarly, I can basically be running a Mapreduce. Now to run a Mapreduce, I can say Hadoop jar, and that basically needs a class. So we can look for the default path, which is opt Cloudera parcels cdh lib Hadoop Mapreduce Hadoop Mapreduce examples, and then we can look at this particular jar file, and if I hit on enter, it shows me the different classes which are part of this jar. And here I would like to use word count. So I could just give this, I could say word count. Now remember, I could run the job in a particular queue by giving in an argument here. So I could say -d mapred dot job dot queue dot name, and then I can point my job to a particular queue. I can even give different arguments in saying I would want my Mapreduce output to be compressed, or I want it to be stored in a particular directory, and so on. So here I have the word count, and then basically what I can be doing is I can be pointing it to a particular input path, and then I can have my output which can be getting stored here, again a directory which we need to choose, and I will say output new, and I can submit my job. Now once I've submitted my job, it connects to resource manager. It basically gets a job ID, it gets an application ID, it shows you from where you can track your application. You can always go to the Yarn UI and you can be looking at your application and the resources it is using. So my application was not a big one, and it has already completed. It triggered one map task, it launched one reduce task. It was working on around 12,466 records, where you have then the output of map, which is these many number of output records, which was then taken by a combiner, and finally by a reducer, which basically gives you the output. So this is my Yarn application which has completed. Now I could be looking into the Yarn UI, and if my job has completed, you might not see your application here. So as of now, it shows up here, the word count which I ran. It also shows me my previous Spark Shell job. It shows me my application is completed, and if you would want further information on this, you can click and go to the history server if you have been given access to it, or directly go to the history server web UI where your application shows up. It shows how many map and reduce tasks it was running. You can click on this particular application, which basically gives you information of your map and reduce tasks. You can look at different counters for your application, right? You can always look at map specific tasks. You can always look into one particular task, what it did, on which node it was running, or you can be looking at the complete application log. So you can always click on the logs, and here you have click here for full log, which gives you the information, and you can always look for your application, which can give you information of app master being launched, or you could have search for the word container. So you could see a job which needs one or multiple containers, and then you could say container is being requested. Then you could see container is being allocated. Then you can see what is the container size, and then basically your task moves from initializing to running in the container. And finally, you can even search for release, which will tell you that the container was released. So you can always look into the log for more information. So this is how you can interact with Yarn. This is how you can interact with your command line to look for more information or using your Yarn web UI, or you can also be looking into your Hue for more information.
Welcome to Sqoop Tutorial, one of the many features of the Hadoop ecosystem for the Hadoop file system. What's in it for you? Today we're going to cover the need for Sqoop, what is Sqoop, Sqoop features, Sqoop architecture, Sqoop import, Sqoop export, Sqoop processing, and then finally we'll have a little hands-on demo on Sqoop so you can see what it looks like. So where does the need for Sqoop come in our big data Hadoop file system? Processing huge volumes of data requires loading data from diverse sources into Hadoop cluster. And you can see here we have our data processing, and this process of loading data from the heterogeneous sources comes with a set of challenges. So what are the challenges? Maintaining data consistency, ensuring efficient utilization of resources, especially when you're talking about big data. We can certainly use up the resources when importing terabytes and petabytes of data over the course of time. Loading bulk data to Hadoop was not possible. This is one of the big challenges that came up when they first had the Hadoop file system going. And loading data using script was very slow. In other words, you'd write a script in whatever language you were in, and then it would very slowly load each piece and parse it in. So the solution? Sqoop. Sqoop helped in overcoming all the challenges to traditional approach and could lead bulk data from RDBMS to Hadoop very easily. So think your enterprise server, you want to take the from MySQL or your SQL, and you want to bring that data into your Hadoop warehouse, your data filing system. And that's where Sqoop comes in. So what exactly is Sqoop? Sqoop is a tool used to transfer bulk of data between Hadoop and external data stores, such as relational databases, and MySQL Server, or the Microsoft SQL Server, or MySQL Server. So Sqoop equals SQL plus Hadoop. And you can see here where we have our RDBMS, all the data we have stored on there, and then your Sqoop is the middle ground, and it brings the import into the Hadoop file system. It also is one of the features that goes out and grabs the data from Hadoop and exports it back out into an RDBMS. Let's take a look at Sqoop features. Sqoop features has parallel import and export. It has import results of SQL query, connectors for all major RDBMS databases, Kerberos security integration, provides full and incremental load. So when we look at parallel import and export, Sqoop uses Yarn, yet another resource negotiator, framework to import and export data. This provides fault tolerance on top of parallelism. Sqoop allows us to import the result returned from an SQL query into the Hadoop file system, or the HDFS. And you can see here where the import results of SQL query come in. Sqoop provides connectors for multiple relational database management system, RDBMSs, databases, such as MySQL and Microsoft SQL Server. And it has connectors for all major RDBMS databases. Sqoop supports Kerberos Computer Network Authentication Protocol that allows nodes communicating over a non-secure network to prove their identity to one another in a secure manner. Sqoop can load the whole table or parts of the table by a single command. Hence, it supports full and incremental load. Let's dig a little deeper into the Sqoop architecture. We have our client, in this case a hooded wizard behind his laptop. You never know who's going to be accessing the Hadoop cluster. And the client comes in and sends their command, which goes into Sqoop. The client submits the import-export command to import or export data. Data from different databases is fetched by Sqoop. And so you have your enterprise data warehouse, document-based systems. You have connector for your data warehouse, a connector for document-based systems, which reaches out to those two entities. And we have our connector for the RDBMS. So connectors help in working with a range of popular databases. Multiple mappers perform map tasks to load the data onto HDFS, the Hadoop file system. And you can see here we have the map task. If you remember from Hadoop, Hadoop is based on Mapreduce. Because we're not reducing the data, we're just mapping it over, it only accesses the mappers, and it opens up multiple mappers to do parallel processing. And you can see here the HDFS HBase Hive is where the target is for this particular one. Similarly, multiple map tasks will export the data from HDFS onto RDBMS using Sqoop export command. So just like you can import it, you can now export it using the multiple map routines. Sqoop import. So here we have our RDBMS data store, and we have the folders on there. So maybe it's your company's database, maybe it's an archive at Google with all the searches going on, whatever it is. Usually you think with Sqoop, you think SQL, you think MySQL Server or Microsoft SQL Server, that kind of setup. So it gathers the metadata, and you see the Sqoop import. So introspect database to gather metadata, primary key information. And then it submits. So you can see it submits map only job. Remember we talked about Mapreduce? It only needs the map side of it because we're not reducing the data, we're just mapping it over. Sqoop divides the input data set into splits and uses individual map tests to push the splits into HDFS. So right into the Hadoop file system. And you can see down on the right is kind of a small depiction of a Hadoop cluster. And then you have Sqoop export. So we're going to go the other direction. And with the other direction, you have your Hadoop file system storage, which is your Hadoop cluster. You have your Sqoop job, and each one of those clusters then gets a map. The mapper comes out to each one of the computers that has data on it. So the first step is you've got to gather the metadata. So step 1, you gather the metadata. Step 2, submits map only job. Introspect database to gather metadata, primary key information. Sqoop divides the input dataset into splits and uses individual map tests to push the splits to RDBMS. Sqoop will export Hadoop files back to RDBMS tables. And you can think of this in a number of different manners. One of them would be if you're restoring a backup from the Hadoop file system into your enterprise machines. There's certainly many others as far as exploring data and data science. So as we dig a little deeper into Sqoop input, we have our connect, our JDBC, and our URL. So specify the JDBC connect string. Connecting manager, we specify the connection manager class to use. And you can see here driver with the class name, manually specify the JDBC driver class to use. Hadoop Mapreduce home directory, override Hadoop mapped home, username, set authentication username, and of course help, print usage instructions. And with the export, you'll see that we can specify the JDBC connect string, specify the connection manager class to use, manually specify JDBC driver class to use. You do have to let it know to override the Hadoop Mapreduce home, and that's true on both of these, and set authentication username, and finally you can print out all your help setup. So you can see the format for Sqoop is pretty straightforward, both import and export. So let's continue on our path and look at Sqoop processing and what the computer goes through for that. And we talk about Sqoop processing. First, Sqoop runs in the Hadoop cluster. It imports data from the RDBMS, the NoSQL database, to the Hadoop file system. So remember, it might not be importing the data from a RDBMS. It might actually be coming from a NoSQL, and there's many out there. It uses mappers to slice the incoming data into multiple formats and load the data into HDFS. It exports data back into an RDBMS while making sure that the schema of the data in the database is maintained. So now that we've looked at the basic commands in our Sqoop and the Sqoop processing, or at least the basics as far as theory is concerned, let's just jump in and take a look at a demo on Sqoop. For this demo, I'm going to use our Cloudera Quick Start. If you've been watching our other demos we've done, you'll see that we've been using that pretty consistently. Certainly this will work in any of your Horton Sandbox, which is also a single node testing machine. Cloudera is one of them. There's a Docker version instead of VirtualBox. And you can also set up your own Hadoop cluster. Plan a little extra time. If you're not an admin, it's actually a pretty significant endeavor. For an admin, if you've been adminning Linux machines for a very long time, and you know a lot of the commands, I find it for most admins it takes them about 2 to 4 hours the first time they go in and create a virtual machine and set up their own Hadoop. In this case though, when you're just learning and getting set up, best to start with Cloudera. Cloudera also includes an installed version of MySQL. That way you don't have to worry about installing the SQL version for importing data from and to. Once you're in the Cloudera Quick Start, you'll see it opens a nice CentOS Linux interface, and it has the desktop set up on there. This is really nice for learning, so you're not just looking at command lines. And from in here, it should open up by default to Hue. If not, you can click on Hue. Hue's a kind of a fun little web-based interface. Under Hue, I can go under Query, I can pick an editor, and we'll go right down to Sqoop. So now I'm just going to load the Sqoop editor in our Hue. Now I'm going to switch over and do this all in command line. I just want to show that you can actually do this in Hue through the web-based interface. The reason I like to do the command line is specifically on my computer, it runs much quicker. Or if I do the command line here and I run it, it tends to have an extra lag or an added layer in it. So for this, we're going to go ahead and open our command line. The second reason I do this is we're going to need to go ahead and edit our MySQL so we have something to scoop in. Otherwise, I don't have anything going in there. And of course, we'll zoom in this and increase the size of our screen. So for this demo, our hands-on, I'm going to use Oracle VirtualBox Manager and the Cloudera Quick Start. If you're not familiar with this, we do have another tutorial we put out, and you can send a note in the YouTube video below and let our team know, and they'll send you a link. Or come visit www.simplilearn.com. Now this creates a Linux box on my Windows computer, so we're going to be in Linux, and it'll be the Cloudera version with Sqoop. It will also be using MySQL. MySQL Server. Once inside the Cloudera VirtualBox, we'll go into the Hue editor. Now we're going to do everything in terminal window, but I just want you to be aware that under the Hue editor, you can go under Query Editor, and you'll see as we come down here, here's our Sqoop on this. So you can run your Sqoop from in here. Now before we do this, we have to do a little exploration in MySQL, a MySQL Server. That way we know what data is coming in. So let me go ahead and open up a terminal window. In Cloudera, you have a terminal window at the top here that you can just click on and open it up. And let me just go ahead and zoom in on here. We'll go View and Zoom in. Now to get into MySQL Server, you simply type in MySQL, and this part will depend on your setup. Now the Cloudera Quick Start comes up that the username is root and the password is Cloudera. Kind of a strange quirk is that you can put a space between the -u and the root, but not between the -p and the Cloudera. Usually you'd put in a -P and then it prompts you for your password on here. For this demo, I don't worry too much about you knowing the password on that, so we'll just go right into MySQL Server since this is the standard password for this quick start. And you can see we're now into MySQL. And we're going to do just a couple of quick commands in here. There's show databases, and you follow by the semicolon. That's standard in most of these shell commands, so it knows it's the end of your shell command. And you'll see in here in the Quick Start, Cloudera Quick Start, the MySQL comes with a standard set of databases. These are just, some of these have to do like with the Uzi, which is the Uzi part of Hadoop, where others of these, like customers and employees and stuff like that, those are just for demo purposes. They come as a standard setup in there so that people going in for the first time have a database to play with, which is really good for us, so we don't have to recreate those databases. And you will see on the list here, we have a retail_db. And then we can simply do use retail_db. This will set that as a default in MySQL. And then we want to go ahead and show the tables. And if we show the tables, you can see under the database, the retail DB database, we have categories, customers, departments, order items, orders, products. So there's a number of tables in here. And we're going to go ahead and just use a standard SQL command. And if you did our Hive language, you'll note, remember it's the same for HQL also on this. We're just going to select star everything from departments. So there's our departments table, and we're going to list everything on the departments table. And you'll see we have about 6 lines in here, and it has a department ID and a department name. 2 for fitness, 3 for footwear, so on and so forth. Now at this point, I can just go ahead and exit, but it's kind of nice to have this data up here so we can look at it and flip back and forth between the screens. So I'm going to open up another terminal window, and we'll go ahead and zoom in on this also. And it isn't too important for this particular setup, but it's always kind of fun to know what your setup you're working with. What is your host name? And so we'll go ahead and just type that in. This is a Linux command, and it's hostname -f, and you see we're on Quick Start Cloudera. No surprise there. Now this next command is going to be a little bit longer because we're going to be doing our first Sqoop command. And I'm going to do 2 of them. We're going to list databases and list tables. It's going to take just a moment to get through this because there's a bunch of stuff going on here. So we have Sqoop, we have list databases, we have connect. And under the connect command, we need to let it know how we're connecting. We're going to use the JDBC. This is a very standard one, JDBC MySQL. So you'll see that if you're doing an SQL database, that's how you start it off with. And then the next part, this is where you have to go look it up. It's however it was created. So if your admin created a MySQL server with a certain setup, that's what you have to go by. And you'll see that usually they list this as localhost. So you'll see something like localhost sometimes. There's a lot of different formats, but the most common is either localhost or the actual connection. So in this case, we want to go ahead and do Quick Start 3306. And so Quick Start is the name of the localhost database and how it's hosted on here. And when you set up the Quick Start for for Hadoop under Cloudera, it's port 3306 is where that's coming in. So that's where all that's coming from. And so there's our path for that. And then we have to put in our password. We type password, and if you look it up, password on the Cloudera Quick Start is Cloudera, and we have to also let it know the username. And again, if you're doing this, you'd probably put in a minus capital. You can actually just do for a prompt for the password. So if you leave that out, it'll prompt you. But for this, doesn't really matter. I don't care if you see my password. It's the default one for Cloudera Quick Start. And then the username on here is simply root. And then we're going to put our semicolon at the end. And so we have here our full setup, and we go ahead and list the databases. And you'll see, you might get some warnings on here. I haven't run the updates on the Quick Start. I suggest you're not running the updates either if you're doing this for the first time, because it'll do some reformatting on there. And it quickly pops up, and you can see here's all of our the tables we went in there. And if we go back to on the previous window, we should see that these tables match. So here we come in, and here we have our databases, and you can see back up here where we had the CM, customers, employees, and so on. So the databases match. And then we want to go ahead and list the tables for a specific database. So let's go ahead and do that. I'm a very lazy typist, so I'll put the up arrow in. And you can see here, Sqoop list databases. We're just going to go back and change this from databases to list tables. So we want to list the tables in here. Same connection. So most of the connection is the same, except we need to know which tables we're listing. An interesting fact is you can create a table without being under a database. So if you left this blank, it will show the open tables that aren't connected directly to a database or under a database. But what we want to do is right past this last slash on the 3306, we want to put that retail _ DB, because that's the database we're going to be working with. And this will go in there and show the tables listed under that database. And here we go. We got categories, customers, departments, order items, and products. If we flip back here real quick, there it is, the same thing we had. We had categories, customers, departments, order items, and so on. And so let's go ahead and run our first import command. And again, I'm that lazy typer, so we're going to do Sqoop, and instead of list tables, we want to go ahead and import. So there's our import command. And so once we have our import command in there, then we need to tell it exactly what we're going to import. So everything else is the same. We're importing from the retail DB, so we keep that. And then at the very end, we're going to tag on -- table. That tells it, so we can tell it what table we're importing from. And we're going to import departments. There we go. So this is pretty straightforward, because what's nice about this is you can see the commands are the same. I got the same connection. I change it for whatever database I'm in. Then I come in here, our password and the username are going to be the same. That's all under the MySQL Server setup. And then we let it know what table we're entering in. We run this, and this is going to actually go through the mapper process in Hadoop. So this is a mapping process. It takes the data and it maps it up to different parts in the setup in Hadoop on there, and then saves that data into the Hadoop file system. And it does take it a moment to zip through, which I kind of skipped over for you, since it is running it's designed to run across a cluster, not on a single node. So when you're running on a single node, it's going to run slow, even if you dedicate a couple cores to it. I think I put dedicated 4 cores to this one. And so you can see right down here, we get to the end. It's now mapped in that information. And then we can go in here, we can go under, can flip back to our Hue. And under Hue, on the top, there's databases, and the second icon over is your Hadoop file system. And we can go in here and look at the Hadoop file system, and you'll see it show up underneath our documents. There it is, departments, Cloudera departments. And you can see there's always a delay when I'm working in Hue, which I don't like. And that's the quick start issue. That's not necessarily running it on a server. When I'm running it on a server, you pretty much have to run through some kind of server interface. I still prefer the terminal window. It still runs a lot quicker. But we'll flip back on over here to the command line, and we can do the Hadoop, type in the Hadoop FS, and then list -ls. And if we run this, you'll see underneath our Hadoop file system, there is our departments, which has been added in. And we can also do Hadoop FS, and this is kind of interesting. For those who've gone through the Hadoop file system, everything, you'll recognize this on here. But I'm going to list the contents of departments, and you'll see underneath departments we have part M 000, 001, 002, 003. And so this is interesting because this is how Hadoop saves these files, and this is in the file system. This is not in Hive. So we didn't directly import this into Hive. We put this in the Hadoop file system. Depending on what you're doing, you would then write the schema for Hive to look at the Hadoop file system. Certainly visit our Hive tutorial for more information on Hive specific. So you can see in here are different files that it forms that are part of departments. And we can do something like this. We can look at the contents of one of these files, fs minus ls, or a number of the files. And we'll simply do the full path, which is user, Cloudera. And then we already know the next one is departments. And then after departments, we're going to put /part star. So this is going to say anything that has part in it. So we have part-m000 and so on. We can go ahead and use that cat command or that list command to bring those up, and then we can use the cat command to actually display the contents. And that's a Linux command, Hadoop Linux command, to catenate. Not to be confused with catatonic, catastrophic. There's a lot of cat got your tongue. And we see here fitness, footwear, apparel. That should look really familiar because that's what we had in our MySQL server. When we went in here, we did a select all on here. There it is, fitness, footwear, apparel, golf, outdoors, and fan shop. And then, of course, it's really important, let's flip back on over here, to be able to tell it where to put the data. So we go back to our import command. So here's our Sqoop import. We have our connect. We have the DB underneath our connection, our MySQL server. We have our password, our username, the table where it's going to. The table where it's coming from. And then we can add a target on here. We can put in target dash directory, and you do have to put the full path. That's a Hadoop thing. It's a good practice to be in. And we're going to add it to department, we'll just do department 1. And so here we now add a target directory in here and user Cloudera department 1. And this will take just a moment before, so I'll go ahead and skip over the process since it's going to run very slowly. It's only running on, like I said, a couple cores, and it's also on a single node. And now we can do the Hadoop. Let's just do the up arrow. File system list. We want just straight list. And when we do the Hadoop file system minus ls or list, you'll see that we now have department 1. And we can, of course, do list department 1. And you can see we have the files inside department 1, and they mirrored what we saw before with the same files in there. And the part MMO00 and so on. If we want to look at them, it'd be the same thing we did before with the cat, except instead of departments, we'd be department 1. There we go. And then that's going to come up with the same data we had before. Now, one of the important things when you're importing data, and it's always a question to ask, is do you filter the data before it comes in? Do we want to filter this data as it comes in so we're not storing everything in our file system? You would think Hadoop, big data, put it all in there. I know from experience that putting it all in there can turn a couple hundred terabytes into a petabyte very rapidly. And suddenly you're having to really add on to that data store, and you're storing duplicate data sometimes. So you really need to be able to filter your data out. And so let's go ahead and use our up arrow to go to our last import, since it's still a lot the same stuff. So we have all of our commands on our import. We have the target. We're going to change this to department 2. So we're going to create a new directory for this one. And then after departments, there's another command that we didn't really slide in here, and that's our mapping. And I'll show you what this looks like in a minute. But we're going to put M3 in there. That does have nothing to do with the filtering. I'll show you that in a second, though, what that's for. And we just want to put in where. So where, and what is the where? In this case, we want to know where department ID, and if you want to know where that came from, we can flip back on over here. We have department underscore IDs. This is where that's coming from. That's just the name of the column on here. And so we come in here to department ID is greater than 4. Simple logic there. You can see where you'd use that for maybe creating buckets for ages, age from 10 to 15, 20 to 30. You might be looking for, there's all kinds of reasons why you could use the where command on here and filter information out. Maybe you're doing word counting and you want to know words that are used less than 100 times. You want to get rid of the and is and all the stuff that's used over and over again. So we'll go ahead and put the where, and then department ID is greater than 4. We'll go ahead and hit enter on here, and this will create our department 2 setup on this. And I'll go ahead and skip over some of the runtime. Again, it runs really slow on a single node. Real quick page through our commands. Let's see, here we go. our list, and we should see underneath the list the Department 2 on here now. And there it is, Department 2. And then I can go ahead and do list Department 2. You'll see the contents in here. And you'll see that there is only 3 maps. And it could be that the data created 3 maps, but remember I set it up to only use 3 mappers. So there's 0, 1, and 2. And we can go ahead and do a cat on there. Remember this is Department 2. So we want to look at all the contents of these 3 different files. And there it is. It's greater than 4. So we have golf is 5, outdoors 6, fan shop is 7. So we've effectively filtered out our data and just storing the data we want on our file system. So if you're going to store data on here, the next stage is to export the data. Remember, a lot of times you have MySQL Server and we're continually dumping that data into our long-term storage and access, the Hadoop file system. But what happens when you need to pull that data out and restore a database? Or maybe you have, you just merged with a new company, a favorite topic, merging companies and merging databases. That's listed under Nightmare, and how many different names for company can you have? So you can see where being able to export is also equally important. And let's go ahead and do that. And I'm going to flip back over to MySQL Server here. And we'll need to go ahead and create our database we're going to export into. Now, I'm not going to go too much in detail on this command. We're simply creating a table, and the table is going to have, it's pretty much the same table we already have in here from departments. But in this case, we're going to create a table called DEPT. So it's the same setup, but it's just going to, we're just giving it a different name, a different schema. And so we've done that, and we'll go ahead and do a select star from DEPT. There we go, and it's empty. That's what we expect, a new database, a new data table, and it's empty in there. So now we need to go ahead and export our data that we just filtered out into there. So let's flip back on over here to our Sqoop setup, which is just our Linux terminal window. And let's go back up to one of our commands. Here's Sqoop import. In this case, instead of import, we're going to take the Sqoop and we're going to export. So we're going to just change that, export. And the connection is going to remain the same. So same connect, same database. We're still doing the retail DB. We have the same password, so none of that changes. The big change here is going to be the table. Instead of departments, remember we changed it and gave it a new name. And so we want to change it here also, DEPT. So department. We're not going to worry about the mapper count. And the where was part of our import. There we go. And then finally, it needs to know where to export from. So instead of target directory, we have an export directory. That's where it's coming from. Still user, Cloudera, and we'll keep it as department 2, just so you can see how that data is coming back with that we filtered in. And let's go ahead and run this. It'll take it just a moment to go through its steps. And again, because it's slow, I'm just going to go ahead and skip this so you don't have to sit through it. And once we've wrapped up our export, we'll flip back on over here to MySQL, use the up arrow, and this time we're going to select star from department, and we can see that there it is. It exported the golf, outdoors, and fan shop. And you can imagine also that you might have to use the where command in your export also. So there's a lot of mixing. The command line for Sqoop is pretty straightforward. You're changing the different variables in there, whether you're creating a table, listing databases. Very powerful tool for bringing your data into the Hadoop file system and exporting it. So now that we've wrapped up our demo on Sqoop and gone through a lot of basic commands, let's dive in with a brief history of Hive. So the history of Hive begins with Facebook. Facebook began using Hadoop as a solution to handle the growing big data. And we're not talking about a data that fits on 1 or 2 or even 5 computers. We're talking data that fits on, if you've looked at any of our other Hadoop tutorials, you'll know we're talking about very big data and data pools. And Facebook certainly has a lot of data it tracks. As we know, the Hadoop uses Mapreduce for processing data. Mapreduce required users to write long codes. And so you'd have these really extensive Java codes, very complicated for the average person to use. Not all users were versed in Java and other coding languages. This proved to be a disadvantage for them. Users were comfortable with writing queries in SQL. SQL has been around for a long time, the standard SQL query language. Hive was developed with the vision to incorporate the concepts of tables, columns, just like SQL. So why Hive? Well, the problem was for processing and analyzing data, users found it difficult to code as not all of them were well versed with the coding languages. You have your processing, you have your analyzing, and so the solution was required a language similar to SQL, which was well known to all the users. and thus the Hive or HQL language evolved. What is Hive? Hive is a data warehouse system which is used for querying and analyzing large data sets stored in the HDFS or the Hadoop file system. Hive uses a query language that we call HiveQL or HQL, which is similar to SQL. So if we take our user, the user sends out their Hive queries, and then that is converted into a Mapreduce tasks and then accesses the Hadoop Mapreduce system. Let's take a look at the architecture of Hive. Architecture of Hive. We have the Hive client. So that could be the programmer, or maybe it's a manager who knows enough SQL to do a basic query to look up the data they need. The Hive client supports different types of client applications in different languages for performing queries. And so we have our Thrift application and the Hive Thrift client. Thrift is a software framework. Hive server is based on Thrift, so it can serve the requests from all programming languages that support Thrift. And then we have our JDBC application and the Hive JDBC driver. JDBC, Java Database Connectivity. JDBC application is connected through the JDBC driver. And then you have the ODBC application, or the Hive ODBC driver. The ODBC, or Open Database Connectivity, the ODBC application is connected through the ODBC driver. With the growing development of all of our different scripting languages, Python, C++, Spark, Java, you can find just about any connection in any of the main scripting languages. And so we have our Hive services. As we look deeper into the architecture, Hive supports various services. So you have your Hive server, basically your Thrift application or your Hive Thrift client or your JDBC or your Hive JDBC driver, your ODBC application or your Hive ODBC driver. They all connect into the Hive server. And you have your Hive web interface. You also have your CLI. Now, the Hive web interface is a GUI is provided to execute Hive queries. And we'll actually be using that later on today, so you can see kind of what that looks like and get a feel for what that means. Commands are executed directly in CLI. And then the CLI is a direct terminal window. And I'll also show you that too, so you can see how those two different interfaces work. These then push the code into the Hive driver. Hive driver is responsible for all the queries submitted, so everything goes through that driver. Let's take a closer look at the Hive driver. The Hive driver now performs 3 steps internally. One is a compiler. Hive driver passes query to compiler where it is checked and analyzed. Then the optimizer kicks in, and the optimized logical plan in the form of a graph of Mapreduce and HDFS tasks is obtained. And then finally, in the executor, in the final step, the tasks are executed. When we look at the architecture, we also have to note the metastore. Metastore is a repository for Hive metadata. It stores metadata for Hive tables. And you can think of this as your schema and where is it located. And it's stored on the Apache Derby DB. Processing and resource management is all handled by the Mapreduce v1. You'll see Mapreduce v2, the Yarn, and the Tez. These are all different ways of managing these resources depending on what version of Hadoop you're in. Hive uses Mapreduce framework to process queries. And then we have our distributed storage, which is the HDFS. And if you looked at our Hadoop tutorials, you'll know that these are on commodity machines and are linearly scalable. That means they're very affordable. A lot of time when you're talking about big data, you're talking about 1/10 of the price of storing it on enterprise computers. And then we look at the data flow in Hive. So in our data flow in Hive, we have our Hive in the Hadoop system. And underneath the user interface, or the UI, we have our driver, our compiler, our execution engine, and our metastore. That all goes into the Mapreduce and the Hadoop file system. So when we execute a query, you can see it coming in here. It goes into the driver, step 1. Step 2, we get a plan. What are we going to do? Refers to the query execution. Then we go to the metadata. And it's like, well, what kind of metadata are we actually looking at? Where is this data located? What is the schema on it? Then it comes back with the metadata into the compiler. Then the compiler takes all that information and the send plan returns it to the driver. The driver then sends the execute plan to the execution engine. Once it's in the execution engine acts as a bridge between Hive and Hadoop to process the query. And that's going into your Mapreduce and your Hadoop file system, or your HDFS. And then we come back with the metadata operations. It goes back into the metastore to update or let it know what's going on, which also goes to it's a communication between the execution engine and the metastore. Execution engine communications is bi-directionally with the metastore to perform operations like create, drop tables. Metastore stores information about tables in columns. So again, we're talking about the schema of your database. And once we have that, we have a bi-directional send results communication back into the driver. And then we have the fetch results, which goes back to the client. So let's take a little bit look at the Hive data modeling. Hive data modeling. So you have your Hive data modeling, you have your tables, you have your partitions, and you have buckets. The tables in Hive are created the same way it is done in RDBMS. So when you're looking at your traditional SQL Server or MySQL Server, where you might have enterprise equipment and a lot of people pulling and moving stuff off of there, the tables are going to look very similar. And this makes it very easy to take that information, and let's say you need to keep current information, but you need to store all of your years of transactions back into the Hadoop Hive. So you match those. Those all kind of look the same. The tables are the same. Your databases look very similar, and you can easily import them back. You can easily store them into the Hive system. Partitions. Here, tables are organized into partitions for grouping same type of data based on partition key. This can become very important for speeding up the process of doing queries. So if you're looking at dates, as far as like your employment dates of employees, if that's what you're tracking, you might add a partition there because that might be one of the key things that you're always looking up as far as employees are concerned. And finally, we have buckets. Data present in partitions can be further divided into buckets for efficient querying. Again, there's that efficiency. At this level, a lot of times you're working with the programmer and the admin of your Hadoop file system to maximize the efficiency of that file system. So it's usually a two-person job when we're talking about Hive data modeling. You want to make sure that they work together and you're maximizing your resources. Hive data types. So we're talking about Hive data types. We have our primitive data types and our complex data types. A lot of this will look familiar because it mirrors a lot of stuff in SQL. In our primitive data types, we have the numerical data types, string data type, date time data type, and miscellaneous data type. And these should be they're kind of self-explanatory, but just in case. Numerical data is your floats, your integers, your short integers. All of that numerical data comes in as a number. A string, of course, is characters and numbers. And then you have your date timestamp, and then we have kind of a general way of pulling your own created data types in there. That's our miscellaneous data type. And we have complex data types. So you can store arrays, you can store maps, you can store structures, and even units in there. As we dig into Hive data types, and we have the primitive data types and the complex data types. So we look at primitive data types, and we're looking at numeric data types. Data types like an integer, a float, a decimal, those are all stored as numbers in the Hive data system. A string data types like characters and strings. You store the name of the person you're working with, John Doe, the city, Memphis, the state, Tennessee, maybe it's Boulder, Colorado, USA, or maybe it's Hyderabad, India. That's all going to be string and stored as a string character. And of course we have our date time data type. Data types like timestamp, date, interval. Those are very common as far as tracking cells, anything like that. So you can just think if you can type a stamp of time on it, or maybe you're dealing with a race and you want to know the interval, how long did the person take to complete whatever task it was. All of that is date time data type. And then we talk miscellaneous data type. These are like Boolean and binary. And when you get into Boolean and binary, you can actually almost create anything in there. But your yes, no's, 0, 1. Now let's take a look at complex data types a little closer. We have arrays. So your syntax is of data type, and it's an array. And you can just think of an array as a collection of same entities, 1, 2, 3, 4, if they're all numbers. And you have maps. This is a collection of key value pairs. So understanding maps is so central to Hadoop. So when we store maps, you have a key, which is a set. You can only have one key per mapped value. And so in Hadoop, of course, you collect the same keys and you can add them all up or do something with all the contents of the same key. But this is our map as a primitive type data type in our collection of key value pairs. And then collection of complex data with comment. So we can have a structure where you have like column name, data type, comment, column comment. So you can get very complicated structures in here with your collection of data and your commented setup. And then we have units, and this is a collection of heterogeneous data types. So the syntax for this is union type, data type, and so on. So it's all going to be the same. A little bit different than the arrays where you can actually mix and match. Different modes of Hive. Hive operates in two modes depending on the number and size of data nodes. We have our local mode and our Mapreduce mode. When we talk about the local mode, it is used when Hadoop is having one data node and the data is small. Processing will be very fast on a smaller data sets, which are present in local machine. And this might be that you have a local file of stuff you're uploading into the Hive, and you need to do some processes in there. You can go ahead and run those Hive processes and queries on it. Usually, you don't see much in the way of a single node Hadoop system. If you're going to do that, you might as well just use like an SQL database or even a Java SQLite or something. Python is SQLite. So you don't really see a lot of single node Hadoop databases, but you do see the local mode in Hive where you're working with a small amount of data that's going to be integrated into the larger database. And then we have the Mapreduce mode. This is used when Hadoop is having multiple data nodes and the data is spread across various data nodes. Processing large data sets can be more efficient using this mode. And this you can think of, instead of it being 1, 2, 3, or even 5 computers, we're usually talking with the Hadoop file system, we're looking at 10 computers, 15, 100, where this data is spread across all those different Hadoop nodes. Difference between Hive and RDBMS. Remember, RDBMS stands for the Relational Database Management System. Let's take a look at the difference between Hive and the RDBMS. With Hive, Hive enforces schema on read. And it's very important that whatever's coming in, that's when Hive's looking at it and making sure that it fits the model. The RDBMS enforces a schema when it actually writes the data into the database. So it's read the data, and then once it starts to write it, that's where it's going to give you the error or tell you something's incorrect about your scheme. Hive data size is in petabytes. That is hard to imagine. When we're looking at your personal computer on your desk, maybe you have 10 terabytes if it's a high-end computer. But we're talking petabytes, so that's hundreds of computers grouped together. When RDBMS, data size is in terabytes. Very rarely do you see an RDBMS system that's spread over more than 5 computers. And there's a lot of reasons for that. With the RDBMS, it actually has a high-end amount of writes to the hard drive. There's a lot more going on there. You're writing and pulling stuff. So you really don't want to get too big with an RDBMS or you're going to run into a lot of problems. With Hive, you can take it as big as you want. Hive is based on the notion of write once and read many times. This is so important. They call it worm, which is write, W, once, O, read, R, many times, M. They refer to it as worm, and that's true of a lot of your Hadoop setup. It's altered a little bit, but in general, we're looking at archiving data that you want to do data analysis on. We're looking at pulling all of that stuff off your RDBMS from years and years and years of business or whatever your company does or scientific research and putting that into a huge data pool so that you can now do queries on it and get that information out of it. With the RDBMS, it's based on the notion of read and write many times. So you're continually updating this database. You're continually bringing up new stuff, new cells. The count changes because they have a different licensing now, whatever software you're selling, all that kind of stuff where the data is continually fluctuating. And then Hive resembles a traditional database by supporting SQL, but it is not a database. It is a data warehouse. This is very important, and it goes with all the other stuff we've talked about, that we're not looking at a database but a data warehouse to store the data and still have fast and easy access to it for doing queries. You can think of Twitter and Facebook. They have so many posts that are archived back historically. Those posts aren't going to change. They made the post, they're posted, they're there, and they're in their database, but they have to store it in a warehouse in case they want to pull it back up. With the RDBMS, it's a type of database management system which is based on the relational model of data. And then with Hive, easily scalable at a low cost. Again, we're talking maybe $1,000 per terabyte. The RDBMS is not scalable at a low cost. When you first start on the lower end, you're talking about $10,000 per terabyte of data, including all the backup on the models and all the added necessities to support it. As you scale it up, you have to scale those computers and hardware up. So you might start off with a basic server, and then you upgrade to a Sun computer to run it, and you spend tens of thousands of dollars for that hardware upgrade. With Hive, you just put another computer into your Hadoop file system. So let's look at some of the features of Hive. When we're looking at the features of Hive, we're talking about the use of SQL-like language called HiveQL. A lot of times you'll see that as HQL, which is easier than long codes. This is nice if you're working with your shareholders. You come to them and you say, hey, you can do a basic SQL query on here and pull up the information you need. This way, you don't have to have your programmers jump in every time they want to look up something in the database. They actually now can easily do that if they're not skilled in programming and script writing. Tables are used, which are similar to the RDBMS, hence easier to understand. And one of the things I like about this is when I'm bringing tables in from a MySQL server or SQL server, there's almost a direct reflection between the two. So when you're looking at one, which is a data which is continually changing, and then you're going into the archive database, it's not this huge jump where you have to learn a whole new language. You mirror that same schema into the HDFS, into the Hive, making it very easy to go between the two. And then using HiveQL, multiple users can simultaneously query data. So again, you can have multiple clients in there and they send in their query. That's also true with the RDBMS, which kind of queues them up. Because it's running so fast, you don't notice the lag time. Well, you get that also with the HQL. As you add more computers in, the query can go very quickly, depending on how many computers and how much resources each machine has to pull the information. And Hive supports a variety of data types. So with Hive, it's designed to be on the Hadoop system, which you can put almost anything into the Hadoop file system. So with all that, let's take a look at a demo on HiveQL or HQL. Before I dive into the hands-on demo, let's take a look at the website, hive.apache.org. That's the main website since Apache, it's an Apache open source software. This is the main software or the main site for the build. And if you go in here, you'll see that they're slowly migrating Hive into Beehive. And so if you see Beehive versus Hive, note the Beehive is a new release is coming out. That's all it is, and it reflects a lot of the same functionality of Hive. It's the same thing. And then we like to pull up some kind of documentation on commands. And for this, I'm actually going to go to Hortonworks Hive cheat sheet. And that's because Hortonworks and Cloudera are two of the most common used builds for Hadoop and for which include Hive and all the different tools in there. And so Hortonworks has a pretty good PDF you can download cheat sheet on there. I believe Cloudera does too, but we'll go ahead and just look at the Horton one, because it's the one that comes up really good. And you can see when we look at the query language, it compares MySQL Server to HiveQL or HQL. And you can see the basic select. We select from columns, from table where conditions exist. You know, most basic command on there. And they have different things you can do with it, just like you do with your SQL. And if you scroll down, you'll see data types. So here's your integer, your float, your binary, double string, timestamp, and all the different data types you can use. Some different semantics, different keys, features, functions for running a Hive query, command line setup, and of course the Hive shell setup in here. So you can see right here, if we loop through it, it has a lot of your basic stuff. And we're basically looking at SQL across a Horton database. We're going to go ahead and run our Hadoop cluster Hive demo. And I'm going to go ahead and use the Cloudera Quick Start. And this is in the virtual box. So again, we have an Oracle virtual box, which is open source. And then we have our Cloudera Quick Start, which is the Hadoop setup on a single node. Now, obviously, Hadoop and Hive are designed to run across a cluster of computers. So when we talk about a single node, is for education, testing, that kind of thing. And if you have a chance, you can always go back and look at our demo we had on setting up a Hadoop system in a single cluster. Just set a note down below in the YouTube video, and our team will get in contact with you and send you that link if you don't already have it. Or you can contact us at the www.simplilearn.com. Now in here, it's always important to note that you do need on your computer, if you're running on Windows, because I'm on a Windows machine, you're going to need probably about 12 gigabytes to actually run this. It used to be you could buy with a lot less, but as things have evolved, they take up more and more resources. And you need the professional version. If you have the home version, I was able to get that to run, but boy, did it take a lot of extra work to get the home version to let me use the virtual setup on there. And we'll simply click on the Cloudera Quick Start, and I'm going to go and just start that up. And this is starting up our Linux. So we have our Windows 10, which is the computer I'm on, and then I have the virtual box, which is going to have a Linux operating system in it. And we'll skip ahead so you don't have to watch the whole install. Something interesting to know about the Cloudera is that it's running on Linux CentOS, and for whatever reason, I've always had to click on it and hit the escape button for it to spin up. And then you'll see the DOS come in here. Now that our Cloudera is spun up on our virtual machine with the Linux on, we can see here we have our, it uses the Thunderbird browser on here by default and automatically opens up a number of different tabs for us. And a quick note, because I mentioned like the restrictions on getting set up on your own computer. If you have a home edition computer and you're worried about setting it up on there, you can also go in there and spin up a 1-month free service on Amazon Web Service to play with this. So there's other options. You're not stuck with just doing it on the quick start menu. You can spin this up in many other ways. Now the first thing we want to note is that we've come in here into Cloudera, and I'm going to access this in 2 ways. The first one is we're going to use Hue. And I'm going to open up Hue, and it'll take it a moment to load from the setup on here. And Hue is nice. If I go in and use Hue as an editor into Hive or into the Hadoop setup, usually I'm doing it as a from an admin side because it has a lot more information, a lot of visuals, less to do with actually diving in there and just executing code. And you can also write this code into files and scripts, and there's other ways you can upload it into Hive. But today we're going to look at the command lines, and we'll upload it into Hue, and then we'll go into and actually do our work in a terminal window under the Hive shell. Now in the Hue browser window, if you go under Query and click on the pull down menu, and then you go under Editor, and you'll see Hive. There we go. There's our Hive setup. I go and click on Hive, and this will open up our query down here, and now it has a nice little B that shows our Hive going, and we can go something very simple down here like show databases, and we follow it with the semicolon. And that's the standard in Hive, is you always add our punctuation at the end there. And I'll go ahead and run this, and the query will show up underneath. And you'll see down here, since this is a new quick start I just put on here, you'll see it has the default down here for the databases. That's the database name. I haven't actually created any databases on here. And then there's a lot of other like assistant function, tables, your databases up here. There's all kinds of things you can research, you can look at through Hue as far as a bigger picture. The downside of this is it always seems to lag. For me, whenever I'm doing this, I always seem to run slow. So if you're in Cloudera, you can open up a terminal window. They actually have an icon at the top. You can also go under Applications, and under Applications, System Tools, and Terminal. Either one will work. It's just a regular terminal window. And this terminal window is now running underneath our Linux. So this is a Linux terminal window, or on our virtual machine, which is resting on our regular Windows 10 machine. And we'll go ahead and zoom this in so you can see the text better on your own video. And I simply just clicked on View and Zoom in. And then all we have to do is type in Hive. And this will open up the shell on here. And it takes it just a moment to load. When starting up Hive, I also want to note that depending on your rights on the computer you're on in your action, you might have to do sudo Hive and put in your password and username. Most computers are usually set up with the Hive login. Again, it just depends on how you're accessing the Linux system and the Hive shell. Once we're in here, we can go ahead and do a simple HQL command, show databases. And if we do that, we'll see here that we don't have any databases. So we can go ahead and create a database. And we'll just call it Office for today, for this moment. Now if I do show, we'll just do the up arrow. Up arrow is a hotkey that works in both Linux and in Hive. So I can go back and paste through all the commands I've typed in. And we can see now that I have my, there's of course the default database, and then there's the Office database. So now we've created a database. It's pretty quick and easy. And we can go ahead and drop the database. We can do drop database Office. Now this will work on this database because it's empty. If your database was not empty, you would have to do Cascade. And that drops all the tables in the database and the database itself. Now if we do show database, and we'll go ahead and recreate our database because we're going to use the Office database for the rest of this hands-on demo. A really handy command to now set with the SQL or HQL is to use Office. And what that does is that sets Office as the default database. So instead of having to reference the database every time we work with a table, it now automatically assumes that's the database being used, whatever tables we're working on. The difference is you put the database name period table. And I'll show you in just a minute what that looks like and how that's different. If we're going to have a table and a database, we should probably load some data into it. So let me go ahead and switch gears here and open up a terminal window. You can just open another terminal window and it'll open up right on top of the one that you have Hive shell running in. And when we're in this terminal window, first we're going to go ahead and just do a list, which is of course a Linux command. You can see all the files I have in here. This is the default load. We can change directory to documents. We can list in documents, and we're actually going to be looking at employee.csv. A Linux command is the cat. You can use this actually to combine documents. There's all kinds of things that cat does, but if we want to just display the contents of our employee.csv file, we can simply do cat employee CSV. And when we're looking at this, we want to know a couple things. One, there's a line at the top. Okay, so the very first thing we notice is that we have a header line. The next thing we notice is that the data is comma separated. And in this particular case, you'll see a space here. Generally, with these, you got to be real careful with spaces. There's all kinds of things you got to watch out for because they can cause issues. These spaces won't, because these are all strings that the space is connected to. If this was a space next to the integer, you would get a null value that comes into the database without doing something extra in there. Now, with most of Hadoop, that's important to know that you're writing the data once, reading it many times. And that's true of almost all your Hadoop things coming in. So you really want to process the data before it gets into the database. And for those of you have studied data transformation, that's the ETL, where you extract, transfer, form, and then load the data. So you really want to extract and transform before putting it into the Hive. Then you load it into the Hive with the transformed data. And of course, we also want to note the schema. We have an integer, string, string, integer, integer. So we kept it pretty simple in here as far as the way the data is set up. The last thing that you're going to want to look up is the source. Since we're doing local uploads, we want to know what the path is. We have the whole path. In this case, it's home/Cloudera/documents. And these are just text documents we're working with right now. We're not doing anything fancy. So we can do a simple get edit employee.csv, and you'll see it comes up here. It's just a text document, so I can easily remove these added spaces. There we go. And then we go ahead and just save it. And so now it has the new setup in there. We've edited it. The gedit is usually one of the default that loads into Linux. So any text editor will do. Back to the Hive shell. So let's go ahead and create a table employee. And what I want you to note here is I did not put the semicolon on the end here. The semicolon tells it to execute that line. So this is kind of nice if you can actually just paste it in if you have it written on another sheet. And you can see right here where I have create table employee, and it goes into the next line on there so I can do all of my commands at once. Now, just so I don't have any typo errors, I went ahead and just pasted the next 3 lines in. And the next one is our schema. If you remember correctly from the other side, we had the different values in here, which was ID, name, department, year of joining, and salary. And the ID is an integer, name is a string, department string, year of joining integer, salary an integer. And they're in brackets. We put closed brackets around them. And you could do this all as one line. And then we have row format delimited fields terminated by comma. And this is important because the default is tabs. So if I do it now, it won't find any terminated fields. So you'll get a bunch of null values loaded into your table. And then finally, our table properties, we want to skip the header line count equals 1. Now, this is a lot of work for uploading a single file. It's kind of goofy when you're uploading a single file that you have to put all this in here. But keep in mind, Hive and Hadoop is designed for writing many files into the database. You write them all in there, and then they're saved. It's an archive. It's a data warehouse. And then you're able to do all your queries on them. So a lot of times, we're not looking at just the one file coming up. We're loading hundreds of files. You have your reports coming off of your main database. All those reports are being loaded. You have your log files. You have, all this different data is being dumped into Hadoop, and in this case, Hive on top of Hadoop. And so we need to let it know, hey, how do I handle these files coming in? And then we have the semicolon at the end, which lets us know to go ahead and run this line. And so we'll go ahead and run that. And now if we do a show tables, you can see there's our employee on there. We can also describe. If we do describe employee, you can see that we have our ID integer, name string, department string, year of joining integer, and salary integer. And then finally, let's just do a select star from employee, very basic SQL and HQL command, selecting data. And it's going to come up and we haven't put anything in it, so as we expect, there's no data in it. So if we flip back to our Linux terminal window, you can see where we did the cat employee.csv, and you can see all the data we expect to come into it. And we also did our PWD, and right here you see the path. You need that full path when you are loading data. You know, you can do a browse, and if I did it right now with just the employee.csv as a name, it will work. But that is a really bad habit. In general, when you're loading data, because it's you don't know what else is going on in the computer, you want to do the full path almost in all your data loads. So let's go ahead and flip back over here to our Hive shell we're working in. And the command for this is load data. So that says, hey, we're loading data. That's a Hive command, HQL. And we want local data, so you got to put down local in path. So now it needs to know where the path is. Now, to make this more legible, I'm just going to go ahead and hit enter, and then we'll just paste the full path in there, which I have stored over on the side, like a good prepared demo. And you'll see here we have home, Cloudera, documents, employee.csv. So it's the whole path for this text document in here. And we go ahead and hit enter in there, and then we have to let it know where the data is going. So now we have a source and we need a destination. And it's going to go into the table, and we'll just call it employee. We'll just match the table in there. And because I want it to execute, we put the semicolon on the end. It goes ahead and executes all 3 lines. Now if we go back, if you remember we did the select star from employee, just using the up arrow to page through my different commands I've already typed in. You can see right here we have, as we expect, we have Rose, Sam, Mike, and Nick, and we have all their information showing in our 4 rows. And then let's go ahead and do select and count. We'll just look at a couple of these different select options you can do. We're going to count everything from employee. Now this is kind of interesting because the first one just pops up with a basic select because it doesn't need to go through the full Mapreduce phase. But when you start doing a count, it does go through the full Mapreduce setup in the Hive and Hadoop. And because I'm doing this demo on a single node Cloudera virtual box on top of a Windows 10, all the benefits of running it on a cluster are gone, and instead it's now going through all those added layers, so it takes longer to run. You know, like I said, when you do a single node, as I said earlier, it doesn't do any good as an actual distribution because you're only running it on one computer, and then you've added all these different layers to run it. And we see it comes up with 4, and that's what we expect. We have 4 rows. We expect 4 at the end. And if you remember from our cheat sheet, which we brought up here from Horton's, it's a pretty good one, there's all these different commands we can do. We'll look at one more command where we do the what they call subqueries right down here, because that's really common to do a lot of subqueries. And so we'll do select star or all different columns from employee. Now if we weren't using the Office database, it would look like this, from office.employee. And either one will work on this particular one because we have Office set as a default on there. So from Office employee, and then the command where creates a subset. And in this case, we want to know where the salary is greater than 25,000. There we go. And of course we end with our semicolon. And if we run this query, you can see it pops up, and there's our salaries of people, top earners. We have Rose in IT and Mike in HR. Kudos to them. Of course they're fictional. We don't actually have a Rose and a Mike in those positions, or maybe we do. So finally, what we want to go ahead and do is we're done with this table. Now remember, you're dealing with a data warehouse, so you usually don't do a lot of dropping of tables and databases. But we're going to go ahead and drop this table here. Before we drop it, one more quick note is we can change it. So what we're going to do is we're going to alter table, Office employee, and we want to go ahead and rename it. There's some other commands you can do in here, but rename's pretty common. And we're going to rename it to, and it's going to stay in Office, and it turns out one of our shareholders really doesn't like the word employee. He wants employees plural. It's a big deal to him. So let's go ahead and change that name for the table. It's that easy because it's just changing the metadata on there. And now if we do show tables, you'll see we now have employees, not employee. And then at this point, maybe we're doing some house cleaning because this is all practice. So we're going to go ahead and drop table, and we'll drop table employees because we changed the name in there. So if we did employee, just give us an error. And now if we do show tables, you'll you'll see all the tables are gone. Now, the next thing we want to go ahead and take a look at, and we're going to walk back through the loading of data just real quick, because we're going to load 2 tables in here. And let me just float back to our terminal window so we can see what those tables are that we're loading. And so up here we have a customer file, and we have an order file. We want to go ahead and put the customers and the orders into here. So those are the 2 we're doing. And of course, it's always nice to see what you're working with. So let's do our cat customer.csv. We could always do gedit, but we don't really need to edit these. We just want to take a look at the data in customer. And important in here is, again, we have a header, so we have to skip a line, comma separated. Nothing odd with the data. We have our schema, which is integer, string, integer, string, integer. So you'd want to take that, note that down, or flip back and forth when you're doing it. And then let's go ahead and do cat order.csv, and we can see we have OID, which I'm guessing is the order ID. We have a date. Oh, something new. We've done integers and strings, but we haven't done date. When you're importing new and you never worked with the date, date's always one of the more trickier fields to port in. And that's true of just about any scripting language I've worked with. All of them have their own idea of how date's supposed to be formatted, what the default is. This particular format, where it's year, and it has all 4 digits, dash month, 2 digits, dash day, is the standard import for the Hive. So you'll have to look up and see what the different formats are if you're going to do a different format in there coming in, or you're not able to pre-process the data. But this would be a pre-processing of the data thing coming in. If you remember correctly from our ETL, which is just in case you weren't able to hear me last time, ETL, which stands for extract, transform, then load. So you want to make sure you're transforming this data before it gets into here. And so we're going to go ahead and bring both this data in here. And really we're doing this so we can show you the basic join. There is, if you remember from our setup, merge, join, all kinds of different things you can do. But joining different data sets is so common. So it's really important to know how to do this. We need to go ahead and bring in these 2 data sets. And you can see where I just created a table customer. Here's our schema, the integer, name, age, address, salary. Here's our delimited by commas, and our table properties where we skip a line. Well, let's go ahead and load the data first, and then we'll do that with our order. And let's go ahead and put that in here, and I've got it split into 3 lines so you can see it easily. We got load data local in path. So we know we're loading data, we know it's local, and we have the path. Here's the complete path for, this is supposed to be order, CSV. Grab the wrong one. Of course, it's going to give me errors because you can't recreate the same table on there. And here we go, create table. Here's our integer, date, customer, the basic setup that we had coming in here for our schema, row format, commas, table properties, skip header line. And then finally, let's load the data into our order table. Load data local in path, home Cloudera documents order.csv into table order. Now if we did everything right, we should be able to do select star from customer. And you can see we have all 7 customers, and then we can do select star from order, and we have 4 orders. So this is just like a quick frame. We have, a lot of times when you have your customer databases in business, you have thousands of customers from years and years, and some of them, they close their business, they change names, all kinds of things happen. So what we want to do is we want to go ahead and find just the information connected to these orders and who's connected to them. And so let's go ahead and do, it's a select, because we're going to display information. So select, and this is kind of interesting. We're going to do c.id, and I'm going to define C as customer, as a customer table in just a minute. Then we're going to do c.name, and again we're going to define the c.age. So this means from the customer we want to know their ID, their name, their age, and then I'd also like to know the order amount. So let's do O for .amount. And then this is where we need to go ahead and define what we're doing. And I'll go ahead and capitalize from customer. So we're going to take the customer table in here, and we're going to name it C. That's where the C comes from. So that's the customer table C, and we want to join order as O. That's where our O comes from. So the O.amount is what we're joining in there. And then we want to do this on, we got to tell it how to connect the 2 tables. C.id equals O.customer underscore ID. So now we know how they're joined. And now remember, we have 7 customers in here. We have 4 orders. And as it processes, we should get a return of 4 different names joined together. And they're joined based on, of course, the orders on there. And once we're done, we now have the order number, the person who made the order, their age, and the amount of the order, which came from the order table. So you have your different information, and you can see how the join works here. Very common use of tables and HQL and SQL. And let's do one more thing with our database, and then I'll show you a couple other Hive commands. And let's go ahead and do a drop, and we're going to drop database office. And if you're looking at this and you remember from earlier, this will give me an error. And let's just see what that looks like. It says failed to execute, exception, one or more tables exist. So if you remember from before, you can't just drop a database unless you tell it to cascade. That lets it know, I don't care how many tables are in it, let's get rid of it. And in Hadoop, since it's a warehouse, a data warehouse, you usually don't do a lot of dropping. Maybe at the beginning when you're developing the schemas and you realize you messed up, you might drop some stuff. But down the road, you're really just adding commodity machines to take up so you can store more stuff on it. So you usually don't do a lot of database dropping. And some other fun commands to know is you can do select round 2.3 as round value. You can do a round off in Hive. We can do as floor value, which is going to give us a 2, so it turns it into an integer versus a float. It goes down, basically truncates it, but it goes down. And we can also do ceiling, which is going to round it up. So we're looking for the next integer above. There's a few commands we didn't show in here because we're on a single node. As an admin, to help speediate the process, you usually add in partitions for the data and buckets. You can't do that on a single node because when you add a partition, it partitions it across separate nodes. But beyond that, you can see that it's very straightforward. We have SQL coming in, and all your basic queries that are in SQL are very similar to HQL. Let's get started with Pig. Why Pig? What is Pig? Mapreduce versus Hive versus Pig. Hopefully you've had a chance to do our Hive tutorial and our Mapreduce tutorial. If you haven't, send a note over to Simplilearn and we'll follow up with a link to you. We'll look at Pig architecture, working of Pig, Pig Latin data model, Pig execution modes, a use case Twitter, and features of Pig. And then we'll tag on a short demo so you can see Pig in action. So, why Pig? As we all know, Hadoop uses Mapreduce to analyze and process big data. Processing big data consumed more time. So before we had the Hadoop system, they'd have to expend a lot of money on a huge set of computers and enterprise machines. So he introduced the Hadoop Mapreduce. And so afterwards, processing big data was faster using Mapreduce. Then what is the problem with Mapreduce? Prior to 2006, all Mapreduce programs were written in Java. Non-programmers found it difficult to write lengthy Java codes. They faced issues in incorporating map, sort, reduce to fundamentals of Mapreduce while creating a program. You can see here map phase, shuffle, and sort, reduce phase. Eventually, it became a difficult task to maintain and optimize a code, due to which the processing time increased. You can imagine a manager trying to go in there and needing a simple query to find out data, and he has to go talk to the programmers anytime he wants anything. So that was a big problem. Not everybody wants to have an on-call programmer for every manager on their team. Yahoo faced problems to process and analyze large data sets using Java, as the codes were complex and lengthy. There was a necessity to develop an easier way to analyze large data sets without using time-consuming complex Java modes and codes and scripts and all that fun stuff. Apache Pig was developed by Yahoo. It was developed with the vision to analyze and process large datasets without using complex Java codes. Pig was developed especially for non-programmers. Pig used simple steps to analyze datasets, which was time efficient. So what exactly is Pig? Pig is a scripting platform that runs on Hadoop clusters designed to process and analyze large datasets. And so you have your Pig, which uses SQL-like queries. They're definitely not SQL, but some of them resemble SQL queries. And then we use that to analyze our data. Pig operates on various types of data like structured, semi-structured, and unstructured data. Let's take a closer look at Mapreduce versus Hive versus Pig. So we start with a compiled language, your Mapreduce. And we have Hive, which is your SQL-like query. And then we have Pig, which is a scripting language. It has some similarities to SQL, but it has a lot of its own stuff. Remember, SQL-like query, which is what Hive is based off, looks for structured data. And so when we get into scripting languages like Pig, now we're dealing more with semi-structured and even unstructured data. With a Hadoop Mapreduce, we have a need to write long, complex codes. With Hive, no need to write complex codes. You could just put it in a simple SQL query or HQL, HiveQL. And in Pig, no need to write complex codes as we have Pig Latin. Now remember in the Mapreduce, it can produce structured, semi-structured, and unstructured data. And as I mentioned before, Hive can process only structured data. Think rows and columns. Where Pig can process structured, semi-structured, and unstructured data. You can think of structured data as rows and columns, semi-structured as your HTML, XML documents like you have on your web pages, and unstructured could be anything from groups of documents in written format, Twitter, tweets, any of those things come in as very unstructured data. And with our Hadoop Mapreduce, we have a lower level of abstraction. With both Hive and Pig, we have a higher level abstraction. So it's much more easy for someone to use without having to dive in deep and write a very lengthy Mapreduce code. And those map and reduce codes can take 70, 80 lines of code when you can do the same thing in 1 or 2 lines with Hive or Pig. This is the advantage Pig has over Hive. It can process only structured data in Hive, while in Pig it can process structured, semi-structured, and unstructured data. Some other features to note that separates the different query languages is when we look at map and reduce, Mapreduce supports partitioning features, as does Hive. Pig, no concept of partitioning in Pig, so it doesn't support your partitioning feature. Your partitioning features allow you to partition the data in such a way that it can be queried quicker. You're not able to do that in Pig. Mapreduce uses Java and Python, while Hive uses an SQL-like query language known as HiveQL or HQL. Pig Latin is used, which is a procedural data flow language. Mapreduce is used by programmers, pretty much as straightforward on Java. Hive is used by data analysts. Pig is used by researchers and programmers. Certainly there's a lot of mix between all three. Programmers have been known to go in and use a Hive for a quick query, and anybody's been able to use Pig for a quick query or research. Under Map and Reduce, code performance is really good. Under Hive, code performance is lesser than Map and Reduce in Pig. Under Pig, code performance is lesser than Mapreduce, but better than Hive. So if we're going to look at speed and time, the Mapreduce is going to be the fastest performance on all of those, where Pig will have second and Hive follows in the back. Let's look at components of Pig. Pig has 2 main components. We have Pig Latin. Pig Latin is the procedural data flow language used in Pig to analyze data. It is easy to program using Pig Latin. It is similar to SQL. And then we have the runtime engine. Runtime engine represents the execution environment created to run Pig Latin programs. It is also a compiler that produces MapReduce programs. It uses HDFS, or your Hadoop file system, for storing and retrieving data. And as we dig deeper into the Pig architecture, we'll see that we have Pig Latin scripts. Programmers write a script in Pig Latin to analyze data using Pig. Then you have the grunt shell, and it actually says grunt when we start it up, and we'll show you that here in a little bit, which goes into the Pig server, and this is where we have our parser. Parser checks the syntax of the Pig script. After checking the output will be a DAG, directed acyclic graph. And then we have an optimizer, which optimizes after your DAG, your logical plan is passed to the logical optimizer where an optimization takes place. Finally, the compiler converts the DAG into MapReduce jobs, and then that is executed on the MapReduce under the execution engine. The results are displayed using dump statement and stored in HDFS using store statement. And again, we'll show you that. They kind of end, you always want to execute everything once you've created it, and so dump is kind of our execution statement. And you can see right here, as we were talking about earlier, once we get to the execution engine and it's coded into MapReduce, then the MapReduce processes it onto the HDFS. Working of Pig. Pig Latin script is written by the users. So you have load data and write Pig script and Pig operations. So when we look at the working of Pig, Pig Latin script is written by the users. There's step 1. We load data and write Pig script. And step 2, in this step, all the Pig operations are performed by parser, optimizer, and compiler. So we go into the Pig operations. And then we get to step 3, execution of the plan. In this stage, the results are shown on the screen, otherwise stored in the HDFS as per the code. So it might be you have a small amount of data you're reducing it to and you want to put that on the screen, or you might be converting a huge amount of data which you want to put back into the Hadoop file system for other use. Let's take a look at the Pig Latin data model. The data model of Pig Latin helps Pig to handle various types of data. For example, we have Adam, Rob, or 50. Adam represents any single value of primitive data type in Pig Latin, like integer, float, string. It is stored as a string. Tuple, so we go from our Adam, which are our most basic things. So if you look at just Rob or just 50, that's an Adam. That's our most basic object we have in Pig Latin. Then you have a tuple. Tuple represents sequence of fields that can be of any data type. It is the same as a row in RDBMS. For example, a set of data from a single row. And you can see here we have Rob, 5. And you can imagine with many of our other examples we've used, you might have the ID number, the name, where they live, their age, their date of starting the job. That would all be one row and stored as a tuple. And then we create a bag. A bag is a collection of tuples. It is the same as a table in RDBMS and is represented by brackets. And you can see here we have our table with Rob 5, Mike 10. And we also have a map. A map is a set of key value pairs. Key is of character array type, and a value can be of any type. It is represented by the brackets. And so we have name and age, where the key value is Mike and 10. Pig Latin has a fully nestable data model. That means one data type can be nested within another. Here's a diagram representation of Pig Latin data model. And in this particular example, we have basically an ID number, a name, an age, and a place. And when we break this apart, we look at this model from Pig Latin perspective. We start with our field. And if you can remember, a field contains basically an atom. It is one particular data type. And the atom is stored as a string, which it then converts it into either an integer, or number, or character string. Next we have our tuple. And in this case, you can see that it represents a row. So our tuple would be 3, Joe, 29, California. And finally, we have our bag, which contains 3 rows in it in this particular example. Let's take a quick look at Pig execution modes. Pig works in 2 execution modes, depending on where the data is residing and where the Pig script is going to run. We have local mode. Here, the Pig engine takes input from the Linux file system, and the output is stored in the same file system. Local mode is useful in analyzing small data sets using Pig. And we have the Mapreduce mode. Here, the Pig engine directly interacts and executes in HDFS and Mapreduce. In the Mapreduce mode, queries written in Pig Latin are translated into Mapreduce jobs and are run on a Hadoop cluster. By default, Pig runs in this mode. There are 3 modes in Pig, depending on how a Pig Latin code can be written. We have our interactive mode, batch mode, and embedded mode. The interactive mode means coding and executing the script line by line. When we do our example, we'll be in the interactive mode. In batch mode, all scripts are coded in a file with the extension .pig, and the file is directly executed. And then there's embedded mode. Pig lets its users define their own functions, UDFSs, in a programming language such as Java. So let's take a look and see how this works in a use case. In this case, use case Twitter. Users on Twitter generate about 500 million tweets on a daily basis. The Hadoop Mapreduce was used to process and analyze this data. Analyzing the number of tweets created by a user in the tweet table was done using Mapreduce in Java programming language. And you can see the problem. It was difficult to perform Mapreduce operations as users were not well versed with written complex Java codes. So Twitter used Apache Pig to overcome these problems. And let's see how. Let's start with the problem statement. Analyze the user table and tweet table and find out how many tweets are created by a person. And here you can see we have a user table. We have Alice, Tim, and John with their ID numbers 1, 2, 3, and we have a tweet table. In the tweet table, you have your the ID of the user and then what they tweeted. Google was a good whatever it was, tennis, spacecraft, Olympics, politics, whatever they're tweeting about. The following operations were performed for analyze the given data. First, the Twitter data is loaded into the Pig storage using load command. And you can see here we have our data coming in, and then that's going into Pig storage. And this data is probably on an enterprise computer. So this is actually active Twitters going on, and then it goes into Hadoop file system. Remember, the Hadoop file system is a data warehouse for storing data. And so the first step is we want to go ahead and load it into the Pig storage, into our data storage system. The remaining operations performed are shown below. In join and group operation, the tweet and user tables are joined and grouped using cogroup command. And you can see here where we add a whole column when we go from usernames and one tweet to the ID linked directly to the name. So Alice was user 1, Tim was 2, and John 3. And so now they're listed with their actual tweet. The next operation is the aggregation. The tweets are counted according to the names. The command used is count. So it's very straightforward. We just want to count how many tweets each user is doing. And finally, the result after the count operation is joined with the user table to find out the username. And you can see here where Alice had 3, Tim 2, and John 1. Pig reduces the complexity of the operations, which would have been lengthy using Mapreduce. In join and group operation, the tweet and user tables are joined and grouped using cogroup command. The next operation is the aggregation. The tweets are counted according to the names. The command used is count. The result after the count operation is joined with the user table to find out the username. And you can see we're talking about 3 lines of script versus a Mapreduce code of about 80 lines. Finally, we could find out the number of tweets created by a user in a simple way. So let's go quickly over some of the features of Pig that we already went through most of these. First, ease of programming, as Pig Latin is similar to SQL. Lesser lines of code need to be written. Short development time as the code is simpler, so we can get our queries out rather quickly instead of having to have a programmer spend hours on it. Handles all kind of data like structured, semi-structured, and unstructured. Pig lets us create user-defined functions. Pig offers a large set of operators such as join, filter, and so on. It allows for multiple queries to process in parallel, and optimization and compilation is easy as it is done automatically and internally. So, enough theory. Let's dive in and show you a quick demo on some of the commands you can do in Pig. Today's setup will continue as we have in the last 3 demos to go ahead and use Cloudera Quick Start. And we'll be doing this in VirtualBox. We do have a tutorial in setting that up. You can send a note to our Simplilearn team and then get that link to you. Once your Cloudera Quick Start has spun up, and remember this is VirtualBox. We've created a virtual machine, and this virtual machine is CentOS Linux. Once it's spun up, you'll be in a full Linux system here. And as you can see, we have Thunderbird browser, which opens up to the Hadoop Basic System browser. And we can go underneath the hue, where it comes up by default. If you click on the pull-down menu and go under Editor, you can see there's our Impala, our Hive, Pig, along with a bunch of other query languages you can use. And we're going under Pig. And then once you're in Pig, we can go ahead and use our command line here and just click that little blue button to start it up and running. We will actually be working in terminal window. And so if you're in the Cloudera Quick Start, you can open up the terminal window up top, or if you're in your own setup and you're logged in, you can easily use all of your commands here in terminal window. And we'll zoom in. That way you get a nice view of what's going on. There we go. Now for our first command, we're going to go ahead and do a Hadoop command and import some data into the Hadoop system, in this case a Pig input. And let's just take a look at this. We have Hadoop. Now let's know it's going to be a Hadoop command. DFS. There's actually 4 variations of DFS. So if you have HDFS or whatever, that's fine. All 4 of them used to be different setups underneath different things, and now they all do the same thing. And we want to put this file, which in this case is under Home Cloudera Documents and Sample, and we just want to take that and put it into the Pig input. And let's take a look at that file. If I go under my document browsers and open this up, you'll see it's got a simple ID, name, profession, and age. We have 1 Jack Engineer 25. And that was in one of our earlier things we had in there. And so let's go ahead and hit enter and execute this. And now we've uploaded that data and it's gone into our Pig input. And then a lot of the Hadoop commands mimic the Linux commands. And so you'll see we have cat as one of our commands, or it has a hyphen before it. So we execute that with Hadoop DFS -cat, pull it back up, Pig input, because that's what we called it. That's where we put our sample CSV at. And we execute this. You can see from our Hadoop system, it's going to go in and pull that up, and sure enough, it pulls out the data file we just put in there. And then we can simply enter the Pig Latin or Pig editor mode by typing in Pig. And we can see here by our grunt, I told you that's how it was going to tell you were in Pig Latin. There's our grunt command line. So we are now in the Pig shell. And then we'll go ahead and put our load command in here. And the way this works is I'm going to have office equals load. And here's my load. In this case, it's going to be pig input. We have that in single brackets. You remember that's where the data is in the Hadoop file system where we dumped it into there. We're going to be using pig storage. Our data was separated as with a comma. So there's our comma separator. And then we have as. And in this case, we have an ID character array, name character array, profession character array, and age character array. And we're just going to do them all as character arrays just to keep this simple for this one. And then when I hit put this all in here, you can see that's our full command line going in, and we have our semicolon at the end. So when I hit enter, it's now set office up. But it hasn't actually done anything yet. It doesn't do anything until we do dump office. So there's our command to execute whatever we've loaded or whatever setup we have in here. And we run that. You can see it go through the different languages, and this is going through the Mapreduce. Remember, we're not doing this locally, we're doing this on the Hadoop setup. And once we finished our dump, you can see we have ID, name, profession, age, and all the information that we just dumped into our pig. We can now do, let's say we have a request just for, we'll keep it simple in here, but just for the name and age. And so we can go office, we'll call it each as our variable, underscore each, and we'll say for each office, generate name, comma, age. And for each means that we're going to do this for each row. And if you're thinking Mapreduce, you know that this is a map function because it's mapping each row and generating name and age on here. And of course, we want to go ahead and close it with a semicolon. And then once we've created our query or the command line in here, let's go ahead and dump office underscore each in with our semicolon. And this will go through our Mapreduce setup on here. And if we were on a large cluster, the same processing time would happen. In fact, it's really slow because I have multiple things on this computer, and this particular virtual box is only using a quarter of my processor. It's only dedicated to this. And you can see here, there it is, name and age. And it also included the top row since we didn't delete that out of there or tell it not to. And that's fine for this example. But you need to be aware of those things when you're processing a significantly large amount of data or any data. Then we can also do office, and we'll call this DSC for descending. So maybe the boss comes to you and says, hey, can we order office by ID descending? And of course your boss, you've taught him how to, your shareholder, it sounds a little derogatory when I say boss. You've talked to the shareholder and you said, and you've taught them a little bit of Pig Latin, and they know that they can now create office description, and we can order office by ID description. And of course, once we do that, we have to dump office underscore description so that it'll actually execute, and there goes into our Mapreduce. It'll take just a moment for it to come up because again I'm running on only a quarter of my processor, and you can see we now have our IDs in descending order returned. Let's also look at, and this is so important with anytime you're dealing with big data, let's create office with a limit. And you could of course do any of this instead of with office. We could do this with office descending, so you get just the top two IDs on there. But we're going to limit just to 2, and of course to execute that we have to dump office underscore limit. And you can just think of dumping your garbage into the pig pen for the pig to eat. There we go, dump office limit 2, and that's going to just limit our office to the top 2. And for our output, we get our first row, which had our ID, name, profession, and age, and our second row, which is Jack, who's an engineer. And let's do a filter. We'll call it office underscore filter. You guessed it, equals filter office by profession equals. And keep note, this is similar to how Python does it with the double equal signs for equal for doing a true-false statement. So for your logic statement, remember to use 2 equal signs in pig. And we're going to say it equals doctor. So we want to find out how many doctors do we have on our list. And we'll go ahead and do our dump. We're dumping all our garbage into the pig pen, and we're letting pig take over and see what it can find out and see who's a doctor on our list. And we find employee ID number 2, Bob, is a doctor, 30 years old. For this next section, we're going to cover something we see a lot nowadays in data analysis, and that's word counting, tokenization. That is one of the next big steps as we move forward in our data analysis, where we go from, say, stock market analysis of highs and lows and all the numbers to what are people saying about companies on Twitter? What are they saying on the web pages and on Facebook? Suddenly you need to start counting words and finding out how many words are total, how many are in the first part of the document, and so on. We're going to cover a very basic word count example. And in this case, I've created a document called wordrows.txt. And you can see here we have Simplilearn is a company supporting online learning. Simplilearn helps people attain their certifications. Simplilearn is an online community. I love Simplilearn. I love programming. I love data analysis. And I went and saved this into my documents folder so we could use it. And let me go ahead and open up a new terminal window for our word count. Let me go ahead and close the old one. So we're going to go in here, and instead of doing this as pig, we're going to do pig -x local. And what I'm doing is I'm telling the pig to start the pig shell, but we're going to be looking at files local to our virtual box or this CentOS machine. And let me go ahead and hit enter on there. Just maximize this up. There we go. And it will load pig up, and it's going to look just the same as the pig we were doing, which was defaulted to Hive, to our Hadoop system, to our HDFS. This is now defaulted to the local system. And now we're going to create lines, and we're going to load it straight from the file. Remember last time we took the HDFS and loaded it into there and then loaded it into pig. Since we're on the local, we're just going to run a local script. We have lines equals load home, the actual full path, home, Cloudera, documents, and I called it wordrows.txt. And as line is a character array, so each line, and you can change this to read each document. I certainly have done a lot of document analysis, and then you go through and do word counts and different kind of counts in there. So once we go ahead and create our line, instead of doing the dump, we're going to go ahead and start entering all of our different setups for each of our steps we want to go through. And let's just take a look at this next one, because the load is straightforward. We're loading from this particular file. Since we're local, it's loading it directly from here instead of going into the Hadoop file system. And it says as, and then each line is read as a character array. Now we're going to do words equal for each of the lines, generate flat tokenize line space as word. Now there's a lot of ways to do this. This is if you're a programmer, you're just splitting the line up by spaces. There's actual ways to tokenize it. You gotta look for periods, capitalization. There's all kinds of other things you play with this. But for the most basic word count, we're just going to separate it by spaces. The flatten takes the line and just creates it flattens each of the words out. So this is, we're just going to generate a bunch of words for each line. And then each of those words is as a word. A little confusing in there, but if you really think about it, we're just going down each line, separating it out, and we're generating a list of words. One thing to note is the default for tokenize. You can just do tokenize line without the space in there. If you do that, it'll automatically tokenize it by space. So you can do either one. And then we're going to do group. We're going to group it by words. So we're going to group words by word. So when we split it up, each token is a word and it's a list of words. And so we're going to grouped equals group words by word. So we're going to group all the same words together. And if we're going to group them, then we want to go ahead and count them. And so for count, we'll go ahead and create a word count variable. And here's our for each. So for each grouped is our line where we group all the words in the line that are similar. We're going to generate a group. And then we're going to count the words. For each grouped, so for each line where we group the words together, we're going to generate a group, and that's going to count the words. So we want to know the word count in each of those. And that comes back in our word count. And finally, we want to take this and we want to go ahead and dump word count. And this is a little bit more what you see when you start looking at grunt scripts. You'll see right here, these lines right here, we have each of the steps you take to get there. So we load our file. For each of our lines, we're going to generate and tokenize it into words. Then we're going to take the words and we're going to group them by same words. For each grouped, we're going to generate a group and we're just going to count the words. So we're going to summarize all the words in here. And let's go ahead and do our dump word count, which executes all this. And it goes through our Mapreduce. It's actually a local runner. You'll see down here, you start seeing where they still have Mapreduce, but it's a special runner. We're mapping it. That's a part of each row being counted and grouped. And then when we do the word count, that's the reducer. The reducer creates these keys. And you can see I is used 3 times, A came up once, and came up once, is 2. You can continue on down here to attain, online, people, company, analysis, Simplilearn, they took the top rating with 4. Certification. So all these things are then counted in the how many words are used. And in data analysis, this is probably the beginnings of data analysis, where you might look at it and say, oh, they mentioned love 3 times. So whatever's going on in this post, it's about love. And what do they love? And then you might attach that to the different objects in here. So you can see that Pig Latin is fairly easy to use. There's nothing really, it takes a little bit to learn the script. Depending on how good your memory is. As I get older, my memory leaks a little bit more, so I don't memorize it as much. But that was pretty straightforward, the script we put in there. And then it goes through the full Mapreduce localized run, comes out, and like I said, it's very easy to use. That's why people like Pig Latin, is because it's intuitive. One of the things I like about Pig Latin is when I'm troubleshooting. When we're troubleshooting, a lot of times you're working with a small amount of data, and you start doing one line at a time, and so I can go lines equal load, and there's my loaded text, and maybe I'll just dump lines. And then it's going to run, it's going to show me all the lines that I'm working on in this small amount of data. And that way I can test that. If I got an error on there that said, oh, this isn't working, maybe I'll be like, oh my gosh, I'm in Mapreduce, or I'm in the basic grunt shell instead of the local path grunt. So maybe it'll generate an error on there. And you can see here it just shows each of the lines going down. Hive versus Pig. On one side we'll have our sharp stinger on our black and yellow friend, and on the other side our thick hide on our pig. Let's start with an introduction to HBase. Back in the days, data used to be less and was mostly structured. You can see we have structured data here. We usually had it like in a database where you had every field was exactly the correct length. So if you had a name field, it was exactly 32 characters. I remember the old Access database in Microsoft. The files were small. If we had hundreds of people in one database, that was considered big data. This data could be easily stored in relational database, or RDBMS. When we talk about relational database, you might think of Oracle, you might think of SQL, Microsoft SQL, MySQL. All of these have evolved, even from back then, to do a lot more today than they did. But they still fall short in a lot of ways. And they're all examples of an RDMS, or relationship database. Then Internet evolved, and huge volumes of structured and semi-structured data got generated. And you can see here with the semi-structured data, we have email. If you look at my spam filter, you know what we're talking about. All the HTML pages, XML, which is a lot of times is displayed on our HTML and help desk pages, JSON. All of this really has just, even in the last, each year, it almost doubles from the year before how much of this is generated. So storing and processing this data on an RDBMS has become a major problem. And so the solution is we use Apache HBase. Apache HBase was the solution for this. Let's take a look at the history, the HBase history. And when we look at the HBase history, we're going to start back in 2006, November. Google released a paper on Big Table. And then in 2017, just a few months later, HBase prototype was created as a Hadoop contribution. Later on in the year 2007, in October, first usable HBase along with the Hadoop 0.15 was released. And then in January of 2008, HBase became the subproject of Hadoop. And later on that year in October, all the way into September the next year, HBase was released, the 0.81 version, the 0.19 version, and 0.20. And finally, in May of 2010, HBase became Apache top-level project. And so you can see in the course of about 4 years, HBase started off as just an idea on paper and has evolved all the way till 2010 as a solid project under the Apache. And since 2010, it's continued to evolve and grow as a major source for storing data in semi-structured data. So what is HBase? HBase is a column-oriented database management system derived from Google's NoSQL database, Big Table, that runs on top of the Hadoop file system, or the HDFS. It's an open source project that is horizontally scalable, and that's very important to understand, that you don't have to buy a bunch of huge expensive computers. You're expanding it by continually adding commodity machines. And so it's a linear cost expansion as opposed to being exponential. NoSQL database written in Java, which permits faster querying. So Java is the backend for the HBase setup. And it's well suited for sparse data sets, so it can contain missing or NA values, and this doesn't boggle it down like it would another database. Companies using HBase. So let's take a look and see who is using this NoSQL database for their servers and for storing their data. And we have Hortonworks, which isn't a surprise because they're one of the, like Cloudera, Hortonworks. They are behind Hadoop and one of the big developments and backing of it. And of course, Apache HBase is the open source behind it. And we have Capital One as banks. You also see Bank of America, where they're collecting information on people and tracking it. So their information might be very sparse. They might have one bank way back when they collected information as far as the person's family and what their income for the whole family is and their personal income. And maybe another one doesn't collect the family income. As you start seeing where you have data that is very difficult to store, where it's missing a bunch of data. HubSpot's using it, Facebook, certainly all of your Facebook, Twitter, most of your social medias are using it. And then of course there's JP Morgan, Chase and Company, another bank that uses the HBase as their data warehouse for NoSQL. Let's take a look at an HBase use case so we can dig a little bit more into it to see how it functions. Telecommunication company that provides mobile voice and multimedia services across China, the China Mobile. And China Mobile, they generate billions of call detailed records, or CDR. And so these CDRs and all these records of these calls and how long they are and different aspects of the call, maybe the tower they're broadcasted from, all of that is being recorded so they can track it. Traditional database systems were unable to scale up to the vast volumes of data and provide a cost-effective solution. No good. So storing and real-time analysis of billions of call records was a major problem for this company. Solution? Apache HBase. HBase stores billions of rows of detailed call records. HBase performs fast processing of records using SQL queries. So you can mix your SQL and NoSQL queries. And usually you just say NoSQL queries because of the way the query works. Applications of HBase. One of them would be in the medical industry. HBase is used for storing genome sequences, storing disease history of people of an area, and you can imagine how sparse that is as far as both of those. A genome sequence might be only have pieces to it that each person is unique or is unique to different people. And the same thing with disease. You really don't need a column for every possible disease a person could get. You just want to know what those diseases those people have had to deal with in that area. E-commerce. HBase is used for storing logs about customer search history, performs analytics and target advertisement for better business insights. Sports. HBase stores match details and the history of each match. Uses this data for better prediction. So when we look at HBase, we all want to know what's the difference between HBase versus RDBMS. That is a relational database management system. HBase versus RDBMS. So the HBase does not have a fixed schema. It's schemaless. Defines only column families. And we'll show you what that means later on. An RDBMS has a fixed schema which describes the structure of the tables. And you can think of this as you have a row and you have columns. And each column is a very specific structure, how much data can go in there and what it does. With the HBase, it works well with structured and semi-structured data. With the RDBMS, it works only well with structured data. With the HBase, it can have denormalized data. It can contain missing or null values. With the RDBMS, it can store only normalized data. Now you can still store a null value in the RDBMS, but it still takes up the same space as if you're storing a regular value in many cases. And it also, for the HBase, is built for wide tables. It can be scaled horizontally. For instance, if you were doing a tokenizer of words and word clusters, you might have 1.4 million different words that you're pulling up and combinations of words. So with an RDBMS, it's built for thin tables that are hard to scale. You don't want to store 1.4 million columns in your SQL. It's going to crash and it's going to be very hard to do searches. With the HBase, it only stores that data which is part of whatever row you're working on. Let's look at some of the features of the HBase. It's scalable. Data can be scaled across various nodes as it is stored in the HDFS. And always think about this, it's a linear add-on. For each terabyte of data, I'm adding on roughly $1,000 in commodity computing. With an enterprise machine, we're looking at about $10,000 at the lower end for each terabyte of data. And that includes all your backup and redundancy. So it's a big difference. It's like a tenth of the cost to store it across the HBase. It has automatic failure support. Write-ahead log across clusters, which provides automatic support against failure. Consistent read and write. HBase provides consistent read and write of the data. It's a Java API for client access, provides easy to use Java API for clients. Block cache and bloom filters. So the HBase supports block caching and bloom filters for high volume query optimization. Let's dig a little deeper into the HBase storage. HBase column oriented storage. And I told you we're going to look into this to see how it stores the data. And here you can see you have a row key. And this is really one of the important references is each row has to have its own key or your row ID. And then you have your column family. And in here you can see we have column family 1, column family 2, column family 3. And you have your column qualifiers. So you can have in column family 1, you can have 3 columns in there, and there might not be any data in that. So when you go into column family 1 and do a query for every column that contains a certain thing, that row might not have anything in there and not be queried. Where in column family 2, maybe you have column 1 filled out and column 3 filled out, and so on and so forth. And then each cell is connected to the row where the data is actually stored. Let's take a look at this and what it looks like when you fill the data in. So in here we have a row key with a row ID, and we have our employee ID, 1, 2, 3. That's pretty straightforward. You probably would even have that on an SQL server. And then you have your column family. This is where it starts really separating out. Your column family, you might have personal data, and under personal data you would have name, city, age. You might have a lot more than just that. You might have number of children, you might have degree, all those kinds of different things that go under personal data. And some of them might be missing. You might only have the name and the age of an employee. You might only have the name, the city, and how many children, and not the age. And so you can see with the personal data, you can now collect a large variety of data and store it in the HBase very easily. And then maybe you have a family of professional data, your designation, your salary, all the stuff that the employee is doing for you in that company. Let's dig a little deeper into the HBase architecture. And so you can see here what looks to be a complicated chart. It's not as complicated as you think. From the Apache HBase, we have the Zookeeper, which is used for monitoring what's going on. And you have your HMaster. This is the HBase master assigns regions and load balancing. And then underneath the region, or the HBase master, then under the HMaster, or HBase master, you have your region server serves data for read and write. And the region server, which is all your different computers you have in your Hadoop cluster, you'll have a region, an HLog, you'll have a store, memory store, and then you have your different files for HFile that are stored on there. And those are separated across the different computers. And that's all part of the HDFS storage system. So when we look at the architectural components or regions, and we're drilling down a little bit, HBase tables are divided horizontally by row. So you have a key range into regions. So each of those IDs, you might have IDs 1 to 20, 21 to 50, or whatever they are. Regions are assigned to the nodes in the cluster called region servers. A region contains all rows in the table between the region start key and the end key. Again, 1 to 10, 11 to 20, and so forth. These servers serve data for read and write. And you can see here we have the client and the get sends it out and it finds out where that start, if it's between which start keys and end keys, and then it pulls the data from that different region server. And so the region signed data definition language operation, create, delete, are handled by the HMaster. So the HMaster is telling it, what are we doing with this data? What's going out there? Assigning and reassigning regions for recovery or load balancing and monitoring all servers. So that's also part of it. So, if your IDs, if you have 500 IDs across 3 servers, you're not going to put 400 IDs on server 1 and 100 on the server 2 and leave region 3 and region 4 empty. You're going to split that up, and that's all handled by the HMaster. And you can see here it monitors region servers, assigns regions to region servers, assigns regions to region servers, and so forth and so forth. HBase has a distributed environment where HMaster alone is not sufficient to manage everything. Hence, Zookeeper was introduced. It works with HMaster. So you have an active HMaster which sends a heartbeat signal to Zookeeper indicating that it's active. And the Zookeeper also has a heartbeat to the region servers. So the region servers send their status to Zookeeper indicating they are ready for read and write operation. Inactive server acts as a backup. If the active HMaster fails, it will come to the rescue. Active HMaster and region servers connect with a session to Zookeeper. So you see your active HMaster selection, your region server session. They're all looking at the Zookeeper keeping that pulse. An active HMaster and region server connects with a session to the Zookeeper. And you can see here where we have ephemeral nodes for active sessions via heartbeats to indicate that the region servers are up and running. So let's take a look at HBase read or write going on. There's a special HBase catalog table called the meta table, which holds a location of the regions in the cluster. Here's what happens the first time a client reads or writes data to HBase. The client gets the region server, the host, the meta table from Zookeeper. And you can see right here the client has a request for your region server and goes, hey, Zookeeper, can you handle this? And the Zookeeper takes a look at it and goes, meta location is stored in Zookeeper. So it looks at its metadata on there. And then the metadata table location is sent back to the client. The client will query the meta server to get the region server corresponding to the row key if it wants to access. The client caches this information along with the meta table location. And you can see here the client going back and forth to the region server with the information. And it might be going across multiple region servers depending on what you're querying. So we get the region server for row key from the meta table. That's where that row key comes in and says, hey, this is where we're going with this. And so once it gets the row key from the corresponding region server, we can now put row or get row from that region server. Let's take a look at the HBase meta table. Special HBase catalog table that maintains a list of all the region servers in the HBase storage system. So you see here we have the meta table. We have a row key and a value, table key, region server. So the meta table is used to find the region for the given table key. And you can see down here, our meta table comes in, it's going to figure out where it's going with the region server. And when we look a little closer at the write mechanism in HBase, we have write ahead log, or WAL, as you abbreviate it. Kind of a way to remember WAL is write ahead log. It's a file used to store new data that is yet to be put on permanent storage. It is used for recovery in the case of failure. So you can see here where the client comes in and it literally puts the new data coming in into this kind of temporary storage, or the WAL on there. Once it's gone into the WAL, then the memory store, mem store, is a write cache that stores the new data that has not yet been written to disk. There is one mem store per column family per region. And once we've done that, we have 3 ACK. Once the data is placed in mem store, the client then receives the acknowledgement. When the mem store reaches the threshold, it dumps or commits the data into H-file. And so you can see right here, we've taken it's gone into the WAL then sorts it into the different memory stores, and then the memory stores, it says, hey, we're ready to dump that into our H-files, and then it moves it into the H-files. H-files store the rows of the data as stored key value on disk. So here we've done a lot of theory. Let's dive in and just take a look and see what some of these commands look like and what happens in our HBase when we're manipulating a NoSQL setup. So if you're learning a new setup, it's always good to start with, where is this coming from? It's open source by Apache. And you can go to hbase.apache.org. And you'll see that it has a lot of information. You can actually download the HBase separate from the Hadoop, although most people just install the Hadoop because it's bundled with it. And if you go in here, you'll find a reference guide. And so you can go through the Apache reference guide. And there's a number of things to look at, but we're going to be going through Apache HBase shell. That's what we're going to be working with. And there's a lot of other interfaces on the setup, and you can look up a lot of the different commands on here. So when we go into the Apache HBase reference guide, we can go down to read HBase shell commands from a command file. You can see here where it gives you different options of formats for putting the data in and listing the data. Certainly you can also create files and scripts to do this too. But we're going to look at the basics, and we're going to go through this on a basic HBase shell. And one last thing to look at is, of course, if you continue down the setup, you can see here where they have more detail as far as how to create and how to get to your data on your HBase. Now, I will be working in a virtual box, and this is by Oracle. You can download the Oracle virtual box. You can put a note in below for the YouTube, as we did have a previous session on setting up virtual setup to run your Hadoop system in there. I'm using the Cloudera Quick Start installed in here. There's Hortons. You can also use the Amazon Web Service. There's a number of options for trying this out. In this case, we have Cloudera on the Oracle virtual box. The virtual box has Linux CentOS installed on it, and then the Hadoop has all the different Hadoop flavors, including HBase. And I bring this up because my computer is a Windows 10. The operating system of the virtual box is Linux, and we're looking at the HBase data warehouse. And so we have 3 very different entities all running on my computer. And that can be confusing if it's the first time in and working with this kind of setup. Now you'll notice in our Cloudera setup, they actually have some HBase monitoring. So I can go underneath here and click on HBase and master, and it'll tell me what's going on with my region servers. It'll tell me what's going on with our backup tables. Right now I don't have any user tables because we haven't created any. And this is only a single node and a single HBase store. So you're not going to expect anything too extensive in here, since this is for practice and education and perhaps testing out package you're working on. It's not for really, you can deploy Cloudera of course, but when you talk about a quick start or a single node setup, that's what it's really for. So we can go through all the different HBase and you'll see all kinds of different information with Zookeeper if you saw it flash by down here, what version we're working in, since Zookeeper is part of the HBase setup. Where we want to go is we want to open up a terminal window, and in Cloudera it happens to be up at the top. And when you click on here, you'll see your Cloudera terminal window open. And let me just expand this so we have a nice full screen. And then I'm also going to zoom in. That way you have a nice big picture and you can see what I'm typing and what's going on. And to open up your HBase shell, simply type HBase shell to get in and hit enter. And you'll see it takes just a moment to load, and we'll be in our HBase shell for doing HBase commands. Once we've gotten into our HBase shell, you'll see you'll have the HBase prompt information ahead of it. We can do something simple like list. And this is going to list whatever tables we have. And it so happens that there's a base table that comes with HBase. Now we can go ahead and create, and I'm going to type in just create. What's nice about this is it's going to throw me kind of a, it's going to say, hey, there's no just straight create. But it does come up and tell me all these different formats we can use for create. So we can create our table and one of our families. You can add splits, names, versions, all kinds of things you can do with this. But let's just start with a very basic one on here. And let's go ahead and create, and we'll call it new table. Let's just call it new TBL for table. New table. And then we also want to do, let's do knowledge. So let's take a look at this. I'm creating a new table and it's going to have a family of knowledge in it. And let me hit enter. And it's going to come up. It's going to take it a second to go ahead and create it. Now we have our new table in here. And so if I go list, you'll now see table and new table. So you can now see that we have the new table and of course the default table that's set up in here. And we can do something like describe. We can describe, and then we're going to do new TBL. And when we describe it, it's going to come up. It's going to say, hey, name, I have knowledge, data block encoding none, bloom filter, row, replication scope, version, all the different information you need. New, minimum version, 0, forever, deleted cells, false, block size, in memory. And you can look this stuff up on apache.org to really track it down. One of the things that's important to note is versions. So you have your different versions of the data that's stored. And that's always important to understand that. We might talk about that a little bit later on. And then after we describe it, we can also do a status. The status says I have one active master going on. That's our HBase as a whole. We can do status summary. That should do the same thing as status. So we got the same thing coming up. And now that we've created, let's go ahead and put something in it. So we're going to put new TBL, and then we want row 1. You know what? Before I even do this, let's just type in put. And you can see when I type in put, it gives us like a lot of different options of how it works and different ways of formatting our data as it goes in. And all of them usually begin with the new table, new TBL. Then we have, in this case, we'll call it row 1, and then we'll have knowledge. If you remember, we created knowledge already, and we'll do knowledge sports. And then in knowledge and sports, we're going to set that equal to cricket. So we're going to put underneath this our knowledge setup. We have a thing called sports in there. And we'll see what this looks like in just a second. And let's go ahead and put in, we'll do a couple of these. Let's see, let's do another row 1, and this time, instead of sports, let's do science. This person not only, we have row 1, which is both knowledgeable in cricket and also in chemistry. So it's a chemist who plays cricket in row 1. And let's see, if we have, let's do another row 1 just to keep it going. And we'll do science. In this case, let's do physics. Not only in chemistry, but also physics. physicist. I have quite a joy in physics myself. So here we go. We have row 1. There we go. And then let's do row 2. Let's see what that looks like when we start putting in row 2. And in row 2, this person has knowledge in economics. This is a master of business and how, or maybe it's global economics. Maybe it's just for the business and how it fits in with the country's economics. And we call it macroeconomics. So I guess it is for the whole country there. So we have knowledge economics, macroeconomics. And then let's just do one more. We'll keep it as row 2. And this time our economist is also a musician. So we'll put music. And they happen to have knowledge and they enjoy, let's do pop music. They're into the current pop music going on. So we've loaded our database. And you'll see we have 2 rows, row 1 and row 2 in here. And we can do is we can list the contents of our database by simply doing scan. Scan, and then let's just do scan by itself so you can see how that looks. You can always just type in there and it tells you all the different setups you can do with scan and how it works. In this case, we want to do scan new TBL. And in our scan new TBL, we have row 1, row 1, row 2, row 2. And you'll see row 1 has a column called knowledge, science, timestamp, value crickets, value physics. So it has information as when it was created, when the timestamp is. Row 1 also has knowledge, sports, and a value of cricket. So we have sports and science. And this is interesting because if you remember up here, we also gave it originally, we told it to come in here and have chemistry. We had science, chemistry, and science, physics. And we come down here, I don't see the chemistry. Why? Because we've now replaced chemistry with physics. And so the new value is physics on here. Let me go ahead and clear down a little bit. And in this, we're going to ask the question, is enabled new table? And when I hit enter in here, you're going to see it comes out true. And then we'll go ahead and disable it. Let's go ahead and disable new table. Make sure I have our quotes around it. And now that we've disabled it, what happens when we do the scan? When we do the scan new table, and I hit enter, you're going to see that we get an error coming up. So once it's disabled, you can't do anything with it until we re-enable it. Now, before we enable the table, let's do an alteration on it. And here's our new table. And this should look a little familiar because it's very similar to create. We'll call this test info. And we'll hit enter in there. It'll take just a moment for updating. And then we want to go ahead and enable it. So let's go ahead and enable our new table. So it's back up and running. And then we want to describe. Describe new table. And we come in here, you'll now see we have name knowledge. And under there we have our data encoding and all the information under knowledge. And then we also have down below test info. So now we have the name test info and all the information concerning the test info on here. And we'll simply enable it. New table. So now it's enabled. Oops, I already did that. I guess we'll enable it twice. And so let's start looking at, well, we had scan new table. And you can see here where it brings up the information like this. Well, what if we want to go ahead and get a row? So we'll do R1. And when we do HBase R1, you can see we have knowledge science and it has a timestamp, value physics, and we have knowledge sports and it has a timestamp on it and value cricket. And then let's see what happens when we put into our new table. And in here we want row 1. And if you can guess from earlier, because we did something similar, we're going to do knowledge economics. And then it's going to be, instead of, I think it was macroeconomics, it's now market economics. And we'll go back and do our get command and now see what it looks like. And we can see here where we have knowledge economics. It has a timestamp, value, market economics, physics, and cricket. And this is because we have economics, science, and sports. Those are the 3 different columns that we have, and then each one has different information in it. And so if you manage to go through all these commands and look at basics on here, you'll now have the ability to create a very basic HBase setup, no SQL setup, based on your columns and your rows. And just for fun, we'll go back to the Cloudera, where they have the website up for the HBase master status, and I'll go ahead and refresh it. And then we can go down here and you'll see user tables, table set 1, and we can click on details, and here's what we just did. It goes through, so if you're the admin looking at this, you can go, oh, someone just created new TBL, and this is what they have underneath of it in their new table in there.
Here we will learn on Apache Spark, history of Spark, what is Spark, Hadoop, which is a framework again, Wes Spark, components of Apache Spark, that is Spark Core, Spark SQL, Spark Streaming, Spark MLlib, and graphics. Then we will learn on Spark architecture, applications of Spark, Spark use cases. So let's begin with understanding about history of Apache Spark. It all started in 2009 as a project at UC Berkeley AMP Labs by Mate Zaharia. In 2010, it was open sourced under a BSD license. In 2013, Spark became an Apache top-level project, and in 2014, used by Databricks to sort large-scale datasets, and it set a new world record. So that's how Apache Spark started. And today it is one of the most in-demand processing framework, or I would say in-memory computing framework, which is used across the big data industry. So what is Apache Spark? Let's learn about this. Apache Spark is an open source in-memory computing framework, or you could say data processing engine, which is used to process data in batch and also in real time across various cluster computers. And it has a very simple programming language behind the scenes, that is Scala, which is used. Although if users would want to work on Spark, they can work with Python, they can work with Scala, they can work with Java, and so on, even R for that matter. So it supports all these programming languages, and that's one of the reasons that it is called polyglot, wherein you have good set of libraries and support from all the programming languages. And developers and data scientists incorporate Spark into their applications or build Spark-based applications to process, analyze, query, and transform data at a very large scale. So these are key features of Apache Spark. Now, if you compare Hadoop with Spark, we know that Hadoop is a framework, and it basically has Mapreduce, which comes with Hadoop for processing data. However, processing data using Mapreduce in Hadoop is quite slow because it is a batch-oriented operation and it is time-consuming. If you talk about Spark, Spark can process the same data 100 times faster than Mapreduce, as it is a in-memory computing framework. Well, there can always be conflicting ideas saying, what if my Spark application is not really efficiently coded and my Mapreduce application has been very efficiently coded? Well, then it's a different case. However, normally if you talk about code which is efficiently written for Mapreduce or for Spark-based processing, Spark will win the battle by doing almost 100 times faster than Mapreduce. So as I mentioned, Hadoop performs batch processing, and that is one of the paradigms of Mapreduce programming model, which involves mapping and reducing, and that's quite rigid. So it performs batch processing. The intermittent data is written to HDFS and read back from HDFS, and that makes Hadoop's Mapreduce processing slower. In case of Spark, it can perform both batch and real-time processing. However, a lot of use cases are based on real-time processing. Take an example of Macy's, take an example of retail giant such as Walmart, and there are many use cases who would prefer to do real-time processing, or I would say near real-time processing. So when we say real-time or near real-time, it is about processing the data as it comes in, or you're talking about streaming kind of data. Now, Hadoop or Hadoop's Mapreduce obviously was started to be written in Java. Now you could also write it in Scala or in Python. However, if you talk about Mapreduce, it will have more lines of code since it is written in Java, and it will take more times to execute. You have to manage the dependencies, you have to do the right declarations, you have to create your mapper and reducer and driver classes. However, if you compare Spark, it has few lines of code as it is implemented in Scala, and Scala is a statically typed, dynamically inferred language. It's very, very concise, and the benefit is it has features from both functional programming and object-oriented language. And in case of Scala, whatever code is written, that is converted into bytecodes, and then it runs in the JVM. Now, Hadoop supports Kerberos authentication. There are different kind of authentication mechanisms. Kerberos is one of the well-known ones, and it can really get difficult to manage. Now, Spark supports authentication via a shared secret. It can also run on Yarn, leveraging the capability of Kerberos. So what are Spark features which really makes it unique or in-demand processing framework? When we talk about Spark features, one of the key features is fast processing. So Spark contains resilient distributed datasets. So RDDs are the building blocks for Spark. And we'll learn more about RDDs later. So Spark contains RDDs, which saves huge time taken in reading and writing operations. So it can be 100 times, or you can say 10 to 100 times faster than Hadoop. When we say in-memory computing, here I would like to make a note that there is a difference between caching and in-memory computing. Think about it. Caching is mainly to support read-ahead mechanism where you have your data preloaded so that it can benefit further queries. However, when we say in-memory computing, we are talking about lazy evaluation. We are talking about data being loaded into memory only and only when a specific kind of action is invoked. So data is stored in RAM. So here we can say RAM is not only used for processing, but it can also be used for storage. And we can again decide whether we would want that RAM to be used for persistence or just for computing. So it can access the data quickly and accelerate the speed of analytics. Now, Spark is quite flexible. It supports multiple languages, as I already mentioned, and it allows the developers to write applications in Java, Scala, R, or Python. It's quite fault tolerance. So Spark contains these RDDs, or you could say execution logic, or you could say temporary data sets, which initially do not have any data loaded. And the data will be loaded into RDDs only when execution is happening. So these can be fault tolerant as these RDDs are distributed across multiple nodes. So failure of one worker node in the cluster will really not affect the RDDs because that portion can be recomputed. So it ensures loss of data. It ensures that there is no data loss, and it is absolutely fault tolerant. It is for better analytics. So Spark has a rich set of SQL queries, machine learning algorithms, complex analytics, all of this supported by various Spark components, which we will learn in coming slides. With all these functionalities, analytics can be performed better in terms of Spark. So these are some of the key features of Spark. However, there are many more features which are related to different components of Spark, and we will learn about them. So what are these components of Spark which I'm talking about? Spark Core. So this is the core component, which basically has RDDs, which has a core engine, which takes care of your processing. Now you also have Spark SQL. So people who would be interested in working on structured data or data which can be structurized would want to prefer using Spark SQL. And Spark SQL internally has components or features like data frames and data sets, which can be used to process your structured data in a much faster way. You have Spark Streaming. Now that's again an important component of Spark, which allows you to create your Spark streaming applications, which not only works on data which is being streamed in or data which is constantly getting generated, but you could also transform the data. You could analyze or process the data as it comes in smaller chunks. You have Spark's MLlib. Now this is basically a set of libraries which allows developers or data scientists to build their machine learning algorithms so that they can do predictive analytics or prescriptive, descriptive, preemptive analytics, or they could build their recommendation systems or bigger, smarter machine learning algorithms using these libraries. And then you have graphics. So think about organizations like LinkedIn or say Twitter, where you have data which naturally has a network kind of flow. So data which could be represented in the form of graphs. Now here when I talk about graphs, I'm not talking about pie charts or bar charts, but I'm talking about network related data. That is data which can be networked together, which can have some kind of relationship. Think about Facebook, think about LinkedIn, where you have one person connected to other person or one company connected to other company. So if we have our data which can be represented in the form of network graphs, then Spark has a component called GraphX, which allows you to do graph-based processing. So these are some of the components of Apache Spark: Spark Core, Spark SQL, Spark Streaming, Spark MLlib, and GraphX. So to learn more about components of Spark, let's learn here about Spark Core. Now this is the base engine. And this is used for large-scale, parallel, and distributed data processing. So when you work with Spark, at least and the minimum you would work with is Spark Core, which has RDDs as the building blocks of your Spark. So it is responsible for your memory management, your fault recovery, scheduling, distributing, and monitoring jobs on a cluster, and interacting with storage systems. So here I would like to make a key point that Spark by itself does not have its own storage. It relies on storage. Now that storage could be your HDFS, that is Hadoop's distributed file system. It could be a database like NoSQL database such as HBase, or it could be any other database, say RDBMS, from where you could connect your Spark and then fetch the data, extract the data, process it, analyze it. So let's learn a little bit about your RDDs, resilient distributed datasets. Now Spark Core, which is the base engine or the core engine, is embedded with the building blocks of Spark, which is nothing but your resilient distributed dataset. So as the name says, it is resilient. So it is existing for a shorter period of time, distributed. So it is distributed across nodes. And it is a data set where the data will be loaded or where the data will be existing for processing. So it is immutable, fault tolerant, distributed collection of objects. So that's what your RDD is. And there are mainly two operations which can be performed on an RDD. Now to take an example of this, say I want to process a particular file. Now here I could write a simple code in Scala, and that would basically mean something like this. So if I say val, which is to declare a variable, I would say val x, and then I could use what we call as Spark context, which is basically the most important entry point of your application. So then I could use a method of Spark context, for example, that is text file, and then I could point it to a particular file. So this is just a method of your Spark context, and Spark context is the entry point of your application. Now here I could just give a path in this method. So what does this step do? It does not do any evaluation. So when I say val x, I'm creating an immutable variable, and to that variable I'm assigning a file. Now what this step does is it actually creates a RDD, resilient distributed dataset. So we can imagine this as a simple execution logic, a empty dataset which is created in memory of your node. So if I would say I have multiple nodes in which my data is split and stored, imagining that your Spark is working with Hadoop. So I have Hadoop, which is using say 2 nodes, and this is my distributed file system, HDFS, which basically means my file is written to HDFS, and it also means that the file related blocks are stored in the underlying disk of these machines. So when I say val x equals sc.text file, that is using a method of Spark context. Now there are various other methods like whole text files, parallelize, and so on. This step will create an RDD. So you can imagine this as a logical data set which is created in memory across these nodes, because these nodes have the data. However, no data is loaded here. So this is the first RDD, and I can say first step in what we call as a DAG. A DAG which will have series of steps which will get executed at later stage. Now later I could do further processing on this. I could say val y, and then I could do something on x. So I could say x.map, and I would want to apply a function to every record or every element in this file, and I could give a logic here, x.map. Now this second step is again creating an RDD, a resilient distributed data set. You can say second step in my DAG, okay? And here you have a external RDD, one more RDD created, which depends on the first RDD. So my first RDD becomes the base RDD or parent RDD, and the resultant RDD becomes the child RDD. Then we can go further, and we could say val z, and I would say, okay, now I would want to do some filter on y. So this filter which I am doing here, and then I could give a logic. Might be I'm searching for a word, I'm searching for some pattern, so I could say val z equals y.filter, which again creates one more RDD, a resilient distributed data set in memory. And you can say this is nothing but one more step in the DAG. So this is my DAG, which is a series of steps which will be executed. Now here, when does the execution happen? When will the data get loaded into these RDDs? So all of this, that is using a method, using a transformation like map, using a transformation like filter or flat map or anything else, these are your transformations. So the operations such as map, filter, join, union, and many others will only create RDDs, which basically means it is only creating execution logic. No data is evaluated, no operation is happening right now. Only and only when you invoke an action, that is, might be you want to print some result, might be you want to take some elements and see that, might be you want to do a count. So those are actions which will actually trigger the execution of this DAG right from the beginning. So if I here say z dot count, where I would want to just count the number of words which I'm filtering, this is an action which is invoked, and this will trigger the execution of DAG right from the beginning. So this is what happens in a Spark. Now, if I do a z.count again, it will start the whole execution of DAG again right from the beginning. So my z.count, second time an action is invoked, again the data will be loaded in the first RDD, then you will have map, then you will have filter, and finally you will have result. So this is the core concept of your RDDs, and this is how RDD works. So mainly in Spark, there are two kinds of operations. One is your transformations and one is your actions. Transformations or using a method of Spark context will always and always create an RDD, or you could say a step in the DAG. Actions are something which will invoke the execution, from the first RDD till the last RDD where you can get your result. So this is how your RDDs work. Now, when we talk about components of Spark, let's learn a little bit about Spark SQL. So Spark SQL is a component processing framework which is used for structured and semi-structured data processing. So usually people might have their structured data stored in RDBMS or in files where data is structured with particular delimiters and has a pattern. And if one wants to process this structured data, if one wants to use Spark to do in-memory processing and work on this structured data, they would prefer to use Spark SQL. So you can work on different data formats, say CSV, JSON. You can even work on smarter formats like Avro, Parquet, even your binary files or sequence files. You could have your data coming in from an RDBMS, which can then be extracted using a JDBC connection. So at the bottom level, when you talk about Spark SQL, it has a data source API, which basically allows you to get the data in whichever format it is. Now, Spark SQL has something called as data frame API. So what are data frames? Data frames, in short, you can visualize or imagine as rows and columns, or if your data can be represented in the form of rows and columns with some column headings. So data frame API allows you to create data frames. So like my previous example, when you work on a file, when you want to process it, you would convert that into an RDD using a method of Spark context or by doing some transformations. So in the similar way, when you use data frames or when you want to use Spark SQL, you would use Spark's context, which is SQL context or Hive context or Spark, which allows you to work with data frames. So like in my earlier example, we were saying val x equals sc.text file. Now in case of data frames, instead of sc, you would be using, say, Spark dot something. So Spark context is available for your data frames API to be used. In older versions like Spark 1.6 and so on, we were using Hive context or SQL context. So if you were working with Spark 1.6, you would be saying val x equals SQL context dot. Here we would be using Spark dot. So data frame API basically allows you to create data frames out of your structured data, which also lets Spark know that data is already in a particular structure. It follows a format, and based on that, your Spark's backend DAG scheduler, right? So when I say about DAG, I talk about your sequence of steps. So Spark is already aware of what are the different steps involved in your application. So your data frame API basically allows you to create data frames out of your data. And data frames, when I say, I'm talking about rows and columns with some headings. And then you have your data frame, DSL language, or you can use Spark SQL or Hive query language. Any of these options can be used to work with your data frames. So to learn more about data frames, follow in the next sessions. When you talk about Spark streaming, now this is very interesting for organizations who would want to work on streaming data. Imagine a store like Macy's, where they would want to have machine learning algorithms. Now, what would these machine learning algorithms do? Suppose you have a lot of customers walking in the store and they are searching for particular product or particular item. So there could be cameras placed in the store, and this is being already done. There are cameras placed in the store which will keep monitoring in which corner of the store there are more customers. Now, once camera captures this information can be streamed in to be processed by algorithms, and those algorithms will see which product or which series of product customers might be interested in. And if this algorithm in real time can process based on the number of customers, based on the available product in the store, it can come up with a attractive alternative price, so that which the price can be displayed on the screen and probably customers would buy the product. Now this is a real-time processing where the data comes in, algorithms work on it, do some computation and give out some result, and which can then result in customers buying a particular product. So the whole essence of this machine learning and real-time processing will really hold good if and when customers are in the store. Or this could relate to even an online shopping portal where there might be machine learning algorithms which might be doing real-time processing based on the clicks which customer is doing. Based on the clicks, based on customer history, based on customer behavior, algorithms can come up with recommendation of products or better altered price so that the sale happens. Now, in this case, we would be seeing the essence of real-time processing only in a fixed or in a particular duration of time. And this also means that you should have something which can process the data as it comes in. So Spark Streaming is a lightweight API that allows developers to perform batch processing and also real-time streaming and processing of data. So it provides secure, reliable, fast processing of live data streams. So what happens here in Spark Streaming in brief? So you have an input data stream. Now that data stream could be a file which is constantly getting appended. It could be some kind of metrics. It could be some kind of events based on the clicks which customers are doing or based on the products which they are choosing in a store. This input data stream is then pushed in through a Spark Streaming application. Now, Spark Streaming application will break this content into smaller streams, what we call as discretized streams, or batches of smaller data on which processing can happen in frames. So you could say, process my file every 5 seconds for the latest data which has come in. Now, there are also some Windows-based options. Like when I say Windows, I mean a window of past 3 events. Window of past 3 events, each event being of 5 seconds. So your batches of smaller data is processed by Spark Engine, and this processed data can then be stored or can be used for further processing. So that's what Spark Streaming does. When you talk about MLlib, it's a low-level machine learning library that is simple to use, scalable, and compatible with various programming languages. Now, Hadoop also has some libraries, like you have Apache Mahout, which can be used for machine learning algorithms. However, in terms of Spark, we are talking about machine learning algorithms which can be built using MLlibs libraries, and then Spark can be used for processing. So MLlib eases the deployment and development of scalable machine learning algorithms. I mean, think about your clustering techniques. So think about your classification, where you would want to classify the data, where you would want to do supervised or unsupervised learning. Think about collaborative filtering and many other data science related techniques, or techniques which are required to build your recommendation engines or machine learning algorithms can be built using Spark's MLlib. GraphX is Spark's own graph computation engine. So this is mainly if you are interested in doing a graph-based processing. Think about Facebook, think about LinkedIn, where you can have your data which can be stored, and that data has some kind of network connections. Or you could say it is well networked. I could say X is connected to Y is connected to Z is connected to A. So X, Y, Z, A, all of these are, in terms of graph terminologies, we call as vertices or vertex, which are basically being connected. And the connection between these are called edges. So I could say A is friend to B. So A and B are vertices, and friend, a relation between them, is the edge. Now, if I have my data which can be represented in the form of graphs, if I would want to do a processing in such way, this could be not only for social media, it could be for your network devices, it could be a cloud platform, it could be about different applications which are connected in a particular environment. So if you have data which can be represented in the form of graph, then GraphX can be used to do ETL, that is extraction, transformation, load, to do your data analysis, and also do interactive graph computation. So GraphX is quite powerful. Now, when you talk about Spark, your Spark can work with your different clustering technologies. So it can work with Apache Mesos. That's how Spark came in, where it was initially to prove the credibility of Apache Mesos. Spark can work with Yarn, which is usually you will see in different working environments. Spark can also work as standalone. That means without Hadoop, Spark can have its own setup with master and worker processes. So usually, or you can say technically, Spark uses a master-slave architecture. Now that consists of a driver program that can run on a master node. It can also run on a client node. It depends on how you have configured or what your application is. And then you have multiple executors which can run on worker nodes. So your master node has a driver program, and this driver program internally has the Spark context. So your Spark, every Spark application will have a driver program, and that driver program has a inbuilt or internally used Spark context, which is basically your entry point of application for any Spark functionality. So your driver or your driver program interacts with your cluster manager. Now, when I say interacts with cluster manager, so you have your Spark context, which is the entry point that takes your application request to the cluster manager. Now, as I said, your cluster manager could be, say, Apache Mesos, it could be Yarn, it could be Spark standalone master itself. So your cluster manager in terms of Yarn is your resource manager. So your Spark application internally runs as series or set of tasks and processes. Your driver program, wherever that is run, will have a Spark context, and Spark context will take care of your application execution. How does that do it? Spark context will talk to cluster manager. So your cluster manager could be Yarn, and in terms of when I say cluster manager for Yarn would be resource manager. So at high level, we can say a job is split into multiple tasks, and those tasks will be distributed over the slave nodes or worker nodes. So whenever you do some kind of transformation or you use a method of Spark context, an RDD is created, and this RDD is distributed across multiple nodes. As I explained earlier, worker nodes are the slaves that run different tasks. So this is how a Spark architecture looks like. Now we can learn more about Spark architecture and its interaction with Yarn. So usually what happens when your Spark context interacts with the cluster manager. So in terms of Yarn, I could say resource manager. Now we already know about Yarn. So you would have, say, node managers running on multiple machines, and each machine has some RAM and CPU cores allocated for your node manager. On the same machine, you have the data nodes running, which obviously are there to have the Hadoop related data. So whenever an application wants to process the data, your application via Spark context contacts the cluster managers, that is resource manager. Now what does resource manager do? Resource manager makes a request. So resource manager makes requests to the node manager of the machines wherever the relevant data resides, asking for containers. So your resource manager is negotiating or asking for containers from node manager, saying, hey, can I have a container of 1 GB RAM and 1 CPU core? Can I have a container of 1 GB RAM and 1 CPU core? And your node manager, based on the kind of processing it is doing, will approve or deny it. So node manager would say, fine, I can give you the container. And once this container is allocated or approved by node manager, resource manager will basically start an extra piece of code called app master. So app master is responsible for execution of your applications, whether those are Spark applications or Mapreduce. So your application master, which is a piece of code, will run in one of the containers. That is, it will use the RAM and CPU core, and then it will use the other containers which were allocated by node manager to run the tasks. So it is within this container which can take care of execution. So what is a container? A combination of RAM and CPU core. So it is within this container, we will have a executor process which would run, and this executor process is taking care of your application related tasks. So that's how overall Spark works in integration with Yarn. Now let's learn about this Spark cluster managers. As I said, Spark can work in a standalone mode, so that is without Hadoop. So by default, applications submitted to Spark standalone mode cluster will run in FIFO order, and each application will try to use all the available nodes. So you could have a Spark standalone cluster, which basically means you could have multiple nodes. On one of the nodes, you would have the master process running, and on the other nodes, you would have the Spark worker processes running. So here we would not have any distributed file system because Spark is standalone and it will rely on an external storage to get the data, or probably the file system of the nodes where the data is stored, and processing will happen across the nodes where your worker processes are running. You could have Spark working with Apache Mesos. Now, as I said, Apache Mesos is an open source project to manage your computer clusters and can also run Hadoop applications. Apache Mesos was introduced earlier, and Spark came in and has existence to prove the credibility of Apache Mesos. You can have Spark working with Hadoop's Yarn. This is something which widely you will see in different working environments. So Yarn, which takes care of your processing and can take care of different processing frameworks, also supports Spark. You could have Kubernetes. Now that is something which is making a lot of news in today's world. It is an open source system for automating deployment, scaling, and management of containerized applications. So where you could have multiple Docker-based images which can be connecting to each other. So Spark also works with Kubernetes. Now let's look at some applications of Spark. So JP Morgan Chase and company uses Spark to detect fraudulent transactions, analyze the business spends of an individual to suggest offers, and identify patterns to decide how much to invest and where to invest. So this is one of the examples of banking. A lot of banking environments are using Spark due to its real-time processing capabilities and in-memory faster processing, where they could be working on fraud detection or credit analysis or pattern identification and many other use cases. Alibaba Group, that uses also Spark to analyze large data sets of data such as real-time transaction details. Now that might be based online or in the stores, looking at the browsing history in the form of Spark jobs, and then provides recommendations to its users. So Alibaba Group is using Spark in its e-commerce domain. You have IQVIA, Now, this is a leading healthcare company that uses Spark to analyze patients' data, identify possible health issues, and diagnose it based on their medical history. So there is a lot of work happening in healthcare industry where real-time processing is finding a lot of importance, and real-time and faster processing is what is required. So healthcare industry and IQVIA is also using Spark. You have Netflix, which is known, and you have Riot Games. So entertainment and gaming companies like Netflix and Riot Games use Apache Spark to showcase relevant advertisements to their users based on the videos that they have watched, shared, or liked. So these are few domains which find use cases of Spark, that is banking, e-commerce, healthcare, entertainment, and then there are many more which are using Spark in their day-to-day activities for real-time, in-memory, faster processing. Now, let's discuss about the Spark's use case, and let's talk about Conviva, which is world's leading video streaming companies. So video streaming is a challenge. Now, if you talk about YouTube, which has data, you could always read about it. So YouTube has data which is worth watching 10 years. So there is huge amount of data where people are uploading their videos or companies are doing advertisements, and these videos are streamed in or can be watched by users. So video streaming is a challenge, and especially with increasing demand for high quality streaming experiences. Conviva collects data about video streaming quality to give their customers visibility into the end user experience they are delivering. Now, how do they do it? Apache Spark again. Using Apache Spark, Conviva delivers a better quality of service to its customers by removing the screen buffering and learning in detail about network conditions in real time. This information is then stored in the video player to manage live video traffic coming in from 4 billion video feeds every month to ensure maximum retention. Now, using Apache Spark, Conviva has created an auto diagnostics alert. It automatically detects anomalies along the video streaming pipeline and diagnoses the root cause of the issue. Now, this really makes it one of the leading video streaming companies based on auto diagnostic alerts. It reduces waiting time before the video starts. It avoids buffering and recovers the video from a technical error. And the whole goal is to maximize the viewer engagement. So this is Spark's use case where Conviva is using Spark in different ways to stay ahead in video streaming related deliveries. If we have understood and learned about your Spark components, your Spark architecture, we can also see running a Spark application. Now, a Spark application can run in a standalone mode. That is, you could set up your IDE such as Eclipse with a Scala plugin, and then you could have your coded application which is written in Eclipse to be run in local mode. Now here I have an example of application which can be run in a local mode or on a cluster. So this application is importing some packages, that is Spark Context, Spark Conf. I have created an object which is first app. It is the main class of your project, and other classes can just be extending app rather than having main. Here we declare a variable called X, which is pointing to a file in my project directory. It looks for a file which is abc1.txt, and this file basically has some content. What are we doing in the application? So we create a variable where we assign the file. Then we define or initialize our Spark context. So remember, whenever you work with IDE, you don't have Spark context or Spark available implicitly. That has to be defined. So here we create a configuration object. We set our application name. We set the master as local. If you want to run it in a local mode, if you want to run it, say, on your Windows machine, or if you would want to run on a Spark standalone cluster. If I would be running it on Yarn, then I would remove this property that is set master. Now, once you have defined your configuration object, you can be basically using Spark context. You can use method of it, which will result in RDD. That is what is happening in line 13, val y. And then finally, I can create a variable where I would want to do a flat map transformation on y, which would result in an internal RDT, followed by a map transformation, which would again result in an RDT, and finally reduce by key, which is doing an aggregation. Once all these steps are done, I can decide to display the result on the screen, or I can even use save as text file, point it to a particular location, and then have my application run. Now, this is my Eclipse. Refer to other sessions where I've explained how you can set up IDE on Windows with different environment variables, and then you can run your applications on a particular cluster. If I would want to run this application on a cluster, then I will have to give a particular path. So here in this case, I can say, let's do this. And I will say my file is abc1.txt. Let's save it. And I'll also say my output will be getting stored in a default location. As I intend to run it, I intend to run this application on a cluster. Now in that case, the cluster would usually be set up on Linux machines, would have a Hadoop cluster where you can run this application. So if I would want to run this application on a cluster but not locally on the machine, I can just delete this part. I can keep my application. Now if you see, my application already compiles and does not show any error message, and that is because in my project's build path, I have added all the Spark related jars. All the Spark related jars you can get from your Spark directory, or you can be getting in manually all the dependencies. Some people would prefer to use Maven or say SBT for packaging your application as jar, and that can also be done. So here my code compiles, code is fine, it is pointing to a file, and then it is also creating an output which will have word count. Now what I can do is, since I have my code already written, I know that I have SBT installed on this machine because I would want to package this code as jar and run it on a cluster. So for that, we can look in our command prompt, and here I can go into workspace. I can go into my Scala project, and if you see here, we have your build.sbt file, you have your binaries, and you have your source. So you might not have these Spark related directories. Now these exist in my case because I have been using Spark and I've done some previous runs. Now this is what we have within my Spark apps. So to build my package, I need a build.sbt file. We can see what does that contain. So your build.sbt contains your name, version of your package jar, Scala version, Spark version, and then repository which Spark will refer to when it wants to have the dependencies for all of your components such as Spark Core, Spark SQL, MLlib, and so on. So this is my build.sbt file which exists in the project folder. And if you are intending to use SBT to package your code as jar and then run it on the cluster, in that case, I can even skip adding Spark related jars to the build path. So that is only done to make sure that your code compiles. Now, once I have my code written, I have SBT installed, I have made the file path changes, I can just go to the command line within my project folder and I can say SBT package. Now this will basically resolve all the dependencies based on whatever you have given in the code. It will create a jar file and place it in a particular location, and then we can use the same jar file to run on a particular cluster. So SBT package is busy in creating the jar. Now meanwhile, what I can do is I can open up a lab content, and what I can do is I can just say, for example, Simplilearn. And here I already have a lab set up, so you could have your own Spark standalone cluster where you could also run this jar file. You could have Spark with Hadoop, which is what I have here, and I will use that to submit an application on the Yarn cluster. And let's go to the web console. Let me copy my link. I'll close this. I'll say launch lab, and then I can log in here. I can just do paste my password and I'm logged in. So I can just say Spark 2 shell. Now that's how it has been configured here to work with your Spark version 2. So this is an interactive way of bringing your Spark shell and running your application. But what we are interested in is running the application as a jar file. So let's go and see here where we have our code, and let's see if SBT has done the packaging. Yes, it has done, and it has created a jar file in this location. So what I can do is I need to get this jar file from this location onto my cluster. So what I can do is I can come in here, I can do a FTP. So this basically allows me to push whatever jars I have on my web console. So I'll go in here, I'll say connect. Now I'll search if there is already existing jar file which might create a conflict. So I have something here. So I can for now just delete it. It's done. I will say upload file, and I'm interested in getting the jar file. So here we can click on users, Win10. I have my workspace project. I can get into target, Scala 2.11, and take my jar file and say open. So this will upload my jar file on the web console or the terminal, wherein I can connect to my cluster. Now let's go in here. Let's quit from Spark Shell as we want to run an application on the cluster. How do I do it? So I can search if I have my jar file existing. It's here. So I'll say Spark to submit, and then I will point to my jar file, and then I can simply say class, and I know my code has a package and a class name. So this is package and this is my object or class name. So I can say main.scala.first.app. Now it will be good if we check if the file exists, which our code points to. So I'll just for now comment it out. I will check in my HDFS ls in my default user directory. This is where it will search for a file, and here we can search if I have a file called ABC. So I don't see anything here. So let's do this. What I can do is I can again go to FTP, and basically I can do a upload file like what we did earlier, and this time I'll pick up this existing ABC1 file which I showed you and upload it. Once this is done, I can put it on my cluster by just saying HDFS DFS put. Let's take the ABC1 file and let's put it in my directory. So this will be my input. So I'm putting in a file there, and now I can do a Spark submit to submit the application on the cluster. So if you see here, it has basically started the application. It contacts the resource manager. It gets an application ID, and now it is doing the processing of my file where I would want to get. Once this is done, it will be completed and the temporary directory will be deleted. So this is how I run a Spark application on a cluster. Now once this is done, I can also go to Spark's history server by saying this is the path for my Spark history server. It shows an application which was run today, which was doing a word count. You can click on the application. It says it ended with save as text file. You can click on this, and then it shows you the DAG visualization. It says we started with text file. We did a flat map, we did a map, and then there was some shuffling because we wanted to do reduce by key. So as I said, every RDD by default has two partitions. And if you want to do some aggregate or wider transformations like reduce by key, sort by key, group by key, count by key, and so on, in that case, similar key related data has to be shuffled and brought into one partition. That's where we see shuffling happening here, and it also tells what are the number of tasks which have run per partition. So here we ran a Spark application by packaging it as jar using your SBT. So SBT created the jar file, and then basically we brought our jar file onto the cluster and then submitted it using Spark submit. So this is how a Spark application runs on the cluster. So as I said, your application has a driver program. Now your Spark applications run as independent processes, and they can run on a cluster across the nodes. So we just saw how we can run a Spark application on a cluster. Now we can always look at Spark application's progress or after it has completed by looking into the Spark UI. Your Spark application, as I mentioned, has a driver program, and when you run your application on the cluster, you can always specify where would you want your driver program to run. So in our case, when we ran our Spark application here, we basically just did a simple Spark submit and we gave our jar and the class name. I could also say master, and then I could specify if I would want my application to run in a local mode, or I could say yarn, but that is default. Or if it was a Spark standalone cluster, then I could be giving something like this, your host name, and then your port. So you could do all of these options by specifying minus master. I could also specify how many executors I need, how much memory per executor, how much cores per executor I need. And I could also say deploy mode as client, which basically means my driver will run on this machine. However, my execution of application will happen on cluster nodes. I can also say deploy mode as cluster, which basically means my driver will run on one of the nodes of the cluster. You could submit your application, and then based on whatever arguments you have given, your application will be submitted on the cluster and it will run. So you can have your application running. So as I said, you have an application which has a driver and it also has either Spark session or Spark context, which takes your application request to the resource manager. Now, if your application is completed, you can always come back and look into the Spark history server or Spark UI. If I choose this as my application, which I have run, I can go to executors, and that shows me that there was one for your driver. Now that was running on this particular node, which is my client node. Then I have my executors on my other nodes, which are nodes of my cluster, which used one core, which ran 2 tasks for the partitions which they were working on. And there was some shuffling involved as we were doing a word count, which uses reduce by key. So when you run your application, your yarn or your cluster manager, such as resource manager, negotiates the resources to the slave processes. Your worker node basically will have the resources available for any kind of execution. Now, as I said, your resource manager will request for containers. Your worker nodes will approve those containers. And then within those containers, you will have the executor which will run, which will take care of the task to process the data. So what is a task? It is a unit of work for the data set which has to be worked upon. So your RDDs which get created have partitions, and for every partition you have a task which is taken care by the executor. So the data is loaded into the RDD when an action is invoked, and then your task is worked upon by the executor. So what does it do? It basically gets the data into the partition of RDD and then does the execution as a task on that particular partition. Results are then sent back to the driver, and you can also have your output saved on the disk. So this is how your application runs. Whenever you run a particular application, you can always go to your web console and scroll or look into the logs for more information. So here our application was run, and we can see right from the beginning here when we talk about Spark submit, which is done here. It says running Spark version 2.2. It basically then will see that there will be a driver which will be started. You can further see that it does some memory calculations. It then starts a Spark UI. And here we can see that requesting a new application from cluster with 4 node managers, verify our application has not requested more than maximum memory capability of the cluster. So the container sizing at the cluster level is 3 GB per container, and your application should not be requesting for a container bigger than that. It starts a application master container with specific amount of memory, and then finally your execution starts. If we scroll down and look into the logs, we will see where my driver runs. It will also show you how much memory was utilized, and it will talk about DAG scheduler, which is taking care of execution of your DAG, that is series of your RDDs. And finally, you will see the result getting generated or saved. So this is how you run your Spark application. This is how you can see your Spark applications in History Server or Spark UI. And this is how overall Apache Spark works, utilizing your cluster manager help, getting the resources from the worker processes, and then running the executors within those. Here we will learn on what is Spark Streaming data sources, features of Spark Streaming, working of Spark Streaming, discretized streams, caching or persistence as we call, checkpointing in Spark Streaming, and we will then have a demo on Spark Streaming. So let's learn on what is Spark Streaming and what it is capable of. So it's an extension of core Spark API that basically enables scalable, high throughput, fault-tolerant stream processing of live data streams. Now, data can be ingested from different sources like Kafka, Flume, Kinesis, or TCP sockets, and then it can be processed using complex algorithms expressed with different kind of functions such as map, reduce, join, and window. And when we have the data processed, that data can be pushed out to your file systems, databases, and live dashboards. So if we look on this image, we can clearly see that we would be working on a input data stream which goes into Spark Streaming component of Spark, which gives us batches of input data, or you could say the streaming data is broken down into smaller batches, which would then be worked upon by Spark core engine, and you have finally batches of processed data. Now, when we talk about Spark Streaming and the data sources, you could have streaming data sources coming in from Kafka or Flume or say Twitter API, or also with different formats such as Parquet. You could also have static data sources coming in from MongoDB, HBase, MySQL, and Postgres. So when we talk about Spark Streaming, it receives the input data streams, divides the data into batches, which can then be processed by Spark engine to generate your final stream of results again in batches. So your Spark Streaming actually provides a high-level abstraction called discretized stream, and we will learn about that, or what we call as D-stream, which represents a continuous stream of data. Now, when we look at your different data sources from where the data can come in, Spark Streaming would take in this input, and then you could have even your MLlib component, which could be used. That is Spark's component to build machine learning algorithms, wherein you can train your models with live data, and you can even use your trained model. You could be also going for structured processing or processing the data which is structurized, and that could be done by using Spark's components, that is Spark SQL, which has data frames and data sets. So you could process your data with data frames, interactively query with SQL when Spark Streaming is working on the data which is constantly flowing in. Finally, the data which is processed can be stored in your distributed file systems such as HDFS or any other NoSQL or SQL-based database. Now, when we talk about Spark Streaming, it is good to know some of the features of Spark Streaming. And here you have some of the features. So it enables fast recovery from failures. While it is working on streaming data, you have better load balancing and resource usage. And you can also combine the streaming data with static data sets and perform interactive queries. Now, your Spark Streaming also supports native integration with advanced processing libraries, and that is one of the benefits users can have when they are using Spark Streaming. Let's learn about working of Spark Streaming. So, as I mentioned earlier, at one end, you have your data streams. Now, those data streams are then caught or received by your receivers, which we have to enable in our application. Your data streams or streaming data, which is constantly getting generated and flowing in, is broken down into smaller batches, which will then be processed by Spark. So you would have your final processed results. Now, if we look at the bigger picture here, we will talk about live input data streams that could be divided into smaller batches. And when we say batches, these are batches of input data as RDDs. So Spark Streaming performs computation expressed using these streams. It generates RDD transformations. So you would have your Spark batch jobs to execute RDD transformations, which would give you your final processed result. Now there are various examples and we'll look at examples later. So once your Spark Streaming works on breaking the input into smaller streams, it can then process the data, finally giving you batches of your result. And that is again on the streaming data. Now, what is these D streams? Let's understand about D streams or discretized streams. So that's the basic abstraction provided by Spark Streaming. Now it represents a continuous stream of data, either the input data stream received from the source or the process data stream generated by transforming the input stream. Now here, if we look at the D stream, we would say you would have series of RDDs or series of transformations applied on the data which is flowing in for a particular time frame. Now here we say data from time 0 to 1, and that would result in some of the transformations which you would perform on the data when it has come in between this time zone or time frame. You would have again data from time 1 to 2 and so on. So that's how your Spark Streaming works. So if we look at your different transformations, now there could be various transformations which could be applied on your data. So this is something like your streaming data which comes in. You would want to say have a receiver which monitors a particular socket or a particular port and looks for data coming in. We would also define the time interval, and for that time interval the data is taken. So that's a smaller batch or a D stream on which you could have your processing done. Now within your application you would have series of steps which are nothing but transformations which would be performed on this data within this time frame, giving you a result which could be stored, which could be seen on your console, or which could just be pushed further for processing. And this keeps happening at regular time intervals, whatever you have specified, till the Spark Streaming application continues. Now, when we talk about Spark, we already know that there are different kind of transformations which can be applied. So you have map transformation, wherein you have map and then you pass in a function which basically says you would want to perform a function on every element. So when we say map function, that would return a new D stream by passing each element of the source D stream through a function which is passed. Similarly, it is for flat map, where you would be passing in a function. You would want to perform a flat map transformation on the data stream or D stream which comes in. So each input item can be mapped to 0 or more output elements. You could be doing a filter, wherein you return a D stream by selecting only the records of the source D stream on which the function returns true. So filtering is used when you want to run a transformation where you would want to look at the input data for a particular time interval, as I mentioned earlier, and you would want to filter that data as per whatever your function is applied. Now you could be doing a union, where you could basically be having a union of multiple D streams. So this would return a new D stream that contains union of elements in the source D stream and a other D stream. You could be doing a transform function that contains the union of elements. You could be doing a count. You could be doing a join. So these are some of the transformations which can be performed on your D streams. Now, there is also a concept of windowing, and that is basically to process the data for a series of time intervals. So when I mention windowed stream processing, I'm saying Spark Streaming would allow you to apply transformations over a sliding window of data. Now, this operation is called as windowed computation. Let's see how it looks like. So if you have your original D stream, which is basically your data coming in, now that would be looked upon for specific time intervals such as time 1, time 2, and then you could be doing a windowed computation, which could basically mean that I could have a window which is a series of these time intervals on which you would want to perform series of your RDD transformations. So you have a windowed D stream at time 1, then at time 2 and time 3. So that could be one window wherein you would want to get an output. So here we see window at time 3. Now you could also have another sliding window which would take your time series, and we have time 3, time 4, and time 5, where you could be performing the series of transformations. So this is usually helpful where you would not only want to process the data at particular time interval, but you would want a consolidated processing for series of intervals. And that's what we mean by windowed computation. Now, before we understand about caching and persistence, we can talk a little bit more on windowing. So if one would want to understand the window stream processing, or as we say, Spark streaming's feature of windowed computations, we need to think it as applying transformations over a sliding window of data. Now, as we see here, every time the window slides over a source D stream, the source RDDs that fall within the window are combined and operated upon to produce the RDDs of windowed stream. Now, in this specific case, we can say the operation is applied over last 3 time units of data and slides by 2 time units. This shows that any window operation needs to specify 2 parameters. One is the window length, which is basically the duration of window. So for example, we can say 3 as we see in the figure here, and then you have a sliding interval, which is basically the interval at which window operation is performed. So these 2 parameters must be multiples of the batch interval of source D stream. So that's what we do when we talk about window. Now there are various other transformations which can be applied, or window based operations which can be done on your D streams. Here to talk a little bit more on D streams, which is, as I said, it's a basic abstraction provided by Spark streaming. It represents just remember it as a continuous stream of data. Now either the input data stream received from source or the processed data stream, which is generated by transforming the input stream. So a D stream is represented by, you could say, a continuous series of RDDs, which is Spark's abstraction of an immutable distributed data set. So any operation applied on a D stream, it is basically translating to operations on the underlying RDDs. Now, for example, we can say converting a stream of lines to word, the flat map operation is applied on each RDD in the lines. Now D stream to generate the RDDs of your words D stream. So when we talk about your discretized streams, understand that you would have a series of transformations which would be applied for this time interval, whatever has been specified. Now when you talk about your streaming or Spark streaming architecture, as I mentioned here, that is your receivers. Now that plays a very important role here. So your input D streams or data streams are representing the stream of input data that is received from your streaming sources. Now we could have different kind of data and we could be doing different kind of transformations. So your receiver is basically an object which receives the data from a source and stores it in Spark's memory for processing. And that's the main role of your receiver. Now Spark streaming provides 2 categories of built-in streaming sources. So you have basic sources, that is sources directly available in streaming context, which is a class we learn about it, such as your file systems or socket connections. So those could be your basic sources from where the data is coming in. You could have advanced sources like your Kafka, Flume, Kinesis, etc. And they would be available through extra utility classes. So your receiver is going to be looking into the data which is constantly getting generated and then basically forwarding it for processing by your Spark streaming. When we talk about your Spark streaming, one more important aspect is basically understanding the caching and persistence. Now, as we know from the Spark core engine, or as you should know, that RDDs are, say, your logical steps, or RDDs are created when you perform some transformations. And these transformations or these computations or these RDDs can be cached so that it can improve the performance of your application. So the computed RDDs or the RDDs which are result of performing some transformations, they can be cached so that they can be reutilized down your application for your further processing. So when we talk about your caching and persistence, DStreams also allows developers to persist the stream data in memory. So similar to your concept of RDDs, DStreams can allow you to persist the particular streams data in memory. Now that is by doing or using your persist method on a DStream, which will automatically persist every RDD of that DStream in memory. It could be every RDD or it could be specifically chosen RDDs. Now this is really useful if the data in DStream has to be or would be computed multiple times, say in your application. So for example, if we say window-based operations like reduce by window, reduce by key and window, wherein you have group of operations being done, or you could have state-based operations like update state by key. Now in any of these cases, your DStreams generated by say window-based operations are automatically persisted in memory without the developer calling for the persist method. Now for input streams that receive data over networks such as Kafka, Flume, sockets, etc., the default persistence level is set to replicate the data to 2 nodes for fault tolerance. Now, one thing which we should remember is, unlike your RDDs, the default persistence level of DStreams keeps the data serialized in memory. And that we can discuss again further about your serializations or deserialization. Now, one important aspect which takes care of your fault recovery is checkpointing mechanism in Spark Streaming. Now, when I say checkpointing, a streaming application, as in real scenario we would want, must operate 24/7, and if the streaming application is constantly running, then there has to be a mechanism which can make your streaming application resilient to failures, which can be unrelated to your application logic. So Spark Streaming needs to do the checkpointing. It needs to checkpoint enough information to a fault-tolerant underlying storage system such that it can recover from failures. So your checkpointing is the process to make streaming applications more fault tolerant or resilient to your failures. Now this is usually used when you would want to recover from failure of a node running the driver of streaming application. Now we know driver is existing for every application, and it is basically one which knows the flow of your application. Driver also has the context. In case of streaming application, we would have, say, the Spark streaming context, which is the entry point of your application. Now, when we talk about your checkpointing to ensure your streaming application is more fault tolerant, you have 2 kinds of checkpointing here. So you could have a metadata checkpointing and you could have data checkpointing. Now, when we talk about metadata, what does that include? So metadata includes configuration, DStream operations, or even incomplete batches. So when we talk about metadata, it has configuration. So configuration that was used to create the streaming application. You could have DStream operations, that is set of DStream operations that define the streaming application, that is your series of RDDs. And then you have incomplete batches or batches whose jobs are queued but not have completed. So this would have to be checkpointed. So metadata checkpointing is used for recovering from a node failure running the streaming application driver. Now, your metadata, which has your configuration, incomplete batches, and DStream operations, need to be saved in an underlying storage system. Now, when you talk about data checkpointing, it is mainly about saving the generated RDDs to reliable storage. That is, whatever RDDs are computed. So, saving the information, which is saving the computations to a storage like HDFS. Now, that is used in stateful transformations, combining data across various batches. So when we talk about transformations, whatever RDDs are generated, that depend on RDDs of previous batches if we are talking about stateful, and that can cause the length of dependency chain to increase or keep increasing with time. Now, to avoid any kind of increase in the recovery time, intermediate RDDs can be periodically checkpointed. And that could be done to a reliable storage to basically cut off the growing dependency changes. So if we would want to summarize, we would say metadata checkpointing is primarily needed for recovery from driver failures, whereas data or RDD checkpointing is necessary even for basic functioning if stateful transformations are used. And we should remember we are talking about stateful transformations here. So when we talk about checkpointing, now the question is, when would you enable checkpointing, or what would you do to enable checkpointing? So checkpointing must be enabled for applications with different kind of requirements. So for example, if you are using stateful transformations where one series of RDDs depend on the result of your previous batches, so something like update state by key or reduce by key in window. Now, if these kind of operations are used in your application, then checkpoint directory must be provided to allow for periodic RDD checkpointing. When we say about requirements, then recovering from failures of the driver, which is taking care of your application, metadata checkpoints should be used. When we talk about simple streaming applications without the stateful transformations, they could be run without enabling checkpointing because your one batch of RDDs really does not depend on the previous set of RDDs which were done in the previous time frame. Now, recovery from driver failures will also be partial in that case when you talk about your stateless. So some might be received and your unprocessed data might be lost. But then that's pretty much acceptable when you talk about Spark streaming applications. So here we look at your checkpointing. So we say start. Now you have a checkpointing. Now whenever your application is creating a streaming context, it would set a checkpoint path, and then you would define your D stream, which is nothing but series of your RDD transformations. Your streaming context starts, which is basically your application entry point into the cluster for processing. And at any point of time, if there is any failure, you could always recover using the checkpoint which was created. In case of Spark streaming, one more thing we need to remember is that your checkpointing can be enabled by setting a directory in a fault-tolerant, reliable file system such as HDFS, wherein the checkpointing information will be saved. So we will have to add some methods within your application like streaming context with a checkpoint and then pointing into a checkpoint directory. And in that way, we can have our stateful transformations or metadata information stored in the underlying storage, whichever we have chosen. Now that we have discussed about Spark streaming, some basics of Spark streaming, let's also understand about shared variables, or what we call as accumulator and broadcast variables. So normally when you talk about your Spark operations, such as your map or reduce, these are executed on one of the node of your cluster. And what happens is, when you talk about your operations, they work on separate copies of all variables used in the function. Now, in this case, variables are copied to each machine and no updates to the variables on remote machines are propagated back to the driver program. Now, when we talk about read-write shared variables across tasks, that would be inefficient. So Spark actually provides two limited types of shared variables for common usage patterns, and those are your broadcast variables and your accumulators. Now, when you talk about your accumulators, these are variables that are only added through an associative or commutative operation. So Spark natively supports accumulators of numeric types, and programmers can add support for your new types. So when we talk about accumulators, they can be used to implement counters such as your Mapreduce or sums. So as a user, you can create named or unnamed accumulators. Now, as we see in the image here, a named accumulator in this instance counter will display in web UI for the stage that modifies that accumulator. Spark displays the value for each accumulator modified by a task in the tasks table. Now, tracking accumulators in the UI can be useful for understanding the progress of your running stages. but we should remember that as of now, this is not supported in Python. Might be in future, the support for Python will also be added. Now, when you talk about your accumulators, you can have, say, a numeric accumulator created by calling a Spark context and its method, such as long accumulator, or you could have double accumulator to accumulate values of type long or double respectively. So tasks running on a cluster can then add to it using the add method. Now we cannot, in this case, the value cannot be read, but driver program can read the accumulator's value using its value method. We can look at some examples to understand this later. Now, when you talk about your broadcast variables, that is one more type of variables, which allows the programmers to keep a read-only variable cached on each machine rather than shipping a copy of it with tasks. Now, what we know is sometimes you might be doing very costlier operations like joins, where you might be working on multiple RDDs, they need to be joined, and these RDDs could also be pair RDDs, which could be key value pairs. Now, whenever you're performing a join, there would be kind of two levels of shuffling. One, within a particular RDD. So if you're joining two RDDs, the first RDD, which might have data in the form of key value pairs, that RDD would have to have some shuffling where all the similar keys can be brought into one partition. And this would happen on the second RDD also, which has again key value pairs. And then if you're doing a join, these RDDs will be shipped to the node, or basically the data would be loaded in the memory, and then basically your transformations will happen. This can be a costlier affair. So what can be done is you could create broadcast variables. So for example, if we have two RDDs and we want to perform a join operation, and if one RDD is known to be smaller, then we can create a broadcast variable of the smaller RDD so that this variable itself can be shipped to each machine, and then this variable can be used for your join operations with the other RDD, which is existing in the memory of those nodes. So that saves time and that improves your performance. So Spark basically attempts to distribute the broadcast variable using efficient broadcast algorithms to reduce the communication cost. Now, if, for example, you have multiple nodes in a cluster, and if you would want to give every node a copy of large input data set in an efficient manner, so Spark actions are executed through a set of stages. Now we know that. And stages are separated by your shuffle operations. So whenever we talk about narrow dependencies such as map, flat map, filter, you would not have any shuffling involved. But if you go for group by key, reduce by key, and such operations to bring the similar keys together, there would be shuffling involved. And also this applies when you're doing some join operations. So in that case, broadcast variables could be a really plus, where one set of data or RDD, which is already computed, that could be broadcasted to other nodes. So the data broadcasted will be cached in serialized form and deserialized before running each task. This means that explicitly creating broadcast variables can be useful when tasks across multiple stages need the same data, or when caching the data in deserialized form is important. So we can create broadcast variables using Spark context and its method called broadcast. And your broadcast variable can then be shipped to other nodes, which can be used for your other operations. Now, when you talk about Spark streaming, it is used in various use cases. You could talk about speech recognition, you could talk about sentiment analysis, you could talk about streaming applications which would be performing some kind of analytics on the data which is coming in. It is also used widely in retail chain companies. Now, if we look at the example here, so big retail chain companies would want to build real-time dashboards so that they can keep a track of their inventory and operations. And for this, they would need one, streaming data, or data which is constantly getting generated at source, which needs to be processed on, and this information can then be populating your dashboards to give you a real-time scenario or real-time information of what is happening. So in case of an inventory dashboard, you could use then these interactive dashboards wherein you could draw insights about the business, and that's what retail companies are doing. So how many products are being purchased, or products that have been shipped, or how many products have been delivered to customers, and this kind of information would be good to capture in real time. So when the streaming data is basically being processed. So at one end, you have your data which is getting generated. That might be based on the sales which are happening. That might be based on the products which are being shipped, or that might be based on the acknowledgement that the products have been received. Now, while this data is getting generated at various sources, it can be subjected to a Spark streaming application, which will look into the streaming data, perform series of transformations which you would want to process the data at regular time intervals, and then pushing it to your dashboards or to your storage layer, wherein it could then be used to answer such questions. So when we talk about Spark streaming, it's an ideal choice to process this kind of data in real time, and there are various use cases. So at one end, if you see, you have an input stream which shows the product status. That is how many products were purchased or shipped or delivered. Now this would be then handled by your Spark streaming and also your Spark core engine, which would then process the data to give you an output stream, which gives you a status, such as what was the total count of products which were purchased, products which were shipped, and products which were delivered. So this was a quick and brief introduction to Spark streaming and how it works. Now we can also see how Spark streaming works, or how we create an application. For that, what we can do is we can basically set up our Eclipse to have your Scala based Spark applications. And for that, what you could do is you could have your Eclipse, which can then be having a Scala plugin added to it. Now, if somebody would want to look at the Scala plugin, then you can always go to scala.ide.org, and this is the place where you can scroll towards the bottom. You can click on stable, and that basically also shows you a video how Scala plugin can be added to your Eclipse. It also tells from where you can get the Scala latest release, and this can be added to your Eclipse. So in my case, it has already been added to the Eclipse. I'm bringing it up here, and then you can have your applications built using your IDE. People would prefer to use IntelliJ, and that's also fine. So you could also look for videos on setting up IntelliJ with your Scala plugin. Now there are two ways. One, you can build your application, run it on your Windows machine, wherein you could have some kind of utility like Netcat, which can be used to send in some messages in a streaming fashion. You could have a receiver which looks at a particular socket at a particular port, and you could build a streaming application within your IDE, run it on your Windows machine in a local mode, which would then be looking at your source where the data is getting generated. That's one option. The second option is you could build your application, package it as jar, and then run it on a cluster. Now that could be a Spark standalone cluster or Spark with Yarn, and then you could be packaging your application using tools like SBT, and then use Spark Submit to submit your application. Now I'll show you both the ways in which you can work with streaming applications. So first is get your Eclipse and make sure that Scala plugin is already added. Now in my case, on the right top corner, I see Scala symbol that says I can be using Scala Perspective. Now here I have some projects. So what you can do is you can create a project by saying new Scala project. You can give it a name. So for example, I could say my apps 3, and then you can say finish. So that creates a project. Now within your project, what you can do is you can create a package. So for example, I could say something like main.scala, and then say finish. So that creates your package. Now also one thing to remember is it would be good to change your compiler instead of 2.12 to 2.11. Normally for different environments, you might have Spark with different versions and Scala with 2.10 or 2.11. So it would be good to have the compiler change to the bundle 2.11. So we can select this project. I can do a right click. I can go to the build path. I can say configure build path, and then I can click on Scala compiler where I will use project settings and I will choose to 2.11 bundle. So that would make sure that your applications can compile. Just say OK. It might say the compiler settings have changed. A full rebuild is required for changes to take effect. Just hit on OK. So that's the first thing you need to do. The second thing is, for your code to compile, it would be good to have your jars added to your build path. Now we could do that, or as I said, you could be writing your application which might not compile within your IDE, but you could package it using SBT and then run it as jar. So what I'm doing here is, on my machine within my C drive, I already have Spark distribution which I've downloaded. So basically I have downloaded Spark and then untarred it. So Spark 2.4.3, I have unzipped or untarred it. I have kept it in my C, and this basically has my Spark now, within which I have my jars, and this has all my Spark related jars. So technically speaking, I can even use Windows command line and I can start working on Spark in an interactive way, or packaging my application and running it in a local mode. So you could also do this. So basically have your Spark, and then if you see on my desktop, I have a Hadoop folder within which I have a bin folder, and within which I have a winutils.exe, and this will be basically required when you want to try out your Spark based applications, whether that is streaming or data frames, to be tested on your Windows machine. So you can always search and download the winutils.exe, place it in a Hadoop folder within the bin folder on your machine. So once you get your winutils.exe, once you have your jars, what you can do is, for your project, you can just say right click, you can go to the build path and you can say configure build path, and here you had add external jars. So we can select all of these jars here, which I would want to add to my build path so that my code can compile and I can test it on the Windows machine itself. I can say open and then just basically do apply and OK. So that has created my project with a package. My compiler is changed to 2.11. I have added the external jars, the Spark related jars, and that is good enough for my code. Now what we need is a streaming application which we need to build. So let me show you from my existing project how it looks like. So within your source, the same way I have main package, and here I have a streaming application. So this streaming application is to test or to work on capturing the data which is generated at this particular stream on a particular IP and a particular port, and I would want to do some series of transformations on that. So this gives me an example of doing a word count, and then I would want to print the results. I could also be saving the output in a particular location. So for this application, we need basically to import certain packages, that is, say Spark Streaming, Spark Context, and also you have Spark Conf. So these are the packages which we need to import. Now here I have created an object. I've called this fifth app and I'm saying extends app. And this is because within my project, I already have an application which has been defined as main. So if your application has been defined as main, one application is already existing, then you can just have your new objects with extending app. So we don't need to define the main method here. Now here I'm saying val conf new spark conf. So I'm creating a configuration object. I'm setting my application name, and to test it on Windows, we will have to set the master as local, and it is advisable to give it more than one thread because you would be creating a receiver within your application that would utilize one thread. So here I'm saying set master local, and then I'm saying 2 threads. I'm also creating my Spark context, which we need to initialize based on the configuration object we just created in the previous step. Then we need to create a Spark streaming context, and this streaming context depends on Spark context, and I've given a time interval of 10 seconds. So this is the time interval which I'm setting for which I would want to work on the stream of data which comes in every 10 seconds on a particular socket. Now here we are setting up a receiver. So I say stream RDD, which is basically be Spark streaming context, and then you use your socket text stream. Now there are various methods of Spark streaming context. For example, if I just go here and if I just do a dot, it shows me what are the different options. You have file stream, you have queue stream, you have socket stream, receiver stream, and so on. So I am using socket text stream and I would want to point it to this machine. So I'll say 127.0.0.1. I will also specify port 2222. Okay, and here once I have created my configuration object, my Spark context, my Spark streaming context with a time interval, and I have set my receiver to use the socket text stream method on this particular IP on this particular port. Now then I'm specifying what I would want to do on the data which gets generated on this machine at this particular port. So I'm saying val word counts. So I would want to work on the stream RTD, that is the D stream. I would want to do a flat map on it to split the data based on space. I would want to map every word to word comma 1, and then I would want to do a reduce by key. Now reduce by key, you can pass in specifically the function you would want to do. I could do a count of this, I could print the result, or I could even save it with an output using the Java method to create a random string attached to the output. Once you're done with this, here I'm mentioning Spark streaming context start. Now this will basically trigger my Spark streaming context to start, and it will run till we terminate this application. Now here, to run this on Windows machine, you can always look into your run configuration. And what I have done is in my environment, I basically want to use, let's say, okay, now let's look at the configuration, what you need to set. So here I have my streaming application, and let's look at the run configuration, which basically shows my application has started and it's running on the environment. So if you see here, I have added Hadoop_home pointing to this Hadoop directory which has bin and win utils X. I have also given Spark local IP, which is 127.0.0.1. So that is my run configuration. Now if you see here, my streaming application has started. My streaming application has not yet started. Probably it is running a different application. So we can come back and check this. So we can go to run as Scala application and let's see what it does. So it tries to connect to 127.0.0.1. So receiver is trying to do that, but it does not find anything on that particular machine on that particular port. So my receiver is not able to find, it is not able to establish a connection. Now what I can do is I can go to my command line, and here I will go into downloads. So I've already downloaded the netcat utility for Windows, and here we can basically search for something which I have on my machine within downloads, and that is your netcat utility. So what I would do is I will come back here and I would say nc.exe lvp, and then I could say my port which I have specified in my streaming application, and I can just start this netcat utility. Now here it says listening on 222, it says connection to 127.0.0.1, and then if I look in the background, my receiver will now be able to establish a connection with this netcat utility. Now whatever I type here will be taken for processing every 10 seconds, and we would see a word count while my application is running. So let's test this. So I'll say this is a test is being done, and as soon as I pass in this message, we see that there is a word count happening for the stream of data which is coming in. We can say winters are coming, winters will be cold, and once I given these messages, we will see our streaming application which will try to work on the data which is coming in and process it and show us the result. So we can say this is a test of winters, and let's see if it continues to do the processing and shows us the out, right? So my streaming application is running fine. It is looking at the words which we are passing in, and we can say if it is able to process my data, and every 10 seconds the text socket stream is looking on this machine at this particular port, doing a series of transformations, and these series of transformations and then are seen within your console. Now in my application, if I had used word counts.save as text file, then I could also have my output getting generated at every 10-second interval, and that would get saved here. I could also decide to have my output saved and stored on a HDFS or any other storage. So this is a simple streaming application what we saw, which is using socket text stream. It is looking at this machine on a particular port where we are running a netcat utility. It does series of your RDT transformations, that is flat map, map, and then your reduce by key. And finally, we are invoking an action such as print, which basically triggers these RDTs, which work on my streaming data. So this is one example. Now what I could also be doing is, this is particularly my application. Now I already have SBT for Windows installed. So I can be going into my project space. So I could say workspace. I could go into my apps and I'm in my project folder. So I could say SBT package. And this will basically then, based on my build file, which I already have within my project folder. So if you see here, this is my build file, which says name, the version, Scala version, Spark version, and the repository with the Spark to manage the dependencies for all its components like Spark Core, SQL, MLlib, streaming, and Hive. So you need to have this build.sbt file within your project folder, which can be used to package your application as jar. Now we have done the packaging and it shows me that it has created a jar of my applications within this particular folder. Now once I have this, I can basically then import this package into my cluster where I can run it on a cluster using Spark Submit. Now to run the Spark streaming application on a cluster, here I have a 2-node cluster which will then have my Spark standalone cluster. You could look at the previous videos wherein I explain how to set up a Spark standalone cluster. Now here I can go into the Spark directory and then I could just say sbin start all.sh, which will start my Spark master and worker node. Now I do have Hadoop cluster also set up on this, but right now I'm running a Spark standalone cluster, which shows me I have a master and a worker process on this machine, and I have a worker process on this machine. So my Spark standalone cluster is running. We can always bring up the UI to see how it looks like. So here I can just be giving http://um18080. So that's my Spark standalone cluster with 2 worker nodes. Right now there is no application running. We can come back here and we can check if we have my jar file. So I've already placed my jar here. Now at any point of time, if you have your jar which has been packaged, you can always go and do a jar -xvf and you can choose your jar to see what is within your jar, which I've already done on this machine. So if I look in the main folder, I have Scala, and within Scala, if you see, these are the different classes what we have. So my code was packaged as a jar. It has a 5th app class which we would want to run here. So what I can do is I can just be saying Spark submit, because now I would want my application to run on the cluster. So I can say class main.scala and then my object name. So I will say 5th app. Now that's my class. My jar is this one, and we will also say master, which is going to be Spark, which is running on UM1 and it listens on 7077 port. So that would basically start my streaming application. But what we would also need is, like our Windows, we would also need some utility like netcat. So basically what I can do is I can here use a netcat utility to basically connect or send in some messages for our streaming application. So let's say, let me search if I have already the netcat, which I might have used here. So let's see. So on your Ubuntu machine, you will have to install your netcat utility by saying a apt-get netcat. So here I can say nc minus L, and then I can say port, which is 2222. So we can see if this is working. So this is a test, and let's see if it works. So let's start our application, streaming application, which then needs the receiver to establish a connection with the particular machine, and let's see if that is done. So here I could also be canceling this and give it a particular port. So I can say 192.168.0.18. Now the only problem is when we packaged our application, we should be specifically giving the IP and also comment out the local. So when I package this to run on the cluster, I commented out this part, and I obviously would not be giving 127 but the IP where my netcat is running. So right now let's test it. So we will say this is a test, new test for our application, and I'm sending in some messages. So it is already doing the word count as we expected it to do. And if while we are doing it, if you come back here, so you would see your application is now running on the cluster. So it is my application. It is using 4 cores. What is the memory per executor? And you can basically click on your application. Now here you can look at the application detail UI to see what is being done. So for our application, we have a streaming job running receiver, which says this is my application. It says it is running. You can basically click on this, and it says your DAG visualization, which will say the streaming job which is running. You can look at the stages if you would want to see if there are multiple stages, which we don't have because we are not doing any wider transformation. We can look at storage if we have used some persisting or caching. We can look at the executors which are being used. And one of the important things when you talk about your streaming is the streaming tab which gets activated. Now that does not show up when you run your batch applications, but in your streaming applications you have the UI shows you the streaming tab, and that basically says running batches of 10 seconds for 2 minutes 9 seconds already. Now we see the input rate, we see the receivers, we see if there is any delay in scheduling, what is the processing time, how many batches it has completed, and it basically shows me what is the processing time, how many tasks were run, and so on. So my application is running fine, and unless and until we go ahead and cancel this, my application will continue to run. It will keep looking for messages which we keep typing in. So for example, if I would want to just copy this and start again, where I would keep passing in, this is a test 1 is this, where we test streaming application, right? And I can be seeing that my messages are being processed. I'm getting a word count. So we can say winter, summer, old, winter, and you can always look at if your streaming application is doing the word count. So this is a simple way where you can run your streaming application either on a Windows machine in a local mode, or you could be running on a Spark standalone cluster, or you could also deploy your application to run on a yarn-based cluster. Now that we have seen a streaming application which does a word count, it will be interesting to also see the window-based computation or windowing operation which is supported in Spark Streaming, as I explained. And for that, we can look at a different application here which is streaming with a window option. Let's look into this, what this application does. So here I'm importing some packages that is streaming context, your Spark and Spark context, Spark configuration. I'm also using the Spark API Java function. I'm then using Spark Streaming API, and I'm also using storage level because I also intend to have the persistence or caching done. Now here we create an application, say streaming app, extends app. We create our configuration object where we say app name, and then we set master with appropriate number of threads. We create the Spark streaming context, that's we initialize it, and then we have the Spark streaming context which depends on SC, and we have given a time interval of 10 seconds. We then set up a receiver, so we say stream RDD, which will use socket text stream like we did earlier, which will look for this particular machine at this port, wherein I'm also using storage level. So what I would want is that the data stream which would get generated here every 10 seconds should be cached in memory. Now we could use different storage levels. That is, we could use memory only, disk only, memory and disk. You could have memory and disk with replication factor. So you have different storage levels. Now here we are then doing some series of transformations like what we did earlier. But if you see in my previous example, we just had reduce by key, and here I'm using a transformation which is reduce by key and window. Now this one basically takes the function. As I said, the windowing takes associative or commutative functions. So instead of using the shortcut way, we will be specifying our function. So we say it takes A and B, and basically it uses this function. Now here we have to give the interval, that is 30 seconds. That's my window time frame. And then within that, what will be my each interval which we would want to look at. So these are the two main aspects. One is using your window based transformation, and then also specifying your time interval for your windowing, which basically means we would still do a word count, but then here we would basically not only be doing a word count for every 10 seconds for the data which is coming in here, but we would also want to have a consolidated set of computation done every 30 seconds. So that is looking at the last 3 time intervals. Now, if you also notice, I'm also doing a check pointing here, wherein I have not specified a specific directory, but what I'm saying here is I would want to checkpoint, or I would want to basically save my computations for any kind of fault recovery. Now, this is a streaming application with window-based computation. We are using storage level for persistence. We are also doing the checkpointing, which takes care of fault recovery. Now, to run this application, we have already set our environment variables and so on. So I can basically start this application by just doing a run as Scala application. Now, this would start my streaming application with window-based computations. Now we can open up our command line where we would want to start a netcat utility. So I could go to downloads. Let me just minimize this window here. And what I can do is I can then be starting my netcat utility. So I could say nc.exe minus lvp and on a port 222. As soon as I do this in background, my application receiver will be able to establish connection to this netcat utility running on this particular port. Now that's done. So we can see if the word count happens for our 10-second interval. So let's do that. So I'll say this is my first test, and if I do this, it should give me the word count for the data which I have passed in. Now I can say this is my second test, this is my third test, and if you see here, it basically is doing this. Now if I say this is my first test again, so since we are doing window based operation also, we will see a consolidated set of transformations which happen for a window of 3 intervals. So if you see here, now my this is giving me a count, but it is not showing me totally this as 4 or say this, because it is only looking at a window of last 2 or 3 time intervals. So now it is back because it is looking at the last one. So if I say this is my test, test is done, test is done. So if you do this, it will show you the word count which is for whatever you have passed in, like test is done is twice, test is thrice. But then since windowing based operation is done, you will look at the time interval of the messages which were passed within that particular window. Now we can also, since my application is running and it is on Windows, we can bring up your Spark UI. So I can go to http and / I can be looking at my machine and the port. So for example, I could do this. This shows my streaming application which is running in, wherein I can see the window-based application which is running. But what would be interesting is to look at the stages. If there is any kind of shuffling which is happening, looking at the storage should show me the persistence which we are doing. Now if you see here, it shows me that we have been persisting in the memory, what size it occupies, how many partitions were cached, used, and this is because of the persistence or the storage level what we have used as memory only. Now if we change that to disk, we will see our RDDs will be cached on disk. And then you can look at your streaming tab, which gives you more information about your batches. So this is a very simple example. Obviously you can change what kind of RDD computations you would want to do here, whether you want to do a word count or something else, whether you want to save your processed output. Now here we are able to do that. You can always do a refresh on your project, and here what we see is we see some entries of a folder getting created, right? And we can decide whether we would want our output to be created. We can also see within this what would be containing, and since we have set checkpointing in the project folder, it would also be checkpointing temporarily the information for any kind of failure. So this is a classic example of streaming application using window-based computations, persisting your computations, and also doing the checkpointing simultaneously. In this tutorial,
here we have some list of questions and an explanation of those so that you can be well prepared for your Hadoop interviews. Now let's look at some general Hadoop questions. So what are the different vendor specific distributions of Hadoop? Now all of you might be aware that Hadoop or Apache Hadoop is the core distribution of Hadoop. And then you have different vendors in the market which have packaged the Apache Hadoop in a cluster management solution which allows everyone to easily deploy, manage, monitor, upgrade your clusters. So here are some vendor specific distributions. We have Cloudera, which is the dominant one in the market. We have Hortonworks, and now you might be aware that Cloudera and Hortonworks have merged. So it has become a bigger entity. You have Mapr, you have Microsoft Azure, IBM's InfoSphere, and Amazon Web Services. So these are some popularly known vendor specific distributions. If you would want to know more about the Hadoop distributions, you should basically look into Google and you should check for Hadoop different distributions wiki page. So if I type Hadoop different distributions and then I check for the wiki page, that will take me to the distributions and commercial support page, and this basically says that the sole products that can be called a release of Apache Hadoop come from apache.org. So that's your open source community. And then you have various vendor specific distributions which basically are running in one or the other way Apache Hadoop, but they have packaged it as a solution like an installer so that you can easily set up clusters on set of machines. So have a look at this page and read through about different distributions of Hadoop. Coming back, let's look at our next question. So what are the different Hadoop configuration files? Now, whether you're talking about Apache Hadoop, Cloudera, Hortonworks, Mapr, or no matter which other distribution, these config files are the most important and existing in every distribution of Hadoop. So you have Hadoop environment.sh, wherein you will have environment variables such as your Java path, what would be your process ID path, where will your logs get stored, what kind of metrics will be collected, and so on. Your core-site file has the HDFS path. Now this has many other properties like enabling thrash or enabling high availability or discussing or mentioning about your zookeeper. But this is one of the most important file. You have HDFS-site file. Now this file will have other information related to your Hadoop cluster, such as your replication factor, where will name node store its metadata on disk. If a data node is running, where would data node store its data? If a secondary name node is running, where would that store a copy of name node's metadata? And so on. Your Mapred-site file is a file which will have properties related to your Mapreduce processing. You also have masters and slaves. Now these might be deprecated in a vendor specific distribution, and in fact you would have a yarn-site file which is based on the yarn processing framework which was introduced in Hadoop version 2, and this would have all your resource allocation and resource manager and node manager related properties. Again, if you would want to look at default properties for any one of these, for example, let's say HDFS-site file, I could just go to Google and type in
one of the properties. For example, I would say dfs.nameNode.name.directory, and as I know this property belongs to HDFS-site file, and if you search for this, it will take you to the first link which says HDFS default XML. You can click on this and this will show you all the properties which can be given in your HDFS-site file. It also shows you which version you are looking at, and you can always change the version here. So for example, if I would want to look at 2.6.5, I just need to change the version and that should show me the properties. Similarly, you can just give a property which belongs to, say, core-site file. For example, I would say fs.defaultfs, and that's a property which is in core-site file, and somewhere here you would see core-default.xml, and this will show you all the properties. So similarly, you could search for properties which are related to yarn-site file or Mapred-site file. So I could say yarn.resource manager, and I could look at one of these properties which will directly take me to yarn default XML, and I can see all the properties which can be given in yarn. And similarly, you could say Mapreduce.job.reduces, and I know this property belongs to Mapreduce-site file, and this takes you to the default XML. So these are important config files, and no matter which distribution of Hadoop you're working on, you should be knowing about these config files. Whether you work as a Hadoop admin or you work as a Hadoop developer, knowing these config properties would be very important, and that would also showcase your internal knowledge about the configs which drive your Hadoop cluster. Let's look at the next question. So what are the three modes in which Hadoop can run? So you can have Hadoop running in a standalone mode. Now that's your default mode. It would basically use a local file system and a single Java process. So when you say standalone mode, it is as you downloading Hadoop related package on one single machine, but you would not have any process running. That would just be to test Hadoop functionalities. You could have a pseudo distributed mode, which basically means it's a single node Hadoop deployment. Now Hadoop as a framework has many services. So it has a lot of services, and those services would be running irrespective of your distribution, and each service would then have multiple processes. So your pseudo distributed mode is a mode of cluster where you would have all the important processes belonging to one or multiple services running on a single node. If you would want to work on a pseudo distributed mode and using a Cloudera, you can always go to Google and search for Cloudera's Quick Start VM. You can download it by just saying Cloudera Quick Start VM, and you can search for this, and that will allow you to download a Quick Start VM, follow the instructions, and you can have a single node Cloudera cluster running on your virtual machines. For more information, you can refer to the YouTube tutorial where I have explained about how to set up a Quick Start VM. Coming back, you could have finally a production setup or a fully distributed mode, which basically means that your Hadoop framework and its components would be spread across multiple machines. So you would have multiple services such as HDFS, Yarn, Flume, Sqoop, Kafka, HBase, Hive, Impala, and for these services there would be one or multiple processes distributed across multiple nodes. So this is normally what is used in production environment. So you could say standalone would be good for testing, pseudo distributed could be good for testing and development, and fully distributed would be mainly for your production setup. Now, what are the differences between regular file system and HDFS? So when you say regular file system, you could be talking about a Linux file system, or you could be talking about a Windows-based operating system. So in regular file system, we would have data maintained in a single system. So the single system is where you have all your files and directories. So it is having low fault tolerance, right? So if the machine crashes, your data recovery would be very difficult unless and until you have a backup of that data. That also affects your processing. So if the machine crashes or if the machine fails, then your processing would be blocked. Now, the biggest challenge with regular file system is the seek time, the time taken to read the data. So you might have one single machine with huge amount of disks, and huge amount of RAM. But then the time taken to read that data when all the data is stored in one machine would be very high, and that would be with least fault tolerance. If you talk about HDFS, your data is distributed. So HDFS stands for Hadoop Distributed File System. So here your data is distributed and maintained on multiple systems. So it is never one single machine. It is also supporting reliability. So whatever is stored in HDFS, say a file being stored, depending on its size, is split into blocks, and those blocks will be spread across multiple nodes. Not only that, every block which is stored on a node will have its replicas stored on other nodes. Replication factor depends, but this makes HDFS more reliable. In cases of your slave nodes or data nodes crashing, you will rarely have data loss because of auto replication feature. Now, time taken to read the data is comparatively more, as you might have situations where your data is distributed across the nodes, and even if you are doing a parallel read, your data read might take more time because it needs coordination from multiple machines. However, if you are working with huge data which is getting stored, it will still be beneficial in comparison to reading from a single machine. So you should always think about its reliability through auto replication feature, its fault tolerance because of your data getting stored across multiple machines, and its capability to scale. So when you talk about HDFS, we are talking about horizontal scalability or scaling out. When you talk about regular file system, you are talking about vertical scalability, which is scaling up. Now, let's look at some specific HDFS questions. What is this? Why is HDFS fault tolerant? Now, as I just explained in previous slides, your HDFS is fault tolerant as it replicates data on different data nodes. So you have a master node and you have multiple slave nodes or data nodes where actually the data is getting stored. Now, we also have a default block size of 128 MB. That's the minimum since Hadoop version 2. So any file which is up to 128 MB would be using one logical block. And if the file size is bigger than 128 MB, then it will be split into blocks, and those blocks will be stored across multiple machines. Now, since these blocks are stored across multiple machines, it makes it more fault tolerant because even if your machines fail, you would still have a copy of your block existing on some other machine. Now, there are two aspects here. One, we talk about the first rule of replication, which basically means you will never have two identical blocks sitting on the same machine. And the second rule of replication is in terms of rack awareness. So if your machines are placed in racks, as we see in the right image, you will never have all the replicas placed on the same rack, even if they are on different machines. So it has to be fault tolerant and it has to maintain redundancy. So at least one replica will be placed on some other node on some other rack. That's how HDFS is fault tolerant. Now, here let's understand the architecture of HDFS. Now, as I mentioned earlier, you would in a Hadoop cluster, the main service is your HDFS. So for your HDFS service, you would have a name node, which is your master process running on one of the machines, and you would have data nodes, which are your slave machines getting stored across or the processes running across multiple machines. Each one of these processes has an important role to play. When you talk about HDFS, whatever data is written to HDFS, that data is split into blocks depending on its size, and the blocks are randomly distributed across nodes. With auto replication feature, these blocks are also auto replicated across multiple machines, with the first condition that no two identical blocks will sit on the same machine. Now, as soon as the cluster comes up, your data nodes, which are part of the cluster and based on config files, would start sending their heartbeat to the name node. And this would be every 3 seconds. What does name node do with that? Name node will store this information in its RAM. So name node starts building a metadata in its RAM, and that metadata has information of what are the data nodes which are available in the beginning. Now, when a data writing activity starts and the blocks are distributed across data nodes every 10 seconds will also send a block report to name node. So name node is again adding up this information in its RAM or the metadata in RAM, which earlier had only data node information. Now name node will also have information about what are the files. The files are split in which blocks, the blocks are stored on which machines, and what are the file permissions. Now, while name node is maintaining this metadata in RAM, name node is also maintaining metadata in disk. Now, that is what we see in the red box, which basically has information of whatever information was written to HDFS. So to summarize, your name node has metadata in RAM and metadata in disk. Your data nodes are the machines where your blocks or data is actually getting stored. And then there is a auto replication feature which is always existing unless and until you have disabled it. And your read and write activity is a parallel activity. However, replication is a sequential activity. Now, this is what I mentioned about when you talk about name node, which is the master process hosting metadata in disk and RAM. So when we talk about disk, it basically has a edit log, which is your transaction log, and your FS image, which is your file system image. Right from the time the cluster was started, this metadata in disk was existing, and this gets appended every time read, write, or any other operations happen on HDFS. Metadata in RAM is dynamically built every time the cluster comes up, which basically means that if your cluster is coming up, name node in the initial few seconds or few minutes would be in a safe mode, which basically means it is busy registering the information from data nodes. So name node is one of the most critical processes. If name node is down and if all other processes are running, you will not be able to access the cluster. Name node's metadata in disk is very important for name node to come up and maintain the cluster. Name node's metadata in RAM is basically for all or satisfying all your client requests. Now when we look at data nodes, as I mentioned, data nodes hold the actual data blocks and they are sending these block reports every 10 seconds. So the metadata in name node's RAM is constantly getting updated, and metadata in disk is also constantly getting updated based on any kind of write activity happening on the cluster. Now data node, which is storing the block, will also help in any kind of read activity whenever a client requests. So whenever a client or an application or an API would want to read the data, it would first talk to name node. Name node would look into its metadata on RAM and confirm to the client which machines could be reached to get to that data. That's where your client would try to read the data from HDFS, which is actually getting the data from data nodes. And that's how your read-write requests are satisfied. Now, what are the two types of metadata in name node server holds? As I mentioned earlier, metadata in disk, very important to remember, edit log and FS image. Metadata in RAM, which is information about your data nodes, files being split into blocks residing on data nodes, and file permissions. So I will share a very good link on this, and you can always look for more detailed information about your metadata. So you can search for HDFS metadata directories explained. Now this is from Hortonworks. However, it talks about the metadata in disk, which name node manages, and details about this. So have a look at this link if you are more interested in learning about metadata on disk. Coming back, let's look at the next question. What is the difference between federation and high availability? Now these are the features which were introduced in Hadoop version 2. Both of these features are about horizontal scalability of name node. So prior to version 2, the only possibility was that you could have one single master, which basically means that your cluster could become unavailable if name node would crash. So Hadoop version 2 introduced two new features, federation and high availability. However, high availability is a popular one. So when you talk about federation, it basically means any number of name nodes. So there is no limitation to the number of name nodes. Your name nodes are in a federated cluster, which basically means name nodes still belong to the same cluster, but they are not coordinating with each other. So whenever a write request comes in, one of the name node picks up that request and it guides that request for the blocks to be written on data nodes. But for this, your name node does not have to coordinate with other name node to find out if the block ID which was being assigned was the same one as assigned by other name node. So all of them belong to a federated cluster. They are linked via a cluster ID. So whenever an application or an API is trying to talk to cluster, it is always going via an cluster ID, and one of the name node would pick up the read activity or write activity or processing activity. So all the name nodes are sharing a pool of metadata in which each name node will have its own dedicated pool. And we can remember that by a term called namespace or name service. So this also provides high fault tolerance. Suppose your one name node goes down, it will not affect or make your cluster unavailable. You will still have your cluster reachable because there are other name nodes running and they are available. Now when it comes to heartbeats, all your data nodes are sending their heartbeats to all the name nodes, and all the name nodes are aware of all the data nodes. When you talk about high availability, this is where you would only have two name nodes. So you would have an active and you would have a standby. Now normally in any environment you would see a high availability setup with Zookeeper. So Zookeeper is a centralized coordination service. So when you talk about your active and standby name nodes, election of a name node to be made as active and taking care of an automatic failover is done by your Zookeeper. High availability can be set up without Zookeeper, but that would mean that an admin's intervention would be required to make a name node as active from standby or also to take care of failover. Now at any point of time in high availability, a active name node would be taking care of storing the edits about whatever updates are happening on HDFS, and it is also writing these edits to a shared location. Standby name node is the one which is constantly looking for these latest updates and applying to its metadata, which is actually a copy of whatever your active name node has. So in this way, your standby name node is always in sync with the active name node, and if for any reason active name node fails, your standby name node will take over and become the active. Remember, Zookeeper plays a very important role here. It's a centralized coordination service. One more thing to remember here is that in your high availability, secondary name node will not be allowed. So you would have an active name node and then you will have a standby name node which will be configured on a separate machine, and both of these will be having access to a shared location. Now that shared location could be NFS or it could be a quorum of journal nodes. So for more information, refer to the tutorial where I have explained about HDFS, high availability and federation. Now let's look at some logical question here. So if you have an input file of 350 MB, which is obviously bigger than 128 MB, how many input splits would be created by HDFS? And what would be the size of each input split? So for this, you need to remember that by default, the minimum block size is 128 MB. Now that's customizable. If your environment has more number of larger files written on an average, then obviously you have to go for a bigger block size. If your environment has a lot of files being written, but these files are of smaller size, you could be okay with 128 MB. Remember, in Hadoop, every entity, that is your directory on HDFS, file on HDFS, and a file having multiple blocks, each of these are considered as objects. And for each object, Hadoop's name node's RAM, 150 bytes is utilized. So if your block size is very small, then you would have more number of blocks, which would directly affect the name node's RAM. If you keep a block size very high, that will reduce the number of blocks. But remember, that might affect in processing, because processing also depends on splits. More number of splits, more the parallel processing. So setting of block size has to be done with consideration about your parallelism requirement and your name node's RAM which is available. Now coming to the question, if you have a file of 350 MB, that would be split into 3 blocks, and here 2 blocks would have 128 MB data and the third block although the block size would still be 128, it would have only 94 MB of data. So this would be the split of this particular file. Now let's understand about rack awareness. How does rack awareness work? Or why do we even have racks? So organizations always would want to place their nodes or machines in a systematic way. There can be different approaches. You could have a rack which would have machines running on the master processes, and the intention would be that this particular rack could have higher bandwidth, more cooling, dedicated power supply, top of rack switch, and so on. The second approach could be that you could have one master process running on one machine of every rack, and then you could have other slave processes running. Now, when you talk about your rack awareness, one thing to understand is that if your machines are placed within racks, and we are aware that Hadoop follows auto-replication, the rule of replication in a rack-aware cluster would be that you would never have all the replicas placed on the same rack. So if we look at this, if we have block A in blue color, you will never have all the 3 blue boxes in the same rack, even if they are on different nodes, because that makes it less fault tolerant. So you would have at least one copy of block which would be stored on a different rack on a different node. Now let's look at this. So basically here we are talking about replicas being placed in such a way. Now somebody could ask a question, can I have my block and its replicas spread across 3 racks? And yes, you can do that, but then in order to make it more redundant, you are increasing your bandwidth requirement. So the better approach would be 2 blocks on the same rack on different machines and 1 copy on a different rack. Now let's proceed. How can you restart name node and all daemons in Hadoop? So if you were working on an Apache Hadoop cluster, then you could be doing a start and stop using Hadoop daemon scripts. So there are these Hadoop daemon scripts which would be used to start and stop your Hadoop. And this is when you talk about your Apache Hadoop. So let's look at one particular file which I would like to show you more information here. And this talks about your different clusters. So let's look into this. And so let's look at the start and stop. And here I have a file. Let's look at this one. And this gives you highlights. So if you talk about Apache Hadoop, this is how the setup would be done. So you would have it download the Hadoop tar file, you would have to untar it, edit the config files, you would have to do formatting, and then start your cluster. And here I have said using scripts. So this is in case of Apache Hadoop, you could be using a start all script that internally triggers start DFS and start yarn. And these scripts, start DFS, internally would run Hadoop daemon multiple times based on your configs to start your different processes. Then your start yarn would run yarn daemon script to start your processing related processes. So this is how it happens in Apache Hadoop. Now in case of Cloudera or Hortonworks, which is basically a vendor specific distribution, you would have say multiple services which would have one or multiple daemons running across the machines. Let's take an example here that you would have machine 1, machine 2 and machine 3 with your processes spread across. However, in case of Cloudera and Hortonworks, these are cluster management solutions. So you would never be involved in running a script individually to start and stop your processes. In fact, in case of Cloudera, you would have a Cloudera SCM server running on one of the machines and then Cloudera SCM agents running on every machine. If you talk about Hortonworks, you would have Ambari server and Ambari agent running. So your agents which are running on every machine are responsible to monitor the processes, send also their heartbeat to the master, that is your server, and your server is the one or a service which basically will give instructions to the agents. So in case of vendor specific distribution, your start and stop of processes is automatically taken care by these underlying services. And these services internally are still running these commands. However, only in Apache Hadoop you have to manually follow these to start and stop. Coming back, we can look into
some command related questions. So which command will help you find the status of blocks and file system health? So you can always go for a file system check command. Now that can show you the files for a particular HDFS path. It can show you the blocks, and it can also give you information on status such as under replicated blocks, over replicated blocks, misreplicated blocks, default replication, and so on. So your FSCK file system check utility does not repair if there is any problem with the blocks, but it can give you information of blocks related to the files, on which machines they are stored, if they are replicated as per the replication factor, or if there is any problem with any particular replica. Now, what would happen if you store too many small files in a cluster? And this relates to the block information which I gave some time back. So remember, Hadoop is coded in Java. So here every directory, every file and file related block is considered as an object. And for every object within your Hadoop cluster, name node's RAM gets utilized. So more number of blocks you have, more would be usage of name node's RAM. And if you're storing too many small files, it would not affect your disk. It would directly affect your name node's RAM. That's why in production clusters, admin guys or infrastructure specialists will take care that everyone who is writing data to HDFS follows a quota system, so that you could be controlled in the amount of data you write plus the count of data an individual writes on HDFS. Now, how do you copy data from local system onto HDFS? So you can use a put command or a copy from local, and then given your local path, which is your source, and then your destination, which is your HDFS path. Remember, you can always do a copy from local using a -f option. That's a flag option, and that also helps you in writing the same file or a new file to HDFS. So with your -f, you have a chance of overwriting or rewriting the data which is existing on HDFS. So copy from local or -put, both of them do the same thing, and you can also pass an argument when you're copying to control your replication or other aspects of your file. Now, when do you use DFS admin refresh nodes or RM admin refresh nodes? So as the command says, this is basically to do with refreshing the node information. So your refresh nodes is mainly used when, say, a commissioning or decommissioning of nodes is done. So when a node is added into the cluster, or when a node is removed from the cluster, you are actually informing Hadoop master that this particular node would not be used for storage and would not be used for processing. Now in that case, you would be, once you are done with the process of commissioning or decommissioning, you would be giving these commands, that is refresh nodes and RM admin refresh nodes. So internally, when you talk about commissioning, decommissioning, there are include and exclude files which are updated. And these include and exclude files will have entry of machines which are being added to the cluster or machines which are being removed from the cluster. And while this is being done, the cluster is still running. So you do not have to restart your master process. However, you can just use these refresh commands to take care of your commissioning, decommissioning activities. Now, is there any way to change replication of files on HDFS after they are already written? And the answer is, of course, yes. So if you would want to set a replication factor at a cluster level, and if you have admin access, then you could edit your HDFS-site file, or you could say Hadoop-site file. And that would take care of replication factor being set at a cluster level. However, if you would want to change the replication after the data has been written, you could always use a setrep command. So setrep command is basically to change the replication after the data is written. You could also write the data with a different replication, and for that you could use a -d dfs.replication and give your replication factor when you are writing data to the cluster. So in Hadoop, you can let your data be replicated as per the property set in the config file. You could write the data with a different replication.
You could change the replication after the data is written. So all these options are available. Now, who takes care of replication consistency in a Hadoop cluster? And what do you mean by under, over replicated blocks? Now, as I mentioned, your fsck command can give you information of over or under replicated blocks. Now, in a cluster, it is always and always name node which takes care of replication consistency. So for example, if you have set up a replication of 3, and since we know the first rule of replication, which basically means that you cannot have 2 replicas residing on the same node, it would mean that if your replication is 3, we would need at least 3 data nodes available. Now say for example, you had a cluster with 3 nodes and replication was set to 3. At one point of time, one of your name node crashed. And if that happens, your blocks would be under replicated. That means there was a replication factor set, but now your blocks are not replicated, or there are not enough replicas as per the replication factor set. This is not a problem. Your master process or name node will wait for some time before it will start the replication of data again. So if a data node is not responding, or if a disk has crashed, and if name node does not get information of a replica, name node will wait for some time and then it will start re-replication of those missing blocks from the available nodes. However, while name node is doing it, the blocks are in under replicated situation. Now when you talk about over replicated, this is a situation where name node realizes that there are extra copies of block. Now this might be the case that you had 3 nodes running with a replication of 3. One of the node went down due to a network failure or some other issue. Within few minutes, name node re-replicated the data, and then the failed node is back with its set of blocks. Again, name node is smart enough to understand that this is a over replication situation, and it will delete set of blocks from one of the nodes. It might be the node which has been recently added, it might be your old node which has joined your cluster again, or any node. That depends on the load on a particular node. Now, we discussed about Hadoop, we discussed about HDFS. Now we will discuss about Mapreduce, which is the programming model, and you can say processing framework. What is distributed cache in Mapreduce? Now we know that when we talk about Mapreduce, the data which has to be processed might be existing on multiple nodes. So when you would have your Mapreduce program running, it would basically read the data from the underlying disks. Now this could be a costly operation if every time the data has to be read from disk. So distributed cache is a mechanism wherein data set or data which is coming from the disk can be cached and available for all worker nodes. Now how will this benefit? So when a Mapreduce is running, instead of every time reading the data from disk, it would pick up the data from distributed cache, and this will benefit your Mapreduce processing. So distributed cache can be set in your job conf, where you can specify that a file should be picked up from distributed cache. Now let's understand about these roles. So what is a record reader, what is a combiner, what is a partitioner, and what kind of roles do they play in a Mapreduce processing paradigm or Mapreduce operation. So record reader communicates with the input split, and it basically converts the data into key value pairs. And these key value pairs are the ones which will be worked upon by the mapper. Your combiner is an optional phase. It's like a mini reduce. So combiner does not have its own class. It relies on the reducer class. Basically, your combiner would receive the data from your map tasks which would have completed, works on it based on whatever reducer class mentions, and then passes its output to the reducer phase. Partitioner is basically a phase which decides how many reduce tasks would be used, aggregate or summarize your data. So partitioner is a phase which would decide based on the number of keys, based on the number of map tasks. Your partitioner would decide if one or multiple reduced tasks would be used to take care of processing. So either it could be partitioner, which decides on how many reduced tasks would run, or it could be based on the properties which we have set within the cluster, which will take care of the number of reduced tasks which would be used. Always remember, your partitioner decides how outputs from combiner are sent to reducer and to how many reducers. It controls the partitioning of keys of your intermediate map outputs. So map phase, whatever output it generates, is an intermediate output, and that has to be taken by your partitioner or by a combiner and then partitioner to be sent to one or multiple reduced tasks. This is one of the common questions which you might face. Why is Mapreduce slower in processing? So we know Mapreduce goes for parallel processing. We know we can have multiple map tasks running on multiple nodes at the same time. We also know that multiple reduced tasks could be running. Now, why does then Mapreduce become a slower approach? First of all, your Mapreduce is a batch oriented operation. Now, Mapreduce is very rigid and it strictly uses mapping and reducing phases. So no matter what kind of processing you would want to do, you would have to still provide the mapper function and the reducer function to work on data. Not only this, whenever your map phase completes, the output of your map phase, which is an intermittent output, would be written to HDFS and thereafter underlying disks. And this data would then be shuffled and sorted and picked up for reducing phase. So every time your data being written to HDFS and retrieved from HDFS makes Mapreduce a slower approach. The question is, for a Mapreduce job, is it possible to change the number of mappers to be created? Now, by default, you cannot change the number of map tasks because number of map tasks depends on the input splits. However, there are different ways in which you can either set a property to have more number of map tasks which can be used, or you can customize your code or make it use a different format which can then control the number of map tasks. By default, number of map tasks are equal to the number of splits of file you are processing. So if you have a 1 GB of file that is split into 8 blocks of 128 MB, there would be 8 map tasks running on the cluster. These map tasks are basically running your mapper function. If you have hard-coded properties in your mapred-site file to specify more number of map tasks, then you could control the number of map tasks. Let's also talk about some data types. So when you prepare for Hadoop, when you want to get into big data field, you should start learning about different data formats. Now there are different data formats such as Avro, Parquet, you have sequence file or binary format, and these are different formats which are used. Now when you talk about your data types in Hadoop, these are implementation of your writable and writable comparable interfaces. So for every data type in Java, you have a equivalent in Hadoop. So int in Java would be int writable in Hadoop, float would be float writable, long would be long writable, double writable, boolean writable, array writable, map writable, and object writable. So these are your different data types that could be used within your Mapreduce program. And these are implementation of writable and writable comparable interfaces. What is speculative execution? Now imagine you have a cluster which has huge number of nodes and your data is spread across multiple slave machines or multiple nodes. Now at a point of time, due to a disk degrade or network issues or machine heating up or more load being on a particular node, there can be a situation where your data node will execute task in a slower manner. Now in this case, if speculative execution is turned on, there would be a shadow task or another similar task running on some other node for the same processing. So whichever task finishes first will be accepted and the other task would be killed. So speculative execution could be good if you are working in an intensive workload kind of environment, where if a particular node is slower, you could benefit from a unoccupied or a node which has less load to take care of your processing. Going further, this is how we can understand. So node A, which might be having a slower task, you would have a scheduler which is maintaining or having knowledge of what are the resources available. So if speculative execution as a property is turned on, then the task which was running slow, a copy of that task, or you can say a shadow task, would run on some other node, and whichever task completes first will be considered. This is what happens in your speculative execution. Now, how is identity mapper different from chain mapper? Now, this is where we are getting deeper into Mapreduce concepts. So when you talk about mapper, identity mapper is the default mapper which is chosen when no mapper is specified in Mapreduce driver class. So for every Mapreduce program, you would have a map class which is taking care of your mapping phase, which basically has a mapper function and which would run one or multiple map tasks, right? Your program would also have a reduce class, which would be running a reducer function, which takes care of reduce tasks running on multiple nodes. Now, if a mapper is not specified within your driver class, so driver class is something which has all information about your flow. What's your map class? What is your reduce class? What's your input format? What's your output format? What are the job configurations and so on? So identity mapper is the default mapper which is chosen when no mapper class is mentioned in your driver class. It basically implements an identity function which directly writes all its key pairs into output. And it was defined in old Mapreduce API in this particular package. But when you talk about chaining mappers or chain mapper, this is basically a class to run multiple mappers in a single map task. Or basically you could say multiple map tasks would run as a part of your processing. The output of first mapper would become as an input to second mapper and so on. And this can be defined in the undermentioned class or package. What are the major configuration parameters required in a Mapreduce program? Obviously, we need to have the input location. We need to have the output location. So input location is where the files will be picked up from, and this would preferably on HDFS directory. Output location is the path where your job output would be written by your Mapreduce program. You also need to specify input and output formats. If you don't specify, the defaults are considered. Then we need to also have the classes which have your map and reduce functions. And if you intend to run the code on a cluster, you need to package your class in a jar file, export it to your cluster, and then this jar file would have your mapper, reducer, and driver classes. So these are important configuration parameters which you need to consider for a Mapreduce program. Now, what is the difference, or what do you mean by map side join and reduce side join? Map side join is basically when the join is performed at the mapping level or at the mapping phase, or is performed by the mapper. So each input data which is being worked upon has to be divided into same number of partitions. Input to each map is in the form of a structured partition and is in sorted order. So map side join, you can understand it in a simpler way that if you compare it with RDBMS concepts where you had two tables which were being joined, it will always be advisable to give your bigger table as the left side table or the first table for your join condition, and it would be your smaller table on the left side and your bigger table on the right side, which basically means the smaller table could be loaded in memory and could be used for joining. So map side join is a similar kind of mechanism where input data is divided into same number of partitions. When you talk about reduce side join, here the join is performed by the reducer. So it is easier to implement than map side join, as all the sorting and shuffling will send the values or send all the values having identical keys to the same reducer. So you don't need to have your data set in a structured form. So look into your map side join or reduce side join and other joins just to understand how Mapreduce works. However, I would suggest not to focus more on this because Mapreduce is still being used for processing, but the amount of Mapreduce based processing has decreased overall or across the industry. Now, what is the role of output committer class in a Mapreduce job? So output committer, as the name says, describes the commit of task output for a Mapreduce job. So we could have this as mentioned: org Apache Hadoop Mapreduce output committer. You could have a class which extends your output committer class. So Mapreduce relies on this. Mapreduce relies on the output committer of the job to set up the job initialization, cleaning up the job after the job completion. That means all the resources which were being used by a particular job, setting up the task temporary output, checking whether a task needs a commit, committing the task output, and discarding the task out. So this is a very important class and can be used within your Mapreduce job. What is the process of spilling in Mapreduce? What does that mean? So spilling is basically a process of copying the data from memory buffer to disk when obviously the buffer usage reaches a certain threshold. So if there is not enough memory in your buffer, in your memory, then the content which is stored in buffer or memory has to be flushed out. So by default, a background thread starts spilling the content from memory to disk after 80% of buffer size is filled. Now, when is the buffer being used? So when your Mapreduce processing is happening, the data is being read from the disk, loaded into the buffer, and then some processing happens. Same thing also happens when you are writing data to the cluster. So you can imagine for a 100 megabyte size buffer, the spilling will start after the content of buffer reaches 80 megabytes. This is customizable. How can you set the mappers and reducers for a Mapreduce job? So these are the properties. So number of mappers and reducers, as I mentioned earlier, can be customized. So by default, your number of map tasks depends on the split, and number of reduced tasks depends on the partitioning phase, which decides number of reduced tasks which would be used depending on the keys. However, we can set these properties either in the config files or provide them on the command line, or also make them part of our code, and this can control the number of map tasks or reduced tasks which would be run for a particular job. Let's look at one more interesting question. What happens when a node running a map task fails before sending the output to the reducer? So there was a node which was running a map task, and we know that there could be one or multiple map tasks running on one or multiple nodes, and all the map tasks have to be completed before the further stages that such as combiner or reducer come into existence. So in a case, if a node crashes where a map task was assigned to it, the whole task will have to be run again on some other node. So in Hadoop version 2, Yarn framework has a temporary daemon called application master. So your application master is taking care of execution of your application. And if a particular task on a particular node failed due to unavailability of node, it is the role of application master to have this task scheduled on some other node. Now, can we write the output of Mapreduce in different formats? Of course we can. So Hadoop supports various input and output formats. So you can write the output of Mapreduce in different formats. So you could have the default format, that is text output format, wherein records are written as line of text. You could have sequence file, which is basically to write sequence files or your binary format files, where your output files need to be fed into another Mapreduce jobs. You could go for a map file output format to write output as map files. You could go for a sequence file as a binary output format. So that's again a variant of your sequence file input format. It basically writes keys and values to a sequence file. So when we talk about binary format, we are talking about a non-human readable format. DB output format. Now this is basically used when you would want to write data to say relational databases or say NoSQL databases such as HBase. So this format also sends the reduce output to a SQL table. Now let's learn a little bit about Yarn. Yarn, which stands for yet another resource negotiator. It's the processing framework. So what benefits did Yarn bring in Hadoop version 2, and how did it solve the issues of Mapreduce version 1? So Mapreduce version 1 had major issues when it comes to scalability or availability because, in Hadoop version 1, you had only one master process for processing layer, and that is your job tracker. So your job tracker was listening to all the task trackers which were running on multiple machines. So your job tracker was responsible for resource tracking and job scheduling. In Yarn, you still have a processing master, but that's called resource manager instead of job tracker. And now with Hadoop version 2, you could even have resource manager running in high availability mode. You have node managers which would be running on multiple machines, and then you have a temporary daemon called application master. So in case of Hadoop version 2, your resource manager or master is only handling the client connections and taking care of tracking the resources. The jobs scheduling, or basically taking care of execution across multiple nodes, is controlled by application master till the application completes. So in Yarn, you can have different kind of resource allocations that could be done, and there is a concept of container. So container is basically a combination of RAM and CPU cores. Yarn can run different kind of workloads. So it is not just MapReduce kind of workload which can be run on Hadoop version 2, but you could have graph processing, massive parallel processing, you could have real-time processing, and huge processing applications could run on a cluster based on Yarn. So when we talk about scalability, in case of your Hadoop version 2, you can have a cluster size of more than 10,000 nodes and can run more than 100,000 concurrent tasks. And this is because for every application which is launched, you have this temporary daemon called application master. So if I would have 10 applications running, I would have 10 app masters running, taking care of execution of these applications across multiple nodes. Compatibility. So Hadoop version 2 is fully compatible with whatever was developed as per Hadoop version 1, and all your processing needs would be taken care by Yarn. So dynamic allocation of cluster resources, taking care of different workloads, allocating resources across multiple machines and using them for execution, all that is taken care by Yarn. Multi-tenancy, which basically means you could have multiple users or multiple teams. You could have open source and proprietary data access engines, and all of these could be basically hosted using the same cluster. Now, how does Yarn allocate resources to an application with the help of its architecture? So basically, you have a client or an application or an API which talks to resource manager. Resource manager is, as I mentioned, managing the resource allocation in the cluster. When you talk about resource manager, you have its internal two components. One is your scheduler and one is your applications manager. So when we say resource manager being the master is tracking the resources, resource manager is the one which is negotiating the resources with slave. It is not actually resource manager who is doing it, but these internal components. So you have a scheduler which allocates resources to various running applications. So scheduler is not bothered about tracking your resources or basically tracking your applications. So we can have different kind of schedulers such as FIFO, which is first in first out. You could have a fair scheduler or you could have a capacity scheduler. And these schedulers basically control how resources are allocated to multiple applications when they are running in parallel. So there is a queue mechanism. So scheduler will schedule resources based on requirements of application, but it is not monitoring or tracking the status of applications. Your applications manager is the one which is accepting the job submissions. It is monitoring and restarting the application masters. So it's application manager which is basically then launching a application master which is responsible for an application. So this is how it looks. So whenever a job submission happens, we already know that resource manager is aware of the resources which are available with every node manager. So on every node which has fixed amount of RAM and CPU cores, some portion of resources, that is your RAM and CPU cores, are allocated to node manager. Now resource manager is already aware of how much resources are available across nodes. So whenever a client request comes in, resource manager will make a request to node manager. It will basically request node manager to hold some resources for processing. Node manager would basically approve or disapprove this request of holding resources. And these resources, that is a combination of RAM and CPU cores, are nothing but containers. We can allocate containers of different sizes within yarn-site file. So your node manager, based on a request from resource manager, guarantees the container which would be available for processing. That's when your resource manager starts a temporary daemon called application master to take care of your execution. So your app master, which was launched by resource manager, or we can say internally by applications manager, will run in one of the containers, because application master is also a piece of code. So it will run in one of the containers, and then other containers will be utilized for execution. This is how yarn is basically taking care of your allocation. Your application master is managing resource needs. It is the one which is interacting with scheduler, and if a particular node crashes, it is the responsibility of app master to go back to the master, which is resource manager, and negotiate for more resources. So your app master will never ever negotiate resources with node manager directly. It will always talk to resource manager, and resource manager is the one which negotiates the resources. Container, as I said, is a collection of resources like your RAM, CPU, network bandwidth, and your container is allocated based on the availability of resources on a particular node. So, which of the following has occupied the place of a job tracker of Mapreduce? So it is your resource manager. So resource manager is the name of the master process in Hadoop version 2. Now, if we would have to write yarn commands to check the status of an application, so we could just say yarn application minus status and then the application ID. And you could kill it also from the command line. Remember, your yarn has a UI, and you can even look at your applications from the UI. You can even kill your applications from the UI. However, knowing the command line commands would be very useful. Can we have more than one resource manager in a yarn-based cluster? Yes, we can. That is what Hadoop version 2 allows us to have. So you can have a high availability yarn cluster where you have an active and standby, and the coordination is taken care by your zookeeper. At a particular time, there can only be one active resource manager, and if active resource manager fails, your standby resource manager comes and becomes active. However, zookeeper is playing a very important role. Remember, zookeeper is the one which is coordinating the server state, and it is doing the election of active to standby failover. What are the different schedulers available in yarn? So you have a FIFO scheduler, that is first in first out, and this is not a desirable option, because in this case a longer running application might block all other small running applications. Your capacity scheduler is basically a scheduler where dedicated queues are created and they have fixed amount of resources. So you can have multiple applications accessing the cluster at the same time, and they would be using their own queues and the resources allocated to them. If you talk about fair scheduler, you don't need to have a fixed amount of resources. You can just have a percentage, and you could decide what kind of fairness is to be followed, which basically means that if you were allocated 20 gigabytes of memory, however the cluster has 100 gigabytes and the other team was assigned 80 gigabytes of memory, then you have 20% access to the cluster, another team has 80%. However, if the other team does not come up or does not use the cluster, in a fair scheduler, you can go up to maximum of 100% of your cluster. To find out more information about your schedulers, you could either look in Hadoop Definitive Guide, or what you could do is you could just go to Google
and you could type, for example, yarn scheduler. Let's search for yarn scheduler, and then you can look in Hadoop definitive guide. And so this is your Hadoop definitive guide, and it beautifully explains about your different schedulers, how do multiple applications run, and that could be in your FIFO kind of scheduling, it could be in capacity scheduler, or it could be in a fair scheduling. So have a look at this link. It's a very good link. You can also search for yarn untangling, and this is a blog of this is a series of 4 blogs where it's beautifully explained about your yarn, how it works, how the resource allocation happens, what is a container, and what runs within the container. So you can scroll down, you can be reading through this, and you can then also search for part 2 of it, which talks about allocation and so on. So coming back, we basically have these schedulers. What happens if a resource manager fails while executing an application in a high availability cluster? So in a high availability cluster, we know that we would have 2 resource managers, one being active, one being standby, and Zookeeper, which is keeping a track of the server states. So if a RM fails in case of high availability, the standby will be elected as active, and then basically your resource manager or the standby would become the active one. And this one would instruct the application master to abort in the beginning. Then your resource manager recovers its running state. So there is something called as RM state store, where all the applications which are running, their status is stored. So resource manager recovers its running state by looking at your state store, by taking advantage of container statuses, and then continues to take care of your processing. Now, in a cluster of 10 data nodes, each having 16 GB and 10 cores, what would be total processing capacity of the cluster? Take a minute to think. 10 data nodes, 16 GB RAM, per node 10 cores. So, if you mention the answer as 160 GB RAM and 100 cores, then you went wrong. Now think of a cluster which has 10 data nodes, each having 16 GB RAM and 10 cores. Remember, on every node in a Hadoop cluster, you would have one or multiple processes running. Those processes would need RAM. The machine itself, which has a Linux file system, would have its own processes. So that would also be having some RAM usage, which basically means that if you talk about 10 data nodes, you should deduct at least 20 to 30% towards the overheads, towards the Cloudera based services, towards the other processes which are running. And in that case, I could say that you could have 11 or 12 GB available on every machine for processing, and say 6 or 7 cores. Multiply that by 10, and that's your processing capacity. Remember, the same thing applies to the disk usage also. So if somebody asks you, in a 10 data node cluster where each machine has 20 terabytes of disks, what is my total storage capacity available for HDFS? So the answer would not be 200. You have to consider the overheads. And this is basically which gives you your processing capacity. Now let's look at one more question. So what happens if requested memory or CPU cores goes beyond the size of container? Now, as I said, you can have your configurations which can say that in a particular data node which has 100 GB RAM, I could allocate say 50 GB for the processing. Out of 100 cores, I could say 50 cores for processing. So if you have 100 GB RAM and 100 cores, you could ideally allocate 100 for processing, but that's not ideally possible. So if you have 100 GB RAM, you would go for 50 GB. And if you have 100 cores, you would go for 50 cores. Now, within this RAM and CPU cores, you have the concept of containers, right? So container is a combination of RAM and CPU cores. So you could have a minimum size container and maximum size container. Now, at any point of time, if your application starts demanding more memory or more CPU cores, and this cannot fit into a container allocation, your application will fail. Your application will fail because you requested for a memory or a combination of memory and CPU cores which is
more than the maximum container size. So look into this yarn tangling website which I mentioned and look for the second blog in those series which explains about these allocations. Now here we will discuss on Hive, Pig, HBase and these components of Hadoop which are being used in the industry for various use cases. Let's look at some questions here and let's look how you should prepare for them. So first of all, we will learn on Hive, which is a data warehousing package. So the question is, what are the different components of a Hive architecture? Now, when we talk about Hive, we already know that Hive is a data warehousing package, which basically allows you to work on structured data or data which can be structurized. So normally people are well versed with querying or basically processing the data using SQL queries. A lot of people come from database backgrounds and they would find it comfortable if they know structured query language. Hive is one of the data warehousing package which resides within a Hadoop ecosystem. It uses Hadoop's distributed file system to store the data, and it uses RDBMS usually to store the metadata, although metadata can be stored locally also. So what are the different components of an Hive architecture? So it has a user interface. So user interface calls the execute interface to the driver. This creates a session to the query and then it sends the query to the compiler to generate an execution plan for it. Usually whenever Hive is set up, it would have its metadata stored in an RDBMS. Now to establish the connection between RDBMS and Hadoop, we need ODBC or JDBC connector jar file, and that connector jar file has a driver class. Now this driver class is mandatory to create a connection between Hive and Hadoop. So user interface creates this interface using the driver. Now we have Metastore. Metastore stores the metadata information. So any object which you create, such as database, table, indexes, their metadata is stored in Metastore, and usually this Metastore is stored in an RDBMS so that multiple users can connect to Hive. So your Metastore stores the metadata information and sends that to the compiler for execution of a query. What does the compiler do? It generates the execution plan. It has a DAG. Now DAG stands for Direct Acyclic Graph. So it has a DAG of stages where each stage is either a metadata operation, a Mapreduce job, or an operation on HDFS. And finally, we have execution engine that acts as a bridge between Hive and Hadoop to process the query. So execution engine communicates bidirectionally with Metastore to perform operations like create or drop tables. So these are four important components of Hive architecture. Now, what is the difference between external table and managed table in Hive? So we have various kinds of table in Hive, such as external table, managed table, partition table. The major difference between your managed and external table is in respect to what happens to the data if the table is dropped. Usually whenever we create a table in Hive, it creates a managed table, or we could also call that as an internal table. Now this manages the data and moves it into warehouse directory by default. Whether you create a managed table or external table, usually the data can reside in Hive's default warehouse directory, or it could be residing in a location chosen. However, when we talk about managed table, if one drops a managed table, not only the metadata information is deleted, but the table's data is also deleted from HDFS. If we talk about external table, it is created with an external keyword explicitly, and if an external table is dropped, nothing happens to the data which resides in HDFS. So that's the main difference between your managed and external table. What might be the use case if somebody asks you? There might be a migration kind of activity, or you are interested in creating a lot of tables using your queries. So in that case, you could dump all the data on HDFS, and then you could create a table by pointing to a particular directory or multiple directories. Now, you could then do some testing of your tables and would decide that you might not need all the tables. So in that case, it would be advisable to create external tables so that even if the table is later dropped, the data on HDFS will be intact unlike your managed table, where dropping of table will delete the data from HDFS also. Let's learn a little bit on partition. So what is partition in Hive and why is partitioning required in Hive? If somebody asks you that. Now, normally in world of RDBMS, partition is the process to group similar type of data together. And that is usually done on basis of a column or what we call as partitioning key. Now, each table usually has one column in context of RDBMS, which could be used to partition the data. And why do we do that? So that we can avoid scanning the complete table for a query and restrict the scan to set of data or to a particular partition. In Hive, we can have any number of partition keys. So partitioning provides granularity in Hive table. It reduces the query latency by scanning only relevant partition data instead of whole data set. We can partition at various levels. Now, if I compare RDBMS with Hive, in case of RDBMS, you could have one column which could be used for partitioning, and then you could be querying the specific partition. So in case of RDBMS, your partition column is usually a part of the table definition. So for example, if I have an employee table, I might have employee ID, employee name, employee age, and employee salary as 4 columns, and I would decide to partition the table based on salary column. Now, why would I partition it? Because I feel that employee table is growing very fast. It will have huge amount of data. And later when we query the table, we don't want to scan the complete table. So I could split my data into multiple partition based on a salary column giving some ranges. In Hive, it is a little different. In Hive, you can do partitioning, and there is a concept of static and dynamic partitioning. But in Hive, the partition column is not part of table definition. So you might have an employee table with employee ID, name, age, and that's it. That would be the table definition. But you could then have partitioning done based on salary column, which will then create a specific folder on HDFS. In that case, when we query the data, we can see the partition column also showing up. So we can partition the transaction data for a bank, for example, based on month like Jan, Feb, etc. And any operation regarding a particular month will then allow us to query that particular folder. That is where partitioning is useful. Now, why does Hive not store metadata information in HDFS if somebody asks you? So we know that Hive's data is stored in HDFS, which is Hadoop Distributed File System. However, the metadata is either stored locally, and that mode of Hive would be called as embedded mode, or you could have Hive's metadata stored in RDBMS so that multiple clients can initiate a connection. Now, this metadata, which is very important for Hive, would not be stored in HDFS. So we already know that HDFS read and write operations are time consuming. It is a distributed file system and it can accommodate huge amount of data. So Hive stores metadata information in Metastore using RDBMS instead of HDFS. So this allows to achieve low latency and faster data access. Now, if somebody asks, what are the components used in Hive query processor? So usually we have the main components are your parser, your execution engine, logical plan generation, optimizer, and type checking. So whenever a query is submitted, it will go through a parser, and parser would check the syntax, it would check for objects which are being queried and other things to see if the query is fine. Now internally you have a semantic analyzer which will also look at the query. You have an execution engine which basically will work on the execution part. That is the best generated execution plan which could be used to get the results for the query. You could also have user-defined functions which a user would want to use, and these are normally created in Java or Java programming language, and then basically these user-defined functions are added to the class path. Now you would have a logical plan generation which basically looks at your query and then generates a logical plan or the best execution path which would be required to get to the results. Internally, there is a physical plan generated which is then looked in by optimizer to get the best path to get to the data. And That might also be checking your different operators which you are using within your query. Finally, we would also have type checking. So these are important components in Hive. So somebody might ask you, if you are querying your data using Hive, what are the different components involved? Or if you could explain what are the different components which work when a query is submitted. So these are the components. Now, let's look a scenario-based question. Suppose there are a lot of small CSV files which are present in a HDFS directory, and you want to create a single Hive table from these files. So data in these files have fields like registration number, name, email, address. So if this is what needs to be done, what will be your approach to solve it? Where will you create a single Hive table for lots of small files without degrading the performance of the system? So there can be different approaches. Now we know that there are a lot of small CSV files which are present in a directory. So we know that when we create a table in Hive, we can use a location parameter. So I could say create table, give a table name, give the column and their data types. I could specify the delimiters, and finally I could say location and then point it to a directory on HDFS. And this directory might be the directory which has a lot of CSV files. So in this case, I will avoid loading the data in the table, because table pointing to the directory will directly pick up the data from one or multiple files. And we also know that Hive does schema check on read. So it does not do a schema check on write. So in case there were one or two files which did not follow the schema of the table, it would not prevent data loading. Data would anyways be loaded. Only when you query the data, it might show you null values if data which was loaded does not follow the schema of the table. This is one approach. What is the other approach? So let's look at that. You can think about sequence file format, which is basically a smart format or a binary format, and you can group these small files together to form a sequence file. Now this could be one other smarter approach. So we could create a temporary table. So we could say create table, give a table name, give the column names and their data types. We could specify the delimiters as it shows here, that is row format, and fields terminated by. And finally, we can store that as text file. Then we can load data into this table by giving a local file system path. And then we can create a table that will store data in sequence file format. So my point 1 is storing the data in text file. Point 3 would be storing the data in sequence file format. So we say create table, give the specifications. We say row format delimited, fields are terminated by, comma, stored as sequence file. Then we can move the data from test table into test sequence file table. So I could just say insert overwrite my new table as select star from other table. Remember, in Hive, you cannot do insert, update, delete. However, if the table is existing, you can do a insert overwrite from an existing table into a new table. So this could be one approach where we could have a lot of CSV files or smaller files clubbed together as one big sequence file and then store it in the table. Now, if somebody asks you, write a query to insert a new column, that is integer data type, into a Hive table, and the requirement might be that you would want to insert this table at a position before an existing column. Now that's possible by doing an alter table, giving your table name, and then specifying change column, giving your new column with the data type before an existing column. This is a simple way wherein you can insert a new column into a Hive table. What are the key differences between Hive and Pig? Now, some of you might have heard Hive is a data warehousing package and Pig is more of a scripting language. Both of them are used for data analysis, trend detection, hypothesis testing, data transformation, and many other use cases. So if we compare Hive and Pig, Hive uses a declarative language called HiveQL, that is Hive querying language, similar to SQL, and it is for reporting or for data analysis, even for data transformation or for your data extraction. Pig uses a high-level procedural language called Pig Latin, for programming. Both of them, remember, use Mapreduce processing framework. So when we run a query in Hive to process the data, or when we create and submit a pig script, both of them trigger a Mapreduce job unless and until we have set them to local mode. Hive operates on the server side of the cluster and basically works on structured data or data which can be structurized. Pig usually works or operates on the client side of the cluster and allows both structured, unstructured, or even I could say semi-structured data. Hive does not support Avro file format by default. However, that can be done by using the write serializer deserializer. So we can have Hive table related data stored in Avro format, in sequence file format, in Parquet format, or even as a text file format. However, when we are working on smarter formats like Avro or sequence file or Parquet, we might have to use specific serializers, deserializers. For Avro, this is the package which allows us to use Avro format. Pig supports Avro format by default. Hive was developed by Facebook and it supports partitioning. And Pig was developed by Yahoo and it does not support partitioning. So these are high-level differences. There are lots and lots of differences. Remember, Hive is more of a data warehousing package and Pig is more of a scripting language or a strictly procedural flow following scripting language which allows us to process the data. Now let's get more deeper and learn about Pig, which is, as I mentioned, a scripting language which can be used for your data processing. It also uses Mapreduce, although we can even have Pig run in a local mode. Let's learn about Pig in the next section. Now let's learn on some questions about Pig, which is a scripting language and it is extensively used for data processing and data analysis. So the question is, how is Apache Pig different from Mapreduce? Now we all know that Mapreduce is a programming model. It's quite rigid when it comes to processing the data because you have to do the mapping and reducing. You have to write huge code. Usually Mapreduce is written in Java, but now it can also be written in Python. It can be written in Scala and other programming languages. So if we compare Pig with Mapreduce, Pig obviously is very concise. It has less lines of code when compared to Mapreduce. Now, we also know that Pig script internally will trigger a Mapreduce job. However, user need not know about Mapreduce programming model. They can simply write simple scripts in Pig and that will automatically be converted into Mapreduce. However, Mapreduce has more lines of code. Pig is high-level language which can easily perform join operations or other data processing operations. Mapreduce is a low-level language which cannot perform join operations easily. So we can do join using Mapreduce. However, it's not really easy in comparison to Pig. Now, as I said, on execution, every Pig operator is converted internally into a Mapreduce job. So every Pig script which is run, which would be converted into Mapreduce job. Now, Mapreduce overall is a batch-oriented processing, so it takes more time to compile, it takes more time to execute, either when you run a Mapreduce job or when it is triggered by Pig script. Pig works with all versions of Hadoop, and when we talk about Mapreduce program, which is written in one Hadoop version, may not work with other versions. It might work or it might not. It depends on what are the dependencies, what is the compiler you're using, what programming language you have used, and what version of Hadoop you are working on. So these are the main differences between Apache Pig and Mapreduce. What are the different ways of executing Pig script? So you could create a script file, store it in .pig or .text, and then you could execute it using the pig command. You could be bringing up the grunt shell, that is Pig's shell. Now that usually starts with Mapreduce mode, but then we can also bring it up in a local mode, and we can also run Pig embedded as an embedded script in other programming language. So these are the different ways of executing your Pig script. Now, what are the major components of pig execution environment? This is a very common question. Interviewers would always want to know different components of Hive, different components of pig, even different components which are involved in Hadoop ecosystem. So when we want to learn about major components of pig execution environment, here are some. So you have pig scripts. Now that is written in pig Latin using built-in operators and user-defined functions and submitted to the execution environment. That's what happens when you would want to process the data using pig. Now there is a parser which does type checking and checks the syntax of the script. The output of parser is a DAG, direct acyclic graph. So look in Wikipedia for DAG. So DAG is basically a sequence of steps which run in one direction. Then you have an optimizer. Now this optimizer performs optimization using merge, transform, split, etc. It aims to reduce the amount of data in the pipeline. That's the whole purpose of optimizer. You have a internal compiler. So pig compiler converts the optimized code into a Mapreduce job. And here user need not know the Mapreduce programming model or how it works or how it is written. They all need to know about running the pig script, which would be internally converted into a Mapreduce job. And finally, we have an execution engine. So Mapreduce jobs are submitted to the execution engine to generate the desired results. So these are major components of pig execution environment. Now, let's learn about different complex data types in pig. Pig supports various data types. The main ones are tuple, bag, and map. What is tuple or tuple? As you might have heard, a tuple is an ordered set of fields which can contain different data types for each field. So in array, you would have multiple elements, but that would be of same types. List can also have different types. Your tuple is a collection which has different fields, and each field can be of different type. Now we could have an example as 1, 3 or 1, 3, a string or a float element, and all of that form a tuple. Bag is a set of tuples. So that's represented by curly braces. So you could also imagine this like a dictionary which has various different collection elements. What is a map? Map is a set of key value pairs used to represent data. So when you work in big data field, you need to know about different data types which are supported by pig, which are supported by Hive, which are supported in other components of Hadoop. So tuple, bag, map, array buffer. You can think about list, you can think about dictionaries, you can think about map, which is key value pair. So these are your different complex data types other than the primitive data types such as integer, character, string, boolean, float, and so on. Now, what are the various diagnostic operators available in Apache Pig? So these are some of the operators or options which you can give in a pig script. You can do a dump. Now, dump operator runs the pig Latin scripts and displays the result on the screen. So either I could do a dump and see the output on the screen, or I can even do a dump into and I could store my output in a particular file. So we can load the data using load operator in pig. And then pig also has different internal storage like JSON loader or pig storage, which can be used if you're working on specific kind of data. And then you could do a dump either before processing or after processing, and dump would produce the result. The result could be stored in a file or seen on the screen. You also have a describe operator. Now that is used to view the schema of a relation. So you can load the data and then you can view the schema of relation using describe operator. Explain, as we might already know, displays the physical, logical, and Mapreduce execution plans. So normally in RDBMS, when we use explain, we would like to see what happens behind the scenes when a particular script or a query runs. So we could load the data using load operator as in any other case. And if we would want to display the logical, physical, and Mapreduce execution plans, we could use explain operator. There is also an illustrate operator. Now that gives the step-by-step execution of sequence of statements. So sometimes when we would want to analyze our script to see how good or bad they are, or would that really serve our purpose, we could use illustrate. And again, you can test that by loading the data using load operator, and you could just use a illustrate operator to have a look at the step-by-step execution of the sequence of statements which you would want to execute. So these are different diagnostic operators available in Apache Pig. Now, if somebody asks, state the usage of group, order by, and distinct keywords in Pig script. So as I said, Pig is a scripting language. So you could use various operators. So group basically collects various records with the same key and groups the data in one or more relations. Here is an example. You could do a group data. So that is basically a variable, or you can give some other name, and you can say group relation name by age. Now say I have a file where I have various fields, and one of the field is a relation name. So I could group that by a different field. Order by is used to display the contents of relation in a sorted order, whether ascending or descending. So I could create a variable called relation2, and then I could say order relation name 1 by ascending or descending order. Distinct basically removes the duplicate records, and it is implemented only on entire records, not on individual records. So if you would want to find out the distinct values and relation name field, I could use distinct. What are the relational operators in Pig? So you have various relational operators which help data scientists or data analysts or developers who are analyzing the data, such as co-group, which joins two or more tables and then performs group operation on the join table result. You have cross. It is used to compute the cross product, that is a Cartesian product of two or more relations. For each is basically to do some iteration. So if it will iterate through tuples of a relation, generating a data transformation. So for example, if I say variable A equals, and then I load a file in A, and then I could create a variable called B, where I could say for each A, I would want to do something, say group. Join is to join two or more tables in a relation. Limit is to limit the number of output tuples or output results. Split is to split the relation into two or more relations. Union is to get a combination, it will merge the contents of two or more relations. And order is to get a sorted result. So these are some relational operators which are extensively used in Pig for analysis. What is the use of having filters in Apache Pig? Now, say for example, I have some data which has three fields: year, product, quantity, and this is my phone sales data. So filter operator could be used to select the required values from a relation based on a condition. It also allows you to remove unwanted records from data file. So for example, filter the products where quantity is greater than 1000. So I see that I have one row wherein, or multiple rows where the quantity is greater than 1000, such as 1500, 1700, 1200. So I could create a variable called A. I would load my file using Pig storage. As I explained earlier, Pig storage is an internal parameter which can be used to specify the delimiters. Now here my delimiter is comma. So I could say using Pig storage as, and then I could specify the data type for each field. So year being integer, product being character array, and quantity being integer. Then B, I could say filter A, whatever we have in A, by quantity greater than 1000. So it's very concise, it's very simple, and it allows us to extract and process data in a simpler way. Now, suppose there is a file called test.txt having 150 records in HDFS. So this is a file which is stored on HDFS, and it has 150 records, where we can consider every record being one line. And if somebody asks you to write a Pig command to retrieve the first 10 records of the file, first we will have to load the data. So I could create a variable called test_data, and I would say load my file using Pig storage, specifying the delimiter as comma, as, and then I could specify my fields, whatever fields our file have. And then I would want to get only 10 records, for which I could use the limit operator. So I could say limit on test data and give me 10 records. This is very simple, and we can extract 10 records from 150 records which are stored in the file on HDFS. Now, we have learned on Pig we have learned some questions on Hive. You could always look more in books like Programming in Hive or Programming in Pig and look for some more examples and try out these examples on a existing Hadoop setup. Now let's learn on HBase, which is a NoSQL database. Now HBase is a 4-dimensional database in comparison to your RDBMS, which usually are 2-dimensional. So RDBMS have rows and columns, but HBase has 4 coordinates. It has row key, which is always unique, column family, which can be any number, column qualifiers, which can again be any number per column family, and then you have a version. So these 4 coordinates make HBase a 4-dimensional key value store or a column family store, which is unique for storing huge amount of data and extracting data from HBase. There is a very good link which I would suggest everyone can look at if you would want to learn more on HBase, and you could just say HBase mapper. And this basically brings up a documentation which is from Mapr, but then that's not specific to Mapr. And you can look at this link, which will give you a detailed explanation of HBase, how it works, what are the architectural components, and how data is stored, and how it makes HBase a very powerful NoSQL database. So let's learn on some of the important or critical questions on HBase which might be asked by the interviewer in an interview when you're applying for a big data admin or a developer position role. So what are the key components of HBase? Now, as I said, this is one of the favorite questions of interviewers where they would want to understand your knowledge on different components for a particular service. HBase, as I said, is a NoSQL database, and that comes as a part of service with Cloudera or Hortonworks. And with Apache Hadoop, you could also set up HBase as an independent package. So what are the key components of HBase? HBase has a region server. Now, HBase follows the similar kind of topology like Hadoop. Now, Hadoop has a master process that is name node and slave processes such as data nodes and secondary name node. In the same way, HBase also has a master, which is HMaster, and the slave processes are called region servers. So these region servers are usually co-located with data nodes. However, it is not mandatory that if you have 100 data nodes, you would have 100 region servers. So it purely depends on admin. So what does this region server contain? So region server contains HBase tables that are divided horizontally into regions. Or you could say group of rows is called regions. So in HBase, you have 2 aspects. One is group of columns, which is called column family, and one is group of rows, which is called regions. Now these regions or these rows are grouped based on the key values, or I would say row keys, which are always unique. When you store your data in HBase, you would have data in the form of rows and columns. So group of rows are called regions, or you could say these are horizontal partitions of the table. So a region server manages these regions on the node where a data node is running. A region server can have up to 1,000 regions. It runs on every node and decides the size of region. So region server, as I said, is a slave process which is responsible for managing HBase data on the node. Each region server is a worker node or a worker process co-located with data node, which will take care of your read, write, update, delete request from the clients. Now, when we talk about more components of HBase, as I said, you have HMaster. So you would always have a connection coming in from a client or an application. What does HMaster do? It assigns regions. It monitors the region servers. It assigns regions to region servers for load balancing. And it cannot do that without the help of Zookeeper. So if we talk about components of HBase, there are 3 main components. You have Zookeeper, you have HMaster, and you have region server. Region server being the slave process, your HMaster being the master process, which takes care of all your table operations, assigning regions to the region servers, taking care of read and write requests which come from client. And for all of this, HMaster will take in help of Zookeeper, which is a centralized coordination service. So whenever a client wants to read or write or change the schema or any other metadata operations, it will contact HMaster. HMaster internally will contact Zookeeper. So you could have HBase set up also in high availability mode, where you could have a active HMaster and a backup HMaster. You would have a Zookeeper quorum, which is the way Zookeeper works. So Zookeeper is a centralized coordination service which will always run with a quorum of processes. So Zookeeper would always run with odd number of processes such as 3, 5, and 7. Because Zookeeper works on the concept of majority consensus. Now Zookeeper, which is a centralized coordination service, is keeping a track of all the servers which are alive, available, and also keeps a track of their status. For every server which Zookeeper is monitoring, Zookeeper keeps a session alive with that particular server. HMaster would always check with Zookeeper which region servers are available, alive, so that regions can be assigned to the region server. At one end, you have region server which are sending their status to the Zookeeper, indicating if they are ready for any kind of read or write operation. And at other end, HMaster is querying the Zookeeper to check the status. Now Zookeeper internally manages a meta table. Now that meta table will have information of which regions are residing on which region server and what row keys those regions contain. So in case of a read activity, HMaster will query Zookeeper to find out the region server which contains that meta table. Once HMaster gets the information of meta table, it can look into the meta table to find out the row keys and the corresponding region servers which contain the regions for those row keys. Now, if we would want to understand row key and column families in HBase, let's look at this, and it would be good if we could look this on an Excel sheet. So row key is always unique. It acts as a primary key for any HBase table. It allows logical grouping of cells and makes sure that all cells with the same row key are co-located on the same server. So as I said, you have 4 coordinates for HBase. You have a row key, which is always unique. You have column families, which is nothing but group of columns. And when I say column families, one column family can have any number of columns. So when I talk about HBase, HBase is 4-dimensional, and in terms of HBase, it is also called as a column-oriented database, which basically means that every row in one column could have a different data type. Now, you have a row key which uniquely identifies the row. You have column families, which could be one or many, depending on how the table has been defined. And a column family can have any number of columns. Or I could say, for every row within a column family, you could have different number of columns. So I could say for my row 1, I could just have 2 columns such as name and city within the column family. For my row 2, I could have name, city, age, designation, salary. For my third row, I could have 1,000 columns, and all that could belong to one column family. So this is a horizontally scalable database. So column family consists of group of columns which is defined during table creation, and each column family can have any number of column qualifiers separated by a delimiter. Now, a combination of row key, column family, column qualifier such as name, city, age, and the value within the cell makes the HBase a unique 4-dimensional database. For more information, if you would want to learn on HBase, please refer this link, which is HBase Mapper, and this gives a complete HBase architecture. That is 3 components of name node, 3 components that is name node, region servers, and Zookeeper, how it works, how HMaster interacts with Zookeeper, what Zookeeper does in coordination, how are the components working together, and how does HBase take care of read and write. Coming back and continuing, why do we need to disable a table? So there are different table operations what you can do in HBase, and one of them is disabling a table. Now if you would want to check the status of table, you could check that by is disabled and giving the table name, or is enabled and the table name. So the question is, why do we need to disable a table? Now, if we would want to modify a table, or we are doing some kind of maintenance activity, in that case, we can disable the table so that we can modify or change its settings. When a table is disabled, it cannot be accessed through the scan command. Now, if we have to write a code to open a connection in HBase, now to interact with HBase, one could either use a graphical user interface such as Hue, or you could be using the command line HBase shell, or you could be using HBase admin API if you are working with Java, or say HappyBase if you are working with Python, where you may want to open a connection with HBase so that you can work with HBase programmatically. In that case, we have to create a configuration object, that is configuration myconf, and then create a configuration object. And then you can use different classes like htable interface to work on a new table. You could use hcolumn qualifier and many other classes which are available in HBase admin API. What does replication mean in terms of HBase? So HBase, as I said, works in a cluster way. And when you talk about cluster, you could always set up a replication from one HBase cluster to other HBase cluster. So this replication feature in HBase provides a mechanism to copy data between clusters or sync the data between different clusters. This feature can be used as a disaster recovery solution that provides high availability for HBase. So if I have HBase cluster 1, where I have one master and multiple region servers running in a Hadoop cluster, I could use the same Hadoop cluster to create a HBase replica cluster, or I could have a totally different HBase replica cluster where my intention is that if things are changing in a particular table in cluster 1, I would want them to be replicated across different clusters. So I could alter the HBase table and set the replication scope to 1. Now, a replication scope of 0 indicates that table is not replicated. But if we set the replication to 1, we basically will have to set up a HBase cluster where we can replicate HBase tables data from cluster 1 to cluster. So these are the commands which can be used to enable replication and then replicate the data of table across clusters. Can we import and export in HBase? Of course we can. It is possible to import and export tables from one HBase cluster to other HBase cluster, or even within a cluster. So we can use the HBase export utility, which comes in this particular package. Give a table name and then a target location. So that will export the data of a HBase table into a directory on HDFS. Then I could create a different table which would follow some kind of same definition as the table which was exported, and then I could use import to import the data from the directory on HDFS to my table. If you would want to learn more on HBase import and export, you could look at HBase import operations. Let's search for the link, and this is the link where you could learn more about HBase import export utilities, how you could do a bulk import, bulk export, which internally uses Mapreduce, and then you could do a import and export into HBase tables. Moving further, what do we mean by compaction in HBase? Now, we all know that HBase is a NoSQL database which can be used to store huge amount of data. However, whenever a data is written in HBase, it is first written to what we call as write ahead log, and also to memstore, which is write cache. Now, once the data is written in WAL and your memstore, it is offloaded to form an internal HBase format file, which is called H file. And usually these H files are very small in nature. So we also know that HDFS is good when we talk about few number of larger files in comparison to large number of smaller files due to the limitation of name nodes memory. Compaction is process of merging HBase files, that is these smaller H files, into a single large file. This is done to reduce the amount of memory required to store the files and number of disk seeks needed. So we could have a lot of H files which get created when the data is written to HBase, and these smaller files can then be compacted through a major or minor compaction, creating one big H file, which internally would then be written to HDFS and HDFS format of blocks. That is the benefit of compaction. There is also a feature called Bloom filter. So how does Bloom filter work? So Bloom filter or HBase Bloom filter is a mechanism to test whether a H file contains a specific row or a row column cell. Bloom filter is named after its creator Burton Howard Bloom. It is a data structure which predicts whether a given element is a member of a set of data. It provides an in-memory index structure that reduces the disk reads and determines the probability of finding a row in a particular file. This is one of very useful features of HBase, which allows for faster access and avoids disk seeks. Does HBase have any concept of namespace? So namespace is when you have similar elements grouped together. So namespace, yes, HBase supports namespace. So namespace is a logical grouping of tables, analogous to a database in RDBMS. So you can create HBase namespace to the schema of RDBMS database. So you could create a namespace by saying create namespace and giving it a name. And then you could also list the tables within a namespace. You could create tables within a specific namespace. Now, this is usually done in production environment where a cluster might be multi-tenant cluster and there might be different users of the same NoSQL database. In that case, admin would create specific namespace, and for specific namespace, you would have different directories on HDFS, and users of a particular business unit or a team can work on their HBase objects within a specific namespace. This is a question which is again very important to understand about the writes or reads. So how does write ahead log wall help when a region server crashes? Now, as I said, when a write happens, it will happen into memstore and wall, that is your edit log or write ahead log. So whenever a write happens, it will happen in two places, memstore, which is the write cache, and wall, which is an edit log. Only when the data is written in both these places and based on the limitation of memstore, the data will be flushed to create an HBase format file called hfile. These files are then compacted and created into one bigger file, which will then be stored on HDFS. And HDFS data, as we know, is stored in the form of blocks on the underlying data nodes. So if a region server hosting a memstore crashes, now where is region server running? That would be co-located with data node. So if a data node crashes, or if a region server which was hosting the memstore write cache crashes, data in memory, the data that in memory which was not persisted, is lost. Now, how does HBase recover from this? As I said, your data is written into wall and memstore at the same time. HBase recovers against that by writing to wall before the write completes. So whenever a write happens, it happens in memstore and wall at the same time. HBase cluster keeps a wall to record changes as they happen, and that's why we call it as also an edit log. If HBase goes down or the node that goes down, the data that was not flushed from memstore to hfile can be recovered by replaying the write ahead log, and that's the benefit of your edit log or write ahead log. Now, if we would have to write HBase command to list the contents and update the column families of a table, I could just do a scan, and that would give me complete data of a table. If you are very specific and if you would want to look at a particular row, then you could do a get table name and then give the row key. However, you could do a scan to get the complete data of a particular table. You could also do a describe to see what are the different column families. And if you would want to alter the table and add a new column family, it is very simple. You can just say alter, give the HBase table name, and then give your new column family name, which will then be added to the table. What are catalog tables in HBase? So as I mentioned, your Zookeeper knows the location of this internal catalog table, or what we call as the meta table. Now, catalog tables in HBase have two tables. One is HBase meta table and one is -root. The catalog table HBase meta exists as an HBase table and is filtered out of HBase shell's list command. So if I give a list command on HBase, it would list all the tables which HBase contains, but not the meta table. It's an internal table. This meta table keeps a list of all regions in the system and location of HBase meta stored in Zookeeper. So if somebody wants to find out or look for particular rows, they need to know the regions which contain that data, and those regions are located on region server. To get all this information, one has to look into this meta table. However, we will not be looking into meta table directly. We would just be giving a write or a read operation. Internally, your HBase master queries the Zookeeper. Zookeeper has the information of where the meta table exists, and that meta table which is existing on region server contains information of row keys and the region servers where those rows can be found. Your root table keeps a track of location of the meta table. What is hotspotting in HBase and how to avoid hotspotting? Now, this is a common problem, and always admin guys or guys who are managing the infrastructure would think about it. So one of the main idea is that HBase would be leveraging the benefit of HDFS. Your all read and write requests should be uniformly distributed across all of the regions in region servers. Otherwise, what's the benefit of having a distributed cluster? So you would have your data stored across region servers in the form of regions, which are horizontal partitions of the table. And whenever read and write requests happen, they should be uniformly distributed across all the regions in the region servers. Now, hotspotting occurs when a given region serviced by a region server receives most or all of read and write requests, which is basically a unbalanced way of read-write operations. Now, hotspot can be avoided by designing the row key in such a way that data being written should go to multiple regions across the cluster. So you could do techniques such as salting, hashing, reversing the key, and many other techniques which are employed by users of HBase. We need to just make sure that when the regions are distributed across region servers, they should be spread across region servers so that your read and write request can be satisfied from different region servers in parallel, rather than all read and write requests hitting the same region server, overloading the region server, which may also lead to the crashing of a particular region server. So these were some of the important questions of HBase, and then there are many more. Please refer to the link which I specified during my discussion, and that gives you a detailed explanation of how HBase works. You can also look into HBase Definitive Guide by O'Reilly or HBase in Action, and these are really good books to understand about HBase internals and how it works. Now that we have learned on Hive, which is a data warehousing package, we have learned on Pig, which is a scripting or a scripting language which allows you to do data analysis, and we have learned some questions on a NoSQL database. Just note it that there are more than 225 NoSQL databases existing in market. And if you would want to learn and know about more NoSQL databases, you can just go to Google and type NoSQL databases.org, and that will take you to the link which is for NoSQL databases, and this shows there are more than 225 NoSQL databases existing in market, and these are for different use cases used by different users and with different features. So have a look at this link. Now, when you talk about data ingestion, so let's look at data ingestion, and this is one good link which I would suggest to have a look at, which lists down around 18 different ingestion tools. So when you talk about different data ingestion tools, some are for structured data, some are for streaming data, some are for data governance, some are for data ingestion and transformation, and so on. So have a look at this link, which also gives you a comparison of different data ingestion tools. So here, let's learn about some questions on Sqoop, which is one of the data ingestion tools mainly used for structured data, or you could say data which is coming in from RDBMS or data which is already structured, and you would want to ingest that. You would want to store that on HDFS, which could then be used for Hive, which could be used for any kind of processing using Mapreduce or Hive or Pig or Spark or any other processing frameworks, or you would want to load that data into, say, Hive or HBase tables. Sqoop is mainly for structured data. It is extensively used when organizations are migrating from RDBMS to a big data platform, and they would be interested in ingesting the data, that is doing import and export of data from RDBMS to HDFS or vice versa. So let's learn about some important questions on Sqoop, which you may be asked by an interviewer when you apply for a big data related position. How is Sqoop different from Flume? So this is a very common question which is asked. Sqoop, which is mainly for structured data. So Sqoop works with RDBMS. It also works with NoSQL databases to import and export data. So you can import data into HDFS. You can import data into data warehousing packets such as Hive directly, or also in HBase. And you could also export data from Hadoop ecosystem to your RDBMS. However, when it comes to Flume, Flume is more of a data ingestion tool which works with streaming data or unstructured data. So data which is constantly getting generated, for example, log files or metrics from server or some chat messenger and so on. So if you are interested in working on capturing and storing the streaming data in a storage layer such as HDFS or HBase, you could be using Flume. There could be other tools also like Kafka or Storm or Chukwa or Samza, NiFi, and so on. Sqoop, however, is mainly for structured data. Your loading data in Sqoop is not event driven, so it is not based on event. It basically works on data which is already stored in RDBMS. In terms of Flume, it is completely event driven. That is, as the messages or as the events happen, as the data is getting generated, you can have that data ingested using Flume. Sqoop works with structured data sources, and you have various Sqoop connectors which are used to fetch data from external data structures or RDBMS. So for every RDBMS such as MySQL, Oracle, DB2, Microsoft SQL Server, you have different connectors which are available. Flume, it works on fetching streaming data such as tweets or log files or server metrics from your different sources where the data is getting generated. And if you are interested in not only ingesting that data, which is getting generated in a streaming fashion, but if you would be interested in processing the data as it arrives, Sqoop can import data from RDBMS onto HDFS and also export it back to RDBMS. Flume is then used for streaming data. Now you could have one-to-one, one-to-many, or many-to-one kind of relation. So in terms of Flume, you have components such as your source, sink, and channel. That's the main difference between your Sqoop and Flume. What are the different file formats to import data using Sqoop? Well, there are lots and lots of formats in which you can import data into Sqoop. When you talk about Sqoop, you can have delimited text file format. Now that's the default import format. It can be specified explicitly using as text file argument. So when I want to import data from an RDBMS, I could get that data in HDFS using different compression schemes or in different formats using the specific arguments. So I could specify an argument which will write string-based representation of each record to output files with delimiters between individual columns and rows. So that is the default format which is used to import data using Sqoop. So to learn more about your Sqoop and different arguments which are available, you can click on sqoop.apache.org. You can look into the documentation, and I would suggest choosing one of the versions and looking into the user guide. And here you can search for arguments and look for specific control arguments which show how you can import data using Sqoop. So here we have common arguments, and then you also have import control arguments, wherein we have different options like getting data as Avro, as sequence file, as text file, or Parquet file. These are different formats. You can also get data in default compression scheme, that is gzip, or you can specify compression codec, and then you can specify what compression mechanism you would want to use when you're importing your data using Sqoop. When it comes to default format for Flume, we could say sequence file, which is a binary format that stores individual records in record-specific data types. So these data types are manifested as Java classes, and Sqoop will automatically generate these data types for you. So Sqoop does that. When we talk about your sequence file format in terms of your Sqoop, you could be extracting storage of all data in binary representation. So as I mentioned, you can import data in different formats such as Avro, Parquet, sequence file, that is binary format or machine readable format. And then you could also have data in different compression schemes. Let me just show you some quick examples here. So if I look in the content, and here I could search for a Sqoop based file where I have listed down some examples. So if I would want to use different compression schemes, here are some examples. Have a look at these. So I'm doing a Sqoop import. I'm also giving an argument so that Sqoop, which also triggers a Mapreduce job, or I would say map only job. So when you run a Sqoop import, it triggers a map only job. No reduce happens here. And you could specify this parameter or this argument on the command line mapreduce.framework.name so that you could run your map only job in a local mode to save time, or that would interact with yarn and run a full-fledged map only job. We can give the connection and then connect to whatever RDBMS we are connecting, mentioning the database name, give your username and password, give the table name, give a target directory, or it would create a directory same as the table name, which would work only once. And then I could say -z to get data in a compressed format, that is gzip, or I could be specifying compression codec, and then I could specify what compression codec I would want to use, say snappy, bzip, lz4, default. I could also run a query by giving a Sqoop import. And when I'm specifying a query, if you notice, I've not given any table name because that would be included in the query. I can get my data as a sequence file format, which is a binary format, which will create a huge file. So we could also have compression enabled. And then I could say the output of my map job should use a compression at record level for my data coming in sequence file. So sequence file or a binary format supports compression at record level or at block level. I could get my data in an Avro file where data has embedded schema within the file, or a Parquet file also. So these are different ways in which you can set up different compression schemes, or you can even get data in different formats, and you could be doing a simple Sqoop import for these. Looking further, what is the importance of eval tool in Sqoop? So there is something called as eval tool. So Sqoop eval tool allows users to execute user-defined queries against respective database servers and preview the result in the console. So either I could be running a straight away query to import the data into my HDFS, or I could just use Sqoop eval, connect to my external RDBMS, specify my username and password, and then I could be giving in a query to see what would be the result of the query which we intend to import. Now, let's learn about how Sqoop imports and exports data between RDBMS and HDFS with its architecture. So RDBMS, as we know, has your database structures, your tables, which all of them are logical. And internally, there is always metadata which is stored. Your Sqoop import connects to an external RDBMS, and for this connection, it uses an internal connector jar file which has a driver class. So that's something which needs to be set up by admin, but they need to make sure that whichever RDBMS you intend to connect to, they need to have the JDBC connector for that particular RDBMS stored within the Sqoop lib folder. So Sqoop import gets the metadata, and then for your Sqoop command, it converts that into a map only job, which might have one or multiple map tasks. Now that depends on your Sqoop command. You could be specifying that you would want to do a import only in one task, or in multiple tasks. These multiple map tasks will then run on a section of data from RDBMS and then store it in HDFS. So at high level, we could say Sqoop will introspect database to gather the metadata. It divides the input data set into splits, and this division of data into splits mainly happens on primary key column of the table. Now, if somebody might ask, what if my table in RDBMS does not have a primary key column? Then when you're doing a Sqoop import, either you will have to import it using one mapper task by specifying -m equals 1, or you would have to say split by parameter to specify a numeric column from RDBMS. And that's how you can import the data. Let me just show you a quick example on this. So I could just look in again into the Sqoop command file, and here we could be looking at an example. So if you see this one, here we are specifying -m equals 1, which basically means I would want to import the data using one map task. Now in this case, whether the table has a primary key column or does not have a primary key column will not matter. But if I say a -MS6, where I'm specifying multiple map tasks to be imported, then this will look for a primary key column in the table which you are importing. Now, if the table does not have a primary key column, then I could be specifying a split by and then specify the column so that the data could be split into multiple chunks and multiple map tasks could take it. Now, if the second scenario is your table does not have a primary key column and it does not have a numeric column on which you could do a split by, in that case, and if you would want to use multiple mappers, you could still say split by on a textual column, but you will have to add this property so that it allows splitting the data which is non-numeric. All of these options are given in the sqoopapache.org link. Going further, how Sqoop imports and exports data between RDBMS and HDFS with its architecture. So as I said, it submits the map only job to the cluster, and then it basically does a import or export. So if we are exporting the data from HDFS, in that case, again, there would be a map only job. It would look at multiple splits of the data which is existing, which your map only job would process through one or multiple map task and then export it to RDBMS. Suppose you have a database testDB in MySQL. If somebody asked you to write a command to connect this database and import tables to Sqoop. So here is a quick example as I showed you in the command file. So you could say Sqoop import. This is what we would want to do. You connect using JDBC. Now this will only work if the JDBC connector already exists within your Sqoop lib directory. Admin has to set up that. So you can connect to your RDBMS. You can point to the database. So here our database name is test_db. I could give username, and then either I could give password on the command line or just say capital P so that I could be prompted for the password. And then I could give the table name which I would want to import. I could also be specifying -m and specify how many map tasks do I want to use for this import, as I showed in previous screen. How to export a table back to RDBMS? Now for this, we need the data in a directory on HDFS. So for example, there is a departments table in retail database, which is already imported into Sqoop, and you need to export this table back to RDBMS. So this is the content of the table. Now create a new department table in RDBMS. So I could create a table specifying the column names, whether that supports null or no, if that has a primary key column, which is always recommended. And then I can do a Sqoop export. I can connect to the RDBMS, specifying my username and password, specify the table into which you want to export the data, and then you give export directory pointing to a directory on HDFS which contains the data. This is how you can export data into table. Seeing example on this. So I could again look into my file, and here I have an example of import. This is where you are importing data directly into Hive. And you have Sqoop import where you are importing data directly into HBase table, and you can then query your HBase table to look at the data. You could also do a export by running your map only job in a local mode, connecting to the RDBMS, specifying your username, specifying the table where you would want to export, and the directory on HDFS where you have kept the relevant data. This is a simple example of export. Looking further, what is the role of JDBC driver in Sqoop setup? So as I said, if you would want to use Sqoop to connect to an external RDBMS, we need the JDBC ODBC connector jar file. Now, one or admin could download the JDBC connector jar file and then place the jar file within the Sqoop lib directory wherever Sqoop is installed. And this JDBC connector jar file contains a driver. Now, JDBC driver is a standard Java API which is used for accessing different databases in RDBMS. So this connector jar file is very much required, and this connector jar file has a driver class, and this driver class enables the connection between your RDBMS and your Hadoop structure. Each database vendor is responsible for writing their own implementation that will allow communication with the corresponding database, and we need to download the drivers which allow our Sqoop to connect to external RDBMS. So your JDBC driver alone is not enough to connect to Sqoop. We also need connectors to interact with different databases. So a connector is a pluggable piece that is used to fetch metadata and allow Sqoop to overcome the differences in SQL dialects. So this is how connection can be established. So normally your admins would, when they are setting up Sqoop and Hadoop, they would download, say, MySQL JDBC connector, and this is how they would go to the MySQL connectors. If you are connecting to MySQL, similarly for your other RDBMS, you could be, say, going in here, you could be looking for a previous version, depending, you could be going for platform independent, and then you could be downloading the connector jar file. Now, if you untar this jar file, you would see a MySQL connector jar. And if we look in com.mysql.jdbc.com.mysql.jdbc.driver, so this is the package which is within the connector jar file, and this has the driver class which allows the connection of your Sqoop with your RDBMS. So these things will have to be done by your admin so that you can have your Sqoop connecting to an external RDBMS. Now, how do you update the columns that are already exported? So if I do a export and I put my data in RDBMS, can I really update the columns that are already exported? Yes, I can, using a update key parameter. So Sqoop export command remains the same. The only thing I will have to specify now is the table name, your fields terminated by if you have a specific delimiter, and then you can say update key and then the column name. So this allows us to update the columns that are already exported in RDBMS. What is CodeGen? So Sqoop commands translate into your Mapreduce job or map only job. So CodeGen is basically a tool in Sqoop that generates data access objects, DAO, Java classes that encapsulate and interpret imported records. So if I do a Sqoop CodeGen connect to an RDBMS using my username and give a table, this will generate a Java code for employee table in the test database. So this CodeGen can be useful for us to understand what data we have in this particular table. Finally, can Sqoop be used to convert data in different formats? I think I already answered that, right? If no, which tools can be used for this purpose? So Sqoop can be used to convert data in different formats, and that depends on the different arguments which you use when you do a import, such as Avro file, Parquet file, binary format with record or block level compression. So if you're interested in knowing more on different data formats, then I think I can suggest a link for that. And we can say Hadoop formats. I think it is tech Maggie, Avro, Parquet. Let's see if we can find out the link. Tech Maggie. Yeah, this is a very good link which specifies or talks about different data formats which you should know, such as your text file format, different compression schemes, how is data organization, what are the common formats, what do you have in text file, structured, binary, sequence files with compression, without compression, what is record level, what is block level, what is a Avro data file, what is a Sqoop, what is a Parquet data file or a columnar format, and other formats like ORC, RC, and so on. So please have a look at this.
And with that, we have come to the end of this video on Big Data Engineer full course. I hope it was informative and interesting. If you have any questions related to the topics that were covered in this video, please ask away in the comment section below. Our team will help you solve your queries. Thanks for watching, stay safe and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.